The movements of plants. Introduction. The chief object of the present work is to describe and connect together several large classes of movement common to almost all plants. The most widely prevalent movement is essentially of the same nature as that of the stem of a climbing plant, which bends successively to all points of the compass, so that the tip revolves. This movement has been called by Sachs revolving nutation, but we have found it much more convenient to use the terms circumnutation and circumnudate, as we shall have to say much about this movement. It will be useful here briefly to describe its nature. If we observe a circumnudating stem, which happens at the time to be bent, we will say towards the north it will be found gradually to bend more and more easterly until it faces the east, and so onwards to the south, then to the west and back again to the north. If the movement had been quite regular, the apex would have described a circle, or rather, as the stem is always growing upwards, a circular spiral. But it generally describes irregular elliptical or oval figures, for the apex, after pointing in any one direction, commonly moves back to the opposite side, not however returning along the same line afterwards. Other irregular ellipses or ovals are successively described with their longer axes directed to different points of the compass. Whilst describing such figures, the apex often travels in a zigzag line, or makes small subordinate loops or triangles. In the case of leaves, the ellipses are generally narrow. Until recently, the cause of all such bending movements was believed to be due to the increased growth of the side, which becomes for a time convex, that this side does temporarily grow more quickly than the concave side has been well established. But de Vries has lately shown that such increased growth follows a previously increased state of turgescence on the convex side. One, in the case of parts provided with a so-called joint cushion or pulvinus, which consists of an aggregate of small cells that have ceased to increase in size from a very early age, we meet with similar movements, and here, as Pfeffer has shown too, and as we shall see in the course of this work, the increased turgescence of the cells on opposite sides is not followed by increased growth. Wiesner denies in certain cases the accuracy of de Vries' conclusion about turgescence, and maintains 3. That the increased extensibility of the cell walls is the more important element, that such extensibility must accompany increased turgescence in order that the part may bend is manifest, and this has been insisted on by several botanists, but in the case of unicellular plants, it can hardly fail to be the more important element. On the whole, we may at present conclude that increased growth first on one side, and then on another, is a secondary effect, and that the increased turgescence of the cells together with the extensibility of their walls is the primary cause of the movement of circumnutation. 4. In the course of the present volume, it will be shown that apparently every growing part of every plant is continually circumnudating, though often on a small scale. Even the stems of seedlings, before they have broken through the ground, as well as their buried radicals, circumnudate as far as the pressure of the surrounding earth permits. In this universally present movement, we have the basis or groundwork for the acquirement, according to the requirements of the plant, of the most diversified movements. Thus the great sweeps made by the stems of twining plants, and by the tendrils of other climbers, result from a mere increase in the amplitude of the ordinary movement of circumnutation. The position which young leaves and other organs ultimately assume is acquired by the circumnutating movement being increased in some one direction. The leaves of various plants are said to sleep at night, and it will be seen that their blades then assume a vertical position through modified circumnutation, in order to protect their upper surfaces from being chilled through radiation. The movements of various organs to the light, which are so general throughout the vegetable kingdom, and occasionally from the light or transversely with respect to it, are all modified forms of circumnutation, as again are the equally prevalent movements of stems, etc., towards the zenith, and of roots towards the center of the earth. In accordance with these conclusions, a considerable difficulty in the way of evolution is in part removed, for it might have been asked, how did all these diversified movements for the most different purposes first arise? As the case stands, we know that there is always movement in progress, and its amplitude or direction, or both, have only to be modified for the good of the plant, in relation with internal or external stimuli. Besides describing the several modified forms of circumnutation, some other subjects will be discussed. The two which have interested us most are firstly the fact that with some seedling plants, the uppermost part alone is sensitive to light, and transmits an influence to the lower part, causing it to bend. If therefore the upper part be wholly protected from light, the lower part may be exposed for hours to it, and yet does not become in the least bent, although this would have occurred quickly if the upper part had been excited by light. Secondly, with the radicals of seedlings, The tip is sensitive to various stimuli, especially to very slight pressure, and when thus excited transmits an influence to the upper part, causing it to bend from the pressed side. On the other hand, if the tip is subjected to the vapor of water proceeding from one side, the upper part of the radical bends towards this side again. It is the tip as stated by Cieślski, though denied by others, which is sensitive to the attraction of gravity and by transmission causes the adjoining parts of the radical to bend towards the center of the earth. These several cases of the effects of contact, other irritants, vapor, light, and the attraction of gravity being transmitted from the excited part for some little distance along the organ in question, have an important bearing on the theory of all such movements. Terminology. A brief explanation of some terms, which will be used, must here be given. With seedlings, the stem, which supports the cotyledons (1e), the organs, which represent the first leaves, has been called by many botanists the hypocotyledonous stem. But for brevity's sake we will speak of it merely as the hypocotyl. The stem immediately above the cotyledons will be called the epicotyl or plumule. The radical can be distinguished from the hypocotyl only by the presence of root hairs, and the nature of its covering. The meaning of the word circumnutation has already been explained. Authors speak of positive and negative heliotropism 5, that is, the bending of an organ to or from the light, but it is much more convenient to confine the word heliotropism to bending towards the light, and to designate as a pheliotropism bending from the light. There is another reason for this change, for writers, as we have observed, occasionally drop the adjectives positive and negative, and thus introduce confusion into their discussions. Diheliotropism may express a position more or less transverse to the light, and induced by it in like manner. Positive geotropism, or bending towards the center of the earth, will be called by us geotropism. Apogeotropism will mean bending in opposition to gravity or from the center of the earth, and digeotropism a position more or less transverse to the radius of the earth. The words heliotropism and geotropism properly mean the act of moving in relation to the light or the earth, but in the same manner as gravitation, though defined as the act of tending to the center, is often used to express the cause of a body falling, so it will be found convenient occasionally to employ heliotropism and geotropism, etc., as the cause of the movements in question. The term epinasty is now often used in Germany, and implies that the upper surface of an organ grows more quickly than the lower surface, and thus causes it to bend downwards. Hyponasty is the reverse, and implies increased growth along the lower surface, causing the part to bend upwards. 6. Methods of observation. The movements, sometimes very small and sometimes considerable, in extent of the various organs observed by us were traced in the manner which after many trials we found to be best, and which must be described. Plants growing in pots were protected wholly from the light, or had light admitted from above or on one side as the case might require, and were covered above by a large horizontal sheet of glass, and with another vertical sheet on one side, a glass filament not thicker than a horsehair, and from 1/4 to 3/4 of an inch in length, was affixed to the part to be observed. By means of shellac, dissolved in alcohol, the solution was allowed to evaporate until it became so thick that it set hard in 2 or 3 seconds, and it never injured the tissues, even the tips of tender radicals, to which it was applied to the end of the glass filament. An excessively minute bead of black sealing wax was cemented below or behind which a bit of card with a black dot was fixed to a stick driven into the ground. The weight of the filament was so slight that even small leaves were not perceptibly pressed down. Another method of observation, when much magnification of the movement was not required, will presently be described. The bead and the dot on the card were viewed through the horizontal or vertical glass plate according to the position of the object, and when one exactly covered the other, a dot was made on the glass plate with a sharply pointed stick, dipped in thick Indian ink. Other dots were made at short intervals of time, and these were afterwards joined by straight lines. The figures thus traced were therefore angular, but if dots had been made every 1 or 2 minutes, the lines would have been more curvilinear, as occurred when radicals were allowed to trace their own courses on smoked glass plates. To make the dots accurately was the sole difficulty, and required some practice, nor could this be done quite accurately when the movement was much magnified, such as 30 times and upwards. Yet even in this case, the general course may be trusted to test the accuracy of the above method of observation. A filament was fixed to an inanimate object, which was made to slide along a straight edge, and dots were repeatedly made on a glass plate. When these were joined, the result ought to have been a perfectly straight line, and the line was very nearly straight. It may be added that when the dot on the card was placed 1/2 inch below or behind the bead of sealing wax, and when the glass plate, supposing it to have been properly curved, stood at a distance of 7 inches in front, a common distance. Then the tracing represented the movement of the bead, magnified 15 times. Whenever a great increase of the movement was not required another, and in some respects better method of observation was followed, this consisted in fixing 2-minute triangles of thin paper, about 120 inch in height, to the two ends of the attached glass filament, and when their tips were brought into a line, so that they covered one another, dots were made as before on the glass plate. If we suppose the glass plate to stand at a distance of 7 inches from the end of the shoot, bearing the filament, the dots when joined will give nearly the same figure as if a filament 7 inches long dipped in ink had been fixed to the moving shoot, and had inscribed its own course on the plate. The movement is thus considerably magnified. For instance, if a shoot 1 inch in length were bending, and the glass plate stood at the distance of 7 inches, the movement would be magnified 8 times. It would, however, have been very difficult to have ascertained in each case how great a length of the shoot was bending, and this is indispensable for ascertaining the degree to which the movement is magnified. After dots had been made on the glass plates by either of the above methods, they were copied on tracing paper and joined by ruled lines, with arrows showing the direction of the movement. The nocturnal courses are represented by straight broken lines. The first dot is always made larger than the others, so as to catch the eye, as may be seen in the diagrams. The figures on the glass plates were often drawn on too large a scale to be reproduced on the pages of this volume, and the proportion in which they have been reduced is always given 7, whenever it could be approximately told how much the movement had been magnified. This is stated. We have perhaps introduced a superfluous number of diagrams, but they take up less space than a full description of the movements. Almost all the sketches of plants asleep, etc., were carefully drawn for us by Mr. George Darwin. As shoots, leaves, etc., in circumnudating, bend more and more, first in one direction, and then in another, they were necessarily viewed at different times more or less obliquely, and as the dots were made on a flat surface, the apparent amount of movement is exaggerated according to the degree of obliquity of the point of view. It would therefore have been a much better plan to have used hemispherical glasses if we had possessed them of all sizes, and if the bending part of the shoot had been distinctly hinged and could have been placed so as to have formed one of the radii of the sphere. But even in this case, it would have been necessary afterwards to have projected the figures on paper, so that complete accuracy could not have been attained from the distortion of our figures. Owing to the above causes, they are of no use to anyone who wishes to know the exact amount of movement or the exact course pursued, but they serve excellently for ascertaining whether or not the part moved at all, as well as the general character of the movement. In the following chapters, the movements of a considerable number of plants are described, and the species have been arranged according to the system adopted by Hooker in Le Mouat and Dekesne's descriptive botany. No one who is not investigating the present subject need read all the details which, however, we have thought it advisable to give to save the reader trouble. The conclusions, and most of the more important parts, have been printed in larger type than the other parts. He may, if he thinks fit, read the last chapter first, as it includes a summary of the whole volume, and he will thus see what points interest him, and on which he requires the full evidence. Finally, we must have the pleasure of returning our sincere thanks to Sir Joseph Hooker and to Mr. W. Thistleton Dyer for their great kindness in not only sending us plants from Kew, but in procuring others from several sources when they were required for our observations, also for naming many species, and giving us information on various points. Chapter I. The circumnudating movements of seedling plants. Brassica oleracea. Circumnutation of the radicle of the arched hypocotyl, whilst still buried beneath the ground, whilst rising above the ground and straightening itself, and when erect. Circumnutation of the cotyledon's rate of movement. Analogous observations on various organs in species of Githago Gossypium, Oxalis tropiolum, Citrus sculus, of several leguminous and cucurbitaceous genera, Opuntia helianthus, Primula cyclamen stipelia, Cerinth nalana solanum, Beta ricinus quercus corylus pinus cycas, Canna allium asparagus phalaris, Zea vena nephrodium, and Selaginella. The following chapter is devoted to the circumnudating movements of the radicles, hypocotyls, and cotyledons of seedling plants, and when the cotyledons do not rise above the ground, to the movements of the epicotyl. But in a future chapter, we shall have to recur to the movements of certain cotyledons which sleep at night. Brassica oleracea cruciferi. Fuller details will be given with respect to the movements in this case than in any other, as space and time will thus ultimately be saved. Radicale seed with the radicle projecting 5 inch was fastened with shellac to a little plate of zinc, so that the radical stood up vertically, and a fine glass filament was then fixed near its base, that is close to the seed coats. The seed was surrounded by little bits of wet sponge, and the movement of the bead at the end of the filament was traced Fig 1 during 60 hours. In this time, the radical increased in length from 5 to 11 inch, had the filament been attached at first close to the apex of the radical, and if it could have remained there all the time, the movement exhibited would have been much greater, for at the close of our observations, the tip, instead of standing vertically upwards, had become bowed downwards through geotropism, so as almost to touch the zinc plate, as far as we could roughly ascertain by measurements made with compasses on other seeds. The tip alone, for a length of only 20/100 to 30/100 of an inch, is acted on by geotropism, but the tracing shows that the basal part of the radical continued to circumnudate irregularly during the whole time. The actual extreme amount of movement of the bead at the end of the filament was nearly 5 inch, but to what extent the movement of the radical was magnified by the filament, which was nearly 34 inch in length, it was impossible to estimate. Fig 1 Brassica auracea circumnutation of radical traced on horizontal glass from 9a Roman 1000 Jan 31st to 9p Roman 1000 Feb, second movement of bead at end of filament, magnified about 40 times. Another seed was treated and observed in the same manner, but the radical in this case protruded 1 inch and was not fastened so as to project quite vertically upwards. The filament was affixed close to its base. The tracing Fig 2 reduced by half shows the movement from 9a Roman 1000 Jan 31st to 7a Roman 1000 Feb 2nd, but it continued to move during the whole of the second in the same general direction and in a similar zigzag manner, from the radical not being quite perpendicular when the filament was affixed. Geotropism came into play at once, but the irregular zigzag course shows that there was growth, probably preceded by turgescence, sometimes on one and sometimes on another side. Occasionally, the bead remained stationary for about an hour, and then probably growth occurred on the side opposite to that which caused the geotropic curvature in the case previously described. The basal part of the very short radical, from being turned vertically upwards, was at first very little affected by geotropism. Filaments were affixed in 2 other instances to rather longer radicals protruding obliquely from seeds, which had been turned upside down, and in these cases the lines traced on the horizontal glasses were only slightly zigzag, and the movement was always in the same general direction through the action of geotropism. All these observations are liable to several causes of error, but we believe from what will hereafter be shown with respect to the movements of the radicals of other plants that they may be largely trusted. Fig 2 Brassica auracea circumnu, ding and geotropic movement of radical traced on horizontal glass during 46 hours. Hypocotyl. The hypocotyl protrudes through the seed coats as a rectangular projection, which grows rapidly into an arch like the letter U turned upside down, the cotyledons being still enclosed within the seed. In whatever position the seed may be embedded in the earth or otherwise, fixed, both legs of the arch bend upwards through apogeotropism, and thus rise vertically above the ground. As soon as this has taken place, or even earlier, the inner or concave surface of the arch grows more quickly than the upper or convex surface, and this tends to separate the 2 legs and aids in drawing the cotyledons out of the buried seed coats. By the growth of the whole arch, the cotyledons are ultimately dragged from beneath the ground, even from a considerable depth, and now the hypocotyl quickly straightens itself by the increased growth of the concave side. Even whilst the arched or doubled hypocotyl is still beneath the ground, it circumnudates as much as the pressure of the surrounding soil will permit, but this was difficult to observe, because as soon as the arch is freed from lateral pressure, the 2 legs begin to separate even at a very early age. Before the arch would naturally have reached the surface, seeds were allowed to germinate on the surface of damp earth, and after they had fixed themselves by their radicals, and after the as yet only slightly arched hypocotyl had become nearly vertical, a glass filament was affixed on 2 occasions near to the base of the basal leg, Roman 1e, the one in connection with the radical, and its movements were traced in darkness on a horizontal glass. The result was that long lines were formed running in nearly the plane of the vertical arch due to the early separation of the 2 legs now freed from pressure. But as the lines were zigzag showing lateral movement, the arch must have been circumnudating whilst it was straightening itself by growth along its inner or concave surface. A somewhat different method of observation was next followed. As soon as the earth with seeds in a pot began to crack, the surface was removed in parts to the depth of 2 inch, and a filament was fixed to the basal leg of a buried and arched hypocotyle just above the summit of the radicle, the cotyledons were still almost completely enclosed within the much-cracked seed coats, and these were again covered up with damp adhesive soil pressed pretty firmly down. The movement of the filament was traced Fig 3 from 11A Roman 1000 Feb 5th till 8A Roman 1000 Feb 7th. By this latter period the cotyledons had been dragged from beneath the pressure-down earth, but the upper part of the hypocotyle still formed nearly a right angle with the lower part. The tracing shows that the arched hypocotyle tends at this early age to circumnudate irregularly on the first day. The greater movement from right to left in the figure was not in the plane of the vertical and arched hypocotyle, but at right angles to it, or in the plane of the two cotyledons, which were still in close contact. The basal leg of the arch, at the time when the filament was affixed to it, was already bowed considerably backwards, or from the cotyledons. Had the filament been affixed before this bowing occurred, the chief movement would have been at right angles to that shown in the figure. A filament was attached to another buried hypocotyle of the same age, and it moved in a similar general manner, but the line traced was not so complex. This hypocotyle became almost straight, and the cotyledons were dragged from beneath the ground on the evening of the second day. Fig 3 Brassica auracea circumnudating movement of buried and arched hypocotyle, dimly illuminated from above, traced on horizontal glass during 45 hours. Movement of bead of filament, magnified about 25 times in here, reduced to 1/2 of original scale. Fig 4 Brassica auracea circumnudating movement of buried and arched hypocotyle, with the two legs of the arch tied together, traced on horizontal glass during 12 hours. Movement of the bead of filament, magnified about 26 times in here, reduced to 1/2 original scale. Before the above observations were made, some arched hypocotyls buried at the depth of 1/4 of an inch were uncovered, and in order to prevent the two legs of the arch from beginning to separate at once, they were tied together with fine silk. This was done partly because we wished to ascertain how long the hypocotyle in its arched condition would continue to move, and whether the movement, when not masked and disturbed by the straightening process, indicated circumnutation. Firstly, a filament was fixed to the basal leg of an arched hypocotyle close above the summit of the radicle. The cotyledons were still partially enclosed within the seed coats. The movement was traced Fig 4 from 9A Roman 1000 on deck 23rd to 6A Roman 1000 on deck 25th. No doubt the natural movement was much disturbed by the two legs having been tied together, but we see that it was distinctly zigzag, first in one direction, and then in an almost opposite one after 3P Roman 1000 on the 24th. The arched hypocotyle sometimes remained stationary for a considerable time, and when moving moved far slower than before. Therefore, on the morning of the 25th, the glass filament was removed from the base of the basal leg, and was fixed horizontally on the summit of the arch, which from the legs having been tied had grown broad and almost flat. The movement was now traced during 23 hours. Fig 5, and we see that the course was still zigzag, which indicates a tendency to circumnutation. The base of the basal leg, by this time, had almost completely ceased. Fig 5 Brassica auracea circumnudating movement of the crown of a buried and arched hypocotyle, with the two legs tied together, traced on a horizontal glass during 23 hours. Movement of the bead of the filament, magnified about 58 times in here, reduced to 1/2 original scale. As soon as the cotyledons have been naturally dragged from beneath the ground, and the hypocotyle has straightened itself by growth along the inner or concave surface, there is nothing to interfere with the free movements of the parts, and the circumnutation now becomes much more regular and clearly displayed as shown in the following cases. A seedling was placed in front and near a northeast window, with a line joining the two cotyledons parallel to the window. It was thus left the whole day so as to accommodate itself to the light. On the following morning, a filament was fixed to the midrib of the larger and taller cotyledon, which enfolds the other and smaller one whilst still within the seed, and a mark being placed close behind the movement of the whole plant, that is of the hypocotyle and cotyledon, was traced greatly magnified on a vertical glass. At first, the plant bent so much towards the light that it was useless to attempt to trace the movement, but at 10A Roman 1000 heliotropism almost wholly ceased, and the first dot was made on the glass. The last was made at 8P Roman 1017 dots being altogether made in this interval of 10H45 Roman 1000. See Fig 6. It should be noticed that when I looked shortly after 4P Roman 1000, the bead was pointing off the glass, but it came on again at 5P Roman 1000, and the course during this interval of 1H30 Roman 1000 has been filled up by imagination, but cannot be far from correct. The bead moved 7 times from side to side, and thus described 312 ellipses in 1034h, each being completed on an average in 3h4 Roman 1000 Fig 6 Brassica auracea, conjoint circumnutation of the hypocarpal and cotyledons, during 10 hours 45 minutes, figure here, reduced to 1/2 original scale. On the previous day another seedling had been observed under similar conditions, excepting that the plant was so placed that a line joining the two cotyledons pointed towards the window, and the filament was attached to the smaller cotyledon on the side furthest from the window. Moreover, the plant was now for the first time placed in this position. The cotyledons bowed themselves greatly towards the light from 8 to 10 A Roman 1000. When the first dot was made, Fig 7, during the next 12 hours, the bead swept obliquely up and down 8 times, and described 4 figures representing ellipses, so that it travelled at nearly the same rate as in the previous case during the night. It moved upwards owing to the sleep movement of the cotyledons, and continued to move in the same direction till 9 A Roman 1000 on the following morning, but this latter movement would not have occurred with seedlings under their natural conditions, fully exposed to the light. Fig 7 Brassica auracea, conjoint circumnutation of the hypocarpal and cotyledons from 10 A Roman 1000 to 8 A Roman 1000, on the following morning, tracing made on a vertical glass. By 9 A Roman 1000 on this second day, the same cotyledon had begun to fall, and a dot was made on a fresh glass. The movement was traced until 5 P Roman 1000, as shown in Fig 8, which is given because the course followed was much more irregular than on the 2 previous occasions during these 8 hours. The bead changed its course greatly 10 times. The upward movement of the cotyledon during the afternoon and early part of the night is here plainly shown. Fig 8 Brassica auracea, conjoint circumnutation of the hypocarpal and cotyledons during 8 hours, figure here, reduced to 1/3 of the original scale, as traced on a vertical glass. As the filaments were fixed in the 3 last cases to one of the cotyledons, and as the hypocarpal was left free, the tracings show the movement of both organs conjoined, and we now wish to ascertain whether both circumnudated filaments were therefore fixed horizontally to 2 hypocarpals close beneath the petioles of their cotyledons. These seedlings had stood for 2 days in the same position before a northeast window in the morning up to about 11 A Roman 1000. They moved in zigzag lines towards the light, and at night they again became almost upright through apogeotropism. After about 11 A Roman 1000, they moved a little back from the light, often crossing and recrossing their former path in zigzag lines. The sky on this day varied much in brightness, and these observations merely proved that the hypocarpals were continually moving in a manner resembling circumnutation on a previous day which was uniformly cloudy. A hypocarpal was firmly secured to a little stick, and a filament was fixed to the larger of the 2 cotyledons, and its movement was traced on a vertical glass. It fell greatly from 8 A Roman 1000 when the first dot was made till 10 A Roman 1000. It then rose greatly until 12 P Roman 1000. Afterwards, it fell a little and made a loop, but by 2 P Roman 1000, it had risen a little and continued rising till 9 P Roman 1000, when it made another loop, and at 10 P Roman 1000 was again rising. These observations show that the cotyledons move vertically up and down all day long, and as there was some slight lateral movement, they circumnutated. Fig 9 Brassica auracea, circumnutation of hypocarpal in darkness, traced on a horizontal glass, by means of a filament with a bead fixed across its summit between 9 A Roman 1000 and 8 A Roman 1000 on the following morning, figure here, reduced to 1/2 of original scale. The cabbage was one of the first plants, the seedlings of which were observed by us, and we did not then know how far the circumnutation of the different parts was affected by light. Young seedlings were therefore kept in complete darkness, except for a minute or 2 during each observation when they were illuminated by a small wax taper, held almost vertically above them. During the first day, the hypocarpal of one changed its course 13 times, see Fig 9, and it deserves notice that the longer axes of the figures described often cross one another at right or nearly right angles. Another seedling was observed in the same manner, but it was much older, for it had formed a true leaf 1/4 of an inch in length, and the hypocarpal was 1/38 inch in height. The figure traced was a very complex one, though the movement was not so great in extent as in the last case. The hypocarpal of another seedling of the same age was secured to a little stick, and a filament having been fixed to the midrib of one of the cotyledons, the movement of the bead was traced during 14H15 Roman 1000, see Fig 10. In darkness, it should be noted that the chief movement of the cotyledons, namely up and down, would be shown on a horizontal glass plate only by the lines in the direction of the midrib, that is up and down, as Fig 10 here stands being a little lengthened or shortened, whereas any lateral movement would be well exhibited. The present tracing shows that the cotyledon did thus move laterally, that is from side to side in the tracing 12 times in the 14H15 Roman 1000 of observation. Therefore the cotyledons certainly circumnudated, though the chief movement was up and down in a vertical plane. Fig 10 Brassica or racia circumnutation of a cotyledon, the hypocotyle having been secured to a stick, traced on a horizontal glass in darkness, from 8A Roman 1000 to 10P Roman 1000 movement of the bead of the filament, magnified 13 times. Rate of movement. The movements of the hypocotyls and cotyledons of seedling cabbages of different ages have now been sufficiently illustrated. With respect to the rate, seedlings were placed under the microscope with the stage removed, and with a micrometer eyepiece so adjusted that each division equaled 1500 inch, the plants were illuminated by light passing through a solution of bichromate of potassium so as to eliminate heliotropism. Under these circumstances, it was interesting to observe how rapidly the circumnudating apex of a cotyledon passed across the divisions of the micrometer. Whilst travelling in any direction, the apex generally oscillated backwards and forwards to the extent of 1500 and sometimes of nearly 1250 of an inch. These oscillations were quite different from the trembling caused by any disturbance in the same room or by the shutting of a distant door. The first seedling observed was nearly 2 inches in height and had been etiolated by having been grown in darkness. The tip of the cotyledon passed across 10 divisions of the micrometer, that is 150 of an inch in 6 Roman 1000 s. Short glass filaments were then fixed vertically to the hypocotyls of several seedlings, so as to project a little above the cotyledons, thus exaggerating the rate of movement. But only a few of the observations thus made are worth giving. The most remarkable fact was the oscillatory movement above described, and the difference of rate at which the point crossed the divisions of the micrometer after short intervals of time. For instance, a tall notiolated seedling had been kept for 14H in darkness. It was exposed before a northeast window for only 2 or 3 minutes, whilst a glass filament was fixed vertically to the hypocotyl. It was then again placed in darkness for half an hour and afterwards observed by light passing through bichromate of potassium. The point oscillating as usual crossed 5 divisions of the micrometer Roman 1 E 1100 inch in 1 Roman 1000 s. The seedling was then left in darkness for an hour. And now it required 3 Roman 1000 s to cross 1 division, that is 15 Roman 1000 s to have crossed 5 divisions. Another seedling, after being occasionally observed in the back part of a northern room with a very dull light, and left in complete darkness for intervals of half an hour, crossed 5 divisions in 5 Roman 1000 in the direction of the window, so that we concluded that the movement was heliotropic. But this was probably not the case, for it was placed close to a northeast window and left there for 25 Roman 1000, after which time, instead of moving still more quickly towards the light, as might have been expected, it travelled only at the rate of 12 Roman 1000 s for 5 divisions. It was then again left in complete darkness for 1H, and the point now travelled in the same direction as before, but at the rate of 3 Roman 1000 s for 5 divisions. We shall have to recur to the cotyledons of the cabbage in a future chapter, when we treat of their sleep movements. The circumnutation also of the leaves of fully developed plants will hereafter be described. Fig 11 Githego segetum circumnutation of hypocotyl traced on a horizontal glass, by means of a filament fixed transversely across its summit, from 8A Roman 1000 to 12P Roman 1000, on the following day. Movement of bead of filament, magnified about 13 times here, reduced to 1/2 the original scale. Githego segetum caryophily, a young seedling, was dimly illuminated from above, and the circumnutation of the hypocotyl was observed during 28H as shown in Fig 11. It moved in all directions, the lines from right and to left in the figure being parallel to the blades of the cotyledons. The actual distance travelled from side to side by the summit of the hypocotyl was about 2 of an inch, but it was impossible to be accurate on this head, as the more obliquely the plant was viewed, after it had moved for some time, the more the distances were exaggerated. We endeavoured to observe the circumnutation of the cotyledons, but as they closed together, unless kept exposed to a moderately bright light, and as the hypocotyl is extremely heliotropic, the necessary arrangements were too troublesome, we shall recur to the nocturnal or sleep movements of the cotyledons in a future chapter. Fig 12 Gossypium circumnutation of hypocotyl traced on a horizontal glass from 10A Roman 1000 to 9A Roman 1000 on following morning, by means of a filament fixed across its summit movement of beta filament, magnified about twice seedling, illuminated from above. Gossypium var nenkin cart malvacy, the circumnutation of a hypocotyle was observed in the hothouse, but the movement was so much exaggerated that the bead twice passed for a time out of view. It was however manifest that two somewhat irregular ellipses were nearly completed. In 9H another seedling 112 in height was then observed during 23H, but the observations were not made at sufficiently short intervals, as shown by the few dots in Fig 12, and the tracing was not now sufficiently enlarged. Nevertheless, there could be no doubt about the circumnutation of the hypocotyle, which described in 12H a figure representing three irregular ellipses of unequal sizes. The cotyledons are in constant movement up and down during the whole day, and as they offer the unusual case of moving downwards late in the evening, and in the early part of the night, many observations were made on them. A filament was fixed along the middle of one, and its movement traced on a vertical glass, but the tracing is not given as the hypocotyle was not secured, so that it was impossible to distinguish clearly between its movement and that of the cotyledon. The cotyledons rose from 10A Roman 1000 to about 3P Roman 1000. They then sank till 10P Roman 1000, rising however greatly in the latter part of the night. The angles above the horizon, at which the cotyledons of another seedling stood at different hours, is recorded in the following short table. Arct 22, P Roman 100,025, above horizon Arct 24, P Roman 100,022, above horizon Arct 25, P Roman 100,015, above horizon Arct 2010, P Roman 10,008, above horizon Arct 21, 8A Roman 100,028, above horizon Arct 21, 11A Roman 100,035, above horizon Arct 21, 9P Roman 100,010, below horizon. The position of the two cotyledons was roughly sketched at various hours, with the same general result. In the following summer, the hypocotyle of a fourth seedling was secured to a little stick, and a glass filament with triangles of paper having been fixed to one of the cotyledons, its movements were traced on a vertical glass under a double skylight in the house. The first dot was made at 4P Roman 1000 June 20th, and the cotyledon fell till 10P Roman 1000 in a nearly straight line, just past midnight. It was found a little lower and somewhat to one side by the early morning at 3A Roman 1000. It had risen greatly, but by 6A Roman 1000 had fallen a little during the whole of this day 21st. It fell in a slightly zigzag line, but its normal course was disturbed by the want of sufficient illumination, for during the night it rose only a little, and travelled irregularly during the whole of the following day and night of June 22nd. The ascending and descending lines traced during the 3 days did not coincide, so that the movement was one of circumnutation. This seedling was then taken back to the hothouse, and after 5 days was inspected at 10P Roman 1000, when the cotyledons were found hanging so nearly vertically down that they might justly be said to have been asleep on the following morning. They had resumed their usual horizontal position. Oxalis rosea oxalide, the hypocotyle was secured to a little stick, and an extremely thin glass filament with 2 triangles of paper was attached to one of the cotyledons, which was 15 inch in length in this, and the following species. The end of the petiole, where united to the blade, is developed into a pulvinus. The apex of the cotyledon stood only 5 inches from the vertical glass, so that its movement was not greatly exaggerated, as long as it remained nearly horizontal. But in the course of the day, it both rose considerably above and fell beneath a horizontal position, and then of course the movement was much exaggerated in Fig 13. Its course is shown from 6A Roman 1000 on June 17th to 7A Roman 1000 on the following morning, and we see that during the daytime in the course of 11H15 Roman 1000, it travelled thrice down and twice up. After 5P Roman 1000, it moved rapidly downwards, and in an hour or two depended vertically. It thus remained all night asleep. This position could not be represented on the vertical glass, nor in the figure here given by 6A Roman 1000 on the following morning 18th. Both cotyledons had risen greatly, and they continued to rise until 8A Roman 1000, when they stood almost horizontally. Their movement was traced during the whole of this day, and until the next morning, but a tracing is not given, as it was closely similar to Fig 13, excepting that the lines were more zigzag. The cotyledons moved 7 times either upwards or downwards, and at about 4P Roman 1000, the great nocturnal sinking movement commenced. Fig 13 Oxalis rosea circumnutation of cotyledons, the hypocotyl being secured to a stick, illuminated from above figure here, given 1/2 of original scale. Another seedling was observed in a similar manner during nearly 24H, but with the difference that the hypocotyl was left free, the movement also was less magnified between 8A Roman 1000 and 5P Roman 1000 on the 18th. The apex of the cotyledon moved 7 times upwards or downwards. Fig. 14 The nocturnal sinking movement, which is merely a great increase of one of the diurnal oscillations, commenced about 4P Roman 1000 Oxalis valdiviana. This species is interesting, as the cotyledons rise perpendicularly upwards at night, so as to come into close contact, instead of sinking vertically downwards, as in the case of O. rosea. A glass filament was fixed to a cotyledon 17 of an inch in length, and the hypocotyl was left free on the first day. The seedling was placed too far from the vertical glass, so that the tracing was enormously exaggerated, and the movement could not be traced when the cotyledon either rose or sank much. But it was clearly seen that the cotyledons rose thrice, and fell twice between 8A Roman 1000 and 4P Roman 1000 early, on the following morning June 19th. The apex of a cotyledon was placed only 1/78 inch from the vertical glass at 6A Roman 1000. It stood horizontally. It then fell till 8 and then rose altogether in the course of 12H. It rose thrice, and fell thrice, as may be seen in Fig 15. The great nocturnal rise of the cotyledons usually commences about 4 or 5P Roman 1000, and on the following morning they are expanded or stand horizontally at about 6A Roman 1000. In the present instance, however, the great nocturnal rise did not commence till 7P Roman 1000, but this was due to the hypocotyl having from some unknown cause temporarily bent to the left side, as is shown in the tracing to ascertain positively that the hypocotyl circumnudated a mark was placed at 8P Roman 1000 behind the two now closed and vertical cotyledons, and the movement of a glass filament fixed upright to the top of the hypocotyl was traced until 10P Roman 1000. During this time it moved from side to side, as well as backwards and forwards, plainly showing circumnutation. But the movement was small in extent, therefore, Fig 15 represents fairly well the movements of the cotyledons alone, with the exception of the one great afternoon curvature to the left. Fig 14 Oxalis rosea, conjoint circumnutation of the cotyledons, and hypocotyl traced from 8A Roman 1000 on June 18th to 7A Roman 1000. The apex of the cotyledon stood only 3/34 inches from the vertical glass figure, here given 1/2 of original scale. Fig 15 Oxalis valdiviana, conjoint circumnutation of a cotyledon, and the hypocotyl traced on vertical glass during 24 hours figure here, given 1/2 of original scale seedling, illuminated from above. Oxalis corniculata var caprea, the cotyledons rise at night to a variable degree above the horizon generally, about 45. Those on some seedlings between 2 and 5 days old were found to be in continued movement all day long, but the movements were more simple than in the last two species. This may have partly resulted from their not being sufficiently illuminated, whilst being observed, as was shown by their not beginning to rise until very late in the evening. Oxalis biophytum sensitiva, the cotyledons are highly remarkable from the amplitude and rapidity of their movements. During the day, the angles at which they stood above or beneath the horizon were measured at short intervals of time, and we regret that their course was not traced during the whole day. We will give only a few of the measurements which were made. Whilst the seedlings were exposed to a temperature of 2212 to 2412 Roman 100, one cotyledon rose 70. In 11 Roman 1000 another, on a distinct seedling, fell 80 in 12 Roman 1000 immediately. Before this latter fall, the same cotyledon had risen from a vertically downward to a vertically upward position in 1H 48 Roman 1000, and had therefore passed through 180 in under 2H. We have met with no other instance of a circumnutating movement of such great amplitude as 180, nor of such rapidity of movement as the passage through 80 in 12 Roman 1000. The cotyledons of this plant sleep at night by rising vertically and coming into close contact. This upward movement differs from one of the great diurnal oscillations above described only by the position being permanent during the night, and by its periodicity, as it always commences late in the evening. Tropiolum minus var tam thumb tropioli, the cotyledons are hypogene or never rise above the ground. By removing the soil, a buried epicotyl or plumule was found with its summit arched abruptly downwards like the arched hypocotyl of the cabbage, previously described a glass filament with a bead at its end, was affixed to the basal half or leg, just above the hypogene. Cotyledons, which were again almost surrounded by loose earth. The tracing Fig 16 shows the course of the bead during 11H. After the last dot given in the figure, the bead moved to a great distance, and finally off the glass in the direction indicated by the broken line. This great movement, due to increased growth along the concave surface of the arch, was caused by the basal leg bending backwards from the upper part, that is, in a direction opposite to the dependent tip. In the same manner as occurred with the hypocotyl of the cabbage, another buried and arched epicotyl was observed in the same manner, excepting that the two legs of the arch were tied together with fine silk. For the sake of preventing the great movement just mentioned, it moved, however, in the evening in the same direction as before, but the line followed was not so straight. During the morning, the tied arch moved in an irregularly circular, strongly zigzag course, and to a greater distance than in the previous case, as was shown in a tracing magnified 18 times. The movements of a young plant bearing a few leaves, and of a mature plant, will hereafter be described. Fig 16 tropiolum minus circumnutation of buried and arched epicotyl, traced on a horizontal glass, from 9A Roman 1000 to 8P Roman 1000. Movement of bead of filament, magnified 27 times. Citrus aurantium orange aurantiaceae. The cotyledons are hypogene. The circumnutation of an epicotyl, which at the close of our observations was 59 of an inch 15 Roman 2000 in height above the ground, is shown in the annexed figure, Fig 17, as observed during a period of 44H 40 Roman 1000. Fig 17 Citrus aurantium circumnutation of epicotyl with a filament fixed transversely near its apex, traced on a horizontal glass from 12P Roman 1000 on Feb 20th to 8A Roman 1000 on 22nd. The movement of the bead of the filament was at first magnified 21 times, or 1012, in figure here given, and afterwards 36 times, or 18, as here given. Seedling illuminated from above. Sculus hippocastanum hippocastani. Germinating seeds were placed in a tin box, kept moist internally, with a sloping bank of damp argillaceous sand, on which 4 smoked glass plates rested inclined at angles of 70 and 65, with the horizon. The tips of the radicals were placed so as just to touch the upper end of the glass plates, and as they grew downwards, they pressed lightly owing to geotropism on the smoked surfaces and left tracks of their course in the middle part of each track. The glass was swept clean, but the margins were much blurred, and irregular copies of 2 of these tracks, all 4 being nearly alike, were made on tracing paper, placed over the glass plates after they had been varnished, and they are as exact as possible considering the nature of the margins. Fig 18, they suffice to show that there was some lateral, almost serpentine movement, and that the tips in their downward course pressed with unequal force on the plates. As the tracks varied in breadth, the more perfectly serpentine tracks made by the radicals of Phasalis multiflorus and Viscia faber, presently to be described, render it almost certain that the radicals of the present plant circumnudated. Fig 18 Sculus hippocastanum. Outlines of tracks left on inclined glass plates by tips of radicals. In A, the plate was inclined at 70 with the horizon, and the radical was 1 inch in length and 23 inch in diameter at base. In B, the plate was inclined 65 with the horizon, and the radical was a trifle larger. Phasalis multiflorus leguminosae. 4 smoked glass plates were arranged in the same manner as described under Sculus, and the tracks left by the tips of 4 radicals of the present plant, whilst growing downwards, were photographed as transparent objects. 3 of them are here exactly copied. Fig 19 Their serpentine courses show that the tips moved regularly from side to side. They also pressed alternately with greater or less force on the plates, sometimes rising up and leaving them altogether for a very short distance. But this was better seen on the original plates than in the copies. These radicals therefore were continually moving in all directions, that is, they circumnudated the distance between the extreme right and left positions of the radical A in its lateral movement was 2 Roman 2000, as ascertained by measurement with an eyepiece micrometer. Fig 19 Phasalis multiflorus tracks left on inclined smoked glass plates by tips of radicals in growing downwards are in C plates, inclined at 60B, inclined at 68 with the horizon. Viscia faber common bean leguminosae. Radical. Some beans were allowed to germinate on bare sand, and after one had protruded its radical to a length of 2 of an inch, it was turned upside down, so that the radical, which was kept in damp air, now stood upright. A filament, nearly an inch in length, was affixed obliquely near its tip, and the movement of the terminal bead was traced from 8A Roman 1000 to 10 p Roman 1000, as shown in Fig. 18. The radical at first changed its course twice abruptly, then made a small loop, and then a larger zigzag curve during the night, until 11 a Roman 1000 on the following morning, the bead moved to a great distance in a nearly straight line in the direction indicated by the broken line in the figure. This resulted from the tip bending quickly downwards, as it had now become much declined, and had thus gained a position highly favorable for the action of geotropism. Fig. 20. Vischer-Farber circumnutation of a radical at first pointing vertically upwards, kept in darkness traced on a horizontal glass during 14 hours movement of bead of filament, magnified 23 times here, reduced to 1/2 of original scale. Fig. 21. Vischer-Farber tracks left on inclined smoked glass plates by tips of radicals in growing downwards. Plate C was inclined at 63 plates A and D at 71, plate B at 75, and plate E at a few degrees beneath the horizon. We next experimented on nearly a score of radicals by allowing them to grow downwards over inclined plates of smoked glass in exactly the same manner as with sculus and physalis. Some of the plates were inclined only a few degrees beneath the horizon, but most of them between 60 and 75. In the latter cases, the radicals in growing downwards were deflected only a little from the direction which they had followed whilst germinating in sawdust, and they pressed lightly on the glass plates. Fig. 21. 5 of the most distinct tracks are here copied, and they are all slightly sinuous, showing circumnutation. Moreover, a close examination of almost every one of the tracks clearly showed that the tips in their downward course had alternately pressed with greater or less force on the plates, and had sometimes risen up so as nearly to leave them for short intervals. The distance between the extreme right and left positions of the radical A was 0 Roman 2000, ascertained in the same manner as in the case of physalis. Epicartal at the point where the radical had protruded from a bean laid on its side, a flattened solid lump, projected 1 inch in the same horizontal plane with the bean. This protuberance consisted of the convex summit of the arched epicartal, and as it became developed, the two legs of the arch curved themselves laterally upwards, owing to apogeotropism, at such a rate that the arch stood highly inclined after 14h, and vertically. In 48h, a filament was fixed to the crown of the protuberance before any arch was visible, but the basal half grew so quickly that on the second morning the end of the filament was bowed greatly downwards. It was therefore removed and fixed lower down the line traced during these 2 days, extended in the same general direction, and was in parts nearly straight, and in others plainly zigzag, thus giving some evidence of circumnutation. As the arched epicartal, in whatever position it may be placed, bends quickly upwards through apogeotropism, and as the two legs tend at a very early age to separate from one another, as soon as they are relieved from the pressure of the surrounding earth, it was difficult to ascertain positively whether the epicartal, whilst remaining arched, circumnudated. Therefore, some rather deeply buried beans were uncovered, and the two legs of the arches were tied together, as had been done with the epicartal of tropialum and the hypocartal of the cabbage. The movements of the tied arches were traced in the usual manner on 2 occasions during 3 days, but the tracings made under such unnatural conditions are not worth giving, and it need only be said that the lines were decidedly zigzag, and that small loops were occasionally formed. We may therefore conclude that the epicartal circumnudates whilst still arched, and before it has grown tall enough to break through the surface of the ground. In order to observe the movements of the epicartal at a somewhat more advanced age, a filament was fixed near the base of one, which was no longer arched, for its upper half now formed a right angle with the lower half. This bean had germinated on bare damp sand, and the epicartal began to straighten itself much sooner than would have occurred if it had been properly planted. The course pursued during 50h from 9 a Roman 1000 dec 26 to 11 a Roman 1000 is here shown. Fig. 22, and we see that the epicartal circumnudated during the whole time. Its basal part grew so much during the 50h that the filament at the end of our observations was attached at the height of 4 inch above the upper surface of the bean instead of close to it. If the bean had been properly planted, this part of the epicartal would still have been beneath the soil. Fig. 22, Vischer-Farber circumnutation of young epicartal, traced in darkness during 50 hours on a horizontal glass movement of bead of filament, magnified 20 times here, reduced to 1/2 of original scale. Late in the evening of the 28th, some hours after the above observations were completed, the epicartal had grown much straighter, for the upper part now formed a widely open angle with the lower part. A filament was fixed to the upright basal part, higher up than before, close beneath the lowest scale-like process, homologue of a leaf, and its movement was traced during 38H Fig 23, we here again have plain evidence of continued circumnutation. Had the bean been properly planted, the part of the epicotyle to which the filament was attached, the movement of which is here shown, would probably have just risen above the surface of the ground. Fig 23 Vischer Faber circumnutation of the same epicotyle, as in Fig 22, a little more advanced in age, traced under similar conditions, as before, from 8A Roman 1000 dec 28th to 10A Roman 1000th movement of bead here, magnified 20 times. Lathyrus nisolia leguminosae. This plant was selected for observation from being an abnormal form with grass-like leaves. The cotyledons are hypogene, and the epicotyle breaks through the ground, in an arched form, the movements of a stem 1 inch in height, consisting of 3 internodes, the lower one almost wholly subterranean, and the upper one bearing a short, narrow leaf is shown during 24H in Fig 24. No glass filament was employed, but a mark was placed beneath the apex of the leaf. The actual length of the longer of the two ellipses described by the stem was about 14 of an inch on the previous day. The chief line of movement was nearly at right angles to that shown in the present figure, and it was more simple. Fig 24 Lathyrus nisolia circumnutation of stem of young seedling, traced in darkness on a horizontal glass, from 6A Roman 1000 Nav 22nd to 7A Roman 1000th movement of end of leaf, magnified about 12 times here, reduced to 1/2 of original scale. Cassia tora 1 leguminosae A seedling was placed before a northeast window. It bent very little towards it, as the hypocotyle which was left free was rather old, and therefore not highly heliotropic. A filament had been fixed to the midrib of one of the cotyledons, and the movement of the whole seedling was traced during 2 days. The circumnutation of the hypocotyle is quite insignificant compared with that of the cotyledons. These rise up vertically at night, and come into close contact, so that they may be said to sleep. This seedling was so old that a very small, true leaf had been developed, which at night was completely hidden by the closed cotyledons. On Sept 24th, between 8A Roman 1000 and 5P Roman 1000, the cotyledons moved 5 times up and 5 times down. They therefore described 5 irregular ellipses in the course of the 9H. The great nocturnal rise commenced about 4P Roman 10,001. Seeds of this plant, which grew near the seaside, were sent to us by Fritz Müller from S. Brazil. The seedlings did not flourish or flower well with us. They were sent to Q, and were pronounced not to be distinguishable from Roman 100 tora. Fig 25 Cassia tora conjoint circumnutation of cotyledons and hypocotyle traced on vertical glass, from 7A Roman 1000, Sept 25th, to 7A Roman 1000th. Figure here, given reduced to 1/2 of original scale. On the following morning, Sept 25th, the movement of the same cotyledon was again traced in the same manner during 24H, and a copy of the tracing is here given. Fig 25 The morning was cold, and the window had been accidentally left open for a short time, which must have chilled the plant, and this probably prevented it from moving quite as freely as on the previous day, for it rose only 4 and sank only 4 times during the day, one of the oscillations being very small at 7A Roman 1000. When the first dot was made, the cotyledons were not fully open or awake. They continued to open till about 9A Roman 1000, by which time they had sunk a little beneath the horizon. By 9A Roman 1000, they had risen, and then they oscillated up and down, but the upward and downward lines never quite coincided. At about 4P Roman 1000, the great nocturnal rise commenced. At 7A Roman 1000 on the following morning, Sept 26, they occupied nearly the same level as on the previous morning as shown in the diagram. They then began to open or sink in the usual manner. The diagram leads to the belief that the great periodical daily rise and fall does not differ essentially excepting in amplitude from the oscillations during the middle of the day. Lotus jacobous leguminosae, the cotyledons of this plant after the few first days of their life, rise so as to stand almost though rarely quite vertically at night. They continue to act in this manner for a long time, even after the development of some of the true leaves with seedlings 3 inches in height, and bearing 5 or 6 leaves. They rose at night about 45, they continued to act thus for about an additional fortnight. Subsequently they remained horizontal at night though still green, and at last dropped off. Their rising at night, so as to stand almost vertically, appears to depend largely on temperature, for when the seedlings were kept in a cool house, though they still continued to grow, the cotyledons did not become vertical at night. It is remarkable that the cotyledons do not generally rise at night to any conspicuous extent during the first 4 or 5 days after germination. but the period was extremely variable, with seedlings kept under the same conditions, and many were observed glass filaments with minute triangles of paper were fixed to the cotyledons, 112 Roman 2000 in breadth of 2 seedlings, only 24h old, and the hypocotyl was secured to a stick. Their movements, greatly magnified, were traced, and they certainly circumnudated the whole time on a small scale, but they did not exhibit any distinct nocturnal and diurnal movement. The hypocotyls, when left free, circumnudated over a large space. Another and much older seedling bearing a half-developed leaf had its movements traced in a similar manner during the 3 first days and nights of June, but seedlings at this age appear to be very sensitive to a deficiency of light. They were observed under a rather dim skylight at a temperature of between 16 to 1712 Roman 100, and apparently in consequence of these conditions, the great daily movement of the cotyledons ceased on the 3rd day. During the first 2 days they began rising in the early afternoon in a nearly straight line, until between 6 and 7 p. Roman 1000, when they stood vertically during the latter part of the night, or more probably in the early morning. They began to fall or open so that by 6 a. Roman 1000 they stood fully expanded, and horizontal they continued to fall slowly for some time, and during the 2nd day described a single small ellipse between 9 a. Roman 1000 and 2 p. Roman 1000. In addition to the great diurnal movement, the course pursued during the whole 24h was far less complex than in the foregoing case of Cassia. On the 3rd morning, they fell very much, and then circumnudated on a small scale round the same spot by 8 p. Roman 1000. They showed no tendency to rise at night, nor did the cotyledons of any of the many other seedlings in the same pot rise. And so it was on the following night of June 5th, the pot was then taken back into the hothouse where it was exposed to the sun, and on the succeeding night all the cotyledons rose again to a high angle, but did not stand quite vertically on each of the above days. The line representing the great nocturnal rise did not coincide with that of the great diurnal fall, so that narrow ellipses were described. As is the usual rule with circumnudating organs, the cotyledons are provided with a pulvinus, and its development will hereafter be described. Mimosa pudica leguminosae, the cotyledons rise up vertically at night, so as to close together. 2 seedlings were observed in the greenhouse temp, 16 to 17 Roman 100 or 63 to 65. Their hypocotyls were secured to sticks, and glass filaments bearing little triangles of paper were affixed to the cotyledons of both. Their movements were traced on a vertical glass during 24h on November 13th. The pot had stood for some time in the same position, and they were chiefly illuminated through the glass roof. The cotyledons of one of these seedlings moved downward in the morning till 11 a. Roman 1000, and then rose, moving rapidly in the evening until they stood vertically, so that in this case there was simply a single great daily fall and rise. The other seedling behaved rather differently, for it fell in the morning until 11 a. Roman 1000 and then rose, but after 12 p. Roman 1000 again fell, and the great evening rise did not begin until 1 p. Roman 1000 on the following morning. This cotyledon had fallen greatly from its vertical position by 8 a. Roman 1002 other seedlings 17, and the other 8 days old, had been previously observed under unfavorable circumstances, for they had been brought into a room and placed before a northeast window, where the temperature was between only 56 and 57. They had moreover to be protected from lateral light, and perhaps were not sufficiently illuminated under these circumstances. The cotyledons moved simply downwards from 7 a. Roman 1000 till 2 p. Roman 1000, after which hour, and during a large part of the night, they continued to rise between 7 and 8 a. Roman 1000. On the following morning they fell again, but on this 2nd, and likewise on the 3rd day, the movements became irregular, and between 3 and 10 p. Roman 1000 they circumnudated to a small extent about the same spot, but they did not rise at night. Nevertheless, on the following night they rose as usual. Cytisus fragrans leguminosae, only a few observations were made on this plant. The hypocotyl circumnudated to a considerable extent, but in a simple manner, namely for 2 hours in one direction, and then much more slowly back again in a zigzag course, almost parallel to the first line, and beyond the starting point it moved in the same direction all night, but next morning began to return. The cotyledons continually move both up and down, and laterally, but they do not rise up at night in a conspicuous manner. Lupinus luteus leguminosae seedlings of this plant were observed, because the cotyledons are so thick, about 1/8 of an inch, that it seemed unlikely that they would move. Our observations were not very successful, as the seedlings are strongly heliotropic, and their circumnutation could not be accurately observed near a northeast window. Although they had been kept during the previous day in the same position, a seedling was then placed. In darkness, with the hypocotyl secured to a stick, both cotyledons rose a little at first, and then fell during the rest of the day and the evening between 5 and 6 p. Roman 1000. They moved very slowly during the night, one continued to fall, and the other rose, though only a little. The tracing was not much magnified, and as the lines were plainly zigzag, the cotyledons must have moved a little laterally, that is, they must have circumnudated. The hypocotyl is rather thick, about 12 of inch. Nevertheless, it circumnudated in a complex course, though to a small extent the movement of an old seedling with 2 true leaves partially developed was observed in the dark, as the movement was magnified about 100 times. It is not trustworthy, and is not given, but there could be no doubt that the hypocotyl moved in all directions during the day, changing its course 19 times, the extreme actual distance from side to side, through which the upper part of the hypocotyl passed in the course of 12 hours, was only 160 of an inch. It sometimes travelled at the rate of 150 of an inch in an hour. Cucurbita ovifera, cucurbitase radical, a seed which had germinated on damp sand, was fixed, so that the slightly curved radical, which was only 7 inch in length, stood almost vertically upwards, in which position geotropism would act at first with little power. A filament was attached near to its base and projected at about an angle of 45 above the horizon. The general course followed during the 11 hours of observation, and during the following night is shown in the accompanying diagram Fig. 26, and was plainly due to geotropism, but it was also clear that the radical, circumnudated by the next morning, the tip had curved so much downwards that the filament, instead of projecting at 45 above the horizon, was nearly horizontal. Another germinating seed was turned upside down and covered with damp sand, and a filament was fastened to the radical so as to project at an angle of about 50 above the horizon. This radical was 35 of an inch in length, and a little curved. The course pursued was mainly governed, as in the last case, by geotropism, but the line traced during 12 hours, and magnified, as before, was more strongly zigzag, again showing circumnutation. Fig. 26, cucurbita ovifera course, followed by a radical in bending geotropically downwards, traced on a horizontal glass between 11 A Roman 1000 and 10 P Roman 1000. The direction during the night is indicated by the broken line movement of bead, magnified 14 times. 4 radicals were allowed to grow downwards over plates of smoked glass, inclined at 70 to the horizon under the same conditions, as in the cases of Sculus facialis and Vischer facsimiles, are here given. Fig. 27 of 2 of these tracks, and a third short one was almost as plainly serpentine as that at A. It was also manifest by a greater or less amount of soot having been swept off the glasses, that the tips had pressed alternately with greater and less force on them. There must therefore have been movement in at least 2 planes at right angles to one another. These radicals were so delicate that they rarely had the power to sweep the glasses quite clean. One of them had developed some lateral or secondary rootlets, which projected a few degrees beneath the horizon, and it is an important fact that 3 of them left distinctly serpentine tracks on the smoked surface, showing beyond doubt that they had circumnudated like the main or primary radical, but the tracks were so slight that they could not be traced and copied after the smoked surface had been varnished. Fig. 27, cucurbita ovifera, tracks left by tips of radicals in growing downwards over smoked glass plates, inclined at 70 to the horizon. Fig. 28, cucurbita ovifera, circumnutation of arched hypocotyl, at a very early age, traced in darkness on a horizontal glass, from 8 A Roman 1000 to 10 A Roman 1000, on the following day. The movement of the bead magnified 20 times here, reduced to 1/2 of original scale. Fig. 29, cucurbita ovifera, circumnutation of straight and vertical hypocotyl, with filament fastened transversely across its upper end, traced in darkness on a horizontal glass, from 8 A Roman 1000 to 8 P Roman 1000. The movement of the terminal bead, originally magnified about 18 times here, only 412 times. Hypocotyl A seed lying on damp sand was firmly fixed by 2 crossed wires, and by its own growing radical, the cotyledons were still enclosed within the seed coats, and the short hypocotyl between the summit of the radical and the cotyledons was as yet only slightly arched. A filament 85 of inch in length was attached at an angle of 35 above the horizon to the side of the arch adjoining the cotyledons. This part would ultimately form the upper end of the hypocotyl after it had grown straight and vertical. Had the seed been properly planted, the hypocotyl at this stage of growth would have been deeply buried beneath the surface. The course followed by the bead of the filament is shown in Fig 28. The chief lines of movement from left to right in the figure were parallel to the plane of the two united cotyledons and of the flattened seed, and this movement would aid in dragging them out of the seed coats, which are held down by a special structure. Hereafter to be described, the movement at right angles to the above lines was due to the arched hypocotyl becoming more arched as it increased in height. The foregoing observations apply to the leg of the arch, next to the cotyledons, but the other leg adjoining the radical likewise, circumnudated at an equally early age. The movement of the same hypocotyl after it had become straight and vertical, but with the cotyledons only partially expanded, is shown in Fig 29. The course pursued during 12H apparently represents 4½ ellipses or ovals, with the longer axis of the first at nearly right angles to that of the others. The longer axes of all were oblique to a line joining the opposite cotyledons. The actual extreme distance from side to side over which the summit of the tall hypocotyl passed in the course of 12H was 28 of an inch. The original figure was traced on a large scale, and from the obliquity of the line of view, the outer parts of the diagram are much exaggerated. Cotyledons. On 2 occasions, the movements of the cotyledons were traced on a vertical glass, and as the ascending and descending lines did not quite coincide, very narrow ellipses were formed. They therefore circumnudated. Whilst young they rise vertically up at night, but their tips always remain reflexed on the following morning. They sink down again, with a seedling kept in complete darkness. They moved in the same manner, for they sank from 8A Roman 1000 to 4P Roman 1000. They then began to rise and remained close together until 10P Roman 1000, when they were last observed at 7A Roman 1000 on the following morning. They were as much expanded as at any hour on the previous day. The cotyledons of another young seedling exposed to the light were fully open for the first time on a certain day, but were found completely closed at 7A Roman 1000 on the following morning. They soon began to expand again and continued doing so till about 5P Roman 1000. They then began to rise, and by 10P Roman 1000 stood vertically, and were almost closed at 7A Roman 1000 on the third morning. They were nearly vertical and again expanded during the day. On the fourth morning they were not closed, yet they opened a little in the course of the day, and rose a little on the following night. By this time, a minute true leaf had become developed. Another seedling, still older, bearing a well-developed leaf, had a sharp, rigid filament affixed to one of its cotyledons 85 Roman 2000 in length, which recorded its own movements on a revolving drum with smoked paper. The observations were made in the hothouse where the plant had lived, so that there was no change in temperature or light. The record commenced at 11A Roman 1000 on February 18th, and from this hour till 3P Roman 1000, the cotyledon fell. It then rose rapidly till 9P Roman 1000, then very gradually till 3A Roman 1000 February 19th, after which hour it sank gradually till 4P Roman 1000, but the downward movement was interrupted by one slight rise or oscillation about 1P Roman 1000 after 4P Roman 100,000 19th. The cotyledon rose till 1A Roman 1000 in the night of February 20th, and then sank very gradually till 9A Roman 1000. When our observations ceased, the amount of movement was greater on the 18th than on the 19th, or on the morning of the 20th. Cucurbita aurantia, an arched hypocotyl, was found buried a little beneath the surface of the soil, and in order to prevent it straightening itself quickly when relieved from the surrounding pressure of the soil, the two legs of the arch were tied together. The seed was then lightly covered with loose damp earth. A filament with a bead at the end was affixed to the basal leg, the movements of which were observed during 2 days in the usual manner. On the first day, the arch moved in a zigzag line towards the side of the basal leg. On the next day, by which time the dependent cotyledons had been dragged above the surface of the soil, the tied arch changed its course greatly. Times in the course of 1412H, it swept a large, extremely irregular circular figure, returning at night to nearly the same spot whence it had started early in the morning. The line was so strongly zigzag that it apparently represented 5 ellipses with their longer axes pointing in various directions with respect to the periodical movements of the cotyledons. Those of several young seedlings formed together at 4P Roman 1000 an angle of about 60, and at 10P Roman 1000 their lower parts stood vertically and were in contact. Their tips, however, as is usual in the genus, were permanently reflexed. These cotyledons at 7A Roman 1000 on the following morning were again well expanded. Legionaria vulgaris var miniature Bartlegird cucurbitaceae a seedling, opened its cotyledons, the movements of which were alone observed slightly on June 27th, and closed them at night next day at noon 28th. They included an angle of 53, and at 10 p Roman 1000 they were in close contact, so that each had risen 26:12 at noon on the 29th. They included an angle of 118, and at 10 p Roman 1000, an angle of 54, so each had risen 32 on the following day. They were still more open, and the nocturnal rise was greater, but the angles were not measured. 2 other seedlings were observed, and behaved during 3 days in a closely similar manner. The cotyledons therefore open more and more on each succeeding day, and rise each night about 30. Consequently, during the first 2 nights of their life, they stand vertically, and come into contact. Fig 30 Legionaria vulgaris circumnutation of a cotyledon 112 inch in length apex, only 434 inches from the vertical glass, on which its movements were traced from 7 A Roman 1000 July 11th to 9 A Roman 1000 on the 14th figure here, given reduced to 1/3 of original scale. In order to ascertain more accurately the nature of these movements, the hypocotyl of a seedling with its cotyledons well expanded was secured to a little stick, and a filament with triangles of paper was affixed to one of the cotyledons. The observations were made under a rather dim skylight, and the temperature during the whole time was between 1712 to 18 Roman 10,063 to 65. Had the temperature been higher, and the light brighter, the movements would probably have been greater. On July 11th, see Fig 30, the cotyledon fell from 7 A Roman 1000 till 10 A Roman 1000. It then rose rapidly after 4 P Roman 1000, till it stood quite vertically at 8 P Roman 1000 during the early morning of the next day 12th. It fell, and continued to fall till 8 A Roman 1000, after which hour it rose, then fell, and again rose, so that by 10 P Roman 1000 it stood much higher than it did in the morning, but was not vertical as on the preceding night. During the following early morning, and whole day 13th, it fell and circumnudated, but had not risen when observed late in the evening, and this was probably due to the deficiency of heat or light, or of both. We thus see that the cotyledons became more widely open at noon on each succeeding day, and that they rose considerably each night, though not acquiring a vertical position, except during the first 2 nights. Cucumis dudame cucurbitaceae, 2 seedlings had opened their cotyledons for the first time during the dayon to the extent of 90, and the other rather more. They remained in nearly the same position until 10 P Roman 1000, but by 7 A Roman 1000 on the following morning, the one which had been previously opened to the extent of 90 had its cotyledons vertical, and completely shut. The other seedling had them nearly shut. Later in the morning they opened in the ordinary manner. It appears therefore that the cotyledons of this plant close and open at somewhat different periods from those of the foregoing species of the allied genera of Cucurbita and Legionaria. Fig 31 Opuntia basilaris conjoint circumnutation of hypocotyl and cotyledon filament, fixed longitudinally to cotyledon, and movement traced during 66H on horizontal glass movement of the terminal bead, magnified about 30 times here, reduced to 1/3 scale seedling, kept in hothouse, feebly illuminated from above. Opuntia basilaris cacti a seedling was carefully observed, because considering its appearance and the nature of the mature plant, it seemed very unlikely that either the hypocotyl or cotyledons would circumnudate to an appreciable extent. The cotyledons were well developed, being 9 of an inch in length, 22 in breadth, and 15 in thickness. The almost cylindrical hypocotyl, now bearing a minute spinous bud on its summit, was only 45 of an inch in height, and 19 in diameter. The tracing Fig 31 shows the combined movement of the hypocotyl and of one of the cotyledons from 4 P Roman 1000 on May 28th to 11 A Roman 1000 on the 31st. On the 29th, a nearly perfect ellipse was completed. On the 30th, the hypocotyl moved from some unknown cause in the same general direction in a zigzag line, but between 4 and 10 P Roman 1000 almost completed a second small ellipse. The cotyledons move only a little up and down. Thus at 10 P Roman 1000 they stood only 10 higher than at noon, the chief seat of movement therefore, at least when the cotyledons are rather old, as in the present case, lies in the hypocotyl. The ellipse described on the 29th had its longer axis directed at nearly right angles to a line joining the 2 cotyledons. The actual amount of movement of the bead at the end of the filament was, as far as could be ascertained, about 14 of an inch. Fig 32 Helianthus annus circumnutation of hypocotyl, with filament fixed across its summit, traced on a horizontal glass in darkness, from 8 Roman 1000 to 10 Roman 1000, and for an hour on following morning movement of bead, magnified 21 times here, reduced to 1/2 of original scale. Helianthus annus composite, the upper part of the hypocotyle moved during the daytime in the course shown in the annexed figure Fig. 32, as the line runs in various directions crossing itself several times. The movement may be considered as one of circumnutation. The extreme actual distance travelled was at least 1 inch. The movements of the cotyledons of 2 seedlings were observed, one facing a northeast window, and the other so feebly illuminated from above us as to be almost in darkness. They continued to sink till about noon, when they began to rise, but between 5 and 7 or 8 Roman 1000, they either sank a little or moved laterally, and then again began to rise at 7 Roman 1000 on the following morning. Those on the plant before the northeast window had opened so little that they stood at an angle of 73 above the horizon, and were not observed any longer. Those on the seedling, which had been kept in almost complete darkness, sank during the whole day without rising about midday, but rose during the night. On the 3rd and 4th days they continued sinking without any alternate ascending movement, and this no doubt was due to the absence of light. Primula sinensis primulaceae, a seedling, was placed with the 2 cotyledons parallel to a northeast window on a day when the light was nearly uniform, and a filament was affixed to one of them from observations subsequently made on another seedling, with the stem secured to a stick. The greater part of the movement shown in the annexed figure Fig. 33 must have been that of the hypocotyle, though the cotyledons certainly move up and down to a certain extent both during the day and night. The movements of the same seedling were traced on the following day with nearly the same result, and there can be no doubt about the circumnutation of the hypocotyle. Fig. 33 Primula sinensis, conjoint circumnutation of hypocotyle and cotyledon traced on vertical glass, from 8 Roman 1000 to 10 Roman 1000 movements of bead, magnified about 26 times. Cyclamen persicum primulaceae, this plant is generally supposed to produce only a single cotyledon, but Dr. H. Gressner, too, has shown that a second one is developed after a long interval of time. The hypocotyle is converted into a globular corm even before the first cotyledon has broken through the ground, with its blade closely enfolded, and with its petiole in the form of an arch like the arched hypocotyle or epicotyle of any ordinary dicotyledonous plant. A glass filament was affixed to a cotyledon 55 of an inch in height, the petiole of which had straightened itself and stood nearly vertical, but with the blade not as yet fully expanded. Its movements were traced during 2412H on a horizontal glass magnified 50 times, and in this interval it described 2 irregular small circles. It therefore circumnudates, though on an extremely small scale. Fig. 34 Stapelia sarpedon circumnutation of hypocotyle, illuminated from above, traced on horizontal glass, from 6 Roman 1000 June 26th to 8 Roman 1000 temp. 23, 24 Roman 100 movement of bead, magnified 21 times. Stapelia sarpedon asclepiade, this plant when mature resembles a cactus. The flattened hypocotyle is fleshy enlarged in the upper part, and bears 2 rudimentary cotyledons. It breaks through the ground in an arched form with the rudimentary cotyledons closed, or in contact. A filament was affixed almost vertically to the hypocotyle of a seedling 1/2 inch high, and its movements were traced during 50H on a horizontal glass. Fig. 34 From some unknown cause, it bowed itself to one side, and as this was affected by a zigzag course it probably circumnudated, but with hardly any other seedling observed by us was this movement so obscurely shown. Ipoma caerulea vel farbitis nil convolvulaceae seedlings of this plant were observed, because it is a twiner, the upper internodes of which circumnudate conspicuously, but like other twining plants, the first few internodes which rise above the ground are stiff enough to support themselves, and therefore do not circumnudate in any plainly recognizable manner. 3 In this particular instance, the 5th internode, including the hypocotyle, was the first which plainly circumnudated and twined round a stick. We therefore wished to learn whether circumnutation could be observed in the hypocotyle. If carefully observed in our usual manner, 2 seedlings were kept in the dark, with filaments fixed to the upper part of their hypocotyles, but from circumstances not worth explaining their movements were traced for only a short time. One moved thrice forwards and twice backwards, in nearly opposite directions, in the course of 3H 15 Roman 1000, and the other twice forwards and twice backwards, in 2H 22 Roman 1000. The hypocotyle therefore circumnudated at a remarkably rapid rate. It may here be added that a filament was affixed transversely to the summit of the second internode above the cotyledons of a little plant 312 inches in height, and its movements were traced on a horizontal glass it circumnudated, and the actual distance travelled from side to side was 1/4 of an inch, which was too small an amount to be perceived without the aid of marks. The movements of the cotyledons are interesting from their complexity and rapidity, and in some other respects, the hypocotyl 2 inches high of a vigorous seedling was secured to a stick, and a filament with triangles of paper was affixed to one of the cotyledons. The plant was kept all day in the hothouse, and at 4 p. Roman 1000 June 20th was placed under a skylight in the house, and observed occasionally during the evening and night. It fell in a slightly zigzag line, to a moderate extent from 4 p. Roman 1000 till 10 p. Roman 1000. When looked at shortly after midnight 12 p. Roman 1000, it had risen a very little and considerably by 3 a. Roman 1000. When again looked at 6 a. Roman 100,000 21st, it had fallen largely. A new tracing was now begun, see Fig. 35, and soon afterwards, at 6 a. Roman 1000, the cotyledon had risen a little during the forenoon. It was observed about every hour, but between 12 and 6 p. Roman 1000 every half-hour. If the observations had been made at these short intervals during the whole day, the figure would have been too intricate to have been copied, as it was the cotyledon moved up and down in the course of 16h 20 Roman 1000 Roman 1 e, between 6 a Roman 1000 and 10 p. Roman 1000 13 times. Fig. 35 Ipoma caerulea circumnutation of cotyledon, traced on vertical glass, from 6 a Roman 1000 June 21st, to 6 a Roman 1000th cotyledon, with petiole 1 inch in length, apex of blade 4 inch from the vertical glass, so movement not greatly magnified. Temp. 20 Roman 100. The cotyledons of this seedling sank downwards during both evenings and the early part of the night, but rose during the latter part. As this is an unusual movement, the cotyledons of 12 other seedlings were observed. They stood almost or quite horizontally at midday, and at 10 p. Roman 1000 were all declined at various angles. The most usual angle was between 30 and 35, but 3 stood at about 50, and 1 at even 70 beneath the horizon. The blades of all these cotyledons had attained almost their full size, viz. from 1 to 112 inches in length measured along their midribs. It is a remarkable fact that whilst young, that is when less than half an inch in length, measured in the same manner, they do not sink downwards in the evening. Therefore their weight, which is considerable, when almost fully developed, probably came into play in originally determining the downward movement. The periodicity of this movement is much influenced by the degree of light to which the seedlings have been exposed during the day, for 3 kept in an obscure place began to sink about noon instead of late in the evening, and those of another seedling were almost paralyzed by having been similarly kept during 2 whole days. The cotyledons of several other species of Ipoma likewise sink downwards late in the evening. Cerinth major borygini, the circumnutation of the hypocotyl of a young seedling with the cotyledons hardly expanded, is shown in the annexed figure Fig. 36, which apparently represents 4 or 5 irregular ellipses, described in the course of a little over 12 hours. 2 older seedlings were similarly observed, excepting that one of them was kept in the dark, their hypocotyls also circumnutated, but in a more simple manner. The cotyledons on a seedling exposed to the light fell from the early morning until a little afternoon, and then continued to rise until 10 p. Roman 1000, or later. The cotyledons of this same seedling acted in the same general manner during the 2 following days. It had previously been tried in the dark, and after being thus kept for only 1h 40 Roman 1000, the cotyledons began at 4 p. Roman 1000 to sink instead of continuing to rise till late at night. Fig. 36 Cerinth major circumnutation of hypocotyl, with filament fixed across its summit, illuminated from above, traced on horizontal glass, from 9 a Roman 1000 to 9 p. Roman 1000, on arced 25th movement of the bead, magnified 30 times, here reduced to 1/3 of original scale. Nalana prostrata nalini, the movements were not traced, but a part with seedlings which had been kept in the dark for an hour was placed under the microscope with the micrometer eyepiece, so adjusted that each division equaled 1/1500th of an inch. The apex of one of the cotyledons crossed rather obliquely 4 divisions in 13 minutes. It was also sinking, as shown by getting out of focus. The seedlings were again placed in darkness for another hour, and the apex now crossed 2 divisions in 6 Roman 1000 s, that is at very nearly the same rate as before. After another interval of an hour in darkness, it crossed 2 divisions in 4 Roman 1000 s, therefore, at a quicker rate in the afternoon. After a longer interval in the dark, the apex was motionless. But after a time, it recommenced moving, though slowly. Perhaps the room was too cold. Judging from previous cases, there can hardly be a doubt that this seedling was circumnutating. Solanum lycopersicum salini, the movements of the hypocartels of 2 seedling tomatoes were observed during 7 hours, and there could be no doubt that both circumnutated. They were illuminated from above, but by an accident, a little light entered on one side, and in the accompanying figure 37, it may be seen that the hypocartel moved to this side, the upper one in the figure, making small loops and zigzagging in its course. The movements of the cartiledons were also traced both on vertical and horizontal glasses. Their angles with the horizon were likewise measured at various hours. They fell from 8A Roman 1000 October 17th to about noon, then moved laterally in a zigzag line, and at about 4P Roman 1000 began to rise. They continued to do so until 10P Roman 1000, by which hour they stood vertically, and were asleep. At what hour of the night or early morning they began to fall was not ascertained, owing to the lateral movement. Shortly after midday, the descending and ascending lines did not coincide, and irregular ellipses were described during each 24H. The regular periodicity of these movements is destroyed, as we shall hereafter see, if the seedlings are kept in the dark. Fig. 37 Solanum lycopersicum circumnutation of hypocartel, with filament fixed across its summit, traced on horizontal glass, from 10A Roman 1000 to 5P Roman 1000 arc 24th, illuminated obliquely from above. Movement of bead magnified about 35 times here, reduced to 1/3 of original scale. Solanum palinacanthum, several arched hypocartels rising nearly 2 of an inch above the ground, but with the cartiledons still buried beneath the surface, were observed, and the tracing showed that they circumnutated. Moreover, in several cases, little open circular spaces or cracks in the argillaceous sand which surrounded the arched hypocartels were visible, and these appeared to have been made by the hypocartels having bent first to one and then to another side, whilst growing upwards. In 2 instances, the vertical arches were observed to move to a considerable distance backwards from the point where the cartiledons lay buried. This movement, which has been noticed in some other cases, and which seems to aid in extracting the cartiledons from the buried seed coats, is due to the commencement of the straightening of the hypocartel. In order to prevent this latter movement, the 2 legs of an arch, the summit of which was on a level with the surface of the soil, were tied together, the earth having been previously removed to a little depth, all round the movement of the arch during 47 hours. Under these unnatural circumstances, is exhibited in the annexed figure. Fig. 38 Solanum palinacanthum circumnutation of an arched hypocartel, just emerging from the ground with the 2 legs tied together, traced in darkness on a horizontal glass, from 9A Roman 1000 dec 17th to 8A Roman 1000th. Movement of bead magnified 13 times, but the filament which was affixed obliquely to the crown of the arch was of unusual length. The cartiledons of some seedlings in the hothouse were horizontal about noon on December 13th, and at 10P Roman 1000 had risen to an angle of 27 above the horizon. At 7A Roman 1000 on the following morning, before it was light, they had risen to 59 above the horizon. In the afternoon of the same day, they were found again horizontal. Beta vulgaris chenopodi, the seedlings are excessively sensitive to light, so that although on the first day they were uncovered only during 2 or 3 minutes at each observation, they all moved steadily towards the side of the room whence the light proceeded, and the tracings consisted only of slightly zigzag lines directed towards the light. On the next day, the plants were placed in a completely darkened room, and at each observation were illuminated as much as possible from vertically above by a small wax taper. The annexed figure Fig. 39 shows the movement of the hypocartel during 9H. Under these circumstances, a second seedling was similarly observed at the same time, and the tracing had the same peculiar character due to the hypocartel often moving and returning in nearly parallel lines. The movement of a third hypocartel differed greatly. Fig. 39 Beta vulgaris circumnutation of hypocartel with filament fixed obliquely across its summit, traced in darkness on horizontal glass, from 8A Roman 1000 to 5P Roman 1000 nav. Fourth movement of bead magnified 23 times here, reduced to 1/3 of original scale. We endeavoured to trace the movements of the cartiledons, and for this purpose some seedlings were kept in the dark, but they moved in an abnormal manner. They continued rising from 8A Roman 1000 to 2P Roman 1000, then moved laterally, and from 3 to 6P Roman 1000 descended, whereas cartiledons which have been exposed all the day to the light rise in the evening so as to stand vertically at night. But this statement applies only to young seedlings. For instance, 6 seedlings in the greenhouse had their cotyledons partially open for the first time on the morning of November 15th, and at 8 p. Roman 1000 all were completely closed, so that they might properly be said to be asleep again on the morning of November 27th. The cotyledons of 4 other seedlings, which were surrounded by a collar of brown paper, so that they received light only from above, were open to the extent of 39 at 10 p. Roman 1000. They were completely closed next morning, November 28th, at 6 a. Roman 1000. Whilst it was still dark, 2 of them were partially open, and all opened in the course of the morning. But at 10 p. Roman 1000, all 4, not to mention 9 others which had been open in the morning, and 6 others on another occasion, were again completely closed on the morning of the 29th. They were open, but at night only 1 of the 4 was closed, and this only partially. The 3 others had their cotyledons much more raised than during the day on the night of the 30th. The cotyledons of the 4 were only slightly raised. Ricinus bourboniensis euphorbiaceae seeds were purchased under the above name, probably a variety of the common castoral plant. As soon as an arched hypocotyl had risen clear above the ground, a filament was attached to the upper leg, bearing the cotyledons which were still buried beneath the surface, and the movement of the bead was traced on a horizontal glass during a period of 34h. The lines traced were strongly zigzag, and as the bead twice returned nearly parallel to its former course in 2 different directions, there could be no doubt that the arched hypocotyl circumnudated at the close of the 34h. The upper part began to rise and straighten itself, dragging the cotyledons out of the ground, so that the movements of the bead could no longer be traced on the glass. Quercus American sb cupuliferae acorns of an American oak which had germinated at Q were planted in a pot in the greenhouse. This transplantation checked their growth, but after a time one grew to a height of 5 inches, measured to the tips of the small, partially unfolded leaves on the summit, and now looked vigorous. It consisted of 6 very thin internodes of unequal lengths. Considering these circumstances, and the nature of the plant, we hardly expected that it would circumnudate, but the annexed figure Fig. 40 shows that it did so in a conspicuous manner, changing its course many times, and travelling in all directions during the 48h of observation. The figure seems to represent 5 or 6 irregular ovals, or ellipses. The actual amount of movement from side to side, excluding one great bend to the left, was about 2 of an inch, but this was difficult to estimate as, owing to the rapid growth of the stem, the attached filament was much further from the mark beneath at the close than at the commencement of the observations. It deserves notice that the pot was placed in a northeast room within a deep box, the top of which was not at first covered up, so that the inside facing the windows was a little more illuminated than the opposite side. And during the first morning, the stem travelled to a greater distance in this direction to the left in the figure than it did afterwards, when the box was completely protected from light. Fig. 40 Quercus American sb circumnutation of young stem traced on horizontal glass from 12 p. Roman 1000 Feb. 22nd to 12 p. Roman 1000th movement of bead, greatly magnified at first, but slightly towards the close of the observations, about 10 times on an average. Quercus robur observations were made only on the movements of the radicals from germinating acorns, which were allowed to grow downwards in the manner previously described over plates of smoked glass, inclined at angles between 65 and 69 to the horizon. In 4 cases the tracks left were almost straight, but the tips had pressed sometimes with more and sometimes with less force on the glass, as shown by the varying thickness of the tracks, and by little bridges of soot left across them. In the 5th case, the track was slightly serpentine, that is, the tip had moved a little from side to side. In the 6th case, Fig. 41a, it was plainly serpentine, and the tip had pressed almost equably on the glass in its whole course. In the 7th case, b, the tip had moved both laterally and had pressed alternately with unequal force on the glass, so that it had moved a little in 2 planes at right angles to one another. In the 8th and last case, c, it had moved very little laterally, but had alternately left the glass and come into contact with it again. There can be no doubt that in the last 4 cases the radical of the oak circumnudated whilst growing downwards. Fig. 41 Quercus robur tracks left on inclined smoked glass plates by tips of radicals in growing downwards, plates A and C inclined at 65, and plate B at 68 to the horizon. Corylus avellana corylacea, the epicotyl breaks through the ground in an arched form, but in the specimen which was first examined, the apex had become decayed, and the epicotyl grew to some distance through the soil, in a tortuous, almost horizontal direction, like a root. In consequence of this injury, it had emitted near the hypogene cotyledons 2 secondary shoots, and it was remarkable that both of these were arched like the normal epicardal in ordinary cases. The soil was removed from around one of these arched secondary shoots, and a glass filament was affixed to the basal leg. The whole was kept damp beneath a metal box with a glass lid, and was thus illuminated only from above, owing apparently to the lateral pressure of the earth being removed. The terminal and bowie-down part of the shoot began at once to move upwards, so that after 24h it formed a right angle with the lower part. This lower part to which the filament was attached also straightened itself and moved a little backwards from the upper part. Consequently, a long line was traced on the horizontal glass, and this was in parts straight and in parts decidedly zigzag, indicating circumnutation. On the following day the other secondary shoot was observed. It was a little more advanced in age, for the upper part, instead of depending vertically downwards, stood at an angle of 45 above the horizon. The tip of the shoot projected obliquely 4 of an inch above the ground, but by the close of our observations, which lasted 47h, it had grown chiefly towards its base to a height of 85 of an inch. The filament was fixed transversely to the basal and almost upright half of the shoot close beneath the lowest scale-like appendage. The circumnudating course pursued is shown in the accompanying figure, Fig. 42. The actual distance traversed from side to side was about 4 of an inch. Fig. 42. Corylus avellana circumnutation of a young shoot, emitted from the epicardal, the apex of which had been injured, traced on a horizontal glass, from 9a Roman 1000 Feb second to 8a Roman 1000th movement of bead, magnified about 27 times. Pinus pinaster carniferae, young hypocardal with the tips of the cotyledons still enclosed within the seedcoats, was at first only 35 of an inch in height, but the upper part grew so rapidly that at the end of our observations it was 6 in height, and by this time the filament was attached some way down the little stem. From some unknown cause, the hypocardal moved far towards the left, but there could be no doubt, Fig. 43, that it circumnudated another hypocardal was similarly observed, and it likewise moved in a strongly zigzag line to the same side. This lateral movement was not caused by the attachment of the glass filaments, nor by the action of light, for no light was allowed to enter when each observation was made, except from vertically above. Fig. 43. Pinus pinaster circumnutation of hypocardal, with filament fixed across its summit, traced on horizontal glass, from 10a Roman 1000 March 21st to 9a Roman 1000th seedling, kept in darkness, movement of bead, magnified about 35 times. The hypocardal of a seedling was secured to a little stick. It bore 9, in appearance distinct cotyledons, arranged in a circle. The movements of 2 nearly opposite ones were observed. The tip of one was painted white with a mark placed below, and the figure described, Fig. 44a, shows that it made an irregular circle in the course of about 8h during the night. It travelled to a considerable distance in the direction indicated by the broken line. A glass filament was attached longitudinally to the other cotyledon, and this nearly completed Fig. 44b, an irregular circular figure, in about 12 hours during the night. It also moved to a considerable distance in the direction indicated by the broken line. The cotyledons therefore circumnudate independently of the movement of the hypocardal. Although they moved much during the night, they did not approach each other so as to stand more vertically than during the day. Fig. 44. Pinus pinaster circumnutation of 2 opposite cotyledons, traced on horizontal glass in darkness, from 8a Roman 1000 to 8p Roman 1000 Nav, 25th movement of tip, in a magnified about 22 times here, reduced to 1/2 of original scale. Cycas pectinata cycade, the large seeds of this plant in germinating first protrude a single leaf, which breaks through the ground with the petiole bowed into an arch, and with the leaflets involuted. A leaf in this condition, which at the close of our observations was 212 inches in height, had its movements traced in a warm greenhouse by means of a glass filament bearing paper triangles attached across its tip. The tracing, Fig. 45, shows how large, complex and rapid were the circumnudating movements. The extreme distance from side to side, which it passed over, amounted to between 6 and 7 of an inch. Fig. 45. Cycas pectinata circumnutation of young leaf, whilst emerging from the ground, feebly illuminated from above, traced on vertical glass, from 5p Roman 1000 May 28th to 11a Roman 1000th movement, magnified 7 times here, reduced to 2/3 of original scale. Canna warsuixii canaceae, a seedling with the plumule projecting 1 inch above the ground, was observed, but not under fair conditions, as it was brought out of the hothouse and kept in a room not sufficiently warm. Nevertheless, the tracing Fig 46 shows that it made 2 or 3 incomplete irregular circles, or ellipses, in the course of 48 hours. The plumule is straight, and this was the first instance observed by us of the part that first breaks through the ground not being arched. Fig 46 can a Warsuixii circumnutation of plumule with filament, affixed obliquely to outer sheath-like leaf, traced in darkness on horizontal glass, from 8a Roman 1000 nav 9th to 8a Roman 1000th movement of bead, magnified 6 times. Allium cepa liliaceae, the narrow green leaf which protrudes from the seed of the common onion, as a cotyledon 4 breaks through the ground in the form of an arch in the same manner as the hypocotyl or epicotyl of a dicotyledonous plant. Long after the arch has risen above the surface, the apex remains within the seed coats, evidently absorbing the still abundant contents. The summit or crown of the arch when it first protrudes from the seed and is still buried beneath the ground is simply rounded, but before it reaches the surface, it is developed into a conical protuberance of a white color, owing to the absence of chlorophyll, whilst the adjoining parts are green with the epidermis, apparently rather thicker and tougher than elsewhere. We may therefore conclude that this conical protuberance is a special adaptation for breaking through the ground 5, and answers the same end as the knife-like white crest on the summit of the straight cotyledon of the gramen. After a time, the apex is drawn out of the empty seed coats, and rises up forming a right angle or more commonly, a still larger angle with the lower part, and occasionally the whole becomes nearly straight. The conical protuberance, which originally formed the crown of the arch, is now seated on one side, and appears like a joint or knee which from acquiring chlorophyll becomes green, and increases in size in rarely or never becoming perfectly straight. These cotyledons differ remarkably from the ultimate condition of the arched hypocotyls or epicotyls of dicotyledons. It is also a singular circumstance that the attenuated extremity of the upper bent portion invariably withers and dies. A filament 1 inch in length was affixed nearly upright beneath the knee to the basal and vertical portion of a cotyledon, and its movements were traced during 14h in the usual manner. The tracing here given Fig 47 indicates circumnutation, the movement of the upper part above the knee of the same cotyledon, which projected at about an angle of 45 above. The horizon was observed at the same time. A filament was not affixed to it, but a mark was placed beneath the apex which was almost white from beginning to wither, and its movements were thus traced. The figure described resembled pretty closely that above given, and this shows that the chief seat of movement is in the lower or basal part of the cotyledon. Fig 47 Allium cepa circumnutation of basal half of arched cotyledon, traced in darkness on horizontal glass, from 8a Roman 1000 to 10p Roman 1000 oct, 31st movement of bead, magnified about 17 times. Asparagus officinalis asparagi, the tip of a straight plumule, or cotyledon, for we do not know which it should be called, was found at a depth of 1 inch beneath the surface, and the earth was then removed all round to the department of 3 inch. A glass filament was affixed obliquely to it, and the movement of the bead magnified 17 times was traced in darkness during the first 1h 15 Roman 1000. The plumule moved to the right, and during the next 2 hours it returned in a roughly parallel but strongly zigzag course. From some unknown cause it had grown up through the soil in an inclined direction, and now through apogeotropism it moved during nearly 24h in the same general direction, but in a slightly zigzag manner until it became upright on the following morning. It changed its course completely. There can therefore hardly be a doubt that the plumule circumnudates whilst buried beneath the ground, as much as the pressure of the surrounding earth will permit. The surface of the soil in the pot was now covered with a thin layer of very fine argillaceous sand which was kept damp, and after the tapering seedlings had grown a few tenths of an inch in height, each was found surrounded by a little open space or circular crack, and this could be accounted for only by their having circumnudated, and thus pushed away the sand on all sides, for there was no vestige of a crack in any other part. In order to prove that there was circumnutation, the movements of 5 seedlings varying in height from 3 inch to 2 inches were traced. They were placed within a box, and illuminated from above, but in all 5 cases, the longer axes of the figures described were directed to nearly the same point, so that more light seemed to have come through the glass roof of the greenhouse on one side than on any other. All 5 tracings resembled each other to a certain extent, and it will suffice to give 2 of them in a Fig 48. The seedling was only 45 of an inch in height, and consisted of a single internode bearing a bud on its summit. the apex described between 8A Roman 1000 and 10P Roman 1000 Roman 1E during nearly 14 hours, a figure which would probably have consisted of 312 ellipses, had not the stem been drawn to one side, until 1P Roman 1000, after which hour it moved backwards on the following morning. It was not far distant from the point whence it had first started. The actual amount of movement of the apex from side to side was very small, viz. about 1/18th of an inch. The seedling, of which the movements are shown in Fig 48b, was 134 inch in height, and consisted of 3 internodes besides the bud on the summit. The figure, which was described during 10H, apparently represents 2 irregular and unequal ellipses, or circles. The actual amount of movement of the apex in the line not influenced by the light was 11 of an inch, and in that thus influenced 37 of an inch, with a seedling 2 inches in height. It was obvious, even without the aid of any tracing, that the uppermost part of the stem bent successively to all points of the compass like the stem of a twining plant. A little increase in the power of circumnudating, and in the flexibility of the stem, would convert the common asparagus into a twining plant, as has occurred with one species in this genus, namely a scandens. Fig 48, asparagus officinalis, circumnutation of plumules with tips whitened and marks placed beneath traced on a horizontal glass. A young plumule movement traced from 8A Roman 1000 Nav 30th to 7A Roman 1000 next morning, magnified about 35 times. B. Older plumule movement traced from 10A Roman 1000 to 8P Roman 1000 Nav 29th, magnified 9 times, but here reduced to 1/2 of original scale. Phalaris canariensis, gramen with the gramen, the part which first rises above the ground, has been called by some authors the piliole, and various views have been expressed on its homological nature. It is considered by some great authorities to be a cotyledon, which term we will use without venturing to express any opinion on the subject. 6. It consists in the present case of a slightly flattened reddish sheath, terminating upwards in a sharp white edge. It encloses a true green leaf, which protrudes from the sheath through a slit-like orifice close beneath and at right angles to the sharp edge on the summit. The sheath is not arched when it breaks through the ground. The movements of 3 rather old seedlings, about 112 inch in height, shortly before the protrusion of the leaves, were first traced. They were illuminated exclusively from above, for, as will hereafter be shown, they are excessively sensitive to the action of light, and if any enters even temporarily on one side, they merely bend to this side, in slightly zigzag lines. Of the 3 tracings, one alone, Fig 49, is here given. Had the observations been more frequent during the 12H2 oval figures, would have been described with their longer axes at right angles to one another. The actual amount of movement of the apex from side to side was about 3 of an inch. The figures described by the other 2 seedlings resembled to a certain extent the one here given. Fig 49, Phalaris canariensis, circumnutation of a cotyledon with a mark placed below the apex, traced on a horizontal glass from 8A Roman 1000 Nav 26th to 8A Roman 1000th movement of apex, magnified 7 times, here reduced to 1/2 scale. A seedling which had just broken through the ground and projected only 1/20th of an inch above the surface was next observed in the same manner as before. It was necessary to clear away the earth all round the seedling to a little depth in order to place a mark beneath the apex. The figure Fig 50 shows that the apex moved to one side, but changed its course 10 times in the course of the 10 hours of observation, so that there can be no doubt about its circumnutation. The cause of the general movement in one direction could hardly be attributed to the entrance of lateral light, as this was carefully guarded against, and we suppose it was in some manner connected with the removal of the earth round the little seedling. Fig 50, Phalaris canariensis, circumnutation of a very young cotyledon with a mark placed below the apex, traced on a horizontal glass from 11A Roman 1000 to 9P Roman 1000 dec 13th movement of apex, greatly magnified here, reduced to 1/4 of original scale. Lastly, the soil in the same part was searched with the aid of a lens, and the white knife-like apex of a seedling was found on an exact level with that of the surrounding surface. The soil was removed all round the apex to the depth of 1/4 of an inch. The seed itself remaining covered. The part protected from lateral light was placed under the microscope with a micrometer eyepiece so arranged that each division equaled 1/1500th of an inch. After an interval of 30 Roman 1000, the apex was observed, and it was seen to cross a little obliquely 2 divisions of the micrometer in 9 Roman 1000s. and after a few minutes it crossed the same space in 8 Roman 1000s. The seedling was again observed after an interval of 3/4 of an hour, and now the apex crossed rather obliquely 2 divisions in 10 Roman 1000. We may therefore conclude that it was travelling at about the rate of 1/150th of an inch in 45 minutes. We may also conclude from these and the previous observations that the seedlings of Phalaris in breaking through the surface of the soil circumnudate, as much as the surrounding pressure will permit this fact accounts, as in the case before given of the asparagus for a circular narrow open space or crack, being distinctly visible round several seedlings, which had risen through very fine argillaceous sand, kept uniformly damp. Fig 51, Z, May's circumnutation of cotyledon traced on horizontal glass from 8a Roman 1000 Feb 4th to 8a Roman 1000th movement of bead, magnified on an average about 25 times. Z. May's gramine A glass filament was fixed obliquely to the summit of a cotyledon rising 2 of an inch above the ground, but by the third morning it had grown to exactly thrice this height, so that the distance of the bead from the mark below was greatly increased. Consequently, the tracing Fig 51 was much more magnified on the first than on the second day. The upper part of the cotyledon changed its course by at least as much as a rectangle, 6 times on each of the 2 days. The plant was illuminated by an obscure light from vertically above. This was a necessary precaution, as on the previous day we had traced the movements of cotyledons placed in a deep box, the inner side of which was feebly illuminated on one side from a distant northeast window, and at each observation by a wax taper held for a minute or 2 on the same side, and the result was that the cotyledons travelled all day long to this side, though making in their course some conspicuous flexures, from which fact alone we might have concluded that they were circumnudating, but we thought it advisable to make the tracing above given. Radicals glass filaments were fixed to 2 short radicals placed so as to stand almost upright, and whilst bending downwards through geotropism, their courses were strongly zigzag. From this latter circumstance circumnutation might have been inferred, had not their tips become slightly withered after the first 24h, though they were watered, and the air kept very damp. 9 radicals were next arranged in the manner formerly described, so that in growing downwards, they left tracks on smoked glass plates inclined at various angles between 45 and 80 beneath the horizon. Almost every one of these tracks offered evidence in their greater or less breadth in different parts, or in little bridges of soot being left, that the apex had come alternately into more and less close contact with the glass. In the accompanying figure Fig 52, we have an accurate copy of one such track in 2 instances alone, and in these the plates were highly inclined. There was some evidence of slight lateral movement. We presume therefore that the friction of the apex on the smoked surface, little as this, could have been sufficed to check the movement from side to side of these delicate radicals. Fig 52, Z. May's track left on inclined smoked glass plate by tip of radical in growing downwards. Avena sativa gramine A cotyledon 112 inch in height was placed in front of a northeast window, and the movement of the apex was traced on a horizontal glass during 2 days. It moved towards the light in a slightly zigzag line from 9 to 11 a Roman 1000 on October 15th. It then moved a little backwards and zigzagged much until 5 p Roman 1000, after which hour, and curring the night it continued to move towards the window on the following morning. The same movement was continued, a nearly straight line, until 12 p Roman 1000, when the sky remained until 2 extraordinarily dark from thunderclouds during this interval of 1h 55 Roman 1000. Whilst the light was obscure, it was interesting to observe how circumnutation overcame heliotropism for the apex, instead of continuing to move towards the window in a slightly zigzag line, reversed its course 4 times, making 2 small narrow ellipses. A diagram of this case will be given in the chapter on heliotropism. A filament was next fixed to a cotyledon only 14 of an inch in height, which was illuminated exclusively from above, and as it was kept in a warm greenhouse it grew rapidly, and now there could be no doubt about its circumnutation, for it described a figure of 8 as well as 2 small ellipses in 512 hours. Nephrodium mall Phyllis A seedling fern of this species came up by chance in a flower pot near its parent. The frond, as yet only slightly lobed, was only 16 of an inch in length and 2 in breadth, and was supported on a rachis as fine as a hair, and 23 of an inch in height. A very thin glass filament, which projected for a length of 36 of an inch, was fixed to the end of the frond. The movement was so highly magnified that the figure Fig 53 cannot be fully trusted, but the frond was constantly moving in a complex manner, and the bead greatly changed its course 18 times in the 12 hours of observation within half an hour. It often returned in a line almost parallel to its former course. The greatest amount of movement occurred between 4 and 6 p Roman 1000. The circumnutation of this plant is interesting because the species in the genus Lygodium are well known to circumnutate conspicuously and to twine round any neighboring object. Fig 53 Nephrodium mall circumnutation of very young frond, traced in darkness on horizontal glass, from 9a Roman 1000 to 9p Roman 1000 oct 30th movement of bead, magnified 48 times. Selaginella crossii lycopodiace, a very young plant, only 4 of an inch in height, had sprung up in a pot in the hothouse. An extremely fine glass filament was fixed to the end of the frond-like stem, and the movement of the bead traced on a horizontal glass. It changed its course several times as shown in Fig 54, whilst observed during 13h15 Roman 1000, and returned at night to a point not far distant from that whence it had started in the morning. There can be no doubt that this little plant circumnutated. Fig 54 Selaginella crossii circumnutation of young plant, kept in darkness traced from 8a Roman 1000 to 10p Roman 1000 oct 31st. Chapter Roman 2 General considerations on the movements and growth of seedling plants. Generality of the circumnudating movement radicals, their circumnutation of service manner, in which they penetrate the ground, manner in which hypocotyls and other organs break through the ground, by being arched, singular manner of germination, in megarrhiza etc. abortion, of cotyledon circumnutation of hypocotyls and epicotyls, whilst still buried and arched, their power of straightening themselves, bursting of the seed coats, inherited effect of the arching process, in hypogene, hypocotyl circumnutation of hypocotyls and epicotyls, when erect circumnutation of cotyledons pulvini, or joints of cotyledons, duration of their activity rudimentary, in oxalis corniculata their development, sensitiveness of cotyledons to light, and consequent disturbance of their periodic movements, sensitiveness of cotyledons to contact. The circumnudating movements of the several parts or organs of a considerable number of seedling plants have been described in the last chapter. A list is here appended of the families, cohorts, subclasses, etc., to which they belong, arranged and numbered, according to the classification adopted by Hooker. Anyone who will consider this list will see that the young plants selected for observation fairly represent the whole vegetable series, excepting the lowest cryptogams, and the movements of some of the latter when mature will hereafter be described. As all the seedlings which were observed, including conifers, cycads, and ferns, which belong to the most ancient types amongst plants, were continually circumnudating, we may infer that this kind of movement is common to every seedling species. Subkingdom Roman 1 Phenogamous plants. Class Roman 1 Dicotyledons. Subclass Roman 1 Angiosperms. Family Cohort 14 Cruciferi, Roman 2 Parietals, 26 Caryophyllae, Roman 4 Caryophyllales, 36 Malvaceae, Roman 6 Malvils, 41 Oxalidae, Roman 7 Geranials, 49 Tropioli, ditto 52 Aurantiaceae, ditto 70 Hippocastaneae, Roman 10 Sapindales, 75 Leguminosae, Roman 11 Rosals, 106 Cucurbidaceae, Roman 12 Passiflorals, 109 Cacti, Roman 14 Ficcidales, 122 Composite, Roman 17 Astrals, 135 Primulaceae, Roman 20 Primulales, 145 Asclepiadae, Roman 22 Gentianales, 151 Convolvulaceae, Roman 23 Pulmonales, 154 Boragini, ditto 156 Nalini, ditto 157 Salini, Roman 24 Salinales, 181 Chenopodiae, Roman 27 Chenopodiales, 202 Euphorbiaceae, Roman 32 Euphorbials, 211 Cupuliferae, Roman 36 Quernils, 212 Coralaceae, ditto. Subclass Roman 2 Gymnosperms, 223 Conifer, 224 Cycade. Class Roman 2 Monocotyledons, 2 Canaceae, Roman 2 Amymales, 34 Liliaceae, Roman 11 Lilials, 41 Asparagi, ditto 55 Gramine, Roman 15 Glumils. Subkingdom Roman 2 Cryptogamic plants. Phyllices, Roman 1 Filicales, 6 Lycopodiaceae, ditto. Radicals. In all the germinating seeds observed by us, the first change is the protrusion of the radical, which immediately bends downwards and endeavours to penetrate the ground. In order to effect this, it is almost necessary that the seed should be pressed down, so as to offer some resistance unless indeed the soil is extremely loose, for otherwise the seed is lifted up instead of the radical penetrating the surface, but seeds often get covered by earth thrown up by burrowing quadrupeds or scratching birds, by the castings of earthworms, by heaps of excrement, the decaying branches of trees, etc., and will thus be pressed down, and they must often fall into cracks when the ground is dry or into holes, even with seeds lying on the bare surface. The first developed root hairs, by becoming attached to stones or other objects on the surface, are able to hold down the upper part of the radicle, whilst the tip penetrates the ground. Sachs has shown too how well and closely root hairs adapt themselves by growth to the most irregular particles in the soil, and become firmly attached to them. This attachment seems to be affected by the softening or liquefaction of the outer surface of the wall of the hair, and its subsequent consolidation, as will be on some future occasion more fully described. This intimate union plays an important part, according to Sachs, in the absorption of water, and of the inorganic matter dissolved in it. The mechanical aid afforded by the root hairs in penetrating the ground is probably only a secondary service. The tip of the radicle, as soon as it protrudes from the seed coats, begins to circumnudate, and the whole growing part continues to do so probably for as long as growth continues. This movement of the radicle has been described in Brassica sculus phasalis, Vischer cucurbita quercus, and Z. The probability of its occurrence was inferred by Sachs 3 from radicles placed vertically upwards being acted on by geotropism, which we likewise found to be the case, for if they had remained absolutely perpendicular, the attraction of gravity could not have caused them to bend to any one side. Circumnutation was observed in the above specified cases, either by means of extremely fine filaments of glass affixed to the radicles in the manner previously described, or by their being allowed to grow downwards over inclined smoked glass plates, on which they left their tracks. In the latter cases, the serpentine course, see Figs. 1921, 2740. One showed unequivocally that the apex had continually moved from side to side. This lateral movement was small in extent, being in the case of phasalis at most about 1 Roman 2000 from a medial line to both sides, but there was also movement in a vertical plane at right angles to the inclined glass plates. This was shown by the tracks often being alternately a little broader and narrower, due to the radicles having alternately pressed with greater and less force on the plates. Occasionally little bridges of soot were left across the tracks, showing that the apex had at these spots been lifted up. This latter fact was especially apt to occur when the radicle, instead of travelling straight down the glass, made a semicircular bend, but Fig 52 shows that this may occur when the track is rectilinear. The apex, by thus rising, was in one instance able to surmount a bristle cemented across an inclined glass plate, but slips of wood only 1/140 of an inch in thickness always caused the radicles to bend rectangularly to one side, so that the apex did not rise to this small height, in opposition to geotropism. In those cases in which radicles with attached filaments were placed so as to stand up almost vertically, they curved downwards through the action of geotropism, circumnudating at the same time, and their courses were consequently zigzag. Sometimes, however, they made great circular sweeps, the lines being likewise zigzag. Radicles closely surrounded by earth, even when this is thoroughly soaked and softened, may perhaps be quite prevented from circumnudating. Yet we should remember that the circumnudating sheath-like cotyledons of Phalaris, the hypocotyls of Solanum, and the epicotyls of Asparagus formed round themselves little circular cracks, or furrows, in a superficial layer of damp argillaceous sand. They were also able, as well as the hypocotyls of Brassica, to form straight furrows in damp sand. Whilst circumnudating and bending towards lateral light in a future chapter, it will be shown that the rocking or circumnudating movement of the flower heads of Trifolium subterraneum aids them in burying themselves. It is therefore probable that the circumnutation of the tip of the radicle aids it slightly penetrating the ground, and it may be observed in several of the previously given diagrams that the movement is more strongly pronounced in radicles when they first protrude from the seed than at a rather later period. But whether this is an accidental or an adaptive coincidence we do not pretend to decide. Nevertheless, when young radicles of Phasalis multiflorus were fixed vertically close over damp sand in the expectation that as soon as they reached it they would form circular furrows, this did not occur, a fact which may be accounted for, as we believe, by the furrow being filled up as soon as formed by the rapid increase of thickness in the apex of the radicle. Whether or not a radicle, when surrounded by softened earth, is aided in forming a passage for itself by circumnudating this movement, can hardly fail to be of high importance by guiding the radicle along a line of least resistance, as will be seen in the next chapter, when we treat of the sensibility of the tip to contact if, however, a radical in its downward growth breaks obliquely into any crevice or a hole left by a decayed root or one made by the larva of an insect, and more especially by worms, the circumnudating movement of the tip will materially aid it in following such open passage, and we have observed that roots commonly run down the old burrows of worms for. When a radical is placed in a horizontal or inclined position, the terminal growing part, as is well known, bends down towards the center of the earth, and Sachs 5 has shown that whilst thus bending the growth of the lower surface is greatly retarded, whilst that of the upper surface continues at the normal rate, or maybe even somewhat increased. He has further shown by attaching a thread running over a pulley to a horizontal radical of large size, namely that of the common bean, that it was able to pull up a weight of only 1 gram or 15 grains. We may therefore conclude that geotropism does not give a radical force sufficient to penetrate the ground, but merely tells it if such an expression may be used which course to pursue. Before we knew of Sachs' more precise observations, we covered a flat surface of damp sand with the thinnest tinfoil, which we could procure 2 to 3 Roman 2000 or 12 to 79 of an inch in thickness, and placed a radical close above in such a position that it grew almost perpendicularly downwards. When the apex came into contact with the polished level surface, it turned at right angles and glided over it, without leaving any impression, yet the tinfoil was so flexible that a little stick of soft wood pointed to the same degree as the end of the radical, and gently loaded with a weight of only 1/4 of an ounce 120 grains, plainly indented the tinfoil. Radicals are able to penetrate the ground by the force due to their longitudinal and transverse growth, the seeds themselves being held down by the weight of the superincumbent soil. In the case of the bean, the apex protected by the root cap is sharp, and the growing part from 8 to 10 Roman 2000 in length is much more rigid, as Sachs has proved, than the part immediately above, which has ceased to increase in length. We endeavored to ascertain the downward pressure of the growing part by placing germinating beans between 2 small metal plates, the upper one of which was loaded with a known weight, and the radical was then allowed to grow into a narrow hole in wood 2 or 3/10 of an inch in depth, and closed at the bottom. The wood was so cut that the short space of radical between the mouth of the hole and the bean could not bend laterally on 3 sides, but it was impossible to protect the 4th side close to the bean. Consequently, as long as the radical continued to increase in length and remained straight, the weighted bean would be lifted up, after the tip had reached the bottom of the shallow hole. Beans, thus arranged, surrounded by damp sand, lifted up 1/4 of a pound in 24 after the tip of the radical had entered the hole. With a greater weight, the radicals themselves always became bent on the one unguarded side, but this probably would not have occurred if they had been closely surrounded on all sides by compact earth. There was, however, a possible but not probable source of error in these trials, for it was not ascertained whether the beans themselves go on swelling for several days after they have germinated, and after having been treated in the manner in which ours had been, namely being first left for 24 in water, then allowed to germinate in very damp air, afterwards placed over the hole, and almost surrounded by damp sand in a closed box. Fig 55 outline of piece of stick, reduced to 1/2 natural size, with a hole through which the radical of a bean grew. Thickness of stick at narrow end, 8 inch at broad end, 16 depth of hole 1 inch. We succeeded better in ascertaining the force exerted transversely by these radicals too were so placed as to penetrate small holes made in little sticks, one of which was cut into the shape here exactly copied. Fig 55, the short end of the stick beyond the hole was purposely split, but not the opposite end, as the wood was highly elastic. The split or fissure closed immediately after being made. After 6 days, the stick and bean were dug out of the damp sand, and the radical was found to be much enlarged above and beneath the hole. The fissure, which was at first quite closed, was now open to a width of 4 Roman 2000. As soon as the radical was extracted, it immediately closed to a width of 2 Roman 2000. The stick was then suspended horizontally by a fine wire passing through the hole lately filled by the radical, and a little saucer was suspended beneath to receive the weights, and it required 8 pounds 8 oz to open the fissure to the width of 4 Roman 2000, that is, the width before the root was extracted, but the part of the radical, only 1 of an inch in length, which was embedded in the hole, probably exerted a greater transverse strain even than 8 pounds 8 oz, for it had split the solid wood for a length of rather more than 1/4 of an inch, exactly 275 inch, and this fissure is shown in Fig 55. A second stick was tried in the same manner, with almost exactly the same result. Fig 56 wooden pincers kept closed by a spiral brass spring with a hole 14-inch in diameter and 6-inch in depth bored through the narrow closed part, through which a radicle of a bean was allowed to grow temp 50-60 F. We then followed a better plan. Holes were bored near the narrow end of 2 wooden clips or pincers, Fig 56 kept closed by brass spiral springs. 2 radicles in damp sand were allowed to grow through these holes. The pincers rested on glass plates to lessen the friction from the sand. The holes were a little larger, viz 14-inch, and considerably deeper, viz 6-inch, than in the trials with the sticks, so that a greater length of a rather thicker radical exerted a transverse strain. After 13 days, they were taken up the distance of 2 dots. See, the figure on the longer ends of the pincers was now carefully measured. The radicals were then extracted from the holes, and the pincers of course closed. They were then suspended horizontally in the same manner as were the bits of sticks, and a weight of 1,500 grams or 3 pounds 4 ounces was necessary with one of the pincers to open them to the same extent as had been affected by the transverse growth of the radical. As soon as this radical had slightly opened the pincers, it had grown into a flattened form, and had escaped a little beyond the hole, its diameter in one direction being 4 Roman 2000, and at right angles 3 Roman 2000. If this escape and flattening could have been prevented, the radical would probably have exerted a greater strain than the 3 pounds 4 ounces. With the other pincers, the radical escaped still further out of the hole, and the weight required to open them to the same extent as had been affected by the radical was only 600 grams. With these facts before us, there seems little difficulty in understanding how a radical penetrates the ground. The apex is pointed and is protected by the root cap. The terminal growing part is rigid and increases in length with a force equal, as far as our observations can be trusted, to the pressure of at least 1/4 pound, probably with a much greater force, when prevented from bending to any side by the surrounding earth. Whilst thus increasing in length, it increases in thickness, pushing away the damp earth on all sides, with force of above 8 pounds, in one case of 3 pounds, in another case. It was impossible to decide whether the actual apex exerts relatively to its diameter the same transverse strain as the parts a little higher up, but there seems no reason to doubt that this would be the case. The growing part therefore does not act like a nail when hammered into a board, but more like a wedge of wood, which, whilst slowly driven into a crevice, continually expands at the same time by the absorption of water, and a wedge thus acting will split even a mass of rock. Manner in which hypocotyls, epicotyls, etc. rise up and break through the ground after the radical has penetrated the ground and fixed the seed. The hypocotyls of all the dicotyledonous seedlings observed by us, which lift their cotyledons above the surface, break through the ground in the form of an arch when the cotyledons are hypogene, that is, remain buried in the soil. The hypocotyl is hardly developed, and the epicotyl or plumule rises in like manner as an arch through the ground. In all, or at least in most of such cases, the downwardly bent apex remains for a time enclosed within the seedcoats with corylus avellina. The cotyledons are hypogene, and the epicotyl is arched, but in the particular case described in the last chapter, its apex had been injured, and it grew laterally through the soil like a root, and in consequence of this, it had emitted 2 secondary shoots, which likewise broke through the ground as arches. Cyclamen does not produce any distinct stem, and only a single cotyledon appears at first. 6. Its petiole breaks through the ground, as an arch. Fig 57 Abronia has only a single fully developed cotyledon, but in this case, it is the hypocotyl which first emerges, and is arched. Abronia umbellata, however, presents this peculiarity, that the enfolded blade of the one developed cotyledon, with the enclosed endosperm, whilst still beneath the surface, has its apex upturned and parallel to the descending leg of the arched hypocotyl, but it is dragged out of the ground by the continued growth of the hypocotyl, with the apex pointing downward. With cycas pectinata, the cotyledons are hypogene, and a true leaf first breaks through the ground with its petiole forming an arch. Fig 57 Cyclamen persicum seedling figure, enlarged C blade of cotyledon, not yet expanded with arched petiole, beginning to straighten itself. H hypocotyl, developed into a corm. R secondary radicals. Fig 58 Acanthus mallees seedling with the hypogene cotyledon on the near side, removed, and the radicals cut off. A blade of first leaf beginning to expand with petiole, still partially arched. B second and opposite leaf, as yet very imperfectly developed. C hypogene cotyledon on the opposite side. In the genus Acanthus, the cotyledons are likewise hypogene. In Amales, a single leaf first breaks through the ground with its petiole arched, and with the opposite leaf much less developed, short, straight, of a yellowish color, and with the petiole at first not half as thick as that of the other, the undeveloped leaf is protected by standing beneath its arched fellow, and it is an intrusive fact that it is not arched, as it has not to force for itself a passage through the ground. In the accompanying sketch Fig. 58, the petiole of the first leaf has already partially straightened itself, and the blade is beginning to unfold. The small second leaf ultimately grows to an equal size with the first, but this process is effected at very different rates in different individuals. In one instance, the second leaf did not appear fully above the ground until 6 weeks after the first leaf, as the leaves in the whole family of the Acanthaceae stand either opposite one another or in whorls, and as these are of equal size, the great inequality between the first two leaves is a singular fact. We can see how this inequality of development and the arching of the petiole could have been gradually acquired if they were beneficial to the seedlings, by favouring their emergence, for with a candelabrum spinosus and latifolius, there was a great variability in the inequality between the two first leaves, and in the arching of their petioles. In one seedling of a candelabrum, the first leaf was arched, and 9 times as long as the second, which latter consisted of a mere little yellowish-white straight hairy style. In other seedlings, the difference in length between the two leaves was as 3 to 2, or as 4 to 3, or as only 76 to 62 inch. In these latter cases, the first and taller leaf was not properly arched. Lastly, in another seedling, there was not the least difference in size between the two first leaves, and both of them had their petioles straight. Their laminae were enfolded and pressed against each other, forming a lance or wedge, by which means they had broken through the ground. Therefore, in different individuals of this same species of acanthus, the first pair of leaves breaks through the ground by 2 widely different methods, and if either had proved decidedly advantageous or disadvantageous, one of them no doubt would soon have prevailed. Gray has described 7 the peculiar manner of germination of 3 widely different plants, in which the hypocotyl is hardly at all developed. These were therefore observed by us in relation to our present subject. Delphinium nudicore, the elongated petioles of the two cotyledons are confluent, as are sometimes their blades at the base, and they break through the ground as an arch. They thus resemble in a most deceptive manner a hypocotyl. At first they are solid, but after a time become tubular, and the basal part beneath the ground is enlarged into a hollow chamber, within which the young leaves are developed without any prominent plumule. Externally, root hairs are formed on the confluent petioles, either a little above or on a level with the plumule. The first leaf at an early period of its growth, and whilst within the chamber, is quite straight, but the petiole soon becomes arched, and the swelling of this part, and probably of the blade, splits open one side of the chamber, and the leaf then emerges. The slit was found in one case to be 3 Roman 2000 in length, and it is seated on the line of confluence of the two petioles. The leaf, when it first escapes from the chamber, is buried beneath the ground, and now an upper part of the petiole near the blade becomes arched in the usual manner. The second leaf comes out of the slit, either straight or somewhat arched, but afterwards the upper part of the petiole certainly in some, and we believe in all case arches itself, whilst forcing a passage through the soil. Megarrhiza californica, the cotyledons of this gourd never free themselves from the seed coats, and are hypogene. Their petioles are completely confluent, forming a tube which terminates downwards in a little solid point, consisting of a minute radicle and hypocotyl, with the likewise minute plumule enclosed within the base of the tube. This structure was well exhibited in an abnormal specimen, in which one of the two cotyledons failed to produce a petiole, whilst the other produced one consisting of an open semi-cylinder ending in a sharp point, formed of the parts just described. As soon as the confluent petioles protrude from the seed, they bend down, as they are strongly geotropic, and penetrate the ground. The seed itself retains its original position either on the surface or buried at some depth, as the case may be. If, however, the point of the confluent petioles meets with some obstacle in the soil, as appears to have occurred with the seedlings described and figured by Gray 8, the cotyledons are lifted up above the ground. The petioles are clothed with root hairs like those on a true radicle, and they likewise resemble radicles in becoming brown when immersed in a solution of permanganate of potassium. Our seeds were subjected to a high temperature, and in the course of 3 or 4 days, the petioles penetrated the soil perpendicularly to a depth of from 2 to 212 inches, and not until then did the true radicle begin to grow. In one specimen, which was closely observed, the petioles in 7 days after their first protrusion attained a length of 212 inches, and the radicle by this time had also become well developed. The plumule, still enclosed within the tube, was now 3 inches in length, and was quite straight, but from having increased in thickness, It had just begun to split open the lower part of the petioles on one side along the line of their confluence by the following morning. The upper part of the plumule had arched itself into a right angle, and the convex side or elbow had thus been forced out through the slit. Here then the arching of the plumule plays the same part as in the case of the petioles of the delphinium. As the plumule continued to grow, the tip became more arched, and in the course of 6 days it emerged through the 212 inches of superincumbent soil, still retaining its arched form. After reaching the surface, it straightened itself in the usual manner in the accompanying figure Fig 58a. We have a sketch of a seedling in this advanced state of development, the surface of the ground being represented by the line GG. Fig 58, a Megarrhiza californica sketch of seedling, carped from a sagre, reduced to 1/2 scale C cotyledons, within seed coats, P the 2 confluent petioles H and R hypocotyl and radical P, 1 plumule GG surface of soil. The germination of the seeds in their native Californian home proceeds in a rather different manner, as we infer from an interesting letter from Mr. Rattan sent to us by Prof. Sagre. The petioles protrude from the seeds soon after the autumnal rains, and penetrate the ground generally in a vertical direction, to a depth of from 4 to even 6 inches. They were found this state by Mr. Rattan during the Christmas vacation, with the plumules still enclosed within the tubes, and he remarks that if the plumules had been at once developed, and had reached the surface as occurred with our seeds, which were exposed to a high temperature, they would surely have been killed by the frost. As it is, they lie dormant at some depth beneath the surface, and are thus protected from the cold, and the root hairs on the petioles would supply them with sufficient moisture. We shall hereafter see that many seedlings are protected from frost, but by a widely different process, namely by being drawn beneath the surface, by the contraction of their radicals. We may, however, believe that the extraordinary manner of germination of Megarrhiza has another and secondary advantage. The radical begins in a few weeks to enlarge into a little tuber, which then abounds with starch, and is only slightly bitter. It would therefore be very liable to be devoured by animals, were it not protected by being buried, whilst young and tender at a depth of some inches beneath the surface. Ultimately, it grows to a huge size. Ipoma leptophylla. In most of the species of this genus, the hypocotyl is well developed and breaks through the ground as an arch, but the seeds of the present species, in germinating, behave like those of Megarrhiza, excepting that the elongated petioles of the cotyledons are not confluent after they have protruded from the seed. They are united at their lower ends with the undeveloped hypocotyl and undeveloped radical, which together form a point only about 1 inch in length. They are at first highly geotropic, and penetrate the ground to a depth of rather above 1/2 inch. The radical then begins to grow on 4 occasions after the petioles had grown for a short distance vertically downwards. They were placed in a horizontal position in damp air in the dark, and in the course of 4 hours they again became curved vertically downwards, having passed through 90 in this time, but their sensitiveness to geotropism lasts for only 2 or 3 days, and the terminal part alone for a length of between 2 and 4 inch is thus sensitive. Although the petioles of our specimens did not penetrate the ground to a greater depth than about 12 inch, yet they continued for some time to grow rapidly, and finally attained the great length of about 3 inches. The upper part is apogeotropic, and therefore grows vertically upwards, excepting a short portion close to the blades which at an early period bends downwards and becomes arched, and thus breaks through the ground afterwards. This portion straightens itself, and the cotyledons then free themselves from the seed coats. Thus we here have in different parts of the same organ widely different kinds of movement, and of sensitiveness. For the basal part is geotropic, the upper part apogeotropic, and a portion near the blades temporarily and spontaneously arches itself. The plumule is not developed for some little time, and as it rises between the bases of the parallel and closely approximate petioles of the cotyledons, which in breaking through the ground have formed an almost open passage, it does not require to be arched, and is consequently always straight, whether the plumule remains buried and dormant for a time in its native country, and is thus protected from the cold of winter. We do not know the radical, like that of the Megarrhiza, grows into a tuber-like mass, which ultimately attains a great size. So it is with Ipoma pandurata, the germination of which, as a Sagre informs us, resembles that of Roman I leptophylla. The following case is interesting in connection with the root-like nature of the petioles. The radical of a seedling was cut off as it was completely decayed, and the 2 now separated cotyledons were planted. They emitted roots from their bases, and continued green and healthy for 2 months. The blades of both then withered, and on removing the earth, the bases of the petioles instead of the radical were found enlarged into little tubers. Whether these would have had the power of producing two independent plants in the following summer we do not know. In Quercus virescens, according to Dr. Engelman 9, both the cotyledons and their petioles are confluent. The latter grow to a length of an inch or even more. And if we understand rightly, penetrate the ground, so that they must be geotropic. The nutriment within the cotyledons is then quickly transferred to the hypocotyl or radicle, which thus becomes developed into a fusiform tuber. The fact of tubers being formed by the foregoing three widely distinct plants makes us believe that their protection from animals at an early age, and whilst tender, is one at least of the advantages gained by the remarkable elongation of the petioles of the cotyledons together, with their power of penetrating the ground like roots under the guidance of geotropism. The following cases may be here given as they bear on our present subject, though not relating to seedlings. The flower stem of the parasitic Lathria squameria, which is destitute of true leaves, breaks through the ground. As an arch 10, so does the flower stem of the parasitic and leafless monotropa Hypopitys with Helleborus niger. The flower stems which rise up independently of the leaves likewise break through the ground. As arches, this is also the case with the greatly elongated flower stems, as well as with the petioles of Epimedium pinnatum. So it is with the petioles of Ranunculus ficaria when they have to break through the ground, but when they arise from the summit of the bulb above ground, they are from the first quite straight. And this is a fact which deserves notice. The rachis of the bracken fern Pteris aquilina, and of some probably many other ferns likewise rises above ground under the form of an arch. No doubt other analogous instances could be found by careful search in all ordinary cases of bulbs, rhizomes, rootstocks, etc. Buried beneath the ground, the surface is broken by a cone formed by the young imbricatid leaves, the combined growth of which gives them force sufficient for the purpose. With germinating monocotyledonous seeds, of which however we did not observe a large number, the plumules, for instance those of asparagus and canna, are straight whilst breaking through the ground. With the gramen, the sheath-like cotyledons are likewise straight. They however terminate in a sharp crest, which is white and somewhat indurated, and this structure obviously facilitates their emergence from the soil. The first true leaves escape from the sheath through a slit beneath the chisel-like apex, and at right angles to it. In the case of the onion Allium cepa, we again meet with an arch, the leaf-like cotyledon being abruptly bowed when it breaks through the ground, with the apex still enclosed within the seed coats. The crown of the arch, as previously described, is developed into a white conical protuberance, which we may safely believe to be a special adaptation for this office. The fact of so many organs of different kinds, hypocotyls and epicotyls, the petioles of some cotyledons, and of some first leaves, the cotyledons of the onion, the rachis of some ferns, and some flower stems being all arched, whilst they break through the ground, shows how just are Dr. Haberlant's 11 remarks on the importance of the arch to seedling plants. He attributes its chief importance to the upper young and more tender parts of the hypocotyl or epicotyl being thus saved from abrasion and pressure, whilst breaking through the ground. But we think that some importance may be attributed to the increased force gained by the hypocotyl, epicotyl, or other organ, by being at first arched. For both legs of the arch increase in length, and both have points of resistance as long as the tip remains enclosed within the seed coats, and thus the crown of the arch is pushed up through the earth with twice as much force as that which a straight hypocotyl etc. could exert. As soon, however, as the upper end has freed itself, all the work has to be done by the basal leg. In the case of the epicotyl of the common bean, the basal leg, the apex having freed itself from the seed coats, grew upwards with a force sufficient to lift a thin plate of zinc, loaded with 12 ounces. 2 more ounces were added, and the 14 ounces were lifted up to a very little height, and then the epicotyl yielded and bent to one side. With respect to the primary cause of the arching process, we long thought in the case of many seedlings that this might be attributed to the manner in which the hypocotyl or epicotyl was packed and curved within the seed coats, and that the arched shape thus acquired was merely retained until the parts in question reached the surface of the ground. But it is doubtful whether this is the whole of the truth. In any case, for instance with the common bean, the epicotyl or plumule is bowed into an arch, whilst breaking through the seed coats as shown in Fig 59p92. The plumule first protrudes as a solid knob E in A, which after 24 hours growth is seen E in B to be the crown of an arch. Nevertheless, with several beans, which germinated in damp air, and had otherwise been treated in an unnatural manner, little plumules were developed in the axils of the petioles of both cotyledons, and these were as perfectly arched as the normal plumule, yet they had not been subjected to any confinement or pressure, for the seed coats were completely ruptured. and they grew in the open air, this proves that the plumule has an innate or spontaneous tendency to arch itself. In some other cases, the hypocotyl or epicotyl protrudes from the seed at first only slightly bowed, but the bowing afterwards increases independently of any constraint. The arch is thus made narrow with the two legs, which are sometimes much elongated parallel and close together, and thus it becomes well fitted for breaking through the ground. With many kinds of plants, the radicle whilst still enclosed within the seed and likewise, after its first protrusion lies in a straight line with the future hypocotyl, and with the longitudinal axis of the cotyledons. This is the case with Cucurbita ovifera. Nevertheless, in whatever position the seeds were buried, hypocotyl always came up arched in one particular direction. Seeds were planted in friable peat, at a depth of about an inch, in a vertical position with the end, from which the radicle protrudes downwards. Therefore all the parts occupied the same relative positions, which they would ultimately hold after the seedlings had risen clear above the surface. Notwithstanding this fact, the hypocotyl arched itself, and as the arch grew upwards through the peat, the buried seeds were turned either upside down, or were laid horizontally, being afterwards dragged above the ground. Ultimately, the hypocotyl straightened itself in the usual manner, and now after all these movements the several parts occupied the same position relatively to one another, and to the centre of the earth which they had done when the seeds were first buried. But it may be argued in this and other such cases that as the hypocotyl grows up through the soil, the seed will almost certainly be tilted to one side, and then, from the resistance which it must offer during its further elevation, the upper part of the hypocotyl will be doubled down, and thus become arched. This view seems the more probable, because with Ranunculus ficaria, only the petioles of the leaves which forced a passage through the earth were arched, and not those which arose from the summits of the bulbs above the ground. Nevertheless, this explanation does not apply to the cucurbita, for when germinating seeds were suspended in damp air in various positions, by pins passing through the cotyledons fixed to the inside of the lids of jars, in which case the hypocotyls were not subjected to any friction or constraint, yet the upper part became spontaneously arched. This fact, moreover, proves that it is not the weight of the cotyledons which causes the arching seeds of Helianthus annus, and of two species of Ipoma, those of Roman 1 bona nox being for the genus large and heavy, were pinned in the same manner, and the hypocotyls became spontaneously arched. The radicles which had been vertically dependent assumed in consequence a horizontal position in the case of Ipoma leptophylla. It is the petioles of the cotyledons which become arched whilst rising through the ground, and this occurred spontaneously when the seeds were fixed to the lids of jars. It may, however, be suggested with some degree of probability that the arching was aboriginally caused by mechanical compulsion, owing to the confinement of the parts in question within the seed coats, or to friction whilst they were being dragged upwards. But if this is so, we must admit from the cases just given that a tendency in the upper part of the several specified organs to bend downwards and thus to become arched has now become with many plants firmly inherited. The arching, to whatever cause it may be due, is the result of modified circumnutation through increased growth along the convex side of the part. Such growth, being only temporary for the part, always straightens itself subsequently by increased growth along the concave side, as will hereafter be described. It is a curious fact that the hypocotyls of some plants which are but little developed, and which never raise their cotyledons above the ground, nevertheless inherit a slight tendency to arch themselves. Although this movement is not of the least use to them, we refer to a movement observed by Sachs in the hypocotyls of the bean and some other leguminaceae, and which is shown in the accompanying figure Fig 59, copied from his Essay 12. The hypocotyl and radicle at first grow perpendicularly downwards as at A and then bend often in the course of 24 hours into the position shown at B. As we shall hereafter often have to recur to this movement, we will for brevity's sake call it Sachs curvature. At first sight, it might be thought that the altered position of the radicle in B was wholly due to the outgrowth of the epicotyl, either petiole P serving as a hinge, and it is probable that this is partly the cause, but the hypocotyl and upper part of the radicle themselves become slightly curved. The above movement in the bean was repeatedly seen by us, but our observations were made chiefly on Phasalis multiflorus, the cotyledons of which are likewise hypogene. Some seedlings with well-developed radicles were first immersed in a solution of permanganate of potassium, and judging from the changes of colour, though these were not very clearly defined, the hypocotyl is about 3 inches in length. Straight, thin black lines of this length were now drawn from the bases of the short petioles along the hypocotyls of 23 germinating seeds, which were pinned to the lids of jars, generally with the hilum downwards, and with their radicals pointing to the center of the earth after an interval of from 24 to 48 hours, the black lines on the hypocotyls of 16 out of the 23 seedlings became distinctly curved, but in very various degrees, namely with radii between 20 and 80 Roman 2000, on Sachs cyclometer, in the same relative direction as shown at B in Fig 59. As geotropism will obviously tend to check this curvature, 7 seeds were allowed to germinate with proper precautions for their growth in a clinostat 13, by which means geotropism was eliminated. The position of the hypocotyls was observed during 4 successive days, and they continued to bend towards the hilum and lower surface of the seed on the 4th day. They were deflected by an average angle of 63 from a line perpendicular to the lower surface, and were therefore considerably more curved than the hypocotyl and radical in the bean at B Fig 59, though in the same relative direction. Fig 59 Vischer Faber germinating seeds, suspended in damp air A with radical growing perpendicularly downwards, B the same bean after 24 hours, and after the radical has curved itself, R radical H short hypocotyl, E epicotyl, appearing as a knob in A, and as an arch in B P petiole of the cotyledon, the latter enclosed within the seed coats. It will, we presume, be admitted that all leguminous plants with hypogene cotyledons are descended from forms which once raised their cotyledons above the ground in the ordinary manner, and in doing so it is certain that their hypocotyls would have been abruptly arched, as in the case of every other dicotyledonous plant. This is especially clear in the case of Phasalis, for out of 5 species, the seedlings of which we observed, namely P. multiflorus caracalla, vulgaris hernandezii and Roxburghii, inhabitants of the Old and New Worlds, the 3 last-named species have well-developed hypocotyls, which break through the ground as arches. Now, if we imagine a seedling of the common bean, or of P. multiflorus, to behave as its progenitors once did, the hypocotyl H Fig 59, in whatever position the seed may have been buried, would become so much arched that the upper part would be doubled down parallel to the lower part, and this is exactly the kind of curvature which actually occurs in these 2 plants, though to a much less degree. Therefore, we can hardly doubt that their short hypocotyls have retained by inheritance a tendency to curve themselves in the same manner as they did at a former period, when this movement was highly important to them for breaking through the ground, though now rendered useless by the cotyledons being hypogene. Rudimentary structures are in most cases highly variable, and we might expect that rudimentary or obsolete actions would be equally so, and Sachs curvature varies extremely in amount, and sometimes altogether fails. This is the sole instance known to us of the inheritance, though in a feeble degree, of movements which have become superfluous from changes which the species has undergone. Rudimentary cotyledons. A few remarks on this subject may be here interpolated. It is well known that some dicotyledonous plants produce only a single cotyledon, for instance certain species of Ranunculus corydalus caraphyllum, and we will here endeavor to show that the loss of one or both cotyledons is apparently due to a store of nutriment being laid up in some other part, as in the hypocotyl or one of the 2 cotyledons, or one of the secondary radicals. With the orange citrus aurantium, the cotyledons are hypogene, and one is larger than the other, as may be seen in a Fig 60. In B, the inequality is rather greater, and the stem has grown between the points of insertion of the 2 petioles, so that they do not stand opposite to one another. In another case, the separation amounted to 1/5 of an inch. The smaller cotyledon of one seedling was extremely thin and not half the length of the larger one, so that it was clearly becoming rudimentary. 14. In all these seedlings, the hypocotyl was enlarged or swollen. Fig 60 Citrus aurantium 2 young seedlings, C larger cotyledon, C smaller cotyledon, H thickened hypocotyl, R radical. In A the epicotyl is still arched, in B it has become erect. Fig 61, Abronia umbellata seedling twice natural size, C cotyledon, C rudimentary, cotyledon H enlarged hypocotyl, with a heel or projection H at the lower end, R radical. With Abronia umbellata, one of the cotyledons is quite rudimentary, as may be seen C in Fig 61. In this specimen, it consisted of a little green flap 1/84 inch in length, destitute of a petiole, and covered with glands like those on the fully developed cotyledon C. At first it stood opposite to the larger cotyledon, but as the petiole of the latter increased in length and grew in the same line with the hypocotyl H, the rudiment appeared in older seedlings as if seated some way down the hypocotyl. With Abronia arenaria, there is a similar rudiment which in one specimen was only 1/100th, and in another 1/160th inch in length. It ultimately appeared as if seated halfway down the hypocotyl, In both these species, the hypocotyl is so much enlarged, especially at a very early age, that it might almost be called a corm. The lower end forms a heel, or projection, the use of which will hereafter be described. In Cyclamen persicum, the hypocotyl, even whilst still within the seed, is enlarged into a regular corm 15, and only a single cotyledon is at first developed. See former Fig 57. With Ranunculus ficaria, 2 cotyledons are never produced, and here one of the secondary radicals is developed at an early age into a so-called bulb 16. Again, certain species of Chaerophyllum and Corydalus produce only a single cotyledon 17 in the former the hypocotyl, and in the latter the radical is enlarged according to Ermisch into a. In the several foregoing cases, one of the cotyledons is delayed in its development, or reduced in size, or rendered rudimentary, or quite aborted. But in other cases both cotyledons are represented by mere rudiments. With Opuntia basilaris, this is not the case, for both cotyledons are thick and large, and the hypocotyl shows at first no signs of enlargement, but afterwards, when the cotyledons have withered and disarticulated themselves, it becomes thickened, and from its tapering form, together with its smooth, tough brown skin, appears when ultimately drawn down to some depth into the soil like a root. On the other hand, with several other cacti, the hypocotyl is from the first much enlarged, and both cotyledons are almost or quite rudimentary. Thus with Cereus lambicae, 2 little triangular projections representing the cotyledons are narrower than the hypocotyl, which is pear-shaped with the point downwards. In Rhipsalis cassitha, the cotyledons are represented by mere points on the enlarged hypocotyl. In Echinocactus viridescens, the hypocotyl is globular with 2 little prominences on its summit. In Pilosrius howletiae, the hypocotyl, much swollen in the upper part, is merely notched on the summit, and each side of the notch evidently represents a cotyledon. Stapelia sarpedon, a member of the very distinct family of the Asclepiadae, is fleshy like a cactus, and here again the upper part of the flattened hypocotyl is much thickened and bears 2 minute cotyledons which, measured internally, were only 15-inch in length, and in breadth not equal to 1/4 of the diameter of the hypocotyl in its narrow axis. Yet these minute cotyledons are probably not quite useless, for when the hypocotyl breaks through the ground in the form of an arch, they are closed or pressed against one another, and thus protect the plumule they afterwards open. From the several cases now given, which refer to widely distinct plants, we may infer that there is some close connection between the reduced size of one or both cotyledons and the formation by the enlargement of the hypocotyl or of the radical of a so-called bulb. But it may be asked, did the cotyledons first tend to abort, or did a bulb first begin to be formed? As all dicotyledons naturally produce 2 well-developed cotyledons, whilst the thickness of the hypocotyl and of the radical differs much in different plants, it seems probable that these latter organs first became from some cause thickened in several instances, apparently in correlation with the fleshy nature of the mature plants, as to contain a store of nutriment sufficient for the seedling, and then that one or both cotyledons, from being superfluous, decreased in size. It is not surprising that one cotyledon alone should sometimes have been thus affected, for with certain plants, for instance the cabbage, the cotyledons are at first of unequal size, owing apparently to the manner in which they are packed within the seed. It does not, however, follow from the above connection that whenever a bulb is formed at an early age, one or both cotyledons will necessarily become superfluous and consequently more or less rudimentary. Finally, these cases offer a good illustration of the principle of compensation or balancement of growth, or as Goethe expresses it, in order to spend on one side, nature is forced to economize on the other side. Circumnutation and other movements of hypocotyls and epicotyls, whilst still arched and buried beneath the ground, and whilst breaking through it according to the position in which a seed may chance to have been buried, the arched hypocotyl or epicotyl will begin to protrude in a horizontal, a more or less inclined, or in a vertical plane, except when already standing vertically upwards. Both legs of the arch are acted on from the earliest period by apogeotropism. Consequently, they both bend upwards until the arch becomes vertical. During the whole of this process, even before the arch has broken through the ground, it is continually trying to circumnudate to a slight extent, as it likewise does if it happens at first to stand vertically eupole, which cases have been observed and described more or less fully in the last chapter. After the arch has grown to some height, upwards the basal part ceases to circumnudate, whilst the upper part continues to do so. That an arched hypocotyl or epicotyl with the 2 legs fixed in the ground should be able to circumnudate seemed to us, until we had read Prof. Wiesner's observations, an inexplicable fact. He has shown 18 in the case of certain seedlings whose tips are bent downwards, or which nudate, that whilst the posterior side of the upper or dependent portion grows, quickest the anterior and opposite side of the basal portion of the same internode grows, quickest these two portions, being separated by an indifferent zone where the growth is equal on all sides. There may be even more than one indifferent zone in the same internode, and the opposite sides of the parts above and below each such zone grow quickest. This peculiar manner of growth is called by Wiesner undulatory nutation circumnutation, depends on one side of an organ growing quickest, probably preceded by increased turgescence, and then another side, generally almost the opposite one, growing quickest. Now if we look at an arch like this upside down U, and suppose the whole of one side, we'll say the whole convex side of both legs to increase in length, this would not cause the arch to bend to either side. But if the outer side or surface of the left leg were to increase in length, the arch would be pushed over to the right, and this would be aided by the inner side of the right leg, increasing in length. If afterwards the process were reversed, arch would be pushed over to the opposite or left side, and so on alternately. That is, it would circumnudate as an arched hypocarpal, with the two legs fixed in the ground certainly circumnudates. And as it consists of a single internode, we may conclude that it grows in the manner described by Wiesner. It may be added that the crown of the arch does not grow or grows very slowly, for it does not increase much in breadth, whilst the arch itself increases greatly in height. The circumnudating movements of arched hypocarpals and epicarpals can hardly fail to aid them in breaking through the ground if this be damp and soft, though no doubt their emergence depends mainly on the force exerted by their longitudinal growth. Although the arch circumnudates only to a slight extent and probably with little force, yet it is able to move the soil near the surface, though it may not be able to do so at a moderate depth. Apart with seeds of Solanum palinacanthum, the tall arched hypocarpals of which had emerged and were growing rather slowly was covered with fine argillaceous sand kept damp, and this at first closely surrounded the bases of the arches, but soon a narrow open crack was formed round each of them, which could be accounted for only by their having pushed away the sand on all sides, for no such cracks surrounded some little sticks and pins which had been driven into the sand. It has already been stated that the cotyledons of Phalaris and Avena, the plumules of asparagus, and the hypocarpals of Brassica were likewise able to displace the same kind of sand, either whilst simply circumnudating or whilst bending towards a lateral light. As long as an arched hypocarpal or epicarpal remains buried beneath the ground, the two legs cannot separate from one another, except to a slight extent from the yielding of the soil. But as soon as the arch rises above the ground, or at an earlier period, if the pressure of the surrounding earth be artificially removed, the arch immediately begins to straighten itself. This no doubt is due to growth along the whole inner surface of both legs of the arch, such growth being checked or prevented as long as the two legs of the arch are firmly pressed together. When the earth is removed all round an arch, and the two legs are tied together at their bases, growth on the underside of the crown causes it after a time to become much flatter and broader than naturally occurs. The straightening process consists of a modified form of circumnutation for the lines described during this process, as with the hypocarpal of Brassica and the epicarpals of Viscia and Corylus were often plainly zigzag and sometimes looped. After hypocarpals or epicarpals have emerged from the ground, they quickly become perfectly straight. No trace is left of their former abrupt curvature, excepting in the case of Allium cepa, in which the cotyledon rarely becomes quite straight owing to the protuberance developed on the crown of the arch. The increased growth along the inner surface of the arch, which renders it straight, apparently begins in the basal leg, or that which is united to the radical for this leg, as we often observed, is first bowed backwards from the other leg. This movement facilitates the withdrawal of the tip of the epicarpal, or of the cotyledons as the case may be, from within the seed coats and from the ground, but the cotyledons often emerge from the ground, still tightly enclosed within the seed coats, which apparently serve to protect them. The seed coats are afterwards ruptured and cast off by the swelling of the closely conjoined cotyledons, and not by any movement or their separation from one another. Nevertheless, in some few cases, especially with the cucurbitaceae, the seed coats are ruptured by a curious contrivance described by Roman 1000 Flaholt 19. A heel or peg is developed on one side of the summit of the radical or base of the hypocarpal, and this holds down the lower half of the seed coats, the radical being fixed into the ground, whilst the continued growth of the arched hypocarpal forced upwards the upper half and tears asunder the seed coats at one end, and the cotyledons are then easily withdrawn. The accompanying figure, Fig 62, will render this description intelligible. 41 seeds of Cucurbita ovifera were laid on friable peat, and were covered by a layer about an inch in thickness, not much pressed down, so that the cotyledons in being dragged up were subjected to very little friction, yet 40 of them came up naked, the seed coats being left buried in the peat. This was certainly due to the action of the peg, for when it was prevented from acting, the cotyledons, as we shall presently see, were lifted up still enclosed in their seed coats. They were, however, cast off in the course of 2 or 3 days by the swelling of the cotyledons. Until this occurs, light is excluded, and the cotyledons cannot decompose carbonic acid, but no one probably would have thought that the advantage thus gained by a little earlier casting off of the seed coats would be sufficient to account for the development of the peg. Yet according to Roman 1000 flaholt seedlings, which have been prevented from casting their seed coats whilst beneath the ground, are inferior to those which have emerged with their cotyledons naked and ready to act. Fig 62, Cucurbita ovifera, germinating seed showing the heel or peg, projecting on one side from summit of radicle and holding down lower tip of seed coats, which have been partially ruptured by the growth of the arched hypocotyl. The peg is developed with extraordinary rapidity, for it could only just be distinguished in 2 seedlings having radicles 35 inch in length. But after an interval of only 24 hours was well developed in both. It is formed, according to Flaholt, by the enlargement of the layers of the cortical parenchyma at the base of the hypocotyl. If, however, we judge by the effects of a solution of permanganate of potassium, it is developed on the exact line of junction between the hypocotyl and radicle, for the flat lower surface, as well as the edges, were coloured brown like the radicle, whilst the upper slightly inclined surface was left uncoloured like the hypocotyl, excepting, indeed, in 1 out of 33 immersed seedlings, in which a large part of the upper surface was coloured brown. Secondary roots sometimes spring from the lower surface of the peg, which thus seems in all respects to partake of the nature of the radicle. The peg is always developed on the side which becomes concave by the arching of the hypocotyl, and it would be of no service if it were formed on any other side. It is also always developed with the flat lower side, which, as just stated, forms a part of the radicle at right angles to it, and in a horizontal plane. This fact was clearly shown by burying some of the thin flat seeds in the same position as in Fig 62, excepting that they were not laid on their flat broad sides, but with one edge downwards. 9 seeds were thus planted, and the peg was developed in the same position relatively to the radicle, as in the figure. Consequently, it did not rest on the flat tip of the lower half of the seed coats, but was inserted like a wedge between the 2 tips. As the arched hypocotyl grew upwards, it tended to draw up the whole seed, and the peg necessarily rubbed against both tips, but did not hold either down. The result was that the cotyledons of 5 out of the 9 seeds thus placed were raised above the ground, still enclosed within their seed coats. 4 seeds were buried with the end from which the radicle protrudes pointing vertically downwards, and owing to the peg being always developed in the same position, its apex alone came into contact with and rubbed against the tip on one side. The result was that the cotyledons of all 4 emerged still within their seed coats. These cases show us how the peg acts in coordination with the position which the flat, thin, broad seeds would almost always occupy when naturally sown. When the tip of the lower half of the seed coats was cut off, Flaholt found, as we did likewise, that the peg could not act since it had nothing to press on, and the cotyledons were raised above the ground, with their seed coats not cast off. Lastly, nature shows us the use of the peg, for in the one cucurbitaceous genus known to us in which the cotyledons are hypogene and do not cast their seed coats, namely Megarrhiza, there is no vestige of a peg. This structure seems to be present in most of the other genera in the family. Judging from Flaholt's statements, we found it well developed and properly acting in Trichosanthes anguina, in which we hardly expected to find it, as the cotyledons are somewhat thick and fleshy. Few cases can be advanced of a structure better adapted for a special purpose than the present one. With Mimosa pudica, the radicle protrudes from a small hole in the sharp edge of the seed, and on its summit, where united with the hypocotyl, a transverse ridge is developed at an early age, which clearly aids in splitting the tough seed coats, but it does not aid in casting them off, as this is subsequently affected by the swelling of the cotyledons after they have been raised above the ground. The ridge or heel, therefore, acts rather differently from that of cucurbita. Its lower surface and the edges were coloured brown by the permanganate of potassium, but not the upper surface. It is a singular fact that after the ridge has done its work and has escaped from the seed coats, it is developed into a frill all round the summit of the radicle 20. At the base of the enlarged hypocotyl of Abronia umbellata, where it blends into the radicle, there is a projection or heel which varies in shape, but its outline is too angular in our former figure. Fig. 61. The radicle first protrudes from a small hole at one end of the tough, leathery winged fruit at this period, the upper part of the radicle is packed within the fruit, parallel to the hypocartel, and the single cotyledon is doubled back parallel to the latter. The swelling of these three parts, and especially the rapid development of the thick heel between the hypocartel and radicle, at the point where they are doubled, ruptures the tough fruit at the upper end, and allows the arched hypocartel to emerge, and this seems to be the function of the heel. A seed was cut out of the fruit, and allowed to germinate in damp air, and now a thin flat disc was developed all round the base of the hypocartel, and grew to an extraordinary breadth, like the frill described under mimosa, but somewhat broader. Flahault says that with mirabilis, a member of the same family with a bronia, a heel or collar, is developed all round the base of the hypocartel, but more on one side than on the other, and that it frees the cotyledons from their seed coats. We observed only old seeds, and these were ruptured by the absorption of moisture independently of any aid from the heel, and before the protrusion of the radicle. But it does not follow from our experience that fresh and tough fruits would behave in a like manner. In concluding this section of the present chapter, it may be convenient to summarize under the form of an illustration the usual movements of the hypocartels and epicartels of seedlings. Whilst breaking through the ground, and immediately afterwards, we may suppose a man to be thrown down on his hands and knees, and at the same time to one side by a load of hay falling on him. He would first endeavour to get his arched back upright, wriggling at the same time in all directions, to free himself a little from the surrounding pressure, and this may represent the combined effects of apogeotropism and circumnutation, when a seed is so buried that the arched hypocartel, or epicartel, protrudes at first in a horizontal or inclined plane. The man, still wriggling, would then raise his arched back as high as he could, and this may represent the growth and continued circumnutation of an arched hypocartel, or epicartel, before it has reached the surface of the ground. As soon as the man felt himself at all free, he would raise the upper part of his body whilst still on his knees and still wriggling, and this may represent the bowing backwards of the basal leg of the arch, which in most cases aids in the withdrawal of the cotyledons from the buried and ruptured seed coats, and the subsequent straightening of the whole hypocartel or epicartel. Circumnutation still continuing. Circumnutation of hypocartels and epicartels. When erect, the hypocartels, epicartels, and first shoots of the many seedlings observed by us, after they had become straight and erect, circumnudated continuously. The diversified figures described by them, often during 2 successive days, have been shown in the woodcuts in the last chapter. It should be recollected that the darts were joined by straight lines, so that the figures are angular, but if the observations had been made every few minutes, the lines would have been more or less curvilinear, and irregular ellipses, or ovals, or perhaps occasionally circles, would have been formed the direction of the longer axes of the ellipses made during the same day, or on successive days, generally changed completely, so as to stand at right angles to one another. The number of irregular ellipses or circles made within a given time differs much with different species. Thus with Brassica auracea, Cerinthe major and Cucurbita ovifera, about 4 such figures were completed in 12H, whereas with Solanum palinacanthum and Opuntia basilaris scarcely more than 1. The figures likewise differ greatly in size, thus they were very small, and in some degree doubtful in Stapelia, and large in Brassica, etc. The ellipses described by Lathyrus nisolia and Brassica were narrow, whilst those made by the oak were broad. The figures are often complicated by small loops and zigzag lines. As most seedling plants before the development of true leaves are of low, sometimes very low stature, the extreme amount of movement from side to side of their circumnudating stems was small. That of the hypocartel of Githagosegetum was about 2 of an inch, and that of Cucurbita ovifera about 28. A very young shoot of Lathyrus nisolia moved about 14, that of an American oak 2, that of the common nut only 4, and a rather tall shoot of the asparagus 11 of an inch. The extreme amount of movement of the sheath-like cotyledon of Phalaris canariensis was 3 of an inch, but it did not move very quickly, the tip crossing on one occasion 5 divisions of the micrometer, that is 1/100th of an inch, in 22 Roman 1000 s. A seedling Nalana prostrata travelled the same distance in 10 Roman 1000 s. Seedling cabbages circumnudate much more quickly, for the tip of a cotyledon crossed 1/100th of an inch on the micrometer in 3 Roman 1000 s. And this rapid movement, accompanied by incessant oscillations, was a wonderful spectacle when beheld under the microscope. The absence of light for at least a day does not interfere in the least with the circumnutation of the hypocartels, epicartels, or young shoots of the various dicotyledonous seedlings, observed by us nor with that of the young shoots of some monocotyledons, the circumnutation was indeed much plainer in darkness than in light, for if the light was at all lateral the stem bent towards it in a more or less zigzag course. Finally, the hypocotyls of many seedlings are drawn during the winter into the ground, or even beneath it, so that they disappear. This remarkable process, which apparently serves for their protection, has been fully described by De Vries 21. He shows that it is affected by the contraction of the parenchymasals of the root, but the hypocotyl itself in some cases contracts greatly, and although at first smooth becomes covered with zigzag ridges, as we observed with Githago segetum. How much of the drawing down and burying of the hypocotyl of Opuntia basilaris was due to the contraction of this part, and how much to that of the radical we did not observe. Circumnutation of cotyledons. With all the dicotyledonous seedlings described in the last chapter, the cotyledons were in constant movement, chiefly in a vertical plane, and commonly once up and once down in the course of the 24 hours, but there were many exceptions to such simplicity of movement. Thus the cotyledons of Ipoma caerulea moved 13 times either upwards or downwards in the course of 16H 18 Roman 1000, those of Oxalis rosea moved in the same manner 7 times in the course of 24H, and those of Cassia tora described 5 irregular ellipses in 9H. The cotyledons of some individuals of Mimosa pudica and of Lotus jacobus moved only once up and down in 24H, whilst those of others performed within the same period an additional small oscillation. Thus with different species, and with different individuals of the same species, there were many gradations from a single diurnal movement to oscillations as complex as those of the Ipoma and Cassia. The opposite cotyledons on the same seedling moved to a certain extent independently of one another. This was conspicuous with those of Oxalis sensitiva, in which one cotyledon might be seen during the daytime rising up until it stood vertically, whilst the opposite one was sinking down. Although the movements of cotyledons were generally in nearly the same vertical plane, yet their upward and downward courses never exactly coincided, so that ellipses more or less narrow were described, and the cotyledons may safely be said to have circumnudated, nor could this fact be accounted for by the mere increase in length of the cotyledons through growth, for this by itself would not induce any lateral movement. That there was lateral movement in some instances, as with the cotyledons of the cabbage, was evident, for these, besides moving up and down, changed their course from right to left 12 times in 14H 15 Roman 1000. With Solanum lycopassicum the cotyledons, after falling in the forenoon, zigzagged from side to side between 12 and 4 P Roman 1000, and then commenced rising. The cotyledons of Lupinus luteus are so thick, about 8 of an inch, and fleshy 22, that they seemed little likely to move, and were therefore observed with especial interest. They certainly moved largely up and down, and as the line traced was zigzag, there was some lateral movement. The 9 cotyledons of a seedling, Pinus pinaster, plainly circumnudated, and the figures described approached more nearly to irregular circles than to irregular ovals or ellipses. The sheath-like cotyledons of the gramen circumnudate, that is, move to all sides as plainly as do the hypocotyls or epicotyls of any dicotyledonous plants. Lastly, the very young fronds of a fern and of a selaginella circumnudated. In a large majority of the cases, which were carefully observed, the cotyledons sink a little downwards in the forenoon, and rise a little in the afternoon or evening. They thus stand rather more highly inclined during the night than during the midday, at which time they are expanded almost horizontally. The circumnudating movement is thus at least partially periodic, no doubt in connection, as we shall hereafter see, with the daily alternations of light and darkness. The cotyledons of several plants move up so much at night as to stand nearly or quite vertically, and in this latter case they come into close contact with one another. On the other hand, the cotyledons of a few plants sink almost or quite vertically down at night, and in this latter case they clasp the upper part of the hypocotyl. In the same genus Oxalis, the cotyledons of certain species stand vertically up, and those of other species vertically down at night. In all such cases, the cotyledons may be said to sleep, for they act in the same manner as do the leaves of many sleeping plants. This is a movement for a special purpose, and will therefore be considered in a future chapter devoted to this subject. In order to gain some rude notion of the proportional number of cases in which the cotyledons of dicotyledonous plants, hypogene ones being of course excluded, changed their position in a conspicuous manner at night, one or more species in several genera were cursorily observed. Besides those described in the last chapter, altogether 153 genera, included in as many families as could be procured, were thus observed by us, the cotyledons were looked at in the middle of the day and again at night, and those were noted as sleeping which stood either vertically or at an angle of at least 60 above or beneath the horizon. Of such genera there were 26, and in 21 of them the cotyledons of some of the species rose, and in only 6 sank at night, and some of these latter cases are rather doubtful from causes to be explained in the chapter on the sleep of cotyledons, when cotyledons which at noon were nearly horizontal stood at night at more than 20, and less than 60 above the horizon, they were recorded as plainly raised, and of such genera there were 38. We did not meet with any distinct instances of cotyledons periodically sinking only a few degrees at night, although no doubt such occur. We have now accounted for 64 genera out of the 153, and there remain 89 in which the cotyledons did not change their position at night by as much as 20, that is, in a conspicuous manner which could easily be detected by the unaided eye and by memory. But it must not be inferred from this statement that these cotyledons did not move at all, for in several cases a rise of a few degrees was recorded when they were carefully observed. The number 89 might have been a little increased, for the cotyledons remained almost horizontal at night in some species. In a few genera, for instance Trifolium and Geranium, which are included amongst the sleepers, such genera might therefore have been added to the 89 again. One species of Oxalis generally raised its cotyledons at night more than 20, and less than 60 above the horizon, so that this genus might have been included under 2 heads, but as several species in the same genus were not often observed, such double entries have been avoided. In a future chapter, it will be shown that the leaves of many plants which do not sleep rise a few degrees in the evening, and during the early part of the night, and it will be convenient to defer, until then, the consideration of the periodicity of the movements of cotyledons. On the pulvini or joints of cotyledons, with several of the seedlings described in this, and the last chapter, the summit of the petiole is developed into a pulvinous cushion, or joint, as this organ has been variously called, like that with which many leaves are provided. It consists of a mass of small cells, usually of a pale color from the absence of chlorophyll, and with its outline more or less convex, as shown in the annexed figure in the case of Oxalis sensitiva 2/3 of the petiole, and in that of Mimosa pudica, apparently, the whole of the short subpetioles of the leaflets have been converted into pulvini with pulvinated leaves. Roman 1e, those provided with a pulvinus, their periodical movements depend according to Pfeffer 23 on the cells of the pulvinus, alternately expanding more quickly on one side than on the other, whereas the similar movements of leaves not provided with pulvini depend on their growth being alternately more rapid on one side than on the other. 24 As long as a leaf provided with a pulvinus is young and continues to grow, its movement depends on both these causes combined. 25 And if the view now held by many botanists be sound, namely, that growth is always preceded by the expansion of the growing cells, then the difference between the movements induced by the aid of pulvini and without such aid is reduced to the expansion of the cells not being followed by growth in the first case, and being so followed in the second case. Fig. 63, Oxalis rosea, longitudinal section of a pulvinus on the summit of the petiole of a cotyledon drawn, with the camera lucida, magnified 75 times pp petiole, f fibrovascular bundle, bb commencement of blade of cotyledon. Darts were made with Indian ink along the midrib of both pulvinated cotyledons of a rather old seedling of Oxalis valdiviana. Their distances were repeatedly measured with an eyepiece micrometer during 834 days, and they did not exhibit the least trace of increase. It is therefore almost certain that the pulvinus itself was not then growing nevertheless during this whole time, and for 10 days afterwards these cotyledons rose vertically every night. In the case of some seedlings raised from seeds purchased under the name of Oxalis floribunda, the cotyledons continued for a long time to move vertically down at night, and the movement apparently depended exclusively on the pulvini, for their petioles were of nearly the same length in young and in old seedlings which had produced true leaves. With some species of cassia, on the other hand, it was obvious without any measurement that the pulvinated cotyledons continued to increase greatly in length during some weeks, so that here the expansion of the cells of the pulvini and the growth of the petiole were probably combined in causing their prolonged periodic movements. It was equally evident that the cotyledons of many plants not provided with pulvini increased rapidly in length, and their periodic movements, no doubt, were exclusively due to growth. In accordance with the view that the periodic movements of all cotyledons depend primarily on the expansion of the cells, whether or not followed by growth, we can understand the fact that there is but little difference in the kind or form of movement in the two sets of cases. This may be seen by comparing the diagrams given in the last chapter. Thus the movements of the cotyledons of Brassica auracea and of Ipoma caerulea, which are not provided with pulvini, are as complex as those of Oxalis and Cassia, which are thus provided the pulvinated cotyledons of some individuals of Mimosa pudica and Lotus jacobus, made only a single oscillation, whilst those of other individuals moved twice up and down in the course of 24 hours, so it was occasionally with the cotyledons of Cucurbita ovifera, which are destitute of a pulvinus. The movements of pulvinated cotyledons are generally larger in extent than those without a pulvinus. Nevertheless, some of the latter moved through an angle of 90. There is, however, one important difference in the two sets of cases: the nocturnal movements of cotyledons, without pulvini for instance, those in the crucifery Cucurbidae scythago, and beta never last even for a week to any conspicuous degree. Pulvinated cotyledons, on the other hand, continue to rise at night for a much longer period, even for more than a month, as we shall now show, but the period, no doubt, depends largely on the temperature to which the seedlings are exposed, and their consequent rate of development. Oxalis valdiviana, some cotyledons which had lately opened, and were horizontal on March 6 at noon, stood at night vertically up on the 13th. The first true leaf was formed, and was embraced at night by the cotyledons on April 9. After an interval of 35 days 6 leaves were developed. And yet the cotyledons rose almost vertically at night. The cotyledons of another seedling, which when first observed had already produced a leaf, stood vertically at night, and continued to do so for 11 additional days. After 16 days from the first observation, 2 leaves were developed, and the cotyledons were still greatly raised at night after 21 days. The cotyledons during the day were deflected beneath the horizon, but at night were raised 45 above it. After 24 days from the first observation begun, after a true leaf had been developed, the cotyledons ceased to rise at night. Oxalis biophytum sensitiva, the cotyledons of several seedlings, 45 days after their first expansion, stood nearly vertical at night, and closely embraced either 1 or 2 true leaves, which by this time had been formed. These seedlings had been kept in a very warm house, and their development had been rapid. Oxalis corniculata, the cotyledons do not stand vertical at night, but generally rise to an angle of about 45 above the horizon. They continued thus to act for 23 days after their first expansion, by which time 2 leaves had been formed. Even after 29 days, they still rose moderately above their horizontal or downwardly deflected diurnal position. Mimosa pudica, the cotyledons were expanded for the first time on Nov 2 and stood vertical at night on the 15th. The first leaf was formed, and at night the cotyledons were vertical on the 28th. They behaved in the same manner on Dec 15th, that is, after 44 days the cotyledons were still considerably raised at night, but those of another seedling only 1 day older were raised very little. Mimosa albida, a seedling, was observed during only 12 days, by which time a leaf had been formed, and the cotyledons were then quite vertical at night. Trifolium subterraneum, a seedling 8 days old, had its cotyledons horizontal at 10 A Roman 1000, and vertical at 9 P Roman 1000, after an interval of 2 months, by which time the first and second true leaves had been developed. The cotyledons still performed the same movement. They had now increased greatly in size, and had become oval, and their petioles were actually 1/8 of an inch in length. Trifolium strictum, after 17 days, the cotyledons still rose at night, but were not afterwards observed. Lotus jacobous, the cotyledons of some seedlings having well-developed leaves, rose to an angle of about 45 at night, and even after 3 or 4 whorls of leaves had been formed, the cotyledons rose at night considerably above their diurnal horizontal position. Cassia mimosoids, the cotyledons of this Indian species, 14 days after their first expansion, and when a leaf had been formed, stood during the day horizontal, and at night vertical. Cassia sp, a large S. Brazilian tree raised from seeds sent us by F. Muller, the cotyledons, after 16 days from their first expansion, had increased greatly in size with 2 leaves just formed. They stood horizontally during the day and vertically at night, but were not afterwards observed. Cassia negulcta, likewise a S. Brazilian species, a seedling 34 days after the first expansion of its cotyledons, was between 3 and 4 inches in height, with 3 well-developed leaves, and the cotyledons, which during the day were nearly horizontal at night, stood vertical, closely embracing the young stem. The cotyledons of another seedling of the same age 5 inches in height, with 4 well-developed leaves, behaved at night in exactly the same manner. It is known 26 that there is no difference in structure between the upper and lower halves of the pulvini of leaves sufficient to account for their upward or downward movements. In this respect, cotyledons offer an unusually good opportunity for comparing the structure of the two halves, for the cotyledons of Oxalis valdiviana rise vertically at night, whilst those of O. rosea sink vertically, yet when sections of their pulvini were made, no clear difference could be detected between the corresponding halves of this organ in the two species which move so differently. With O. rosea, however, there were rather more cells in the lower than in the upper half, but this was likewise the case in one specimen of O. valdiviana. The cotyledons of both species, 312 Roman 2000 in length, were examined in the morning, whilst extended horizontally, and the upper surface of the pulvinus of O. rosea was then wrinkled transversely, showing that it was in a state of compression, and this might have been expected as the cotyledons sink at night. With O. valdiviana, it was the lower surface which was wrinkled, and its cotyledons rise at night. Trifolium is a natural genus, and the leaves of all the species seen by us are pulvinated. So it is with the cotyledons of T. subterraneum and strictum, which stand vertically at night, whereas those of T. resupinatum exhibit not a trace of a pulvinus nor of any nocturnal movement. This was ascertained by measuring the distance between the tips of the cotyledons of 4 seedlings at midday, and at night. In this species, however, as in the others, the first formed leaf, which is simple or not trifoliate, rises up and sleeps like the terminal leaflet on a mature plant. In another natural genus, Oxalis, the cotyledons of O. valdiviana rosea, floribunda articulata and sensitiva, are pulvinated, and all move at night into an upward or downward vertical position. In these several species, the pulvinus is seated close to the blade of the cotyledon, as is the usual rule with most plants. Oxalis corniculata var atropurpurea differs in several respects. The cotyledons rise at night to a very variable amount, rarely more than 45, and in one lot of seedlings purchased under the name of O. tropiolids, but certainly belonging to the above variety, they rose only from 5 to 15 above the horizon. The pulvinus is developed imperfectly and to an extremely variable degree, so that apparently it is tending towards abortion. No such case has hitherto, we believe, been described. It is coloured green from its cells containing chlorophyll, and it is seated nearly in the middle of the petiole, instead of at the upper end, as in all the other species. The nocturnal movement is effected partly by its aid and partly by the growth of the upper part of the petiole, as in the case of plants destitute of a pulvinus. From these several reasons, and from our having partially traced the development of the pulvinus from an early age, the case seems worth describing in some detail. When the cotyledons of O. corniculata were dissected out of a seed, from which they would soon have naturally emerged, no trace of a pulvinus could be detected, and all the cells forming the short petiole, 7 in number in a longitudinal row, were of nearly equal size in seedlings 1 or 2 days old. The pulvinus was so indistinct that we thought at first that it did not exist, but in the middle of the petiole, an ill-defined transverse zone of cells could be seen, which were much shorter than those both above and below. Although of the same breadth with them, they presented the appearance of having been just formed by the transverse division of longer cells, and there can be little doubt that this had occurred, for the cells in the petiole, which had been dissected out of the seed, averaged in length 7 divisions of the micrometer each division, equaling 3 Roman 2000, and were a little longer than those forming a well-developed pulvinus, which varied between 4 and 6 of these same divisions. After a few additional days, the ill-defined zone of cells becomes distinct, and although it does not extend across the whole width of the petiole, and although the cells are of a green colour from containing chlorophyll, yet they certainly constitute a pulvinus, which, as we shall presently see, acts as one. These small cells were arranged in longitudinal rows, and varied from 4 to 7 in number, and the cells themselves varied in length in different parts of the same pulvinus and in different individuals. In the accompanying figures A and B, Fig 64, we have views of the epidermis 27 in the middle part of the petioles of 2 seedlings, in which the pulvinus was for this species well developed. They offer a striking contrast with the pulvinus of O. rosea c. former Fig 63 or of O. valdiviana, with the seedlings falsely called O. tropiolids, the cotyledons of which rise very little at night. The small cells were still fewer in number, and in parts formed a single transverse row, and in other parts short longitudinal rows of only 2 or 3. Nevertheless, they sufficed to attract the eye when the whole petiole was viewed as a transparent object beneath the microscope. In these seedlings, there could hardly be a doubt that the pulvinus was becoming rudimentary and tending to disappear, and this accounts for its great variability in structure and function. Fig 64, Oxalis corniculata, A and B, the almost rudimentary pulvini of the cotyledons of two rather old seedlings, viewed as transparent objects, magnified 50 times. In the following table, some measurements of the cells in fairly well-developed pulvini of O. corniculata are given. Seedling 1 day old, with cotyledon 2 Roman 2000 in length divisions of micrometer 28, average length of cells, of pulvinus 6 to 7 length of longest cell, below the pulvinus 13 length of longest cell, above the pulvinus 20. Seedling 5 days old cotyledon 3 Roman 2000 in length, with the pulvinus quite distinct average length of cells, of pulvinus 6 length of longest cell, below the pulvinus 22 length of longest cell, above the pulvinus 40. Seedling 8 days old cotyledon 5 Roman 2000 in length, with a true leaf formed, but not yet expanded average length of cells of pulvinus 9 length of longest cell, below the pulvinus 44 length of longest cell, above the pulvinus 70. Seedling 13 days old cotyledon 4 Roman 2000 in length, with a small true leaf fully developed average length of cells, of pulvinus 7 length of longest cell, below the pulvinus 30 length of longest cell, above the pulvinus 60. The cotyledons of seedlings only a day old rise at night considerably, sometimes as much as afterwards, but there was much variation in this respect, as the pulvinus is so indistinct at first. The movement probably does not then depend on the expansion of its cells, but on periodically unequal growth in the petiole. By the comparison of seedlings of different known ages, it was evident that the chief seat of growth of the petiole was in the upper part between the pulvinus and the blade, and this agrees with the fact shown in the measurements above, given that the cells grow to a greater length in the upper than in the lower part with a seedling 11 days old. The nocturnal rise was found to depend largely on the action of the pulvinus, for the petiole at night was curved upwards at this point, and during the day, whilst the petiole was horizontal, the lower surface of the pulvinus was wrinkled, with the upper surface tense. Although the cotyledons at an advanced age do not rise at night to a higher inclination, then whilst young yet they have to pass through a larger angle in one instance, amounting to 63, to gain their nocturnal position, as they are generally deflected beneath the horizon. During the day, even with the 11 days old seedling, the movement did not depend exclusively on the pulvinus, for the blade where joined to the petiole was curved upwards, and this must be attributed to unequal growth. Therefore the periodic movements of the cotyledons of O. corniculata depend on two distinct but conjoint actions, namely the expansion of the cells of the pulvinus, and on the growth of the upper part of the petiole, including the base of the blade. Lotus jacobous, the seedlings of this plant present a case parallel to that of Oxalis corniculata in some respects, and in others unique as far as we have seen. The cotyledons during the first 4 or 5 days of their life do not exhibit any plain nocturnal movement, but afterwards they stand vertically or almost vertically up at night. There is, however, some degree of variability in this respect, apparently dependent on the season, and on the degree to which they have been illuminated during the day, with older seedlings having cotyledons 4 Roman 2000 in length, which rise considerably at night. There is a well-developed pulvinus close to the blade, colourless, and rather narrower than the rest of the petiole, from which it is abruptly separated. It is formed of a mass of small cells of an average length of 21 Roman 2000, whereas the cells in the lower part of the petiole are about 6 Roman 2000, and those in the blade from 34 to 4 Roman 2000 in length. The epidermic cells in the lower part of the petiole project conically, and thus differ in shape from those over the pulvinus. Turning now to very young seedlings, the cotyledons of which do not rise at night, and are only from 2 to 212 Roman 2000 in length, their petioles do not exhibit any defined zone of small cells destitute of chlorophyll and differing in shape exteriorly from the lower ones. Nevertheless, the cells at the place where a pulvinus will afterwards be developed are smaller, being on an average 15 Roman 2000 in length than those in the lower parts of the same petiole, which gradually become larger in proceeding downwards, the largest being 30 Roman 2000 in length at this early age. The cells of the blade are about 27 Roman 2000 in length. We thus see that the pulvinus is formed by the cells in the uppermost part of the petiole, continuing for only a short time to increase in length, then being arrested in their growth, accompanied by the loss of their chlorophyll grains, whilst the cells in the lower part of the petiole continue for a long time to increase in length, those of the epidermis becoming more conical. The singular fact of the cotyledons of this plant not sleeping at first is therefore due to the pulvinus not being developed at an early age. We learn from these two cases of lotus and oxalis that the development of a pulvinus follows from the growth of the cells over a small defined space of the petiole being almost arrested at an early age. With lotus jacobus, the cells at first increase a little in length in oxalis corniculata, they decrease a little owing to self-division. A mass of such small cells forming a pulvinus might therefore be either acquired or lost without any special difficulty by different species in the same natural genus, and we know that with seedlings of trifolium lotus and oxalis, some of the species have a well-developed pulvinus, and others have none or one in a rudimentary condition, as the movements caused by the alternate turgescence of the cells in the two halves of a pulvinus must be largely determined by the extensibility and subsequent contraction of their walls. We can perhaps understand why a large number of small cells will be more efficient than a small number of large cells, occupying the same space, as a pulvinus is formed by the arrestment of the growth of its cells' movements, dependent on their action, may be long continued without any increase in length of the part, thus provided, and such long continued movements seem to be one chief end gained by the development of a pulvinus. Long continued movement would be impossible in any part without an inordinate increase in its length, if the turgescence of the cells was always followed by growth. Disturbance of the periodic movements of cotyledons by light. The hypocotyls and cotyledons of most seedling plants are, as is well known, extremely heliotropic, but cotyledons, besides being heliotropic, are affected paratonically, to use Sachs' expression, by light, that is, their daily periodic movements are greatly and quickly disturbed by changes in its intensity, or by its absence. It is not that they cease to circumnudate in darkness, for in all the many cases observed by us, they continued to do so, but the normal order of their movements in relation to the alternations of day and night is much disturbed or quite annulled. This holds good with species the cotyledons of which rise or sink so much at night that they may be said to sleep, as well as with others, which rise only a little, but different species are affected in very different degrees by changes in the light. For instance, the cotyledons of Beta vulgaris solanum lycopersicum, Cerinth major and Lupinus luteus, when placed in darkness, moved down during the afternoon and early night, instead of rising, as they would have done if they had been exposed to the light. All the individuals of the solanum did not behave in the same manner. For the cotyledons of 1, circumnudated about the same spot between 2 and 10 p. Roman 1000, the cotyledons of a seedling of Oxalis corniculata, which was feebly illuminated from above, moved downwards during the first morning in the normal manner, but on the second morning it moved upwards. The cotyledons of Lotus jacobous were not affected by 4h of complete darkness, but when placed under a double skylight, and thus feebly illuminated, they quite lost their periodical movements on the third morning. On the other hand, the cotyledons of Cucurbita ovifera moved in the normal manner during a whole day in darkness. Seedlings of Githagoseggetum were feebly illuminated from above in the morning, before their cotyledons had expanded, and they remained closed for the next 40h. Other seedlings were placed in the dark after their cotyledons had opened in the morning, and these did not begin to close until about 4h had elapsed. The cotyledons of Oxalis rosea sank vertically downwards after being left for 1h 20 Roman 1000 in darkness, but those of some other species of Oxalis were not affected by several hours of darkness. The cotyledons of several species of Cassia are eminently susceptible to changes in the degree of light to which they are exposed. Thus seedlings of an unnamed S. Brazilian species, large and beautiful tree, were brought out of the hothouse and placed on a table in the middle of a room with 2 northeast and 1 northwest window, so that they were fairly well illuminated, though of course less so than in the hothouse, the day being moderately bright, and after 36 Roman 1000, the cotyledons which had been horizontal rose up vertically and closed together as when asleep. After thus remaining on the table for 1h 13 Roman 1000, they began to open. The cotyledons of young seedlings of another Brazilian species, and of Roman 100 Negulcta, treated in the same manner, behaved similarly, excepting that they did not rise up quite so much. They again became horizontal after about an hour. Here is a more interesting case. Seedlings of Cassia tora in 2 parts, which had stood for some time on the table in the room just described, had their cotyledons horizontal. One part was now exposed for 2h to dull sunshine, and the cotyledons remained horizontal. It was then brought back to the table, and after 50 Roman 1000, the cotyledons had risen 68 above the horizon. The other part was placed during the same 2h behind a screen in the room where the light was very obscure, and the cotyledons rose 63 above the horizon, the part was then replaced on the table, and after 50 Roman 1000, the cotyledons had fallen 33. These two parts with seedlings of the same age stood close together, and were exposed to exactly the same amount of light, yet the cotyledons in the one part were rising, whilst those in the other part were at the same time sinking. This fact illustrates in a striking manner that their movements are not governed by the actual amount, but by a change in the intensity or degree of the light. A similar experiment was tried with two sets of seedlings, both exposed to a dull light, but different in degree, and the result was the same. The movements of the cotyledons of this kasha are, however, determined, as in many other cases, largely by habit or inheritance independently of light, for seedlings which had been moderately illuminated during the day were kept all night, and on the following morning in complete darkness, yet the cotyledons were partially open in the morning, and remained open in the dark for about 6h. The cotyledons in another part, similarly treated on another occasion, were open at 7a Roman 1000, and remained open in the dark for 4h 30 Roman 1000, after which time they began to close. Yet these same seedlings, when brought in the middle of the day from a moderately bright into only a moderately dull light, raised, as we have seen, their cotyledons high above the horizon. Sensitiveness of cotyledons to contact. This subject does not possess much interest, as it is not known that sensitiveness of this kind is of any service to seedling plants. We have observed cases in only 4 genera, though we have vainly observed the cotyledons of many others. The genus Cassia seems to be preeminent in this respect. Thus the cotyledons of Roman 100 Tora, when extended horizontally, were both lightly tapped with a very thin twig for 3 Roman 1000, and in the course of a few minutes they formed together an angle of 90, so that each had risen 45. A single cotyledon of another seedling was tapped in a like manner for 1 Roman 1000, and it rose 27 in 9 Roman 1000, and after 8 additional minutes, it had risen 10 more. The opposite cotyledon, which was not tapped, hardly moved at all. The cotyledons in all these cases became horizontal again. In less than half an hour. The pulvinus is the most sensitive part, for on slightly pricking 3 cotyledons with a pin in this part, they rose up vertically, but the blade was found also to be sensitive. Care having been taken that the pulvinus was not touched, drops of water placed quietly on these cotyledons produced no effect, but an extremely fine stream of water ejected from a syringe caused them to move upwards when a part of seedlings was rapidly hit with a stick, and thus jarred. The cotyledons rose slightly when a minute drop of nitric acid was placed on both pulvini of a seedling. The cotyledons rose so quickly that they could easily be seen to move, and almost immediately afterwards they began to fall, but the pulvini had been killed and became brown. The cotyledons of an unnamed species of cassia, a large tree from S. Brazil, rose 31 in the course of 26 Roman 1000 after the pulvini, and the blades had both been rubbed during 1 Roman 1000 with a twig, but when the blade alone was similarly rubbed, the cotyledons rose only 8. The remarkably long and narrow cotyledons of a third unnamed species from S. Brazil did not move when their blades were rubbed on 6 occasions. Pointed stick for 30s or for 1 Roman 1000, but when the pulvinus was rubbed and slightly pricked with a pin, the cotyledons rose in the course of a few minutes through an angle of 6. Several cotyledons of Roman 100 neglecta likewise from S. Brazil rose in from 5 Roman 1000 to 15 Roman 1000 to various angles between 16v and 34, after being rubbed during 1 Roman 1000 with a twig. Their sensitiveness is retained to a somewhat advanced age. For the cotyledons of a little plant of Roman 100 neglecta, 34 days old, and bearing 3 true leaves, rose when lightly pinched between the finger and thumb. Some seedlings were exposed for 30 Roman 1000 to a wind temp 50f, sufficiently strong to keep the cotyledons vibrating. But this, to our surprise, did not cause any movement. The cotyledons of 4 seedlings of the Indian Roman 100 glauca were either rubbed with a thin twig for 2 Roman 1000, or were lightly pinched. 1 rose 34 a second, only 6 a third 13, and a fourth 17. A cotyledon of Roman 100 Florida, similarly treated, rose 9, one of Roman 100 Corymbosa rose 712, and one of the very distinct Roman 100 mimosoids only 6. Those of Roman 100 pubescens did not appear to be in the least sensitive, nor were those of Roman 100 nodosa, but these latter are rather thick and fleshy, and do not rise at night or go to sleep. Smithia sensitiva, this plant belongs to a distinct suborder of the Leguminosae from Cassia. Both cotyledons of an oldish seedling, with the first true leaf partially unfolded, were rubbed for 1 Roman 1000 with a fine twig, and in 5 Roman 1000 each, rose 32. They remained in this position for 15 Roman 1000, but when looked at again, 40 Roman 1000 after the rubbing, each had fallen 14. Both cotyledons of another and younger seedling were lightly rubbed in the same manner for 1 Roman 1000, and after an interval of 32 Roman 1000 each had risen 30, they were hardly at all sensitive to a fine jet of water. The cotyledons of S. fundii, an African water plant, are thick and fleshy, they are not sensitive, and do not go to sleep. Mimosa pudica and albida, the blades of several cotyledons of both these plants were rubbed or slightly scratched with a needle during 1 Roman 1000 or 2 Roman 1000, but they did not move in the least when, however, the pulvini of 6 cotyledons of Roman 1000 pudica were thus scratched. 2 of them were slightly raised in these 2 cases. Perhaps the pulvinus was accidentally pricked, for on pricking the pulvinus of another cotyledon, it rose a little. It thus appears that the cotyledons of mimosa are less sensitive than those of the previously mentioned plants. 29. Oxalis sensitiva, the blades and pulvini of 2 cotyledons standing horizontally, were rubbed, or rather tickled, for 30s with a fine split bristle, and in 10 Roman 1000 each had risen 48. When looked at again, in 35 Roman 1000 after being rubbed, they had risen 4 more after 30 additional minutes. They were again horizontal on hitting a pot rapidly with a stick for 1 Roman 1000. The cotyledons of 2 seedlings were considerably raised in the course of 11 Roman 1000. A pot was carried a little distance on a tray, and thus jolted, and the cotyledons of 4 seedlings were all raised in 10 Roman 1000 after 17 Roman 1001, had risen 56 a second, 40, 5 a third, almost 90, and a fourth 90, after an additional interval of 40 Roman 1003 of them, had re-expanded to a considerable extent. These observations were made before we were aware at what an extraordinarily rapid rate the cotyledons circumnutate, and are therefore liable to error. Nevertheless, it is extremely improbable that the cotyledons in the 8 cases given should all have been rising at the time when they were irritated. The cotyledons of Oxalis valdiviana and rosea were rubbed, and did not exhibit any sensitiveness. Finally, there seems to exist some relation between the habit of cotyledons rising vertically at night, or going to sleep, and their sensitiveness, especially that of their pulvini to touch. For all the above-named plants sleep at night. On the other hand, there are many plants the cotyledons of which sleep, and are not in the least sensitive, as the cotyledons of several species of cassia are easily affected both by slightly diminished light and by contact. We thought that these 2 kinds of sensitiveness might be connected, but this is not necessarily the case, for the cotyledons of Oxalis sensitiva did not rise when kept on one occasion for 112h, and on a second occasion for nearly 4h in a dark closet. Some other cotyledons, as those of Githagoseggetum, are much affected by a feeble light, but do not move when scratched by needle. That with the same plant there is some relation between the sensitiveness of its cotyledons and leaves seems highly probable, for the above described Smithia and Oxalis have been called sensitiva owing to their leaves being sensitive, and though the leaves of the several species of cassia are not sensitive to a touch, yet if a branch be shaken or syringed with water, they partially assume their nocturnal, dependent position. But the relation between the sensitiveness to contact of the cotyledons and of the leaves of the same plant is not very close, as may be inferred from the cotyledons of Mimosa pudica being only slightly sensitive, whilst the leaves are well known to be so in the highest degree. Again, the leaves of Neptunia auracea are very sensitive to a touch, whilst the cotyledons do not appear to be so in any degree. Chapter Roman 3: Sensitiveness of the apex of the radicle to contact and to other irritants. Manner in which radicles bend when they encounter an obstacle in the soil. Viscia faba, tips of radicles, highly sensitive to contact, and other irritants. Effects of 2. Higher temperature power of discriminating between objects attached on opposite sides. Tips of secondary radicals. Sensitive pisum, tips of radicals, sensitive effects of such sensitiveness in overcoming geotropism. Secondary radicals. Phasalis, tips of radicals hardly sensitive to contact, but highly sensitive to caustic, and to the removal of a slice. Tropiolum gossypium cucurbita raffinusculus, tip, not sensitive to slight contact, highly sensitive to caustic. Quercus, tip, highly sensitive to contact. Power of discrimination. Z, tip, highly sensitive. Secondary radicals. Sensitiveness of radicals to moist air. Summary of chapter. In order to see how the radicals of seedlings would pass over stones, roots, and other obstacles, which they must incessantly encounter in the soil, germinating beans Viscia faba were so placed that the tips of the radicals came into contact almost rectangularly, or at a high angle with underlying plates of glass. In other cases, The beans were turned about whilst their radicals were growing so that they descended nearly vertically on their own smooth, almost flat broad upper surfaces. The delicate root cap, when it first touched any directly opposing surface, was a little flattened transversely. The flattening soon became oblique, and in a few hours quite disappeared, the apex now pointing at right angles, or at nearly right angles to its former course. The radical then seemed to glide in its new direction over the surface, which had opposed it, pressing on it with very little force. How far such abrupt changes in its former course are aided by the circumnutation of the tip must be left doubtful. Thin slips of wood were cemented on more or less steeply inclined glass plates at right angles to the radicals, which were gliding down them. Straight lines had been painted along the growing terminal part of some of these radicals before they met the opposing slip of wood, and the lines became sensibly curved in 2H after the apex had come into contact with the slips. In one case of a radical, which was growing rather slowly, the root cap, after encountering a rough slip of wood at right angles, was at first slightly flattened transversely. After an interval of 2H30 Roman 1000, the flattening became oblique, and after an additional 3 hours the flattening had wholly disappeared, and the apex now pointed at right angles to its former course. It then continued to grow in its new direction alongside the slip of wood, until it came to the end of it, round which it bent rectangularly soon afterwards. When coming to the edge of the plate of glass, it was again bent at a large angle, and descended perpendicularly into the damp sand. When, as in the above cases, radicals encountered an obstacle at right angles to their course, the terminal growing part became curved for a length of between 3 and 4 of an inch 810 Roman 2000, measured from the apex. This was well shown by the black lines, which had been previously painted on them. The first and most obvious explanation of the curvature is that it results merely from the mechanical resistance to the growth of the radical in its original direction. Nevertheless, this explanation did not seem to us satisfactory. The radicals did not present the appearance of having been subjected to a sufficient pressure to account for their curvature, and Sachs has shown that the growing part is more rigid than the part immediately above, which has ceased to grow, so that the latter might have been expected to yield and become curved as soon as the apex encountered an unyielding object, whereas it was the stiff growing part which became curved. Moreover, an object which yields with the greatest ease will deflect a radical. Thus, as we have seen, when the apex of the radical of the bean encountered the polished surface of extremely thin tinfoil laid on soft sand, no impression was left on it, yet the radical became deflected at right angles. A second explanation occurred to us, namely, that even the gentlest pressure might check the growth of the apex, and in this case, growth could continue only on one side, and thus the radical would assume a rectangular form. But this view leaves wholly unexplained the curvature of the upper part, extending for a length of 810 Roman 20,001, Arbeiten Bart Inst Wurzburg Heft Roman 3p 398. We were therefore led to suspect that the apex was sensitive to contact, and that an effect was transmitted from it to the upper part of the radical, which was thus excited to bend away from the touching object, as a little loop of fine thread hung on a tendril, or on the petiole of a leaf-climbing plant, causes it to bend. We thought that any small hard object affixed to the tip of a radical, freely suspended and growing in damp air, might cause it to bend if it were sensitive, and yet would not offer any mechanical resistance to its growth. Full details will be given of the experiments which were tried, as the result proved remarkable. The fact of the apex of a radical being sensitive to contact has never been observed, though, as we shall hereafter see, Sachs discovered that the radical a little above the apex is sensitive and bends like a tendril towards the touching object. But when one side of the apex is pressed by any object, the growing part bends away from the object, and this seems a beautiful adaptation for avoiding obstacles in the soil. And as we shall see, for following the lines of least resistance, many organs when touched bend in one fixed direction, such as the stamens of berberis, the lobes of Dioneer, etc., and many organs such as tendrils, whether modified leaves or flower peduncles, and some few stems, bend towards a touching object, but no case, we believe, is known of an organ bending away from a touching object. Sensitiveness of the apex of the radical of Vischer Faber common beans, after being soaked in water for 24H, were pinned with the hilum downwards in the manner followed by Sachs inside the cork lids of glass vessels, which were half filled with water the sides, and the cork were well moistened, and light was excluded as soon as the beans had protruded. Radicals, some to a length of less than 1/10 of an inch, and others to a length of several tenths, little squares or oblongs of card, were affixed to the short sloping sides of their conical, tips. The squares therefore adhered obliquely with reference to the longitudinal axis of the radical, and this is a very necessary precaution, for if the bits of card accidentally became displaced, or were drawn by the viscid matter employed so as to adhere parallel to the side of the radical, although only a little way above the conical apex, the radical did not bend in the peculiar manner, which we are here considering squares of about the 1/120th of an inch Roman 1e about 112 Roman 2000 or oblong bits of nearly the same size were found to be the most convenient and effective. We employed at first ordinary thin card, such as visiting cards or bits of very thin glass and various other objects, but afterwards sandpaper was chiefly employed, for it was almost as stiff as thin card, and the roughened surface favoured its adhesion. At first we generally used very thick gum water, and this of course under the circumstances never dried in the least. On the contrary, it sometimes seemed to absorb vapour, so that the bits of card became separated by a layer of fluid from the tip when there was no such absorption, and the card was not displaced. It acted well and caused the radical to bend to the opposite side. I should state that thick gum water by itself induces no action in most cases. The bits of card were touched with an extremely small quantity of a solution of shellac in spirits of wine which had been left to evaporate until it was thick. It then set hard in a few seconds and fixed the bits of card well. When small drops of the shellac were placed on the tips without any card, they set into hard little beads, and these acted like any other hard object, causing the radicals to bend to the opposite side. Even extremely minute beads of the shellac occasionally acted in a slight degree, as will hereafter be described, but that it was the cards which chiefly acted in our many trials was proved by coating one side of the tip with a little bit of gold beater's skin, which by itself hardly acts, and then fixing a bit of card to the skin with shellac, which never came into contact with the radical. Nevertheless, the radical bent away from the attached card in the ordinary manner. Some preliminary trials were made presently to be described, by which the proper temperature was determined, and then the following experiments were made. It should be premised that the beans were always fixed to the cork lids, for the convenience of manipulation with the edge, from which the radical and plumule protrudes outwards, and it must be remembered that owing to what we have called Sachs curvature, the radicals, instead of growing perpendicularly downwards, often bend somewhat, even as much as about 45 inwards, or under the suspended bean. Therefore, when a square of card was fixed to the apex, in front, the bowing induced by it coincided with Sachs curvature, and could be distinguished from it only by being more strongly pronounced, or by occurring more quickly. To avoid this source of doubt, the squares were fixed either behind, causing a curvature in direct opposition to that of Sachs, or more commonly, to the right or left sides. For the sake of brevity we will speak of the bits of card etc. as fixed in front or behind or laterally, as the chief curvature of the radical is at a little distance from the apex, and as the extreme terminal and basal portions are nearly straight, it is possible to estimate in a rough manner the amount of curvature by an angle, and when it is said that the radical became deflected at any angle from the perpendicular, this implies that the apex was turned upwards by so many degrees from the downward direction which it would naturally have followed, and to the side opposite to that to which the card was affixed, that the reader may have a clear idea of the kind of movement excited by the bits of attached card. We append here accurate sketches of 3 germinating beans, thus treated and selected out of several specimens, to show the gradations in the degrees of curvature. We will now give in detail a series of experiments, and afterwards a summary of the results. Fig 65, Vischer Faber. A radical beginning to bend from the attached little square of card, B bent at a rectangle, C bent into a circle or loop, with the tip beginning to bend downwards through the action of geotropism. In the first 12 trials, little squares or oblongs of sanded card, 1 Roman 2000 in length, and 1 or only 0 Roman 2000 in breadth, Roman 1e 71 of an inch in length, and 59 or 35 of an inch in breadth, were fixed with shellac to the tips of the radicals. In the subsequent trials, the little squares were only occasionally measured, but were of about the same size. 1. A young radical 4 Roman 2000 in length had a card fixed behind after 9h deflected in the plane, in which the bean is flattened 50 from the perpendicular, and from the card, and in opposition to Sachs curvature no change next morning 23h from the time of attachment. 2. Radical 5 Roman 2000 in length card, fixed behind after 9h deflected in the plane of the bean 20 from the perpendicular, and from the card, and in opposition to Sachs curvature after 23h no chain. 3. Radical 11 Roman 2000 in length card, fixed behind after 9h deflected in the plane of the bean 40 from the perpendicular, and from the card, and in opposition to Sachs' curvature the tip of the radical more curved than the upper part, but in the same plane after 23h, the extreme tip was slightly bent towards the card, the general curvature of the radical remaining the same. 4 radical 9 Roman 2000 long card fixed behind, and a little laterally after 9h, deflected in the plane of the bean, only about 7 or 8 from the perpendicular. And from the card in opposition to Sachs' curvature, there was in addition a slight lateral curvature directed partly from the card, after 23h no chain. 5 radical 8 Roman 2000 long card, affixed almost laterally, after 9h deflected 30 from the perpendicular in the plane of the bean, and in opposition to Sachs' curvature, also deflected in a plane at right angles to the above 120 from the perpendicular, after 23h no chain. 6 radical 9 Roman 2000 long card, affixed in front after 9h deflected in the plane of the bean about 40 from the vertical away from the card, and in the direction of Sachs' curvature. Here therefore, we have no evidence of the card being the cause of the deflection, except that a radical never moves spontaneously as far as we have seen as much as 40 in the course of 9h, after 23h no chain. 7 radical 7 Roman 2000 long card, affixed to the back after 9h the terminal part of the radical deflected in the plane of the bean 20 from the vertical away from the card, and in opposition to Sachs' curvature after 22h 30 Roman 1000, this part of the radical had become straight. 8 radical 12 Roman 2000 long card, affixed almost laterally after 9h deflected laterally in a plane at right angles to that of the bean between 40 and 50 from the vertical, and from the card in the plane of the bean itself, the deflection amounted to 8 or 9 from the vertical, and from the card in opposition to Sachs' curvature after 22h 30 Roman 1000, the extreme tip had become slightly curved towards the card. 9 card fixed laterally after 11h 30 Roman 1000 no, affect the radical being still almost vertical. 10 card fixed almost laterally after 11h 30 Roman 1000, deflected 90 from the vertical, and from the card in a plane intermediate between that of the bean itself and one at right angles to it, radical consequently partially deflected from Sachs' curvature. 11 tip of radical, protected with gold beater's skin, with a square of card of the usual dimensions, affixed with shellac, after 11h greatly deflected in the plane of the bean in the direction of Sachs' curvature, but to a much greater degree, and in less time than ever occurs spontaneously. 12 tip of radical, protected as in last case after 11h no effect, but after 24h 40 Roman 1000 radical, clearly deflected from the card. This slow action was probably due to a portion of the gold beater's skin having curled round and lightly touched the opposite side of the tip, and thus irritated it. 13 a radical of considerable length had a small square of card, fixed with shellac to its apex, laterally, after only 7h 15 Roman 1000 a length of 4 of an inch from the apex measured along the middle, was considerably curved from the side bearing the card. 14 case like the last in all respects, except that a length of only 25 of an inch of the radical was thus deflected. 15 a small square of card, fixed with shellac to the apex of a young radical, after 9h 15 Roman 1000, deflected through 90 from the perpendicular, and from the card after 24h deflection much decreased, and after an additional day reduced to 23 from the perpendicular. 16 square of card, fixed with shellac behind the apex of a radical which from its position having been changed during growth, had become very crooked, but the terminal portion was straight, and this became deflected to about 45 from the perpendicular, and from the card in opposition to Sachs' curvature. 17 square of card affixed with shellac after 8h radical, curved at right angles from the perpendicular, and from the card after 15 additional hours curvature much decreased. 18 square of card affixed with shellac after 8h no effect, after 23h 3 Roman 1000, from time of affixing radical much, curved from the square. 19 square of card, affixed with shellac after 24h no effect, but the radical had not grown well, and seemed sickly. 20 square of card affixed with shellac after 24h no effect. 22 squares of card affixed with shellac, after 24h radicals of both curved at about 45 from the perpendicular, and from the cards. 23 square of card fixed with shellac to young radical after 9h, very slightly curved from the card, after 24H tip curved towards card, refixed new square laterally after 9H distinctly curved from the card, and after 24H curved at right angles from the perpendicular, and from the card. 24 A rather large oblong piece of card fixed with shellac to apex after 24H no effect, but the card was found not to be touching the apex. A small square was now refixed with shellac after 16H slight deflection from the perpendicular, and from the card after an additional day, the radical became almost straight. 25 Square of card, fixed laterally to apex of young radical, after 9H deflection from the perpendicular considerable, after 24H deflection reduced refixed a fresh square with shellac, after 24H deflection about 40 from the perpendicular, and from the card. 26 A very small square of card, fixed with shellac to apex of young radical, after 9H the deflection from the perpendicular, and from the card amounted to nearly a right angle, after 24H deflection much reduced, after an additional 24H radical almost straight. 27 Square of card fixed with shellac to apex of young radical, after 9H deflection from the card, and from the perpendicular, a right angle next morning quite straight, refixed a square laterally with shellac, after 9H, a little deflection, which after 24H increased to nearly 20 from the perpendicular, and from the card. 28 Square of card fixed with shellac after 9H some deflection next morning, the card dropped off refixed it with shellac it again became loose, and was refixed, and now on the third trial the radical was deflected, after 14H at right angles from the card. 29 A small square of card was first fixed with thick gumwater to the apex, it produced a slight effect, but soon fell off. A similar square was now affixed laterally with shellac after 9H, the radical was deflected nearly 45 from the perpendicular, and from the card after 36 additional hours angle of deflection, reduced to about 30. 30 A very small piece less than 1/120th of an inch square of thin tinfoil, fixed with shellac to the apex of a young radical, after 24H no effect tinfoil removed, and a small square of sanded card, fixed with shellac, after 9H deflection at nearly right angles from the perpendicular, and from the card next morning deflection, reduced to about 40 from the perpendicular. 31 A splinter of thin glass gum to apex after 9H no effect, but it was then found not to be touching the apex of the radical next morning. A square of card was fixed with shellac to it, and after 9H radical greatly deflected from the card. After 2 additional days, the deflection had decreased, and was only 35 from the perpendicular. 32 Small square of sanded card attached with thick gumwater laterally to the apex of a long straight radical, after 9H greatly deflected from the perpendicular, and from the card curvature extended for a length of 22 of an inch from the apex, after 3 additional hours terminal portion, deflected at right angles from the perpendicular next morning, the curved portion was 36 in length. 33 Square of card gum to apex, after 15H deflected at nearly 90 from the perpendicular, and from the card. 34 Small oblong of sanded card gum to apex, after 15H deflected 90 from the perpendicular, and from the card. In the course of the 3 following days, the terminal portion became much contorted and ultimately coiled into a helix. 35 Square of card gum to apex after 9H deflected from card, after 24H from time of attachment, greatly deflected obliquely, and partly in opposition to Sachs curvature. 36 Small piece of card, rather less than 1/120th of an inch square gum to apex in 9H considerably deflected from card, and in opposition to Sachs curvature after 24H greatly deflected in the same direction. After an additional day, the extreme tip was curved towards the card. 37 Square of card gum to apex in front, caused after 8H 30 Roman 1000 hardly, any effect refixed fresh square laterally, after 15H deflected almost 90 from the perpendicular, and from the card after 2 additional days deflection much reduced. 38 Square of card gum to apex after 9H much deflection, which after 24H from time of fixing, increased to nearly 90, after an additional day terminal portion was curled into a loop, and on the following day into a helix. 39 Small oblong piece of card, gum to apex nearly in front, but a little to one side in 9H slightly deflected in the direction of Sachs curvature, but rather obliquely and to side opposite to card next day more curved in the same direction, and after 2 additional days coiled into a ring. 40 Square of card gum to apex after 9H slightly curved from card, next morning, radical straight and apex had grown beyond the card, refixed another square laterally with shellac in 9H deflected laterally, but also in the direction of Sachs' curvature. After 2 additional days, curvature considerably increased in the same direction. 41 little square of tinfoil fixed with gum to one side of apex of a young and short radical, after 15H no effect, but tinfoil had become displaced. A little square of card was now gummed to one side of apex, which after 8H 40 Roman 1000 was slightly deflected in 24H from the time of attachment, deflected at 90 from the perpendicular, and from the card after 9 additional hours became hooked with the apex pointing to the zenith in 3 days from the time of attachment. The terminal portion of the radical formed a ring or circle. 42 A little square of thick letter paper gummed to the apex of a radical, which after 9H was deflected from it. In 24H from time when the paper was affixed, the deflection much increased, and after 2 additional days it amounted to 50 from the perpendicular and from the paper. 43 A narrow chip of a quill was fixed with shellac to the apex of a radical, after 9H no effect, after 24H moderate deflection, but now the quill had ceased to touch the apex removed quill, and gummed a little square of card to apex, which after 8H caused slight deflection on the 4th day. From the first attachment of any object, the extreme tip was curved towards the card. 44 A rather long and narrow splinter of extremely thin glass fixed with shellac to apex, it caused in 9H slight deflection, which disappeared in 24H. The splinter was then found not touching the apex. It was twice refixed, with nearly similar results, that is, it caused slight deflection, which soon disappeared on the 4th day. From the time of first attachment, the tip was bent towards the splinter. From these experiments, it is clear that the apex of the radical of the bean is sensitive to contact, and that it causes the upper part to bend away from the touching object. But before giving a summary of the results, it will be convenient briefly to give a few other observations. Bits of very thin glass and little squares of common card were affixed with thick gum water to the tips of the radicals of 7 beans as a preliminary trial. 6 of these were plainly acted on, and in 2 cases the radicals became coiled up into complete loops. 1 radical was curved into a semicircle in so short a period as 6H 10 Roman 1000. The 7th radical, which was not affected, was apparently sickly, as it became brown on the following day, so that it formed no real exception. Some of these trials were made in the early spring during cold weather in a sitting room, and others in a greenhouse, but the temperature was not recorded. These 6 striking cases almost convinced us that the apex was sensitive, but of course we determined to make many more trials, as we had noticed that the radicals grew much more quickly when subjected to considerable heat, and as we imagined that heat would increase their sensitiveness. Vessels with germinating beans suspended in damp air were placed on a chimneypiece, where they were subjected during the greater part of the day to a temperature of between 69 and 72 F. Some, however, were placed in the hothouse, where the temperature was rather higher. Above 2 dozen beans were thus tried, and when a square of glass or card did not act, it was removed, and a fresh one affixed, this being often done thrice to the same radical. Therefore, between 5 and 6 dozen trials were altogether made, but there was moderately distinct deflection from the perpendicular, and from the attached object, in only 1 radical out of this large number of cases. In 5 other cases, there was very slight and doubtful deflection. We were astonished at this result, and concluded that we had made some inexplicable mistake in the first 6 experiments, but before finally relinquishing the subject we resolved to make one other trial, for it occurred to us that sensitiveness is easily affected by external conditions, and that radicals growing naturally in the earth in the early spring would not be subjected to a temperature nearly so high as 70 F. We therefore allowed the radicals of 12 beans to grow at a temperature of between 55 and 60 F. The result was that in every one of these cases included in the above described experiments, the radical was deflected in the course of a few hours from the attached object. All the above recorded successful trials, and some others presently to be given, were made in a sitting room at the temperatures just specified. It therefore appears that a temperature of about, or rather above 70 F destroys the sensitiveness of the radicals, either directly or indirectly, through abnormally accelerated growth. And this curious fact probably explains why Sachs, who expressly states that his beans were kept at a high temperature, failed to detect the sensitiveness of the apex of the radical. But other causes interfere with this sensibility. 18 radicals were tried with little squares of sanded card, some affixed with shellac, and some with gum water during the few last days of 1878, and few first days of the next year. They were kept in a room at the proper temperature during the day but were probably too cold at night. As there was a hard frost at the time, the radicals looked healthy, but grew very slowly. The result was that only 6 out of the 18 were deflected from the attached cards, and this only to a slight degree, and at a very slow rate. These radicals therefore presented a striking contrast with the 44 above described on March 6th and 7th, when the temperature of the room varied between 53 and 59 F. 11 germinating beans were tried in the same manner, and now every one of the radicals became curved away from the cards, though one was only slightly deflected. Some horticulturists believe that certain kinds of seeds will not germinate properly in the middle of the winter, although kept at a right temperature. If there really is any proper period for the germination of the bean, the feeble degree of sensibility of the radicals may have resulted from the trial having been made in the middle of the winter, and not simply from the nights being too cold. Lastly, the radicals of 4 beans, which from some innate cause germinated later than all the others of the same lot, and which grew slowly though appearing healthy, were similarly tried, and even after 24H they were hardly at all deflected from the attached cards. We may therefore infer that any cause which renders the growth of the radicals either slower or more rapid than the normal rate lessens, or annuls the sensibility of their tips to contact. It deserves particular attention that when the attached objects failed to act, there was no bending of any kind. Excepting Sachs' curvature, the force of our evidence would have been greatly weakened, if occasionally, though rarely, the radicals had become curved in any direction, independently of the attached objects in the foregoing numbered paragraphs. However, it may be observed that the extreme tip sometimes becomes, after a considerable interval of time, abruptly curved towards the bit of card. But this is a totally distinct phenomenon, as will presently be explained. A summary of the results of the foregoing experiments on the radicals of Vischer Faber: altogether little squares, about 1/120th of an inch, generally of sanded paper, as stiff as thin card, between 15 and 20 Roman 2000, in thickness, sometimes of ordinary card, or little fragments of very thin glass, etc., were affixed at different times to one side of the conical tips of 55 radicals. The 11 last mentioned cases, but not the preliminary ones, are here included. The squares, etc., were most commonly affixed with shellac, but in 19 cases with thick gumwater. When the latter was used, the squares were sometimes found, as previously stated, to be separated from the apex by a layer of thick fluid, so that there was no contact, and consequently no bending of the radical, and such few cases were not recorded. But in every instance in which shellac was employed, unless the square fell off very soon, the result was recorded. In several instances when the squares became displaced so as to stand parallel to the radical, or were separated by fluid from the apex, or soon fell off, fresh squares were attached, and these cases described under the numbered paragraphs are here included. Out of 55 radicals experimented on under the proper temperature, 52 became bent generally to a considerable extent from the perpendicular, and away from the side to which the object was attached. Of the 3 failures, 1 can be accounted for, as the radical became sickly on the following day, and a second was observed only during 11H 30 Roman 1000, as in several cases the terminal growing part of the radical continued for some time to bend from the attached object. It formed itself into a hook with the apex pointing to the zenith, or even into a ring, and occasionally into a spire or helix. It is remarkable that these latter cases occurred more frequently when objects were attached with thick gumwater, which never became dry, than when shellac was employed. The curvature was often well marked in from 7H to 11H, and in one instance, a semicircle was formed in 6H 10M from the time of attachment. But in order to see the phenomenon as well displayed as in the above described cases, it is indispensable that the bits of card, etc., should be made to adhere closely to one side of the conical apex, that healthy radicals should be selected, and kept at not too high or too low a temperature, and apparently that the trials should not be made in the middle of the winter. In 10 instances, radicals which had curved away from a square of card, or other object attached to their tips, straightened themselves to a certain extent, or even completely, in the course of from 1 to 2 days from the time of attachment. This was more especially apt to occur when the curvature was slight. But in one instance, No. 27, a radical which in 9H had been deflected about 90 from the perpendicular became quite straight in 24H, from the period of attachment. With No. 26, the radical was almost straight in 48H. We at first attributed the straightening process to the radicals becoming accustomed to a slight stimulus, in the same manner as a tendril or sensitive petiole becomes accustomed to a very light loop of thread. and unbends itself though the loop remains still suspended. But Sachs states too that radicals of the bean placed horizontally in damp air, after curving downwards through geotropism, straighten themselves a little by growth along their lower, or concave sides. Why this should occur is not clear, but perhaps it likewise occurred in the above 10 cases. There is another occasional movement, which must not be passed over the tip of the radical, for a length of from 2 to 3 Roman 2000 was found in 6 instances after an interval of about 24 or more hours, bent towards the bit of still attached card that is in a direction exactly opposite to the previously induced curvature of the whole growing part, for a length of from 7 to 8 Roman 2000. This occurred chiefly when the first curvature was small, and when an object had been affixed more than once to the apex of the same radical. The attachment of a bit of card by shellac to one side of the tender apex may sometimes mechanically prevent its growth, or the application of thick gumwater more than once to the same side may injure it, and then checked growth on this side, with continued growth on the opposite and unaffected side, would account for the reversed curvature of the apex. Various trials were made for ascertaining as far as we could the nature and degree of irritation to which the apex must be subjected, in order that the terminal growing part should bend away, as if to avoid the cause of irritation. We have seen in the numbered experiments that a little square of rather thick letter paper gummed to the apex induced though slowly considerable deflection, judging from several cases in which various objects had been affixed with gum, and had soon become separated from the apex by a layer of fluid, as well as from some trials in which drops of thick gumwater alone had been applied. This fluid never causes bending. We have also seen in the numbered experiments that narrow splinters of quill and of very thin glass affixed with shellac caused only a slight degree of deflection, and this may perhaps have been due to the shellac itself. Little squares of goldbeater's skin, which is excessively thin, were damped, and thus made to adhere to one side of the tips of 2 radicals. One of these after 24H produced no effect, nor did the other in 8H, within which time squares of card usually act, but after 24H there was slight deflection. An oval bead, or rather cake of dried shellac, 1 Roman 2000 in length and 0 in breadth, caused a radical to become deflected at nearly right angles in the course of only 6H. But after 23H it had nearly straightened itself. A very small quantity of dissolved shellac was spread over a bit of card, and the tips of 9 radicals were touched laterally. With it only 2 of them became slightly deflected to the side opposite to that bearing the speck of dried shellac, and they afterwards straightened themselves. These specks were removed, and both together weighed less than 1/100th of a grain, so that a weight of rather less than 1/200th of a grain 0 mg sufficed to excite movement in 2 out of the 9 radicals here. Then we have apparently reached nearly the minimum weight which will act. A moderately thick bristle, which on measurement was found rather flattened, being 0 Roman 2000 in one diameter, and 0 Roman 2000 in the other, was cut into lengths of about 1/120th of an inch. These, after being touched with thick gumwater, were placed on the tips of 11 radicals. 3 of them were affected, one being deflected in 8H 15 Roman 1000 to an angle of about 90 from the perpendicular, a second to the same amount when looked at after 9H, but after 24H from the time of first attachment, the deflection had decreased to only 19. The third was only slightly deflected after 9H, and the bit of bristle was then found not touching the apex it was replaced, and after 15 additional hours, the deflection amounted to 26 from the perpendicular. The remaining 8 radicals were not at all acted on by the bits of bristle, so that we here appear to have nearly reached the minimum of size of an object which will act on the radical of the bean. But it is remarkable that when the bits of bristle did act, that they should have acted so quickly and efficiently. As the apex of a radical in penetrating the ground must be pressed on all sides, we wish to learn whether it could distinguish between harder or more resisting and softer substances. A square of the sanded paper, almost as stiff as card, and a square of extremely thin paper, too thin for writing on, of exactly the same size, about 1/120th of an inch, were fixed with shellac on opposite sides of the apices of 12 suspended radicals. The sanded card was between 0 and 0 Roman 2000, or between 0 and 0 of an inch, and the thin paper only 0 Roman 2000 or 0 of an inch in thickness. In 8 out of the 12 cases, there could be no doubt that the radical was deflected from the side to which the card-like paper was attached, and towards the opposite side bearing the very thin paper. This occurred in some instances in 9H, but in others not until 24H had elapsed. Moreover, some of the 4 failures can hardly be considered as really failures. Thus in one of them, in which the radical remained quite straight, the square of thin paper was found, when both were removed from the apex, to have been so thickly coated with shellac that it was almost as stiff as the card. In the second case, the radical was bent upwards into a semicircle, but the deflection was not directly from the side bearing the card, and this was explained by the two squares having become cemented laterally together, forming a sort of stiff gable, from which the radical was deflected. In the third case, the square of card had been fixed by mistake in front, and though there was deflection from it, this might have been due to Sachs' curvature. In the fourth case alone, no reason could be assigned why the radical had not been at all deflected. These experiments suffice to prove that the apex of the radical possesses the extraordinary power of discriminating between thin card and very thin paper, and is deflected from the side pressed by the more resisting or harder substance. Some trials were next made by irritating the tips without any object being left in contact with them. 9 radicals suspended over water had their tips rubbed each 6 times with a needle, with sufficient force to shake the whole bean. The temperature was favorable, viz., about 63 F. In 7 out of these cases, no effect whatever was produced. In the 8th case, the radical became slightly deflected from, and in the 9th case, slightly deflected towards the rubbed side, but these 2 latter opposed curvatures were probably accidental, as radicals do not always grow perfectly straight downwards. The tips of 2 other radicals were rubbed in the same manner for 15 seconds, with a little round twig, 2 others for 30 seconds and 2 others for 1 minute, but without any effect being produced. We may therefore conclude from these 15 trials that the radicals are not sensitive to temporary contact, but are acted on only by prolonged though very slight pressure. We then tried the effects of cutting off a very thin slice parallel to one of the sloping sides of the apex, as we thought that the wound would cause prolonged irritation, which might induce bending towards the opposite side. As in the case of an attached object, 2 preliminary trials were made. Firstly, slices were cut from the radicals of 6 beans, suspended in damp air, with a pair of scissors, which though sharp probably caused considerable crushing, and no curvature followed. Secondly, thin slices were cut with a razor obliquely off the tips of 3 radicals similarly suspended, and after 44H2 were found plainly bent from the sliced surface, and the third, the whole apex of which had been cut off obliquely by accident, was curled upwards over the bean, but it was not clearly ascertained whether the curvature had been at first directed from the cut surface. These results led us to pursue the experiment, and 18 radicals, which had grown vertically downwards in damp air, had one side of their conical tip sliced off with a razor. The tips were allowed just to enter the water in the jars, and they were exposed to a temperature 1416 Roman 1,005,761 F. The observations were made at different times. 3 were examined 12H after being sliced and were all slightly curved from the cut surface, and the curvature increased considerably. After an additional 12H8 were examined after 19H4, after 22H30 Roman 1003, after 25H. The final result was that out of the 18 radicals thus tried, 13 were plainly bent from the cut surface after the above intervals of time, and 1 other became so after an additional interval of 13H30 Roman 1000, so that only 4 out of the 18 radicals were not acted on. To these 18 cases, the previously mentioned ones should be added. It may therefore be concluded that a thin slice removed by a razor from one side of the conical apex of the radical causes irritation, like that from an attached object, and induces curvature from the injured surface. Lastly, dry caustic nitrate of silver was employed to irritate one side of the apex if one side of the apex, or of the whole terminal growing part of a radical, is by any means killed or badly injured, the other side continues to grow, and this causes the part to bend over towards the injured side. 3. But in the following experiments we endeavored generally with success to irritate the tips on one side without badly injuring them. This was effected by first drying the tip as far as possible with blotting paper, though it still remained somewhat damp, and then touching it once with quite dry caustic. 17 radicals were thus treated, and were suspended in moist air over water at a temperature of 58 F. They were examined after an interval of 21H or 24H. The tips of 2 were found blackened equally all round so that they could tell nothing, and were rejected. 15 being left of these 10 were curved from the side, which had been touched where there was a minute brown or blackish mark. 5 of these radicals, 3 of which were already slightly deflected, were allowed to enter the water in the jar, and were re-examined after an additional interval of 27H Roman 1E in 48H after the application of the caustic, and now 4 of them had become hooked, being bent from the discolored side, with their points directed to the zenith. The 5th remained unaffected, and straight, thus 11 radicals out of the 15 were acted on, but the curvature of the 4 just described was so plain that they alone would have sufficed to show that the radicals of the bean bend away from that side of the apex, which has been slightly irritated by caustic. The power of an irritant on the apex of the radical of the bean, compared with that of geotropism, we know that when a little square of card or other object is fixed to one side of the tip of a vertically dependent radical, the growing part bends from it, often into a semicircle in opposition to geotropism, which force is conquered by the effect of the irritation from the attached object. Radicals were therefore extended horizontally, in damp air, kept at the proper low temperature for full sensitiveness, and squares of card were affixed with shellac on the lower sides of their tips, so that if the squares acted, the terminal growing part would curve upwards. Firstly, 8 beans were so placed that their short young horizontally extended radicals would be simultaneously acted on both by geotropism and by Sachs curvature if the latter came into play, and they all 8 became bowed downwards to the centre of the earth in 20h, excepting one which was only slightly acted on. 2 of them were a little bowed downwards in only 5h. Therefore the cards affixed to the lower sides of their tips seemed to produce no effect, and geotropism easily conquered the effects of the irritation, thus caused secondly 5 oldish radicals 112" in length, and therefore less sensitive than the above-mentioned young ones, were similarly placed and similarly treated. From what has been seen on many other occasions, it may be safely inferred that if they had been suspended vertically, they would have bent away from the cards, and if they had been extended horizontally, without cards attached to them, they would have quickly bent vertically downwards through geotropism. But the result was that 2 of these radicals were still horizontal, after 23h. 2 were curved only slightly, and the 5th as much as 40 beneath the horizon. Thirdly, 5 beans were fastened with their flat surfaces parallel to the cork lid, so that Sachs curvature would not tend to make the horizontally extended radicals turn either upwards or downwards, and little squares of card were affixed as before to the lower sides of their tips. The result was that all 5 radicals were bent down or towards the centre of the earth, after only 8h 20 Roman 1000 at the same time, and within the same jars, 3 radicals of the same age with squares affixed to one side were suspended vertically, and after 8h 20 Roman 1000 they were considerably deflected from the cards, and therefore curved upwards in opposition to geotropism. In these latter cases the irritation from the squares had overpowered geotropism, whilst in the former cases in which the radicals were extended horizontally, geotropism had overpowered the irritation. Thus within the same jars, some of the radicals were curving upwards and others downwards at the same time. These opposite movements, depending on whether the radicals, when the squares were first attached to them, projected vertically down or were extended horizontally. This difference in their behavior seems at first inexplicable, but can we believe be simply explained by the difference between the initial power of the 2 forces under the above circumstances, combined with the well-known principle of the after-effects of a stimulus. When a young and sensitive radical is extended horizontally, with a square attached to the lower side of the tip, geotropism acts on it at right angles, and as we have seen is then evidently more efficient than the irritation from the square, and the power of geotropism will be strengthened at each successive period by its previous action, that is, by its after-effects. On the other hand, when a square is affixed to a vertically dependent radical, and the apex begins to curve upwards, this movement will be opposed by geotropism acting only at a very oblique angle, and the irritation from the card will be strengthened by its previous action. We may therefore conclude that the initial power of an irritant on the apex of the radical of the bean is less than that of geotropism when acting at right angles, but greater than that of geotropism when acting obliquely on it. Sensitiveness of the tips of the secondary radicals of the bean to contact. All the previous observations relate to the main or primary radical. Some beans suspended to cork lids with their radicals dipping into water had developed secondary or lateral radicals, which were afterwards kept in very damp air at the proper low temperature for full sensitiveness. They projected as usual almost horizontally, with only a slight downward curvature, and retained this position during several days. Sachs has shown that these secondary roots are acted on in a peculiar manner by geotropism, so that if displaced they reassume their former subhorizontal position and do not bend vertically downwards, like the primary radical. Minute squares of the stiff sanded paper were affixed by means of shellac, but in some instances with thick gumwater to the tips of 39 secondary radicals of different ages. Generally, the uppermost ones, most of the squares were fixed to the lower sides of the apex, so that, if they acted, the radical would bend upwards, but some were fixed laterally, and a few on the upper side. Owing to the extreme tenuity of these radicals, it was very difficult to attach the square to the actual apex. Whether owing to this or some other circumstance, only 9 of the squares induced any curvature. The curvature amounted in some cases to about 45 above the horizon, in others to 90. And then the tip pointed to the zenith. In one instance, a distinct upward curvature was observed in 8H15 Roman 1000, but usually not until 24H had elapsed. Although only 9 out of 39 radicals were affected, yet the curvature was so distinct in several of them that there could be no doubt that the tip is sensitive to slight contact, and that the growing part bends away from the touching object. It is possible that some secondary radicals are more sensitive than others for sacs, has proved. 5. The interesting fact that each individual secondary radical possesses its own peculiar constitution. Sensitiveness to contact of the primary radical, a little above the apex in the bean Vischer Faber and P. Pisum. Sativum, the sensitiveness of the apex of the radical in the previously described cases, and the consequent curvature of the upper part from the touching object or other source of irritation, is the more remarkable because Sac 6 has shown that pressure at the distance of a few millimeters above the apex causes the radical to bend like a tendril towards the touching object by fixing pins, so that they pressed against the radicals of beans suspended vertically in damp air. We saw this kind of curvature, but rubbing the part with a twig or needle for a few minutes produced no effect. Haberlant remarks 7. That these radicals in breaking through the seed coats often rub and press against the ruptured edges, and consequently bend round them, as little squares of the card-like paper, affixed with shellac to the tips, were highly efficient in causing the radicals to bend away from them. Similar pieces of about 1/20th inch square, or rather less, were attached in the same manner to one side of the radical, at a distance of 3 or 4 Roman 2000 above the apex. In our first trial on 15 radicals, no effect was produced. In a second trial, on the same number, 3 became abruptly curved, but only one strongly towards the card. Within 24H from these cases, we may infer that the pressure from a bit of card affixed with shellac to one side above the apex is hardly a sufficient irritant, but that it occasionally causes the radical to bend like a tendril towards this side. We next tried the effect of rubbing several radicals at a distance of 4 Roman 2000 from the apex for a few seconds with lunar caustic nitrate of silver, and although the radicals had been wiped dry and the stick of caustic was dry, yet the part rubbed was much injured, and a slight permanent depression was left. In such cases, the opposite side continues to grow, and the radical necessarily becomes bent towards the injured side. But when a 0.4 Roman 2000 from the apex was momentarily touched with dry caustic, it was only faintly discolored, and no permanent injury was caused. This was shown by several radicals thus treated straightening themselves after 1 or 2 days, yet at first they became curved towards the touched side, as if they had been there subjected to slight continued pressure. These cases deserve notice, because when one side of the apex was just touched with caustic, the radical, as we have seen, curved itself in an opposite direction, that is, away from the touched side. The radical of the common P at a point a little above the apex is rather more sensitive to continued pressure than that of the bean, and bends towards the pressed side. 8. We experimented on a variety Yorkshire hero, which has a much wrinkled, tough skin too large for the included cotyledons, so that out of 30 peas which had been soaked for 24H and allowed to germinate on damp sand, the radicals of 3 were unable to escape, and were crumpled up in a strange manner within the skin. 4 other radicals were abruptly bent round the edges of the ruptured skin, against which they had pressed. Such abnormalities would probably never or very rarely occur with forms developed in a state of nature, and subjected to natural selection. One of the 4 radicals just mentioned, in doubling backwards, came into contact with the pin by which the P was fixed to the cork lid, and now it bent at right angles round the pin, in a direction quite different from that of the first curvature due to contact with the ruptured skin, and it thus afforded a good illustration of the tendril-like sensitiveness of the radical a little above the apex. Little squares of the card-like paper were next affixed to radicals of the P at 4 Roman 2000 above the apex in the same manner, as with the bean. 28 radicals, suspended vertically over water, were thus treated on different occasions, and 13 of them became curved towards the cards, the greatest degree of curvature amounted to 62 from the perpendicular, but so large an angle was only once formed on one occasion. A slight curvature was perceptible after 5h45 Roman 1000, and it was generally well marked after 14h. There can therefore be no doubt that with the P irritation from a bit of card attached to one side of the radical above the apex suffices to induce curvature. Squares of card were attached to one side of the tips of 11 radicals within the same jars in which the above trials were made, and 5 of them became plainly, and one slightly curved away from this side. Other analogous cases will be immediately described. The fact is here mentioned because it was a striking spectacle showing the difference in the sensitiveness of the radical in different parts to behold in the same jar. One set of radicals curved away from the squares on their tips, and another set curved towards the squares, attached a little higher up. Moreover, the kind of curvature in the two cases is different. The squares attached above the apex cause the radical to bend abruptly, the part above and beneath remaining nearly straight, so that here there is little or no transmitted effect. On the other hand, the squares attached to the apex affect the radical for a length of from about 4 to even 8 Roman 2000, inducing in most cases a symmetrical curvature, so that here some influence is transmitted from the apex for this distance along the radical. Pisum sativum var Yorkshire hero. Sensitiveness of the apex of the radical. Little squares of the same card-like paper were affixed April 24th with shellac to one side of the apex of 10 vertically suspended radicals. The temperature of the water in the bottom of the jars was 60-61 F. Most of these radicals were acted on in 8h30 Roman 1000, and 8 of them became in the course of 24h conspicuously, and the remaining 2 slightly deflected from the perpendicular and from the side bearing the attached squares. Thus all were acted on, but it will suffice to describe 2 conspicuous cases. In one, the terminal portion of the radical was bent at right angles, a fig 66 after 24h, and in the other B, it had by this time become hooked with the apex pointing to the zenith. The 2 bits of card here used were 7" in length and 4" in breadth. 2 other radicals, which after 8h30 Roman 1000 were moderately deflected, became straight again. After 24h another trial was made in the same manner with 15 radicals, but from circumstances not worth explaining, they were only once and briefly examined after the short interval of 5h30 Roman 1000, and we merely record in our notes, almost all bent slightly from the perpendicular and away from the squares, the deflection amounting in 1 or 2 instances to nearly a rectangle. These 2 sets of cases, especially the first one, proved that the apex of the radical is sensitive to slight contact, and that the upper part bends from the touching object. Nevertheless, on June 1st and 4th, 8 other radicals were tried in the same manner at a temperature of 58-60 F, and after 24h only 1 was decidedly bent from the card, 4 slightly too doubtfully, and 1 not in the least. The amount of curvature was unaccountably small, but all the radicals which were at all bent were bent away from the cards. Fig 66. Pisum sativum deflection, produced within 24 hours in the growth of vertically dependent radicals by little squares of card, affixed with shellac to one side of apex, a bent at right angles be hooked. We now tried the effects of widely different temperatures on the sensitiveness of these radicals, with squares of card attached to their tips. Firstly, 13 Ps, most of them having very short and young radicals, were placed in an icebox, in which the temperature rose during 3 days from 44 to 47 F. They grew slowly, but 10 out of the 13 became in the course of the 3 days very slightly curved from the squares. The other 3 were not affected, so that this temperature was too low for any high degree of sensitiveness, or for much movement. Jars with 13 other radicals were next placed on a chimneypiece, where they were subjected to a temperature of between 68 and 72 F, and after 24h4 were conspicuously curved from the cards 2 slightly, and 7 not at all, so that this temperature was rather too high. Lastly, 12 radicals were subjected to a temperature varying between 72 and 85 F, and none of them were in the least affected by the squares. The above several trials, especially the first recorded one, indicate that the most favorable temperature for the sensitiveness of the radical of the P is about 60 F. The tips of 6 vertically dependent radicals were touched once with dry caustic in the manner described under Vischer Faber. After 24h 4 of them were bent from the side bearing a minute black mark, and the curvature increased in one case after 38h, and in another case after 48h, until the terminal part projected almost horizontally. The 2 remaining radicals were not affected. With radicals of the bean when extended horizontally in damp air geotropism, always conquered the effects of the irritation caused by squares of card attached to the lower sides of their tips. A similar experiment was tried on 13 radicals of the pea, the squares being attached with shellac and the temperature between 58–60 F. The result was somewhat different, for these radicals are either less strongly acted on by geotropism, or what is more probable, are more sensitive to contact. After a time, geotropism always prevailed, but its action was often delayed, and in 3 instances there was a most curious struggle between geotropism and the irritation caused by the cards. 4 of the 13 radicals were a little curved downwards within 6 or 8 H, always reckoning from the time when the squares were first attached, and after 23 H 3 of them pointed vertically downwards, and the 4th at an angle of 45 beneath the horizon. These 4 radicals, therefore, did not seem to have been at all affected by the attached squares. 4 others were not acted on by geotropism within the first 6 or 8 H, but after 23 H were much bowed down. 2 others remained almost horizontal for 23 H, but afterwards were acted on, so that in these latter 6 cases the action of geotropism was much delayed. The 11th radical was slightly curved down after 8 H, but when looked at again after 23 H, the terminal portion was curved upwards. If it had been longer observed, the tip no doubt would have been found again curved down, and it would have formed a loop, as in the following case. The 12th radical after 6 H was slightly curved downwards, but when looked at again after 21 H, this curvature had disappeared, and the apex pointed upwards after 30 H. The radical formed a hook as shown at a Fig 67, which hook after 45 H was converted into a loop. The 13th radical after 6 H was slightly curved downwards, but within 21 H had curved considerably up and then down again, at an angle of 45 beneath the horizon, afterwards becoming perpendicular. In these 3 last cases, geotropism and the irritation caused by the attached squares alternately prevailed, in a highly remarkable manner, geotropism being ultimately victorious. Fig 67 Pisum sativum, a radical extended horizontally in damp air, with a little square of card affixed to the lower side of its tip, causing it to bend upwards in opposition to geotropism. The deflection of the radical after 21 hours is shown at A, and of the same radical after 45 hours at B, now forming a loop. Similar experiments were not always quite so successful as in the above cases. Thus 6 radicals horizontally extended with attached squares were tried on June 8 at a proper temperature, and after 7H30 Roman 1000 none were in the least curved upwards, and none were distinctly geotropic, whereas of 6 radicals without any attached squares, which served as standards of comparison or controls, 3 became slightly, and 3 almost, rectangularly geotropic within the 7H30 Roman 1000, but after 23 H the 2 lots were equally geotropic. On July 10, another trial was made with 6 horizontally extended radicals, with squares attached in the same manner beneath their tips, and after 7H30 Roman 1004 were slightly geotropic. 1 remained horizontal, and 1 was curved upwards, in opposition to gravity or geotropism. This latter radical after 48 H formed a loop like that at B. Fig 67. An analogous trial was now made, but instead of attaching squares of card to the lower sides of the tips, these were touched with dry caustic. The details of the experiment will be given in the chapter on geotropism, and it will suffice here to say that 10 peas with radicals extended horizontally and not cauterized were laid on, and under damp friable peat, these which served as standards or controls, as well as 10 others which had been touched on the upper side with the caustic, all became strongly geotropic. In 24H9 radicals similarly placed had their tips touched on the lower side with the caustic, and after 24H3 were slightly geotropic. 2 remained horizontal, and 4 were bowed upwards in opposition to gravity, and to geotropism. This upward curvature was distinctly visible in 8H45M after the lower sides of the tips had been cauterized. Little squares of card were affixed with shellac on 2 occasions to the tips of 22 young and short secondary radicals, which had been emitted from the primary radical whilst growing in water, but were now suspended in damp air. Besides the difficulty of attaching the squares to such finely pointed objects as were these radicals, the temperature was too high, varying on the first occasion from 72 to 77 F, and on the second being almost steadily 78 F, and this probably lessened the sensitiveness of the tips. The result was that after an interval of 8H30 Roman 1006 of the 22 radicals were bowed upwards, one of them greatly in opposition to gravity, and 2 laterally, The remaining 14 were not affected considering the unfavorable circumstances. And bearing in mind the case of the bean, the evidence appears sufficient to show that the tips of the secondary radicals of the pea are sensitive to slight contact. Physalis multiflorus sensitiveness of the apex of the radical 59 radicals were tried with squares of various sizes of the same card-like paper, also with bits of thin glass and rough cinders, affixed with shellac to one side of the apex. Rather large drops of the dissolved shellac were also placed on them, and allowed to set into hard beads. The specimens were subjected to various temperatures between 60 and 72 F, more commonly at about the latter, but out of this considerable number of trials, only 5 radicals were plainly bent, and 8 others slightly or even doubtfully from the attached objects, the remaining 46 not being at all affected. It is therefore clear that the tips of the radicals of this physalis are much less sensitive to contact than are those of the bean or pea. We thought that they might be sensitive to harder pressure, but after several trials, we could not devise any method for pressing harder on one side of the apex than on the other without at the same time offering mechanical resistance to its growth. We therefore tried other irritants. The tips of 13 radicals dried with blotting paper were thrice touched, or just rubbed on one side with dry nitrate of silver. They were rubbed thrice, because we supposed from the foregoing trials that the tips were not highly sensitive. After 24H the tips were found greatly blackened. 6 were blackened equally all round, so that no curvature to any one side could be expected. 6 were much blackened on one side for a length of about 1/110th of an inch, and this length became curved at right angles towards the blackened surface, the curvature afterwards increasing in several instances, until little hooks were formed. It was manifest that the blackened side was so much injured that it could not grow, whilst the opposite side continued to grow. One alone, out of these 13 radicals, became curved from the blackened side, the curvature extending for some little distance above the apex. After the experience thus gained, the tips of 6 almost dry radicals were once touched with the dry caustic on one side, and after an interval of 10^1000 were allowed to enter water, which was kept at a temperature of 65-67 F. The result was that after an interval of 8H, a minute blackish speck could just be distinguished on one side of the apex of 5 of these radicals, all of which became curved towards the opposite side in 2 cases, at about an angle of 45, in 2 other cases, at nearly a rectangle, and in the 5th case, at above a rectangle, so that the apex was a little hooked in this latter case. The black mark was rather larger than in the others. After 24H from the application of the caustic, the curvature of 3 of these radicals, including the hooked one, had diminished. In the 4th it remained the same, and in the 5th it had increased, the tip being now hooked. It has been said that after 8H black specks could be seen on one side of the apex of 5 of the 6 radicals. On the 6th, the speck, which was extremely minute, was on the actual apex, and therefore central, and this radical alone did not become curved. It was therefore again touched on one side with caustic, and after 15H 30^1000 was found curved from the perpendicular, and from the blackened side at an angle of 34, which increased in 9 additional hours to 54. It is therefore certain that the apex of the radical of this physalis is extremely sensitive to caustic, more so than that of the bean, though the latter is far more sensitive to pressure. In the experiments just given, the curvature from the slightly cauterized side of the tip extended along the radical for a length of nearly 10^2000, whereas, in the first set of experiments, when the tips of several were greatly blackened and injured on one side, so that their growth was arrested, a length of less than 3^2000 became curved towards the much blackened side, owing to the continued growth of the opposite side. This difference in the results is interesting, for it shows that too strong an irritant does not induce any transmitted effect, and does not cause the adjoining upper and growing part of the radical to bend. We have analogous cases with Drosera, for a strong solution of carbonate of ammonia, when absorbed by the glands or too great heat suddenly applied to them or crushing them, does not cause the basal part of the tentacles to bend, whilst a weak solution of the carbonate or a moderate heat or slight pressure always induced such bending. Similar results were observed with Dionea and Pinguicula. The effect of cutting off with a razor a thin slice from one side of the conical apex of 14 young and short radicals was next tried. 6 of them, after being operated on, were suspended in damp air. The tips of the other 8, similarly suspended, were allowed to enter water at a temperature of about 65 F. It was recorded in each case which side of the apex had been sliced off, and when they were afterwards examined, the direction of the curvature was noted before the record was consulted of the 6 radicals in damp air 3, had their tips curved after an interval of 10h15 Roman 1000 directly away from the sliced surface, whilst the other 3 were not affected, and remained straight nevertheless. One of them, after 13 additional hours, became slightly curved from the sliced surface of the 8 radicals, with their tips immersed in water. 7 were plainly curved away from the sliced surfaces after 10h15 Roman 1000, and with respect to the 8th, which remained quite straight too thick, a slice had been accidentally removed, so that it hardly formed a real exception to the general result. When the 7 radicals were looked at again, after an interval of 23h from the time of slicing, 2 had become distorted. 4 were deflected at an angle of about 70 from the perpendicular and from the cut surface, and 1 was deflected at nearly 90, so that it projected almost horizontally, but with the extreme tip now beginning to bend downwards through the action of geotropism. It is therefore manifest that a thin slice cut off one side of the conical apex causes the upper growing part of the radical of this physalis to bend through the transmitted effects of the irritation away from the sliced surface. Tropiolum majus sensitiveness of the apex of the radical to contact little squares of card were attached with shellac to one side of the tips of 19 radicals, some of which were subjected to 78F, and others to a much lower temperature. Only 3 became plainly curved from the squares, 5 slightly, 4 doubtfully, and 7 not at all. These seeds were, as we believed, old, so we procured a fresh lot, and now the results were widely different. 23 were tried in the same manner. 5 of the squares produced no effect, but 3 of these cases were no real exceptions, for in 2 of them the squares had slipped and were parallel to the apex, and in the 3rd the shellac was in excess and had spread equally all round the apex. 1 radical was deflected only slightly from the perpendicular, and from the card, whilst 17 were plainly deflected. The angles, in several of these latter cases, varied between 40 and 65 from the perpendicular, and in 2 of them it amounted, after 15h or 16h, to about 90. In 1 instance, a loop was nearly completed, in 16h. There can therefore be no doubt that the apex is highly sensitive to slight contact, and that the upper part of the radical bends away from the touching object. Gossypium herbaceum sensitiveness of the apex of the radicals were experimented on in the same manner as before, but they proved ill-fitted for our purpose, as they soon became unhealthy when suspended in damp air of 38 radicals, thus suspended at temperatures varying from 66 to 69F, with squares of card attached to their tips. 9 were plainly and 7 slightly or even doubtfully deflected from the squares, and from the perpendicular, 22 not being affected. We thought that perhaps the above temperature was not high enough, so 19 radicals, with attached squares likewise suspended in damp air, were subjected to a temperature of from 74 to 79F, but not one of them was acted on, and they soon became unhealthy. Lastly, 19 radicals were suspended in water at a temperature from 70 to 75F, with bits of glass or squares of the card attached to their tips by means of Canada balsam or asphalt, which adhered rather better than shellac beneath the water. The radicals did not keep healthy for long. The result was that 6 were plainly and 2 doubtfully deflected from the attached objects, and the perpendicular 11 not being affected. The evidence, consequently, is hardly conclusive, though from the 2 sets of cases tried under a moderate temperature, it is probable that the radicals are sensitive to contact, and would be more so under favourable conditions. 15 radicals which had germinated in friable peat were suspended vertically over water. 7 of them served as controls, and they remained quite straight during 24h. The tips of the other 8 radicals were just touched with dry caustic on one side. After only 5h10 Roman 1005 of them were slightly curved from the perpendicular, and from the side bearing the little blackish marks after 8h40 Roman 1004 out of these 5 were deflected at angles between 15 and 65 from the perpendicular. On the other hand, 1, which had been slightly curved after 5h10 Roman 1000 now became straight after 24h. The curvature in 2 cases had considerably increased also in 4 other cases, but these latter radicals had now become so contorted, some being turned upwards, that it could no longer be ascertained whether they were still curved from the cauterized side. The control specimens exhibited no such irregular growth, and the 2 sets presented a striking contrast. Out of the 8 radicals which had been touched with caustic, 2 alone were not affected, and the marks left on their tips by the caustic were extremely minute. These marks in all cases were oval or elongated. They were measured in 3 instances, and found to be of nearly the same size, viz. 23 of a Roman 2000 in length. Bearing this fact in mind, it should be observed that the length of the curved part of the radical, which had become deflected from the cauterized side in the course of 8H40 Roman 1000, was found to be in 3 cases 6-7 and 9 Roman 2000 cucurbita ovifera sensitiveness of the apex of the radical. The tips proved ill-fitted for the attachment of cards, as they are extremely fine and flexible. Moreover, owing to the hypocartels being soon developed and becoming arched, the whole radical is quickly displaced, and confusion is thus caused. A large number of trials were made, but without any definite result, excepting on 2 occasions, when out of 23 radicals 10 were deflected from the attached squares of card and 13 were not acted on. Rather large squares, though difficult to affix, seemed more efficient than very small ones. We were much more successful with caustic, but in our first trial 15 radicals were too much cauterized, and only 2 became curved from the blackened side, the others being either killed on one side or blackened, equally all round. In our next trial, the dried tips of 11 radicals were touched momentarily with dry caustic, and after a few minutes were immersed in water. The elongated marks thus caused were never black, only brown, and about 12 Roman 2000 in length, or even less in 4H30 Roman 1000. After the cauterization, 6 of them were plainly curved from the side, with the brown mark 4 slightly, and 1 not at all. The latter proved unhealthy and never grew, and the marks on 2 of the 4 slightly curved radicals were excessively minute, 1 being distinguishable only with the aid of a lens. Of 10 control specimens tried in the same jars at the same time, not 1 was in the least curved in 8H40 Roman 1000. After the cauterization, 5 of the radicals out of the 10, the 1 unhealthy one being omitted, were deflected at about 90 and 3 at about 45 from the perpendicular, and from the side bearing the brown mark. After 24H all 10 radicals had increased immensely in length. In 5 of them, the curvature was nearly the same. In 2 it had increased, and in 3 it had decreased. The contrast presented by the 10 controls, after both the 8H40 Roman 1000 and the 24H intervals, was very great, for they had continued to grow vertically downwards, excepting 2 which from some unknown cause had become somewhat tortuous. In the chapter on geotropism, we shall see that 10 radicals of this plant were extended horizontally on and beneath damp friable peat, under which conditions they grow better and more naturally than in damp air, and their tips were slightly cauterized on the lower side. Brown marks about 12 Roman 2000 in length being thus caused. Uncauterized specimens, similarly placed, became much bent downwards through geotropism. In the course of 5 or 6 hours, after 8H, only 3 of the cauterized ones were bowed downwards, and this in a slight degree. 4 remained horizontal, and 3 were curved upwards in opposition to geotropism, and from the side bearing the brown mark, 10 other specimens had their tips cauterized at the same time, and in the same degree on the upper side, and this, if it produced any effect, would tend to increase the power of geotropism, and all these radicals were strongly bowed downwards. After 8H, from the several foregoing facts, there can be no doubt that the cauterization of the tip of the radical of this cucurbita on one side, if done lightly enough, causes the whole growing part to bend to the opposite side. Raffinus sativus, sensitiveness of the apex of the radical. We here encountered many difficulties in our trials, both with squares of card and with caustic, for when seeds were pinned to a corklid, many of the radicals, to which nothing had been done, grew irregularly, often curving upwards, as if attracted by the damp surface above, and when they were immersed water they likewise often grew irregularly. We did not therefore dare to trust our experiments with attached squares of card. Nevertheless, some of them seemed to indicate that the tips were sensitive to contact. Our trials with caustic generally failed from the difficulty of not injuring too greatly. The extremely fine tips out of 7 radicals thus tried, 1 became bowed after 22H at an angle of 60 a second at 40, and a third very slightly from the perpendicular, and from the cauterized side. Sculus hippocastanum, sensitiveness of the apex of the radical. Bits of glass and squares of card were affixed with shellac or gum water to the tips of 12 radicals of the horsechestnut, and when these objects fell off they were refixed, but not in a single instance was any curvature thus caused. These massive radicals, one of which was above 2 inches in length and 3-inch diameter at its base, seemed insensible to so slight a stimulus as any small attached object. Nevertheless, when the apex encountered an obstacle in its downward course, the growing part became so uniformly and symmetrically curved that its appearance indicated not mere mechanical bending, but increased growth along the whole convex side, due to the irritation of the apex. That this is the correct view may be inferred from the effects of the more powerful stimulus of caustic. The bending from the cauterized side occurred much slower than in the previously described species, and it will perhaps be worthwhile to give our trials in detail. The seeds germinated in sawdust, and one side of the tips of the radicals were slightly rubbed once with dry nitrate of silver, and after a few minutes were allowed to dip into water. They were subjected to a rather varying temperature, generally between 52 and 58. A few cases have not been thought worth recording in which the whole tip was blackened, or in which the seedling soon became unhealthy. 1. The radical was slightly deflected from the cauterized side. In 1 day Roman 1e24h in 3 days. It stood at 60 from the perpendicular in 4 days at 90 on the 5th day. It was curved up about 40 above the horizon, so that it had passed through an angle of 130 in the 5 days, and this was the greatest amount of curvature observed. 2. In 2 days, radical slightly deflected after 7 days deflected 69 from the perpendicular, and from the cauterized side after 8 days, the angle amounted to nearly 90. 3. After 1 day slight deflection, but the cauterized mark was so faint that the same side was again touched with caustic in 4 days, from the first touch deflection, amounted to 78, which in an additional day increased to 90. 4. After 2 days slight deflection, which during the next 3 days certainly increased, but never became great, the radical did not grow well and died on the 8th day. 5. After 2 days very slight deflection, but this on the 4th day amounted to 56 from the perpendicular, and from the cauterized side. 6. After 3 days doubtfully, but after 4 days certainly deflected from the cauterized side on the 5th day deflection, amounted to 45 from the perpendicular, and this on the 7th day increased to about 90. 7. After 2 days slightly deflected on the 3rd day, the deflection amounted to 25 from the perpendicular, and this did not afterwards increase. 8. After 1 day deflection distinct on the 3rd day, it amounted to 44, and on the 4th day to 72, from the perpendicular and the cauterized side. 9. After 2 days deflection slight yet distinct on the 3rd day, the tip was again touched on the same side with caustic, and thus killed. 10. After 1 day slight deflection, which after 6 days increased to 50 from the perpendicular and the cauterized side. 11. After 1 day decided deflection, which after 6 days increased to 62 from the perpendicular and from the cauterized side. 12. After 1 day slight deflection, which on the 2nd day amounted to 35 on the 4th day to 50, and the 6th day to 63 from the perpendicular and the cauterized side. 13. Whole tip blackened, but more on one side than the other on the 4th day slightly, and on the 6th day greatly deflected from the more blackened side. The deflection on the 9th day amounted to 90 from the perpendicular. 14. Whole tip blackened in the same manner as in the last case on the 2nd day, decided deflection from the more blackened side, which increased on the 7th day to nearly 90 on the following day. The radical appeared unhealthy. 15. Here we had the anomalous case of a radical bending slightly towards the cauterized side on the 1st day, and continuing to do so for the next 3 days, when the deflection amounted to about 90 from the perpendicular. The cause appeared to lie in the tendril-like sensitiveness of the upper part of the radical, against which the point of a large triangular flap of the seedcoats pressed with considerable force, and this irritation apparently conquered that from the cauterized apex. These several cases show beyond doubt that the irritation of one side of the apex excites the upper part of the radical to bend slowly towards the opposite side. This fact was well exhibited in one lot of 5 seeds pinned to the corklid of a jar, for when after 6 days the lid was turned upside down, and viewed from directly above, the little black marks made by the caustic were now all distinctly visible on the upper sides of the tips of the laterally bowed radicals. A thin slice was shaved off with a razor from one side of the tips of 22 radicals in the manner described under the common bean, but this kind of irritation did not prove very effective. Only 7 out of the 22 radicals became moderately deflected in from 3 to 5 days from the sliced surface, and several of the others grew irregularly. The evidence therefore is far from conclusive. Quercus robur sensitiveness of the apex of the radical. The tips of the radicals of the common oak are fully as sensitive to slight contact as are those of any plant examined by us. They remained healthy in damp air for 10 days, but grew slowly. Squares of the card-like paper were fixed with shellac to the tips of 15 radicals, and 10 of these became conspicuously bowed from the perpendicular, and from the squares 2 slightly and 3 not at all, but 2 of the latter were not real exceptions, as they were at first very short, and hardly grew afterwards. Some of the more remarkable cases are worth describing. The radicals were examined on each successive morning at nearly the same hour, that is after intervals of 24h. No one this radical suffered from a series of accidents, and acted in an anomalous manner, for the apex appeared at first insensible, and afterwards sensitive to contact. The first square was attached on Oct. 19th. On the 21st, the radical was not at all curved, and the square was accidentally knocked off. It was refixed on the 22nd, and the radical became slightly curved from the square, but the curvature disappeared on the 23rd, when the square was removed and refixed. No curvature ensued, and the square was again accidentally knocked off and refixed on the morning of the 27th. It was washed off by having reached the water in the bottom of the jar. The square was refixed, and on the 29th, that is 10 days after the first square had been attached, and 2 days after the attachment of the last square, the radical had grown to the great length of 3 inches, and now the terminal growing part had become bent away from the square into a hook. See Fig 68. Fig 68. Quercus rubber radical with square of card, attached to one side of apex, causing it to become hooked, drawing 1/2 natural scale. No 2 square attached on the 19th. On the 20th, radical slightly deflected from it, and from the perpendicular on the 21st, deflected at nearly right angles. It remained during the next 2 days in this position, but on the 25th the upward curvature was lessened through the action of geotropism, and still more so on the 26th. No 3 square attached on the 19th. On the 21st, a trace of curvature from the square which amounted on the 22nd to about 40, and on the 23rd to 53 from the perpendicular. No 4 square attached on the 21st. On the 22nd, trace of curvature from the square on the 23rd, completely hooked with the point turned up to the zenith. 3 days afterwards, Roman 1e26, the curvature had wholly disappeared, and the apex pointed perpendicularly downwards. No 5 square attached on the 21st. On the 22nd, decided though slight curvature from the square on the 23rd, the tip had curved up above the horizon, and on the 24th was hooked with the apex pointing almost to the zenith, as in Fig 68. No 6 square attached on the 21st. On the 22nd, slightly curved from the square. 23rd, more curved. 25th, considerably curved. 27th, all curvature lost, and the radical was now directed perpendicularly downwards. No 7 square attached on the 21st. On the 22nd, a trace of curvature from the square which increased next day, and on the 24th amounted to a right angle. It is therefore manifest that the apex of the radical of the oak is highly sensitive to contact, and retains its sensitiveness during several days. The movement thus induced was, however, slower than in any of the previous cases, with the exception of that of Sculus. As with the bean, the terminal growing part, after bending, sometimes straightened itself through the action of geotropism, although the object still remained attached to the tip. The same remarkable experiment was next tried, as in the case of the bean, namely little squares of exactly the same size of the card-like sanded paper, and of very thin paper, the thicknesses of which have been given under Vischer Faber, were attached with shellac on opposite sides, as accurately as could be done of the tips of 13 radicals suspended in damp air at a temperature of 65–66 F. The result was striking, for 9 out of these 13 radicals became plainly, and one very slightly curved from the thick paper towards the side bearing the thin paper. In 2 of these cases, the apex became completely hooked. After 2 days, in 4 cases, the deflection from the perpendicular and from the side bearing the thick paper amounted in from 2 to 4 days to angles of 90, 72, 60 and 49, but in 2 other cases to only 18 and 15. It should, however, be stated that in the case in which the deflection was 49, the 2 squares had accidentally come into contact on one side of the apex and thus formed a lateral gable, and the deflection was directed in part from this gable and in part from the thick paper. In 3 cases alone, the radicals were not affected by the difference in thickness of the squares of paper attached to their tips, and consequently did not bend away from the side bearing the stiffer paper. May's sensitiveness of the apex of the radical to contact. A large number of trials were made on this plant, as it was the only monocotyledon on which we experimented. An abstract of the results will suffice. In the first place, 22 germinating seeds were pinned to corklids without any object being attached to their radicals, some being exposed to a temperature of 65–66 F, and others to between 74 and 79, and none of them became curved, though some were a little inclined to one side. A few were selected which, from having germinated on sand, were crooked, But when suspended in damp air, the terminal part grew straight downwards. This fact having been ascertained, little squares of the card-like paper were affixed with shellac on several occasions to the tips of 68 radicals of these. The terminal growing part of 39 became within 24H conspicuously curved away from the attached squares, and from the perpendicular 13 out of the 39 forming hooks with their points directed towards the zenith and 8 forming loops. Moreover, 7 other radicals out of the 68 were slightly and 2 doubtfully deflected from the cards. There remained 20 which were not affected. But 10 of these ought not to be counted, for 1 was diseased, 2 had their tips quite surrounded by shellac, and the squares on 7 had slipped so as to stand parallel to the apex instead of obliquely on it. There were therefore only 10 out of the 68, which certainly were not acted on. Some of the radicals which were experimented on were young and short, most of them of moderate length, and 2 or 3 exceeded 3 inches in length. The curvature in the above cases occurred within 24H, but it was often conspicuous within a much shorter period. For instance, the terminal growing part of one radical was bent upwards into a rectangle in 8H 15 Roman 1000, and of another, in 9H on one occasion, a hook was formed in 9H 6 of the radicals, in a jar containing 9 seeds, which stood on a sandbath raised to a temperature varying from 76 to 82 F became hooked, and a 7th formed a complete loop, when first looked at after 15 hours. The accompanying figures of 4 germinating seeds, Fig. 69, show firstly a radical A, the apex of which has become so much bent away from the attached square as to form a hook, secondly B, a hook, converted through the continued irritation of the card, aided perhaps by geotropism, into an almost complete circle, or loop. The tip, in the act of forming a loop, generally rubs against the upper part of the radical and pushes off the attached square. The loop then contracts or closes, but never disappears, and the apex afterwards grows vertically downwards, being no longer irritated by any attached object. This frequently occurred, and is represented at Roman 100. The jar above mentioned, with the 6 hooked radicals, and another jar were kept for 2 additional days for the sake of observing how the hooks would be modified. Most of them became converted into simple loops like that figured at C. But in one case the apex did not rub against the upper part of the radical, and thus removed the card, and it consequently made, owing to the continued irritation from the card, 2 complete loops, that is, a helix of 2 spires which afterwards became pressed closely together. Then geotropism prevailed and caused the apex to grow perpendicularly downwards. In another case shown at D, the apex, in making a second turn or spire, passed through the first loop, which was at first widely open, and in doing so knocked off the card. It then grew perpendicularly downwards, and thus tied itself into a knot which soon became tight. Fig. 69, Z, maize radicals excited to bend away from the little squares of card, attached to one side of their tips. Secondary radicals of Z. A short time after the first radical has appeared, others protrude from the seed, but not laterally from the primary. 110 of these secondary radicals, which were directed obliquely downwards, were experimented on with very small squares of card, attached with shellac to the lower sides of their tips. If therefore the squares acted, the radicals would bend upwards. In opposition to gravity, the jar stood protected from light on a sandbath, which varied between 76 and 82 F. After only 5H1 appeared to be a little deflected from the square, and after 20H formed a loop. 4 others were considerably curved from the squares after 20H, and 3 of them became hooked with their tips pointing to the zenithone after 29H, and the 2 others after 44H. By this latter time, a 6th radical had become bent at a right angle from the side, bearing the square. Thus altogether, 6 out of the 10 secondary radicals were acted on, 4 not being affected. There can therefore be no doubt that the tips of these secondary radicals are sensitive to slight contact, and that when thus excited they cause the upper part to bend from the touching object, but generally, as it appears, not in so short a time as in the case of the first formed radical. Sensitiveness of the tip of the radical to moist air. Sachs made the interesting discovery a few years ago that the radicals of many seedling plants bend towards an adjoining damp surface. 9. We shall here endeavor to show that this peculiar form of sensitiveness resides in their tips. The movement is directly the reverse of that excited by the irritants hitherto considered, which cause the growing part of the radical to bend away from the source of irritation. In our experiments, we followed Sachs' plan, and sieves with seeds germinating in damp sawdust were suspended so that the bottom was generally inclined at 40 with the horizon. If the radicals had been acted on solely by geotropism, they would have grown out of the bottom of the sieve perpendicularly downwards, but as they were attracted by the adjoining damp surface, they bent towards it, and were deflected 50 from the perpendicular for the sake of ascertaining whether the tip or the whole growing part of the radical was sensitive to the moist air. A length of from 1 to 2 Roman 2000 was coated in a certain number of cases with a mixture of olive oil and lampblack. This mixture was made in order to give consistence to the oil so that a thick layer could be applied, which would exclude at least to a large extent the moist air, and would be easily visible. A greater number of experiments than those which were actually tried would have been necessary, had not it been clearly established that the tip of the radical is the part which is sensitive to various other irritants. Phasalis multiflorus 29 radicals to which nothing had been done growing out of a sieve were observed at the same time with those which had their tips greased, and for an equal length of time of the 29-24 curved themselves, so as to come into close contact with the bottom of the sieve. The place of chief curvature was generally at a distance of 5 or 6 Roman 2000 from the apex. 8 radicals had their tips greased for a length of 2 Roman 2000, and 2 others for a length of 112 Roman 2000. They were kept at a temperature of 15-16 Roman 100, after intervals of from 19H to 24H. All were still vertically or almost vertically dependent. For some of them had moved towards the adjoining damp surface by about 10. They had therefore not been acted on, or only slightly acted on by the damper air on one side, although the whole upper part was freely exposed. After 48H, 3 of these radicals became considerably curved towards the sieve, and the absence of curvature in some of the others might perhaps be accounted for by their not having grown very well. But it should be observed that during the first 19H to 24H all grew well, 2 of them having increased 2 and 3 Roman 2000 in length in 11H5, others increased 5 to 8 Roman 2000 in 19H, and 2, which had been at first 4 and 6 Roman 2000 in length, increased in 24H to 15 and 20 Roman 2000. The tips of 10 radicals which likewise grew well were coated with the grease for a length of only 1 Roman 2000. And now the result was somewhat different, for of these 4 curved themselves to the sieve in from 21H to 24H, whilst 6 did not do so. 5 of the latter were observed for an additional day, and now all excepting 1 became curved. The tips of 5 radicals were cauterized with nitrate of silver, and about 1 Roman 2000 in length was thus destroyed. They were observed for periods varying between 11H and 24H, and were found to have grown well. 1 of them had curved, until it came into contact with the sieve. Another was curving towards it, whilst the remaining 3 were still vertically dependent. Of 7 not cauterized radicals observed at the same time, all had come into contact with the sieve. The tips of 11 radicals were protected by moistened goldbeater's skin, which adheres closely for a length varying from 112 to 212 Roman 2000. After 22H to 24H, 6 of these radicals were clearly bent towards, or had come into contact with the sieve. 2 were slightly curved this direction, and 3 not at all. All had grown well. Of 14 control specimens observed at the same time, all excepting 1 had closely approached the sieve. It appears from these cases that a cap of goldbeater's skin checks, though only to a slight degree, the bending of the radicals to an adjoining damp surface, whether an extremely thin sheet of this substance, when moistened, allows moisture from the air to pass through it. We do not know. 1 case indicated that the caps were sometimes more efficient than appears from the above results. Radical which after 23H had only slightly approached the sieve had its cap, 112 Roman 2000 in length, removed, and during the next 15-12H it curved itself abruptly towards the source of moisture, the chief seat of curvature being at a distance of 2 to 3 Roman 2000 from the apex. Vischer Faber. The tips of 13 radicals were coated with the grease for a length of 2 Roman 2000, and it should be remembered that with these radicals, the seat of chief curvature is about 4 or 5 Roman 2000 from the apex. 4 of them were examined after 22H, 3, after 26H, and 6, after 36H, and none had been attracted towards the damp lower surface of the sieve. In another trial, 7 radicals were similarly treated, and 5 of them still pointed perpendicularly downwards after 11H, whilst 2 were a little curved towards the sieve by an accident. They were not subsequently observed in both these trials. The radicals grew well. 7 of them, which were at first from 4 to 11 Roman 2000 in length, were, after 11H, between 7 and 16 Roman 2003, which were at first from 6 to 8 Roman 2000, after 26H were 11 to 18 Roman 2000 in length, and lastly 4 radicals, which were at first 5 to 8 Roman 2000, after 46H were 18 to 23 Roman 2000 in length. The control or ungreased radicals were not invariably attracted towards the bottom of the sieve, but on one occasion 12 out of 13, which were observed for periods between 22H and 36H, were thus attracted on 2 other occasions. Taken together, 38 out of 40 were similarly attracted on another occasion. Only 7 out of 14 behaved in this manner. But after 2 more days, the proportion of the curved increased to 17 out of 23 on a last occasion. Only 11 out of 20 were thus attracted. If we add up these numbers, we find that 78 out of 96 of the control specimens curved themselves towards the bottom of the sieve of the specimens, with grease tips 2 alone out of the 20, but 7 of these were not observed for a sufficiently long time, thus curved themselves. We can therefore hardly doubt that the tip for a length of 2 Roman 2000 is the part which is sensitive to a moist atmosphere, and causes the upper part to bend towards its source. The tips of 15 radicals were cauterized with nitrate of silver, and they grew as well as those above described with grease tips. After an interval of 24H, 9 of them were not at all curved towards the bottom of the sieve. 2 were curved towards it at angles of 20 and 12 from their former vertical position, and 4 had come into close contact with it. Thus the destruction of the tip for a length of about 1 Roman 2000 prevented the curvature of the greater number of these radicals to the adjoining damp surface. Of 24 control specimens, 23 were bent to the sieve, and on a second occasion, 15 out of 16 were similarly curved in a greater or less degree. These control trials are included in those given in the foregoing paragraph. Avena sativa, the tips of 13 radicals, which projected between 2 and 4 Roman 2000 from the bottom of the sieve, many of them, not quite perpendicularly downwards, were coated with the black grease for a length of from 1 to 112 Roman 2000. The sieves were inclined at 30 with the horizon. The greater number of these radicals were examined after 22H and a few after 25H, and within these intervals they had grown so quickly as to have nearly doubled their lengths. With the ungreased radicals, the chief seat of curvature is at a distance of not less than between 3 and 5 Roman 2000, and not more than between 7 and 10 Roman 2000, from the apex. Out of the 13 radicals, with grease tips 4 had not moved at all towards the sieve. 6 were deflected towards it, and from the perpendicular by angles varying between 10 and 35, and 3 had come into close contact with it. It appears therefore at first sight that greasing the tips of these radicals had checked but little their bending to the adjoining damp surface, but the inspection of the sieves on 2 occasions produced a widely different impression on the mind, for it was impossible to behold the radicals with the black grease tips projecting from the bottom, and all those with ungreased tips at least 40 to 50 in number clinging closely to it, and feel any doubt that the greasing had produced a great effect on close examination. Only a single ungreased radical could be found, which had not become curved towards the sieve. It is probable that if the tips had been protected by grease for a length of 2 Roman 2000, instead of from 1 to 112 Roman 2000, they would not have been affected by the moist air, and none would have become curved. Triticum vulgare analogous trials were made on 8 radicals of the common wheat, and greasing their tips produced much less effect than in the case of the oats. After 22H, 5 of them had come into contact with the bottom of the sieve. 2 had moved towards it 10 and 15, and 1 alone remained perpendicular. Not one of the very numerous ungreased radicals failed to come into close contact with the sieve. These trials were made on Nov 28th, when the temperature was only 4 Roman 100, at 10 A Roman 1000. We should hardly have thought this case worth notice had it not been for the following circumstance. In the beginning of October, when the temperature was considerably higher, viz. 12 to 13 Roman 100, we found that only a few of the ungreased radicals became bent towards the sieve, and this indicates that sensitiveness to moisture in the air is increased by a low temperature, as we have seen with the radicals of Vischer faber relatively to objects attached to their tips. But in the present instance, it is possible that a difference in the dryness of the air may have caused the difference in the results at the 2 periods. Finally, the facts just given with respect to Phasalis multiflorus Vischer faber and Avena sativa show, as it seems to us, that a layer of grease spread for a length of 112 to 2 Roman 2000 over the tip of the radical, or the destruction of the tip by caustic greatly lessens or quite annuls in the upper, and exposed part the power of bending towards a neighbouring source of moisture. We should bear in mind that the part which bends most lies at some little distance above the greased or cauterized tip, and that the rapid growth of this part proves that it has not been injured by the tips having been thus treated. In those cases in which the radicals with grease tips became curved, it is possible that the layer of grease was not sufficiently thick wholly to exclude moisture, or that a sufficient length was not thus protected, or in the case of the caustic, not destroyed. When radicals with grease tips are left to grow for several days in damp air, the grease is drawn out into the finest reticulated threads and dots, with narrow portions of the surface left clean. Such portions would, it is probable, be able to absorb moisture, and thus we can account for several of the radicals with grease tips having become curved towards the sieve. After an interval of 1 or 2 days on the whole, we may infer that sensitiveness to a difference in the amount of moisture in the air on the two sides of a radical resides in the tip, which transmits some influence to the upper part, causing it to bend towards the source of moisture. Consequently, the movement is the reverse of that caused by objects attached to one side of the tip, or by a thin slice being cut off, or by being slightly cauterized. In a future chapter, it will be shown that sensitiveness to the attraction of gravity likewise resides in the tip, so that it is the tip which excites the adjoining parts of a horizontally extended radical to bend towards the center of the earth. Secondary radicals becoming vertically geotropic by the destruction or injury of the terminal part of the primary radical. Sachs has shown that the lateral or secondary radicals of the bean, and probably of other plants, are acted on by geotropism in so peculiar a manner that they grow out horizontally, or a little inclined downwards, and he has further shown the interesting fact that if the end of the primary radical be cut off, one of the nearest secondary radicals changes its nature and grows perpendicularly downwards, thus replacing the primary radical. We repeated this experiment and planted beans with amputated radicals in friable peat, and saw the result described by Sachs, but generally 2 or 3 of the secondary radicals grew perpendicularly downwards. We also modified the experiment by pinching young radicals a little way above their tips between the arms of a U-shaped piece of thick leaden wire. The part pinched was thus flattened, and was afterwards prevented from growing thicker. 5 radicals had their ends cut off and served as controls or standards. 8 were pinched. Of these, 2 were pinched too severely, and their ends died and dropped off. 2 were not pinched enough, and were not sensibly affected. The remaining 4 were pinched sufficiently to check the growth of the terminal part, but did not appear otherwise injured. When the U-shaped wires were removed after an interval of 15 days, the part beneath the wire was found to be very thin and easily broken, whilst the part above was thickened. Now in these 4 cases, 1 or more of the secondary radicals arising from the thickened part just above the wire had grown perpendicularly downwards. In the best case, the primary radical, the part below the wire being 112 inch in length, was somewhat distorted, and was not half as long as 3 adjoining secondary radicals which had grown vertically or almost vertically downwards. Some of these secondary radicals adhered together, or had become confluent. We learn from these 4 cases that it is not necessary, in order that a secondary radical should assume the nature of a primary one, that the latter should be actually amputated. It is sufficient that the flow of sap into it should be checked, and consequently should be directed into the adjoining secondary radicals, for this seems to be the most obvious result of the primary radical being pinched between the arms of a U-shaped wire. This change in the nature of secondary radicals is clearly analogous, as Sachs has remarked, to that which occurs with the shoots of trees when the leading one is destroyed, and is afterwards replaced by 1 or more of the lateral shoots, for these now grow upright instead of subhorizontally. But in this latter case, the lateral shoots are rendered apogeotropic, whereas with radicals the lateral ones are rendered geotropic. We are naturally led to suspect that the same cause acts with shoots as with roots, namely an increased flow of sap into the lateral ones. We made some trials with Abies communis and pectinata, by pinching with wire the leading and all the lateral shoots, excepting 1, but we believe that they were too old when experimented on, and some were pinched too severely, and some not enough. Only 1 case succeeded, namely with the sprucifer. The leading shoot was not killed, but its growth was checked. At its base there were 3 lateral shoots in a wall, 2 of which were pinched. 1 being thus killed, the 3rd was left untouched. These lateral shoots, when operated on July 14th, stood at an angle of 8 above the horizon. By Sept 8th the unpinched one had risen 35, by Oct 4th it had risen 46, and by Jan 26th 48, and it had now become a little curved inwards. Part of this rise of 48 may be attributed to ordinary growth, for the pinched shoot rose 12 within the same period. It thus follows that the unpinched shoot stood on Jan 26th 56 above the horizon, or 34 from the vertical, and it was thus obviously almost ready to replace the slowly growing pinched leading shoot. Nevertheless, we feel some doubt about this experiment, for we have since observed with sprucifers growing rather unhealthily that the lateral shoots near the summit sometimes become highly inclined, whilst the leading shoot remains apparently sound. A widely different agency not rarely causes shoots, which naturally would have grown out horizontally, to grow up vertically. The lateral branches of the silver fir pectinata are often affected by a fungus Psidium elatinum, which causes the branch to enlarge into an oval knob formed of hard wood, in one of which we counted 24 rings of growth, according to de Berry 11. When the mycelium penetrates a bud beginning to elongate, the shoot, developed from it, grows vertically upwards. Such upright shoots afterwards produce lateral and horizontal branches, and they then present a curious appearance, as if a young fir tree had grown out of a ball of clay surrounding the branch. These upright shoots have manifestly changed their nature and become apogeotropic, for if they had not been affected by the psidium, they would have grown out horizontally like all the other twigs on the same branches. This change can hardly be due to an increased flow of sap into the part, but the presence of the mycelium will have greatly disturbed its natural constitution. According to Mr. Meehan, 12, the stems of 3 species of euphorbia and of Portulaca auracea are normally prostrate or procumbent, but when they are attacked by Oncidium, they assume an erect habit. Dr. Stahl informs us that he knows of several analogous cases, and these seem to be closely related to that of the abis. Rhizomes of Sparganium ramosum grow out horizontally in the soil to a considerable length, or are diageotropic, but F. Elfing found that when they were cultivated in water their tips turned upwards, and they became apogeotropic. The same result followed when the stem of the plant was bent until it cracked, or was merely much bowed. 13. No explanation has hitherto been attempted of such cases as the foregoing, namely of secondary radicals growing vertically downwards, and of lateral shoots growing vertically upwards after the amputation of the primary radical, or of the leading shoot. The following considerations give us, as we believe, the clue. Firstly, any cause which disturbs the constitution 14 is apt to induce reversion, such as the crossing of 2 distinct races or a change of conditions, as when domestic animals become feral, but the case which most concerns us is the frequent appearance of peloric flowers on the summit of a stem, or in the center of the inflorescence epots, which it is believed receive the most sap, for when an irregular flower becomes perfectly regular or peloric, this may be attributed at least partly to reversion to a primitive and normal type. Even the position of a seed at the end of the capsule sometimes gives to the seedling developed from it a tendency to revert. Secondly, reversions often occur by means of buds, independently of reproduction by seed, so that a bud may revert to the character of a former state. Many bud generations ago, in the case of animals, reversions may occur in the individual, with advancing age. Thirdly and lastly, radicals, when they first protrude from the seed, are always geotropic, and plumules or shoots almost always apogeotropic. If then any cause, such as an increased flow of sap or the presence of mycelium, disturbs the constitution of a lateral shoot or of a secondary radical, it is apt to revert to its primordial state, and it becomes either apogeotropic or geotropic, as the case may be, and consequently grows either vertically upwards or downwards. It is indeed possible, or even probable, that this tendency to reversion may have been increased, as it is manifestly of service to the plant. A part or organ may be called sensitive when its irritation excites movement in an adjoining part. Now, it has been shown in this chapter that the tip of the radicle of the bean is in this sense sensitive to the contact of any small object attached to one side by shellac or gum water, also to a slight touch with dry caustic, and to a thin slice cut off one side. The radicals of the pea were tried with attached objects, and caustic, both of which acted with Phasalis multiflorus. The tip was hardly sensitive to small squares of attached card, but was sensitive to caustic, and to slicing. The radicals of Tropiolum were highly sensitive to contact, and so, as far as we could judge, were those of Gossypium herbaceum, and they were certainly sensitive to caustic. The tips of the radicals of Cucurbita ovifera were likewise highly sensitive to caustic, though only moderately so to contact. Raphanus sativus offered a somewhat doubtful case. With Sculus the tips were quite indifferent to bodies attached to them, though sensitive to caustic. Those of Quercus raba and Z. maiz were highly sensitive to contact, as were the radicals of the latter to caustic. In several of these cases, the difference in sensitiveness of the tip to contact and to caustic was, as we believe, merely apparent, for with Gossypium raphanus and Cucurbita, the tip was so fine and flexible that it was very difficult to attach any object to one of its sides. With the radicals of Sculus, the tips were not at all sensitive to small bodies attached to them, but it does not follow from this fact that they would not have been sensitive to somewhat greater continued pressure if this could have been applied. The peculiar form of sensitiveness which we are here considering is confined to the tip of the radical for a length of from 1 Roman 2000 to 1 Roman 2000, when this part is irritated by contact with any object by caustic, or by a thin slice being cut off the upper adjoining part of the radical for a length of from 6 or 7 to even 12 Roman 2000 is excited to bend away from the side which has been irritated. Some influence must therefore be transmitted from the tip along the radical for this length. The curvature thus caused is generally symmetrical. The part which bends most apparently coincides with that of the most rapid growth. The tip and the basal part grow very slowly, and they bend very little. Considering the widely separated position in the vegetable series of the several above-named genera, we may conclude that the tips of the radicals of all or almost all plants are similarly sensitive and transmit an influence causing the upper part to bend with respect to the tips of the secondary radicals. Those of Viscia faber-pisum sativum and Z. maiz were alone observed, and they were found similarly sensitive. In order that these movements should be properly displayed, it appears necessary that the radicals should grow at their normal rate if subjected to a high temperature, and made to grow rapidly. The tips seem either to lose their sensitiveness or the upper part to lose the power of bending, so it appears to be if they grow very slowly from not being vigorous or from being kept at too low a temperature, also when they are forced to germinate in the middle of the winter. The curvature of the radical sometimes occurs within from 6 to 8 hours after the tip has been irritated, and almost always within 24h, excepting in the case of the massive radicals of Sculus. The curvature often amounts to a rectangle. That is, the terminal part bends upwards, until the tip, which is but little curved, projects almost horizontally. Occasionally, the tip, from the continued irritation of the attached object, continues to bend up, until it forms a hook with the point directed towards the zenith, or a loop, or even a spire. After a time, the radical apparently becomes accustomed to the irritation, as occurs in the case of tendrils, for it again grows downwards. Although the bit of card or other object may remain attached to the tip, it is evident that a small object attached to the free point of a vertically suspended radical can offer no mechanical resistance to its growth as a whole, for the object is carried downwards as the radical elongates, or upwards as the radical curves upwards, nor can the growth of the tip itself be mechanically checked by an object attached to it by gumwater, which remains all the time perfectly soft. The weight of the object, though quite insignificant, is opposed to the upward curvature. We may therefore conclude that it is the irritation due to contact which excites the movement. The contact, however, must be prolonged, for the tips of 15 radicals were rubbed for a short time, and this did not cause them to bend here. Then we have a case of specialized sensibility, like that of the glands of Drosera, for these are exquisitely sensitive to the slightest pressure if prolonged, but not to 2 or 3 rough touches. When the tip of a radical is lightly touched on one side with dry nitrate of silver, the injury caused is very slight, and the adjoining upper part bends away from the cauterized point with more certainty in most cases than from an object attached on one side. Here it obviously is not the mere touch, but the effect produced by the caustic, which induces the tip to transmit some influence to the adjoining part, causing it to bend away. If one side of the tip is badly injured or killed by the caustic, it ceases to grow whilst the opposite side continues growing, and the result is that the tip itself bends towards the injured side and often becomes completely hooked. And it is remarkable that in this case the adjoining upper part does not bend. The stimulus is too powerful or the shock too great for the proper influence to be transmitted from the tip. We have strictly analogous cases with Drosera dionea and pinguicula, with which plants a too powerful stimulus does not excite the tentacles to become incurved, or the lobes to close, or the margin to be folded inwards. With respect to the degree of sensitiveness of the apex to contact under favorable conditions, we have seen that with Viscia faber a little square of writing paper, affixed with shellac, sufficed to cause movement, as did on one occasion a square of merely damped gold beater's skin, but it acted very slowly. Short bits of moderately thick bristle, of which measurements have been given affixed with gumwater, acted in only 3 out of 11 trials, and beads of dried shellac, under 1/1200th of a grain in weight, acted only twice in 9 cases, so that here we have nearly reached the minimum of necessary irritation. The apex, therefore, is much less sensitive to pressure than the glands of Drosera, for these are affected by far thinner objects than bits of bristle, and by a very much less weight than 1/1200th of a grain, But the most interesting evidence of the delicate sensitiveness of the tip of the radical was afforded by its power of discriminating between equal-sized squares of card-like and very thin paper when these were attached on opposite sides, as was observed with the radicals of the bean and oak. When radicals of the bean are extended horizontally with squares of card attached to the lower sides of their tips, the irritation thus caused was always conquered by geotropism, which then acts under the most favorable conditions at right angles to the radical. But when objects were attached to the radicals of any of the above-named genera, suspended vertically, the irritation conquered geotropism, which latter power at first acted obliquely on the radical, so that the immediate irritation from the attached object, aided by its after-effects, prevailed, and caused the radical to bend upwards, until sometimes the point was directed to the zenith. We must however assume that the after-effects of the irritation of the tip by an attached object come into play only after movement has been excited. The tips of the radicals of the pea seem to be more sensitive to contact than those of the bean, for when they were extended horizontally, with squares of card adhering to their lower sides, a most curious struggle occasionally arose, sometimes one, and sometimes the other force prevailing, but ultimately geotropism was always victorious. Nevertheless, in two instances the terminal part became so much curved upwards that loops were subsequently formed with the pea. Therefore the irritation from an attached object, and from geotropism when acting at right angles to the radical, are nearly balanced forces. Closely similar results were observed with the horizontally extended radicals of Cucurbita ovifera, when their tips were slightly cauterized on the lower side. Finally, the several coordinated movements by which radicals are enabled to perform their proper functions are admirably perfect in whatever direction the primary radical first protrudes from the seed. Geotropism guides it perpendicularly downwards, and the capacity to be acted on by the attraction of gravity resides in the tip. But Sachs has proved 15 that the secondary radicals, or those emitted by the primary one, are acted on by geotropism in such a manner that they tend to bend only obliquely downwards. If they had been acted on like the primary radical, all the radicals would have penetrated the ground in a close bundle. We have seen that if the end of the primary radical is cut off or injured, the adjoining secondary radicals become geotropic and grow vertically downwards. This power must often be of great service to the plant when the primary radical has been destroyed by the larvae of insects, burrowing animals, or any other accident. The tertiary radicals, or those emitted by the secondary ones, are not influenced, at least in the case of the bean, by geotropism, so they grow out freely in all directions. From this manner of growth of the various kinds of radicals, they are distributed together with their absorbent hairs throughout the surrounding soil, as Sachs has remarked, in the most advantageous manner for the whole soil, is thus closely searched. Geotropism, as was shown in the last chapter, excites the primary radical to bend downwards with very little force, quite insufficient to penetrate the ground. Such penetration is effected by the pointed apex, protected by the root cap being pressed down by the longitudinal expansion or growth of the terminal rigid portion, aided by its transverse expansion, both of which forces act powerfully. It is, however, indispensable that the seeds should be at first held down in some manner. When they lie on the bare surface, they are held down by the attachment of the root hairs to any adjoining objects, and this apparently is effected by the conversion of their outer surfaces into a cement. But many seeds get covered up by various accidents, or they fall into crevices or holes. With some seeds their own weight suffices. The circumnudating movement of the terminal growing part, both of the primary and secondary radicals, is so feeble that it can aid them very little in penetrating the ground, excepting when the superficial layer is very soft and damp. But it must aid them materially when they happen to break obliquely into cracks or into burrows made by earthworms or larvae. This movement, moreover, combined with the sensitiveness of the tip to contact, can hardly fail to be of the highest importance, for as the tip is always endeavoring to bend to all sides, it will press on all sides, and will thus be able to discriminate between the harder and softer adjoining surfaces in the same manner as it discriminated between the attached squares of cardlike and thin paper. Consequently, it will tend to bend from the harder soil and will thus follow the lines of least resistance. So it will be if it meets with a stone or the root of another plant in the soil, as must incessantly occur if the tip were not sensitive, and if it did not excite the upper part of the root to bend away. Whenever it encountered at right angles some obstacle in the ground, it would be liable to be doubled up into a contorted mass. But we have seen with radicals growing down inclined plates of glass that as soon as the tip merely touched a slip of wood, cemented across the plate, the whole terminal growing part curved away so that the tip soon stood at right angles to its former direction, and thus it would be with an obstacle encountered in the ground as far as the pressure of the surrounding soil would permit. We can also understand why thick and strong radicals like those of sculus should be endowed with less sensitiveness than more delicate ones, for the former would be able by the force of their growth to overcome any slight obstacle. After a radical which has been deflected by some stone or root from its natural downward course reaches the edge of the obstacle, geotropism will direct it to grow again straight downward. But we know that geotropism acts with very little force, and here another excellent adaptation, as Sachs has remarked, 16 comes into play for the upper part of the radical, a little above the apex, is, as we have seen, likewise sensitive, and this sensitiveness causes the radical to bend like a tendril towards the touching object, so that as it rubs over the edge of an obstacle it will bend downwards, and the curvature thus induced is abrupt, in which respect it differs from that caused by the irritation of one side of the tip. This downward bending coincides with that due to geotropism, and both will cause the root to resume its original course. As radicals perceive an excess of moisture in the air on one side, and bend towards this side, we may infer that they will act in the same manner with respect to moisture in the earth. The sensitiveness to moisture resides in the tip, which determines the bending of the upper part. This capacity perhaps partly accounts for the extent to which drainpipes often become choked with roots. Considering the several facts given in this chapter, we see that the course followed by a root through the soil is governed by extraordinarily complex and diversified agencies, be geotropism, acting in a different manner on the primary, secondary, and tertiary radicles, be sensitiveness, to contact different in kind in the apex, and in the part immediately above the apex, and apparently by sensitiveness to the varying dampness of different parts of the soil. These several stimuli to movement are all more powerful than geotropism when this acts obliquely on a radical, which has been deflected from its perpendicular downward course. The roots, moreover, of most plants are excited by light to bend either to or from it, but as roots are not naturally exposed to the light, it is doubtful whether this sensitiveness, which is perhaps only the indirect result of the radicals being highly sensitive to other stimuli, is of any service to the plant. The direction which the apex takes at each successive period of the growth of a root ultimately determines its whole course. It is therefore highly important that the apex should pursue from the first the most advantageous direction, and we can thus understand why sensitiveness to geotropism, to contact, and to moisture all reside in the tip, and why the tip determines the upper growing part to bend either from or to the exciting cause. A radical may be compared with a burrowing animal, such as a mole, which wishes to penetrate perpendicularly down into the ground. By continually moving his head from side to side, or circumnudating, he will feel any stone or other obstacle, as well as any difference in the hardness of the soil, and he will turn from that side. If the earth is damper on one than on the other side, he will turn thitherward as a better hunting ground. Nevertheless, after each interruption, guided by the sense of gravity, he will be able to recover his downward course, and to burrow to a greater depth. Chapter Roman 4: The circumnudating movements of the several parts of mature plants. Circumnutation of stems, concluding remarks on circumnutation of stolons aid, thus afforded in winding amongst the stems of surrounding plant. Circumnutation of flower stems, circumnutation of dicotyledonous leaves, singular oscillatory movement of leaves of Dionaea, leaves of cannabis sink at night, leaves of gymnosperms of monocotyledons, cryptogams. Concluding remarks on the circumnutation of leaves generally rise in the evening and sink in the morning. We have seen in the first chapter that the stems of all seedlings, whether hypocotyls or epicotyls, as well as the cotyledons, and the radicals are continually circumnudating, that is, they grow first on one side, and then on another, such growth being probably preceded by increased turgescence of the cells, as it was unlikely that plants should change their manner of growth with advancing age. It seemed probable that the various organs of all plants at all ages, as long as they continued to grow, would be found to circumnudate, though perhaps to an extremely small extent. As it was important for us to discover whether this was the case, we determined to observe carefully a certain number of plants which were growing vigorously, and which were not known to move in any manner. We commenced with stems. Observations of this kind are tedious, and it appeared to us that it would be sufficient to observe the stems in about a score of genera, belonging to widely distinct families and inhabitants of various countries. Several plants were selected which, from being woody or for other reasons, seemed the least likely to circumnudate the observations, and the diagrams were made in the manner described in the introduction. Plants in pots were subjected to a proper temperature, and whilst being observed were kept either in darkness or were feebly illuminated from above. They are arranged in the order adopted by Hooker in Le Mouat and Dequesne's system of botany. The number of the family to which each genus belongs is appended, as this serves to show the place of each in the series. 1. Iberis umbellata cruciferi, Fam 14. The movement of the stem of a young plant 4 inches in height, consisting of 4 internodes, the hypocotyl included besides a large bud on the summit, was traced as here shown, during 24H Fig 70, as far as we could judge the uppermost inch alone of the stem circumnudated. And this in a simple manner. The movement was slow, and the rate very unequal at different times. In part of its course, an irregular ellipse or rather triangle was completed in 6H 30 Roman 1000 Fig 70, Iberis umbellata circumnutation of stem of young plant, traced from 8A Roman 1000, Sept 13th, to same hour on following morning distance of summit of stem, beneath the horizontal glass 7 inches diagram, reduced to half of original size movement, as here shown magnified between 4 and 5 times. 2. Brassica auracea cruciferi, a very young plant bearing 3 leaves of which the longest was only 3/4 of an inch in length, was placed under a microscope furnished with an eyepiece micrometer, and the tip of the largest leaf was found to be in constant movement. It crossed 5 divisions of the micrometer, that is 1/100th of an inch in 6 Roman 1000 s. There could hardly be a doubt that it was the stem which chiefly moved, for the tip did not get quickly out of focus, and this would have occurred had the movement been confined to the leaf, which moves up or down in nearly the same vertical plane. 3. Linum usitatissimum linni, Fam 39. The stems of this plant shortly before the flowering period are stated by Fritz Müller Genetische Zeitschrift B Roman 5 p. 137 to revolve or circumnudate. 4. Pelargonium zonil geraniaceae, Fam 47. A young plant, 712 inches in height, was observed in the usual manner, but in order to see the bead at the end of the glass filament, and at the same time the mark beneath it, was necessary to cut off 3 leaves on one side. We do not know whether it was owing to this cause, or to the plant having previously become bent to one side through heliotropism, but from the morning of the 7th of March to 10 P Roman 1000 on the 8th, the stem moved a considerable distance in a zigzag line in the same general direction. During the night of the 8th, it moved to some distance at right angles to its former course, and next morning 9th stood for a time almost still. At noon on the 9th, a new tracing was begun, Fig 71, which was continued till 8A Roman 1000 on the 11th between noon on the 9th and 5P Roman 1000 on the 10th Roman 1E in the course of 29H. The stem described a circle. This plant therefore circumnudates, but at a very slow rate and to a small extent. Fig 71, Pelargonium zonil circumnutation of stem of young plant, feebly illuminated from above, movement of bead, magnified about 11 times, traced on a horizontal glass from noon on March 9th to 8A Roman 1000 on the 11th. 5. Tropiolum majus dwarfed var called Tomthumb geraniaceae Fam 47. The species of this genus climb by the aid of their sensitive petioles, but some of them also twine round supports, but even these latter species do not begin to circumnudate in a conspicuous manner, whilst young. The variety here treated of has a rather thick stem and is so dwarf that apparently it does not climb in any manner. We therefore wish to ascertain whether the stem of a young plant, consisting of 2 internodes together 3 inches in height, circumnudated. It was observed during 25H, and we see in Fig 72 that the stem moved in a zigzag course indicating circumnutation. Fig 72, Tropiolum majus circumnutation of stem of young plant, traced on a horizontal glass from 9A Roman 1000 dec. 26th to 10A Roman 1000. On 27th, movement of bead magnified about 5 times in here, reduced to half of original scale. Fig 73, Trifolium resupinatum circumnutation of stem traced on vertical glass from 9A Roman 1000 to 4P Roman 1000 Nav 3rd, tracing not greatly magnified, reduced to half of original size, plant feebly illuminated from above. 6. Trifolium resupinatum leguminosae, Fam 75. When we treat of the sleep of plants, we shall see that the stems in several leguminous genera, for instance those of Hedysarum, Mimosa melillatus etc., which are not climbers, circumnudate in a conspicuous manner. We will here give only a single instance, Fig 73, showing the circumnutation of the stem of a large plant of a clover, Trifolium resupinatum, in the course of 7H, the stem changed its course greatly 8 times, and completed 3 irregular circles or ellipses. It therefore circumnudated rapidly some of the lines run at right angles to one another. Fig 74, rubus hybrid circumnutation of stem traced on horizontal glass, from 4 P Roman 1000 March 14th to 8 A Roman 1000th tracing, much magnified reduced to half of original size plant, illuminated feebly from above. 7 Rubus idus hybrid Rosaceae fam 76, as we happen to have a young plant 11 inches in height, and growing vigorously, which had been raised from a cross between the raspberry Rubus idus and a North American Rubus. It was observed in the usual manner during the morning of March 14th, the stem almost completed a circle, and then moved far to the right at 4 P Roman 1000, it reversed its course, and now a fresh tracing was begun which was continued during 4012H, and is given in Fig 74. We here have well-marked circumnutation. 8 Deutzia gracilis saxifragi fam 77, a shoot on a bush about 18 inches in height, was observed the bead changed its course greatly 11 times in the course of 10H 30 Roman 1000 Fig 75, and there could be no doubt about the circumnutation of the stem. Fig 75 Deutzia gracilis circumnutation of stem, kept in darkness traced on horizontal glass, from 8 A Roman 1000 to 7 P Roman 1000 March 20th movement of bead, originally magnified about 20 times here, reduced to half scale. 9 Fuchsia greenhouse var with large flowers, probably a hybrid Onograrii fam, 100A young plant 15 inches in height, was observed during nearly 48H. The accompanying figure Fig 76 gives the necessary particulars, and shows that the stem circumnutated though rather slowly. Fig 76 Fuchsia garden var circumnutation of stem, kept in darkness traced on horizontal glass, from 8 A Roman 1000 to 7 P Roman 1000 March 20th movement of bead, originally magnified about 40 times here, reduced to half scale. 10 Cereus speciosissimus garden var, sometimes called Phylocactus multiflorus cacti fam, 109. This plant, which was growing vigorously from having been removed a few days before from the greenhouse to the hothouse, was observed with especial interest, as it seemed so little probable that the stem would circumnutate. The branches are flat or flabelliform, but some of them are triangular in section with the 3 sides, hollowed out. A branch of this latter shape 9 inches in length, and 112 in diameter was chosen for observation, as less likely to circumnutate than a flabelliform branch. The movement of the bead at the end of the glass filament, affixed to the summit of the branch, was traced a Fig 77 from 9 A Roman 1000 to 4 P Roman 1000 on Nav 23rd, during which time it changed its course, greatly 6 times. On the 24th another tracing was made CB, and the bead on this day changed its course oftener, making in 8H what may be considered as 4 ellipses with their longer axes differently directed. The position of the stem, and its commencing course on the following morning, are likewise shown. There can be no doubt that this branch, though appearing quite rigid, circumnutated, but the extreme amount of movement during the time was very small, probably rather less than the 120th of an inch. Fig 77 Cereus speciosissimus circumnutation of stem, illuminated from above traced on a horizontal glass in A from 9 A Roman 1000 to 4 P Roman 1000 on Nav 23rd, and in B from 8 A Roman 1000 on the 24th to 8 A Roman 1000 on the 25th movement of the bead, in B magnified about 38 times. 11 Hedera helix Araliaceae fam 114, the stem is known to be a pheliotropic, and several seedlings, growing in a part in the greenhouse, became bent in the middle of the summer at right angles from the light, on Sept 2nd. Some of these stems were tied up so as to stand vertically, and were placed before a northeast window, but to our surprise they were now decidedly heliotropic, for during 4 days they curved themselves towards the light, and their course being traced on a horizontal glass was strongly zigzag. During the 6 succeeding days they circumnudated over the same small space at a slow rate, but there could be no doubt about their circumnutation. The plants were kept exactly in the same place before the window, and after an interval of 15 days, the stems were again observed during 2 days, and their movements traced, and they were found to be still circumnutating, but on a yet smaller scale. 12 Gazania ringens composite fam 122, the circumnutation of the stem of a young plant 7 inches in height, as measured to the tip of the highest leaf, was traced during 33H, and is shown in the accompanying figure. Fig 78. 2 main lines may be observed running at nearly right angles to 2 other main lines, but these are interrupted by small loops. Fig 78 Gazania ringen circumnutation of stem traced from 9a Roman 1000 March 21st to 6p Roman 1000 on 22nd plant, kept in darkness movement of bead, at the close of the observations magnified 34 times here, reduced to half the original scale. 13 Azalea indica ericini fam, 128, a bush 21 inches in height, was selected for observation, and the circumnutation of its leading shoot was traced during 26H 40 Roman 1000, as shown in the following figure Fig 79. 14 Plumbago capensis plumbagini fam, 134, a small lateral branch, which projected from a tall freely growing bush at an angle of 35 above the horizon, was selected for observation for the first 11H. It moved to a considerable distance in a nearly straight line to one side, owing probably to its having been previously deflected by the light while standing in the greenhouse at 7p Roman 1000 on March 7th. A fresh tracing was begun and continued for the next 43H 40 Roman 1000 c Fig 80. During the first 2H, it followed nearly the same direction as before, and then changed it a little during the night. It moved at nearly right angles to its previous course. Next day 8th, it zigzagged greatly, and on the 9th moved irregularly round a small circular space by 3p Roman 1000 on the 9th. The figure had become so complicated that no more dots could be made, but the shoot continued during the evening of the 9th, the whole of the 10th and the morning of the 11th, to circumnudate over the same small space, which was only about the 126th of an inch 97 Roman 2000 in diameter. Although this branch circumnudated to a very small extent, yet it changed its course frequently. The movements ought to have been more magnified. Fig 79 Azalea indica circumnutation of stem, illuminated from above traced on horizontal glass from 9a Roman 1000 March 9th to 12p Roman 1000 on the 10th, but on the morning of the 10th, only 4 dots were made between 8a Roman 1000 and 12p Roman 1000, both hours included, so that the circumnutation is not fairly represented in this part of the diagram. Movement of the bead here magnified about 30 times. Fig 80 Plumbago capensis circumnutation of tip of a lateral branch, traced on horizontal glass from 7p Roman 1000 on March 7th to 3p Roman 1000 on the 9th. Movement of bead magnified 13 times. Plant feebly illuminated from above. 15 Aloysia citriodora verbenacea fam 173. The following figure Fig 81 gives the movements of a shoot during 31H 40 Roman 1000 and shows that it circumnudated the bush was 15 inches in height. Fig 81 Aloysia citriodora circumnutation of stem, traced from 8a Roman 1000 on March 22nd to 4p Roman 1000 on 23rd. Plant kept in darkness movement magnified about 40 times. 16 Verbena melinders, a scarlet-flowered herbaceous var verbenacea, a shoot 8 inches in height, had been laid horizontally for the sake of observing its apogeotropism, and the terminal portion had grown vertically upwards for a length of 112 inch. A glass filament with a bead at the end was fixed upright to the tip, and its movements were traced during 41H 30 Roman 1000 on a vertical glass. Fig 82 Under these circumstances, the lateral movements were chiefly shown, but as the lines from side to side are not on the same level, the shoot must have moved in a plane at right angles to that of the lateral movement, that is, it must have circumnudated on the next day 6th. The shoot moved in the course of 16H 4 times to the right and 4 times to the left, and this apparently represents the formation of 4 ellipses, so that each was completed in 4H 17 Ceratophyllum demersum, Ceratophily fam 220. An interesting account of the movements of the stem of this waterplant has been published by Roman 1000 E. Rhodia. 1. The movements are confined to the young internodes, becoming less and less lower down the stem, and they are extraordinary from their amplitude. The stems sometimes moved through an angle of above 200 in 6H, and in one instance through 220 in 3H. They generally bent from right to left in the morning, and in an opposite direction in the afternoon, but the movement was sometimes temporarily reversed or quite arrested. It was not affected by light. It does not appear that Roman 1000 Rhodia made any diagram on a horizontal plane, representing the actual course pursued by the apex, but he speaks of the branches executing round their axes of growth, a movement of torsion from the particulars above given, and remembering in the case of twining plants, and of tendrils how difficult it is not to mistake their bending to all points of the compass for true torsion, we are led to believe that the stems of this ceratophyllum circumnudate probably in the shape of narrow ellipses, each completed in about 26 h. The following statement, however, seems to indicate something different from ordinary circumnutation, but we cannot fully understand it. Roman 1000 Rhodia, says il, est alors facile de voir, quel mouvement de flexion si produit d'abord dans les méritales supérieurs, quil si propage ensuite en samindrissant du haut en bas tandis, qual contraire le mouvement de redressement commence par la partie inférieure pour s'y terminer, à la partie supérieure qui quelquefois plus de temps avant de s'y relever tout, a fate forme avec l'axe un angle très aigu. Fig 82 Verbena Melinder's circumnutation of stem in darkness, traced on vertical glass, from 5p Roman 1000 on June 5 to 11a Roman 1000 June 7th movement of bead magnified 9 times. 18 Conifer Dr. Maxwell Masters, States Journal Lin Soch Dec 2nd 1879, that the leading shoots of many conifer during the season of their active growth exhibit very remarkable movements of revolving nutation, that is, they circumnudate. We may feel sure that the lateral shoots whilst growing would exhibit the same movement if carefully observed. 19 Lilium auratum fam liliaceae, the circumnutation of the stem of a plant 24 inches in height, is represented in the above figure. Fig 83. Fig 83 Lilium auratum circumnutation of a stem in darkness, traced on a horizontal glass from 8a Roman 1000 on March 14th to 8a Roman 1000 on 16th. But it should be noted that our observations were interrupted between 6p Roman 1000 on the 14th and 12p Roman 1000 on the 15th, and the movements during this interval of 18h 15 Roman 1000 are represented by a long broken line diagram, reduced to half original scale. Fig 84 Cyperus alternifolia circumnutation of stem, illuminated from above traced on horizontal glass, from 9a Roman 1000 March 9th to 9p Roman 1000 on 10th. The stem grew so rapidly whilst being observed that it was not possible to estimate how much its movements were magnified in the tracing. 20 Cyperus alternifolius fam cyperaceae, a glass filament with a bead at the end, was fixed across the summit of a young stem 10 inches in height close beneath the crown of elongated leaves on March 8th, between 12 and 7p Roman 1000. The stem described an ellipse open at one end on the following day. A new tracing was begun. Fig 84, which plainly shows that the stem completed 3 irregular figures in the course of 35h 15 Roman 1000. Concluding remarks on the circumnutation of stems. Anyone who will inspect the diagrams now given and will bear in mind the widely separated position of the plants described in the series, remembering that we have good grounds for the belief that the hypocartals and epicartals of all seedlings circumnudate, not forgetting the number of plants distributed in the most distinct families, which climb by a similar movement, will probably admit that the growing stems of all plants, if carefully observed, would be found to circumnudate to a greater or less extent when we treat of the sleep and other movements of plants. Many other cases of circumnudating stems will be incidentally given in looking at the diagrams. We should remember that the stems were always growing so that in each case the circumnudating apex as it rose will have described a spire of some kind. The dots were made on the glasses generally at intervals of an hour or hour and a half, and were then joined by straight lines. If they had been made at intervals of 2 or 3 minutes, the lines would have been more curvilinear, as in the case of the tracks left on the smoked glass plates by the tips of the circumnudating radicals of seedling plants. The diagrams generally approach in form to a succession of more or less irregular ellipses or ovals with their longer axes directed to different points of the compass during the same day or on succeeding days. The stems therefore sooner or later bend to all sides. But after a stem has bent in any one direction, it commonly bends back at first in nearly, though not quite, the opposite direction, and this gives the tendency to the formation of ellipses which are generally narrow, but not so narrow as those described by stolons and leaves. On the other hand, the figures sometimes approach in shape to circles. Whatever the figure may be, the course pursued is often interrupted by zigzags, small triangles, loops, or ellipses. A stem may describe a single large ellipse one day and 2 on the next with different plants. The complexity, rate, and amount of movement differ much. The stems, for instance, of iberis and azalea described only a single large ellipse in 24h, whereas those of the deutzia made 4 or 5 deep zigzags or narrow ellipses in 11-12h, and those of the trifolium 3 triangular or quadrilateral figures in 7h. Circumnutation of stolons or runners. Stolons consist of much elongated, flexible branches, which run along the surface of the ground and form roots at a distance from the parent plant. They are therefore of the same homological nature as stems, and the 3 following cases may be added to the 20 previously given cases. Fragaria cultivated garden var Rosaceae, a plant growing in a pot, had emitted a long stolon. This was supported by a stick, so that it projected for the length of several inches, horizontally. A glass filament bearing 2-minute triangles of paper was affixed to the terminal bud, which was a little upturned, and its movements were traced during 21h as shown in Fig. 85. In the course of the first 12h, it moved twice up and twice down in somewhat zigzag lines, and no doubt travelled in the same manner during the night on the following morning. After an interval of 20h, the apex stood a little higher than it did at first, and this shows that the stolon had not been acted on within this time by geotropism too, nor had its own weight caused it to bend downwards. Fig. 85. Fragaria circumnutation of stolon, kept in darkness, traced on vertical glass, from 10 A Roman 1000 May 18th to 7 A Roman 1000 on 19th. On the following morning, 19th, the glass filament was detached and refixed close behind the bud, as it appeared possible that the circumnutation of the terminal bud and of the adjoining part of the stolon might be different. The movement was now traced during 2 consecutive days. Fig. 86. During the first day, the filament travelled in the course of 14h 30 Roman 1000 5 times up and 4 times down, besides some lateral movement on the 20th. The course was even more complicated and can hardly be followed in the figure, but the filament moved in 16h at least 5 times up and 5 times down with very little lateral deflection. The first and last dots made on this second day, viz. at 7 A Roman 1000 and 11 P Roman 1000, were close together, showing that the stolon had not fallen or risen. Nevertheless, by comparing its position on the morning of the 19th and 21st, it is obvious that the stolon had sunk, and this may be attributed to slow bending down either from its own weight or from geotropism. Fig. 86. Fragaria circumnutation of the same stolon, as in the last figure, observed in the same manner, and traced from 8 A Roman 1000 May 19th to 8 A Roman 1000th. During a part of the 20th, an orthogonal tracing was made by applying a cube of wood to the vertical glass, and bringing the apex of the stolon at successive periods into a line, with one edge, a dot, being made each time on the glass. This tracing therefore represented very nearly the actual amount of movement of the apex, and in the course of 9h the distance of the extreme dots from one another was 45 inch. By the same method it was ascertained that the apex moved between 7 A Roman 1000 on the 20th and 8 A Roman 1000 on the 21st, a distance of 82 inch. A younger and shorter stolon was supported so that it projected at about 45 above the horizon, and its movement was traced by the same orthogonal method on the first day. The apex soon rose above the field of vision. By the next morning it had sunk, and the course pursued was now traced during 14h 30 Roman 1000. Fig. 87. The amount of movement was almost the same from side to side as up and down, and differed in this respect remarkably from the movement in the previous cases during the latter part of the day, viz. between 3 and 10 P Roman 1000. The actual distance travelled by the apex amounted to 1 inch, and in the course of the whole day to at least 2 inches. This is an amount of movement almost comparable with that of some climbing plants. The same stolon was observed on the following day, and now it moved in a somewhat less complex manner in a plane not far from vertical. The extreme amount of actual movement was 1 inch in one direction, and 6 inch in another direction at right angles. During neither of these days did the stolon bend downwards through geotropism or its own weight. Fig. 87. Fragaria circumnutation of another and younger stolon, traced from 8 A Roman 1000 to 10 P Roman 1000. Figure reduced to 1/2 of original scale. 4 stolons still attached to the plant were laid on damp sand in the back of a room with their tips facing the northeast windows. They were thus placed because De Vries says 3 that they are apheliatropic when exposed to the light of the sun, but we could not perceive any effect from the above feeble degree of illumination. We may add that on another occasion late in the summer, some stolons placed upright before a southwest window on a cloudy day became distinctly curved towards the light, and were therefore heliotropic close in front of the tips of the prostrate stolons. A crowd of very thin sticks and the dried haulms of grasses were driven into the sand to represent the crowded stems of surrounding plants in a state of nature. This was done for the sake of observing how the growing stolons would pass through them. They did so easily in the course of 6 days, and their circumnutation apparently facilitated their passage when the tips encountered sticks so close together that they could not pass between them. They rose up and passed over them. The sticks and haulms were removed after the passage of the 4 stolons, 2 of which were found to have assumed a permanently sinuous shape, and 2 were still straight. But to this subject we shall recur under Saxifraga. Saxifraga sarmentosa saxifragi, a plant in a suspended pot, had emitted long branch stolons, which depended like threads on all sides too, were tied up so as to stand vertically, and their upper ends became gradually bent downwards, but so slowly in the course of several days that the bending was probably due to their weight and not to geotropism. A glass filament with little triangles of paper was fixed to the end of one of these stolons, which was 12 inches in length, and had already become much bent down but still projected at a considerable angle above the horizon. It moved only slightly 3 times from side to side, and then upwards on the following day. The movement was even less, as this stolon was so long we thought that its growth was nearly completed, so we tried another which was thicker and shorter, viz. 14 inches in length. It moved greatly, chiefly upwards, and changed its course 5 times in the course of the day. During the night it curved so much upwards, in opposition to gravity, that the movement could no longer be traced on the vertical glass, and a horizontal one had to be used. The movement was followed during the next 25 as shown in Fig. 88. 3 irregular ellipses with their longer axes somewhat differently directed were almost completed in the first 15 The extreme actual amount of movement of the tip during the 25 was 75 Several stolons were laid on a flat surface of damp sand in the same manner as with those of the strawberry. The friction of the sand did not interfere with their circumnutation, nor could we detect any evidence of their being sensitive to contact, in order to see how in a state of nature they would act when encountering a stone or other obstacle on the ground. Short pieces of smoked glass an inch in height were stuck upright into the sand in front of 2 thin lateral branches. Their tips scratched the smoked surface in various directions. One made 3 upward and 2 downward lines, besides a nearly horizontal one. The other curled quite away from the glass, but ultimately both surmounted the glass and pursued their original course. The apex of a 3rd thick stolon swept up the glass in a curved line, recoiled, and again came into contact with it. It then moved to the right, and after ascending descended vertically. Ultimately, it passed round one end of the glass instead of over it. Fig. 88 Saxifraga sarmentosa circumnutation of an inclined stolon traced in darkness on a horizontal glass from 7 Roman 1000 April 18th to 9 Roman 1000 on 19th. Movement of end of stolon magnified 2 times. Many long pins were next driven rather close together into the sand, so as to form a crowd in front of the same 2 thin lateral branches, but these easily wound their way through the crowd. A thick stolon was much delayed in its passage at one place. It was forced to turn at right angles to its former course at another place. It could not pass through the pins, and the hinder part became bowed. It then curved upwards, and passed through an opening between the upper part of some pins which happened to diverge. It then descended, and finally emerged through the crowd. This stolon was rendered permanently sinuous to a slight degree, and was thicker where sinuous than elsewhere, apparently from its longitudinal growth having been checked. Cotyledon umbilicus crassulace, a plant growing in a pan of damp moss, had emitted 2 stolons 22 and 20 inches in length. One of these was supported, so that a length of 412 inches projected in a straight and horizontal line, and the movement of the apex was traced. The first dart was made at 9 Roman 1000. The terminal portion soon began to bend downwards and continued to do so, until noon. Therefore a straight line very nearly as long as the whole figure here given, Fig. 89, was first traced on the glass, but the upper part of this line has not been copied in the diagram. The curvature occurred in the middle of the penultimate internode, and its chief seat was at the distance of 1/14 inch from the apex. It appeared due to the weight of the terminal portion, acting on the more flexible part of the internode, and not to geotropism. The apex, after thus sinking down from 9 Roman 1000 to noon, moved a little to the left. It then rose up and circumnutated in a nearly vertical plane until 10 Roman 1000 on the following day, 26th. It was observed from 6 Roman 1000 to 5 Roman 1000, and within this time it moved twice up and twice down. On the morning of the 27th, the apex stood as high as it did at 11 Roman 1000 on the 25th, nor did it sink down during the 28th, but continued to circumnutate about the same place. Fig 89 cotyledon umbilicus circumnutation of stolon, traced from 11A Roman 1000 og. 25th to 11A Roman 1000th plant, illuminated from above the terminal internode, was 25 inch in length. The penultimate 2 and the third 3 inches in length apex of stolon stood at a distance of 5 inches from the vertical glass, but it was not possible to ascertain how much the tracing was magnified, as it was not known how great a length of the internode circumnudated. Another stolon which resembled the last in almost every respect was observed during the same 2 days, but only 2 inches of the terminal portion was allowed to project freely and horizontally. On the 25th, it continued from 9A Roman 1000 to 1P Roman 1000 to bend straight downwards, apparently owing to its weight. Fig 90. But after this hour until 10P Roman 1000, it zigzagged. This fact deserves notice, for we here probably see the combined effects of the bending down from weight and of circumnutation. The stolon, however, did not circumnutate when it first began to bend down, as may be observed in the present diagram, and as was still more evident in the last case when a longer portion of the stolon was left unsupported on the following day 26th. The stolon moved twice up and twice down, but still continued to fall in the evening, and during the night it travelled from some unknown cause in an oblique direction. Fig 90 cotyledon umbilicus circumnutation and downward movement of another stolon, traced on vertical glass from 9A Roman 1000 og. 25th to 11A Roman 1000th apex close to glass, so that figure but little magnified and here reduced to 2/3 of original size. We see from these 3 cases that stolons or runners circumnudate in a very complex manner. The lines generally extend in a vertical plane, and this may probably be attributed to the effect of the weight of the unsupported end of the stolon, but there is always some and occasionally a considerable amount of lateral movement. The circumnutation is so great in amplitude that it may almost be compared with that of climbing plants, that the stolons are thus aided in passing over obstacles, and in winding between the stems of the surrounding plants. The observations above given render almost certain, if they had not circumnudated, their tips would have been liable to have been doubled up as often as they met with obstacles in their path, but as it is they easily avoid them. This must be a considerable advantage to the plant in spreading from its parent stock, but we are far from supposing that the power has been gained by the stolons for this purpose, for circumnutation seems to be of universal occurrence with all growing parts, but it is not improbable that the amplitude of the movement may have been specially increased for this purpose. Circumnutation of flower stems. We did not think it necessary to make any special observations on the circumnutation of flower stems, these being axial in their nature like stems or stolons, but some were incidentally made whilst attending to other subjects, and these we will here briefly give. A few observations have also been made by other botanists. These taken together suffice to render it probable that all peduncles and subpeduncles circumnudate whilst growing. Oxalis carnosa, the peduncle which springs from the thick and woody stem of this plant, bears 3 or 4 subpeduncles. A filament with little triangles of paper was fixed within the calyx of a flower, which stood upright. Its movements were observed for 48h. During the first half of this time, the flower was fully expanded, and during the second half withered. The figure here given, Fig 91, represents 8 or 9 ellipses. Although the main peduncle circumnudated and described 1 large and 2 smaller ellipses in the course of 24h, yet the chief seat of movement lies in the subpeduncles, which ultimately bend vertically downwards, as will be described in a future chapter. The peduncles of Oxalis acetosella likewise bend downwards and afterwards when the pods are nearly mature upwards, and this is effected by a circumnudating movement. Fig 91 Oxalis carnosa flower stem, feebly illuminated from above its circumnutation, traced from 9A Roman 1000 April 13th to 9A Roman 1000th summit of flower 8 inches beneath the horizontal glass movement, probably magnified about 6 times. It may be seen in the above figure that the flower stem of O. carnosa circumnudated during 2 days about the same spot. On the other hand, the flower stem of O. sensitiva undergoes a strongly marked daily periodical change of position. When kept at a proper temperature in the middle of the day, it stands vertically up, or at a high angle. In the afternoon it sinks, and in the evening projects horizontally, or almost horizontally, rising again during the night. This movement continues from the period when the flowers are in bud to when, as we believe, the pods are mature, and it ought perhaps to have been included amongst the so-called sleep movements of plants. A tracing was not made, but the angles were measured at successive periods during 1 whole day, and these showed that the movement was not continuous, but that the peduncle oscillated up and down. We may therefore conclude that it circumnudated at the base of the peduncle. There is a mass of small cells forming a well-developed pulvinus, which is exteriorly colored purple and hairy. In no other genus as far as we know is the peduncle furnished with a pulvinus. The peduncle of O. ortogizii behaved differently from that of O. sensitiva, for it stood at a less angle above the horizon in the middle of the day. Then in the morning or evening by 10 p. Roman 1000, it had risen greatly during the middle of the day. It oscillated much up and down. Trifolium subterraneum A filament was fixed vertically to the uppermost part of the peduncle of a young and upright flowerhead, the stem of the plant having been secured to a stick, and its movements were traced during 36h. Within this time it described c. Fig. 92, a figure which represents 4 ellipses, but during the latter part of the time the peduncle began to bend downwards, and after 10 p. Roman 1000 on the 24th, it curved so rapidly down that, by 6 a. Roman 1000 on the 25th, it stood only 19 above the horizon. It went on, circumnudating in nearly the same position for 2 days even after the flowerheads have buried themselves in the ground. They continue, as will hereafter be shown, to circumnudate. It will also be seen in the next chapter that the subpeduncles of the separate flowers of Trifolium repens circumnudate in a complicated course during several days. I may add that the gynophore of Arachis hypogea, which looks exactly like a peduncle, circumnudates, whilst growing vertically downwards, in order to bury the young pod in the ground. Fig. 92 Trifolium subterraneum main flower peduncle, illuminated from above, circumnutation, traced on horizontal glass, from 8 a. Roman 1000 July 23rd to 10 p. Roman 1000th. The movements of the flowers of Cyclamen persicum were not observed, but the peduncle whilst the pod is forming increases much in length, and bows itself down by a circumnudating movement. A young peduncle of Morandia semperflorens 112 inch in length was carefully observed during a whole day, and it made 412 narrow vertical irregular and short ellipses each, at an average rate of about 2h25 Roman 1000, an adjoining peduncle described during the same time similar though fewer ellipses, 4 according to Sachs. 5 The flower stems, whilst growing of many plants, for instance those of Brassica napus, revolve or circumnudate, those of Allium porum bend from side to side. And if this movement had been traced on a horizontal glass, no doubt ellipses would have been formed. Fritz Müller has described 6 the spontaneous revolving movements of the flower stems of an alisma, which he compares with those of a climbing plant. We made no observations on the movements of the different parts of flowers. Morin, however, has observed 7 in the stamens of Sparmania, and Sirius a fremisment spontane, which it may be suspected is a circumnudating movement. The circumnutation of the gynostemium of Stylidium, as described by Gad 8, is highly remarkable and apparently aids in the fertilization of the flowers. The gynostemium, whilst spontaneously moving, comes into contact with the viscid labellum, to which it adheres, until freed by the increasing tension of the parts, or by being touched. We have now seen that the flower stems of plants belonging to such widely different families as the crucifery oxalid leguminosae, primulaceae, scrofulariinae, alismaceae, and liliaceae circumnudate, and that there are indications of this movement in many other families. With these facts before us, bearing also in mind that the tendrils of not a few plants consist of modified peduncles, we may admit without much doubt that all growing flower stems circumnudate. Circumnutation of leaves. Dicotyledons. Several distinguished botanists, Hofmeister, Sachs, Pfeffer, de Vries, Battelin, Millardit, etc., have observed, and some of them with the greatest care, the periodical movements of leaves, but their attention has been chiefly though not exclusively directed to those which move largely, and are commonly said to sleep at night. From considerations hereafter to be given, plants of this nature are here excluded, and will be treated of separately. As we wish to ascertain whether all young and growing leaves circumnudated, we thought that it would be sufficient if we observed between 30 and 40 genera, widely distributed throughout the vegetable series, selecting some unusual forms and others on woody plants. All the plants were healthy and grew in pots. They were illuminated from above, but the light perhaps was not always sufficiently bright, as many of them were observed under a skylight of groundglass. Except in a few specified cases, a fine glass filament with 2-minute triangles of paper was fixed to the leaves, and their movements were traced on a vertical glass when not stated to the contrary in the manner already described. I may repeat that the broken lines represent the nocturnal course. The stem was always secured to a stick close to the base of the leaf under observation. The arrangement of the species with the number of the family appended is the same as in the case of stems. Fig 93 Sarracenia purpurea circumnutation of young pitcher, traced from 8A Roman 1000 July 3rd to 10A Roman 1000th temp, 1718 Roman 100 apex, of pitcher 20 inches from glass, so movement greatly magnified. 1 Sarracenia purpurea sarraceni fam 11A young leaf or pitcher 812 inches in height, with the bladder swollen, but with the hood not as yet open, had a filament fixed transversely across its apex. It was observed for 48h, and during the whole of this time it circumnudated in a nearly similar manner, but to a very small extent. The tracing given Fig 93 relates only to the movement during the first 26h. Fig 94 Glossium luteum circumnutation of young leaf, traced from 9A Roman 1000 June 14th to 8A Roman 1000th, tracing not much magnified, as apex of leaf stood only 512 inches from the glass. 3 Crambe maritima cruciferi fam 14A leaf 912 inches in length on a plant not growing vigorously, was first observed. Its apex was in constant movement, but this could hardly be traced from being so small in extent. The apex, however, certainly changed its course at least 6 times in the course of 14h. A more vigorous young plant bearing only 4 leaves was then selected, and a filament was affixed to the midrib of the third leaf from the base, which with the petiole was 5 inches in length. The leaf stood up almost vertically, but the tip was deflected, so that the filament projected almost horizontally, and its movements were traced during 48h on a vertical glass as shown in the accompanying figure Fig 95. We here plainly see that the leaf was continually circumnudating, but the proper periodicity of its movements was disturbed by its being only dimly illuminated from above through a double skylight. We infer that this was the case because 2 leaves on plants growing out of doors had their angles above the horizon measured in the middle of the day, and at 9 to about 10p Roman 1000 on successive nights, and they were found at this latter hour to have risen by an average angle of 9 above their midday position. On the following morning, they fell to their former position. Now it may be observed in the diagram that the leaf rose during the second night, so that it stood at 6A Roman 1000 higher than at 10p Roman 1000 on the preceding night, and this may be attributed to the leaf adjusting itself to the dim light coming exclusively from above. Fig 95 Crambe maritima circumnutation of leaf disturbed by being insufficiently illuminated from above, traced from 7A Roman 1000 June 23rd to 8A Roman 1000th apex of leaf, 14 inches from the vertical glass, so that the tracing was much magnified, but is here reduced to 1/4 of original scale. 4 Brassica auracea, cruciferi Hofmeister and Battelin 9 state that the leaves of the cabbage rise at night and fall by day. We covered a young plant bearing 8 leaves under a large bell glass, placing it in the same position with respect to the light in which it had long remained, and a filament was fixed at the distance of 4 of an inch from the apex of a young leaf, nearly 4 inches in length. Its movements were then traced during 3 days, but the tracing is not worth giving. The leaf fell during the whole morning and rose in the evening, and during the early part of the night, the ascending and descending lines did not coincide, so that an irregular ellipse was formed each 24h. The basal part of the midrib did not move, as was ascertained by measuring at successive periods the angle which it formed with the horizon, so that the movement was confined to the terminal portion of the leaf, which moved through an angle of 11 in the course of 24h, and the distance travelled by the apex up and down was between 8 and 9 of an inch. In order to ascertain the effect of darkness, a filament was fixed to a leaf 512 inches in length borne by a plant, which after forming a head had produced a stem. The leaf was inclined 44 above the horizon, and its movements were traced on a vertical glass every hour. By the aid of a taper during the first day, the leaf rose from 8A Roman 1000 to 10p Roman 1000. In a slightly zigzag course, the actual distance travelled by the apex being 67 of an inch during the night, the leaf fell whereas it ought to have risen, and by 7A Roman 1000 on the following morning it had fallen 23 of an inch, and it continued falling until 9A Roman 1000. It then rose until 10p Roman 1000, but the rise was interrupted by one considerable oscillation, that is, by a fall and rescent. During the second night it again fell, but only to a very short distance, and on the following morning reascended to a very short distance. Thus the normal course of the leaf was greatly disturbed, or rather completely inverted, by the absence of light, and the movements were likewise greatly diminished in amplitude. We may add that according to Mr. Stephen Wilson 10, the young leaves of the Swedish turnip, which is a hybrid between Beolracea and Rapa, draw together in the evening so much that the horizontal breadth diminishes about 30% of the daylight breadth, therefore the leaves must rise considerably at night. 5. Dianthus caryophyllus caryophyllae fam 26, the terminal shoot of a young plant growing very vigorously, was selected for observation. The young leaves at first stand up vertically and close together, but they soon bend outwards and downwards so as to become horizontal, and often at the same time a little to one side. A filament was fixed to the tip of a young leaf while still highly inclined, and the first dart was made on the vertical glass at 8A Roman 1000 June 13th, but it curved downwards so quickly that by 6A Roman 1000 on the following morning, it stood only a little above the horizon in Fig 96, the long, slightly zigzag line, representing this rapid downward course, which was somewhat inclined to the left, is not given, but the figure shows the highly tortuous and zigzag course together, with some loops pursued during the next 212 days. As the leaf continued to move all the time to the left, it is evident that the zigzag line represents many circumnutations. Fig 96 Dianthus caryophyllus circumnutation of young leaf, traced from 10p Roman 1000 June 13th to 10p Roman 1000th apex of leaf, stood at the close of our observations, 834 inches from the vertical glass, so tracing not greatly magnified the leaf, was 514 inches long temp, 15,121,712, Roman 1006, Camellia japonica camelliaceae, fam 32A youngish leaf, which together with its petiole was 234 inches in length, and which arose from a side branch on a tall bush, had a filament attached to its apex. This leaf sloped downwards at an angle of 40 beneath the horizon, as it was thick and rigid, and its petiole, very short. Much movement could not be expected. Nevertheless, the apex changed its course completely 7 times in the course of 1112h, but moved to only a very small distance on the next day. The movement of the apex was traced during 26h20 Roman 1000 as shown in Fig 97, and was nearly of the same nature but rather less complex. The movement seems to be periodical, for on both days, the leaf circumnutated in the forenoon, fell in the afternoon on the first day, until between 3 and 4p Roman 1000, and on the second day, until 6p Roman 1000, and then rose, falling again during the night or early morning. Fig 97 Camellia japonica circumnutation of leaf, traced from 6A Roman 1000 June 14th to 6A Roman 1000th apex of leaf, 12 inches from the vertical glass, so figure considerably magnified temp, 161,612, Roman 100. In the chapter on the sleep of plants, we shall see that the leaves in several malvaceous genera sink. Fig 98 Pelargonium zonal circumnutation and downward movement of young leaf, traced from 9A Roman 1000 June 14th to 6p Roman 1000th apex of leaf, 91 inches from the vertical glass, so figure moderately magnified temp, 151,612, Roman 100 at night, and as they often do not then occupy a vertical position, especially if they have not been well illuminated during the day, it is doubtful whether some of these cases ought not to have been included in the present chapter. 7. Pelargonium zonal geraniaceae fam 47A young leaf, 114 inch in breadth, with its petiole 1 inch long borne on a young plant, was observed in the usual manner during 61h, and its course is shown in the preceding figure. Fig 98. During the first day and night the leaf moved downwards, but circumnutated between 10A Roman 1000 and 4p Roman 1000 on the second day. It sank and rose again, but between 10A Roman 1000 and 6p Roman 1000, it circumnutated on an extremely small scale on the third day. The circumnutation was more plainly marked. 8. Cissus discolor ampelide fam 67A leaf, not nearly full-grown, the third from the apex of a shoot on a cut-down plant, was observed during 31h30 Roman 1000 c. Fig 99. The day was cold, 1516 Roman 100. And if the plant had been observed in the hothouse, the circumnutation, though plain enough as it was, would probably have been far more conspicuous. Fig 99 Cissus discolor circumnutation of leaf, traced from 10A Roman 1000 May 28th to 6p Roman 1000th apex of leaf, 834 inches from the vertical glass. 9. Vicia faba leguminosae, fam 75A young leaf, 3 inches in length, measured from base of petiole to end of leaflets, had a filament affixed to the midrib of one of the 2 terminal leaflets, and its movements were traced during 5112H. The filament fell all morning July 2nd till 3p Roman 1000, and then rose greatly till 10p Roman 1000. But the rise this day was so great compared with that which subsequently occurred that it was probably due in part to the plant being illuminated from above. The latter part of the course on July 2nd is alone given in the following figure. Fig. 100. On the next day, July 3rd, the leaf again fell in the morning, then circumnudated in a conspicuous manner, and rose till late at night, but the movement was not traced after 7p Roman 1000, as by that time the filament pointed towards the upper edge of the glass. During the latter part of the night or early morning, it again fell in the same manner as before. As the evening rise and the early morning fall were unusually large, the angle of the petiole above the horizon was measured at the two periods, and the leaf was found to have risen 19 between 12p Roman 1000 and 10p Roman 1000, and to have fallen 23:30 seconds between the latter hour and 10a Roman 1000 on the following morning. Fig. 100. Vischer Faber circumnutation of leaf traced from 7p Roman 1000 July 2nd to 10a Roman 1000th apex of the two terminal leaflets, 7/14 inches from the vertical glass figure here, reduced to 2/3 of original scale. Temp. 1718 Roman 100. The main petiole was now secured to a stick close to the base of the two terminal leaflets, which were 1 inch in length, and the movements of one of them were traced during 48H. See Fig. 101. The course pursued is closely analogous to that of the whole leaf. The zigzag line between 8a Roman 1000 and 3p Roman 1000 on the second day represents 5 very small ellipses with their longer axes differently directed from these observations. It follows that both the whole leaf and the terminal leaflets undergo a well-marked daily periodical movement, rising in the evening and falling during the latter part of the night or early morning, whilst in the middle of the day they generally circumnutate round the same small space. Fig. 101. Vischer Faber circumnutation of one of the two terminal leaflets, the main petiole having been secured traced from 10a Roman 1000 July 4th to 10a Roman 1000th apex of leaflet 6/58 inches from the vertical glass, tracing here reduced to 1/2 of original scale. Temp. 1618 Roman 10,010, Acacia retinoides leguminosae, the movement of a young phyllodes 238 inches in length, and inclined at a considerable angle above the horizon, was traced during 45H 30 Roman 1000, but in the figure here given Fig. 102, its circumnutation is shown during only 21H 30 Roman 1000. During part of this time, viz. 14H 30 Roman 1000, the phyllodes described a figure representing 5 or 6 small ellipses. The actual amount of movement in a vertical direction was 3 inch. The phyllodes rose considerably between 1p Roman 1000 and 4p Roman 1000, but there was no evidence on either day of a regular periodic movement. Fig. 102. Acacia retinoides circumnutation of a young phyllodes traced from 10a Roman 1000 July 18th to 8a Roman 1000th apex of phyllodes 9 inches from the vertical glass. Temp. 16,121,712 Roman 10,011. Lupinus speciosus leguminosae plants were raised from seed purchased under this name. This is one of the species in this large genus, the leaves of which do not sleep at night. The petioles rise direct from the ground and are from 5 to 7 inches in length. A filament was fixed to the midrib of one of the longer leaflets, and the movement of the whole leaf was traced as shown in Fig. 103. In the course of 6H 30 Roman 1000, the filament went 4 times up and 3 times down. A new tracing was then begun, not here given, and during 1212H the leaf moved 8 times up and 7 times down, so that it described 712 ellipses in this time, and this is an extraordinary rate of movement. The summit of the petiole was then secured to a stick, and the separate leaflets were found to be continually circumnudating. Fig. 103. Lupinus speciosus circumnutation of leaf traced on vertical glass from 10a Roman 1000 to 5p Roman 1000 Roman 1e during 6H 30 Roman 100,012. Echeveria stolonifera crassulae fam. 80. For the older leaves of this plant are so thick and fleshy, and the young ones so short and broad, that it seemed very improbable that any circumnutation could be detected. A filament was fixed to a young upwardly inclined leaf, 75 inch in length and 28 in breadth, which stood on the outside of a terminal rosette of leaves produced by a plant growing very vigorously. Its movement was traced during 3 days as here shown. Fig. 104. The course was chiefly in an upward direction, and this may be attributed to the elongation of the leaf through growth, but we see that the lines are strongly zigzag, and that occasionally there was distinct circumnutation, though on a very small scale. Fig 104 Echeveria stolonifera circumnutation of leaf traced from 8A Roman 1000 June 25th to 8A Roman 1000th apex of leaf 12-14 inches from the glass, so that the movement was much magnified. Temp. 230-2412, Roman 10,013 Bryophyllum, vel calanch calicinum, Crassules duvel juve bull soche Bart de France, Feb. 14, 1868, measured the distance between the tips of the upper pair of leaves on this plant. With the result shown in the following table, it should be noted that the measurements on deck second were made on a different pair of leaves. 8A Roman 1000 P Roman 1000 P Roman 1000 Nav, 1615 Roman 2025, Roman 2019 48 60 48 Roman 2000 Dec. 222, 4328. We see from this table that the leaves stood considerably further apart at 2P Roman 1000 than at either 8A Roman 1000 or 7P Roman 1000, and this shows that they rise a little in the evening and fall or open in the forenoon. 14 Drosera rotundifolia droseraceae, Fam. 85 The movements of a young leaf having a long petiole, but with its tentacles or gland-bearing hairs as yet unfolded, were traced during 47H15 Roman 1000. The figure Fig 105 shows that it circumnudated largely chiefly in a vertical direction, making 2 ellipses each day on both days. The leaf began to descend after 12 or 1 o'clock, and continued to do so all night, though to a very unequal distance on the 2 occasions. We therefore thought that the movement was periodic, but on observing 3 other leaves during several successive days and nights, we found this to be an error, and the case is given merely as a caution. On the 3rd morning, the above leaf occupied almost exactly the same position as on the 1st morning, and the tentacles by this time had unfolded sufficiently to project at right angles to the blade or disc. Fig 105 Drosera rotundifolia circumnutation of young leaf, with filament fixed to back of blade traced from 9A Roman 1000 June 7th to 8A Roman 1000 June 9th, figure here reduced to 1/2 original scale. The leaves as they grow older generally sink more and more downwards. The movement of an oldish leaf, the glands of which were still secreting freely, was traced for 24H, during which time it continued to sink a little in a slightly zigzag line. On the following morning, at 7A Roman 1000, a drop of a solution of carbonate of ammonia 2Gr to 1 Rs of water was placed on the disc, and this blackened the glands and induced inflection of many of the tentacles. The weight of the drop caused the leaf at first to sink a little, but immediately afterwards it began to rise in a somewhat zigzag course, and continued to do so till 3P Roman 1000. It then circumnutated about the same spot on a very small scale for 21H, and during the next 21H it sank in a zigzag line to nearly the same level which it had held when the ammonia was first administered. By this time, the tentacles had re-expanded, and the glands had recovered their proper color. We thus learn that an old leaf circumnudates on a small scale at least. Whilst absorbing carbonate of ammonia for it is probable that this absorption may stimulate growth, and thus re-excite circumnutation, whether the rising of the glass filament which was attached to the back of the leaf resulted from its margin becoming slightly inflected as generally occurs, or from the rising of the petiole, was not ascertained. In order to learn whether the tentacles or gland-bearing hairs circumnudate the back of a young leaf with the innermost tentacles, as yet incurved, was firmly cemented with shellac to a flat stick, driven into compact damp argillaceous sand. The plant was placed under a microscope with the stage removed, and with an eyepiece micrometer of which each division equaled 1/1500 of an inch. It should be stated that as the leaves grow older, the tentacles of the exterior rows bend outwards and downwards, so as ultimately to become deflected considerably beneath the horizon. A tentacle in the second row from the margin was selected for observation, and was found to be moving outwards at a rate of 1/1500 of an inch in 20 Roman 1000 or 1100 of inch in 1H 40 Roman 1000, but as it likewise moved from side to side to an extent of above 1/1500 of inch, the movement was probably one of modified circumnutation. A tentacle on an old leaf was next observed in the same manner in 15 Roman 1000. After being placed under the microscope, it had moved about 11,000 of an inch. During the next 712H it was looked at repeatedly, and during this whole time it moved only another 11,000 of an inch, and this small movement may have been due to the settling of the damp sand, on which the plant rested. Though the sand had been firmly pressed down, we may therefore conclude that the tentacles when old do not circumnudate. yet this tentacle was so sensitive that in 23 seconds after its gland had been merely touched with a bit of raw meat, it began to curl inwards. This fact is of some importance, as it apparently shows that the inflection of the tentacles from the stimulus of absorbed animal matter, and no doubt from that of contact with any object, is not due to modified circumnutation. 15. Dionea marcipula droseraceae. It should be premised that the leaves at an early stage of their development have the two lobes pressed closely together. These are at first directed back towards the center of the plant, but they gradually rise up and soon stand at right angles to the petiole, and ultimately in nearly a straight line with it. A young leaf which with the petiole was only 1 inch in length had a filament fixed externally along the midrib of the still closed lobes which projected at right angles to the petiole in the evening. This leaf completed an ellipse in the course of 2h on the following day, Sept. 25th. Its movements were traced during 22h, and we see in Fig. 106 that it moved in the same general direction due to the straightening of the leaf, but in an extremely zigzag line. This line represents several drawn-out or modified ellipses. There can therefore be no doubt that this young leaf circumnuted. Fig. 106. Dionea marcipula circumnutation of a young and expanding leaf, traced on a horizontal glass in darkness, from noon Sept. 24th to 10 A Roman 1000th apex, of leaf 13-12 inches from the glass, so tracing considerably magnified. A rather old horizontally extended leaf with a filament attached along the underside of the midrib was next observed during 7h. It hardly moved, but when one of its sensitive hairs was touched the blades closed, though not very quickly. A new dart was now made on the glass, but in the course of 14h 20 Roman 1000 there was hardly any change in the position of the filament. We may therefore infer that an old and only moderately sensitive leaf does not circumnudate plainly, but we shall soon see that it by no means follows that such a leaf is absolutely motionless. We may further infer that the stimulus from a touch does not re-excite plain circumnutation. Another full-grown leaf had a filament attached externally along one side of the midrib and parallel to it, so that the filament would move if the lobes closed. It should be first stated that although a touch on one of the sensitive hairs of a vigorous leaf causes it to close quickly, often almost instantly, yet when a bit of damp meat or some solution of carbonate of ammonia is placed on the lobes, they close so slowly that generally 24h is required for the completion of the act. The above leaf was first observed for 2h 30 Roman 1000 and did not circumnutate, but it ought to have been observed for a longer period, although as we have seen a young leaf completed a fairly large ellipse in 2h. A drop of an infusion of raw meat was then placed on the leaf, and within 2h the glass filament rose a little, and this implies that the lobes had begun to close and perhaps the petiole to rise. It continued to rise with extreme slowness for the next 8h 30 Roman 1000. The position of the part was then 7 P Roman 1000, Sept. 24th slightly changed, and an additional drop of the infusion given, and a new tracing was begun. Fig. 107, by 10 P Roman 1000. The filament had risen only a little more, and it fell during the night. On the following morning, the lobes were closing more quickly, and by 5 P Roman 1000 it was evident to the eye that they had closed considerably. By 8 P Roman 1000, this was still plainer, and by 10 P Roman 1000 the marginal spikes were interlocked. The leaf fell a little during the night, and next morning 25th at 7 A Roman 1000, the lobes were completely shut. The course pursued, as may be seen in the figure, was strongly zigzag, and this indicates that the closing of the lobes was combined with the circumnutation of the whole leaf, and there cannot be much doubt, considering how motionless the leaf was during 2h 30 Roman 1000 before it received the infusion, that the absorption of the animal matter had excited it to circumnudate. The leaf was occasionally observed for the next 4 days, but was kept in rather too cool a place. Nevertheless, it continued to circumnudate to a small extent, and the lobes remained closed. Fig. 107, Dionea marcipula closure of the lobes and circumnutation of a full-grown leaf, whilst absorbing an infusion of raw meat traced in darkness, from 7 P Roman 1000, Sept. 24th, to 9 A Roman 1000th apex, of leaf 812 inches, from the vertical glass figure here, reduced to 2/3 of original scale. It is sometimes stated in botanical works that the lobes close or sleep at night, but this is an error. To test the statement, very long glass filaments were fixed inside the two lobes of 3 leaves, and the distances between their tips were measured in the middle of the day, and at night, but no difference could be detected. The previous observations relate to the movements of the whole leaf, but the lobes move independently of the petiole, and seemed to be continually opening and shutting to a very small extent. A nearly full-grown leaf afterwards proved to be highly sensitive to contact, stood almost horizontally, so that by driving a long thin pin through the foliaceous petiole close to the blade, it was rendered motionless. The plant, with a little triangle of paper attached to one of the marginal spikes, was placed under microscope with an eyepiece micrometer, each division of which equaled 1/1500 of an inch. The apex of the paper triangle was now seen to be in constant slight movement, for in 4h it crossed 9 divisions, or 9500 of an inch, and after 10 additional hours it moved back and had crossed 5500 in an opposite direction. The plant was kept in rather too cool a place, and on the following day it moved rather less, namely 1500 in 3h and 2500 in an opposite direction. During the next 6h, the two lobes therefore seemed to be constantly closing or opening, though to a very small distance, for we must remember that the little triangle of paper affixed to the marginal spike increased its length, and thus exaggerated somewhat the movement. Similar observations, with the important difference that the petiole was left free, and the plant kept under a high temperature, were made on a leaf which was healthy, but so old that it did not close when its sensitive hairs were repeatedly touched, though judging from other cases it would have slowly closed if it had been stimulated by animal matter. The apex of the triangle was in almost, though not quite, constant movement, sometimes in one direction, and sometimes in an opposite one, and it thrice crossed 5 divisions of the micrometer Roman 1e, 1100 of an inch in 30 Roman 1000. This movement on so small a scale is hardly comparable with ordinary circumnutation, but it may perhaps be compared with the zigzag lines and little loops by which the larger ellipses made by other plants are often interrupted. In the first chapter of this volume, the remarkable oscillatory movements of the circumnudating hypocotyl of the cabbage have been described. The leaves of Dionea present the same phenomenon, which is a wonderful one as viewed under a low-power 2-inch object glass with an eyepiece micrometer, of which each division 1500 of an inch appeared as a rather wide space. The young unexpanded leaf of which the circumnudating movements were traced, Fig. 106, had a glass filament fixed perpendicularly to it, and the movement of the apex was observed in the hothouse temp AD 4 to AD 6F, with light admitted only from above, and with any lateral currents of air excluded. The apex sometimes crossed 1 or 2 divisions of the micrometer at an imperceptibly slow rate, but generally it moved onwards by rapid starts or jerks of 21,000 or 31,000, and in one instance of 41,000 of an inch. After each jerk forwards, the apex drew itself backwards with comparative slowness for part of the distance which had just been gained, and then after a very short time made another jerk forwards. 4 conspicuous jerks forwards, with slower retreats, were seen on one occasion to occur in exactly 1 minute, besides some minor oscillations. As far as we could judge, the advancing and retreating lines did not coincide, and if so, extremely minute ellipses were each time described. Sometimes the apex remained quite motionless for a short period. Its general course during the several hours of observation was in 2 opposite directions, so that the leaf was probably circumnudating. An older leaf with the lobes fully expanded, and which was afterwards proved to be highly sensitive to contact, was next observed in a similar manner, except that the plant was exposed to a lower temperature in a room. The apex oscillated forwards and backwards in the same manner as before, but the jerks forward were less in extent, viz. about 11,000 inch, and there were longer motionless periods, as it appeared possible that the movements might be due to currents of air. A wax taper was held close to the leaf during one of the motionless periods, but no oscillations were thus caused. After 10 Roman 1000, however, vigorous oscillations commenced, perhaps owing to the plant having been warmed and thus stimulated. The candle was then removed, and before long the oscillations ceased. Nevertheless, when looked at again, after an interval of 1h 30 Roman 1000, it was again oscillating. The plant was taken back into the hothouse, and on the following morning was seen to be oscillating, though not very vigorously. Another old but healthy leaf, which was not in the least sensitive to touch, was likewise observed during 2 days in the hothouse, and the attached filament made many little jerks forwards of about 21,000 or only 11,000 of an inch. Finally, to ascertain whether the lobes independently of the petiole oscillated, the petiole of an old leaf was cemented close to the blade with shellac to the top of a little stick, driven into the soil, but before this was done, the leaf was observed and found to be vigorously oscillating or jerking, and after it had been cemented to the stick, the oscillations of about 21,000 of an inch still continued. On the following day, a little infusion of raw meat was placed on the leaf, which caused the lobes to close together very slowly in the course of 2 days, and the oscillations continued during this whole time. And for the next 2 days after 9 additional days, the leaf began to open, and the margins were a little everted, and now the apex of the glass filament remained for long periods motionless, and then moved backwards and forwards for a distance of about 11,000 of an inch slowly, without any jerks. Nevertheless, after warming the leaf with a taper held close to it, the jerking movement recommenced. This same leaf had been observed 212 months previously, and was then found to be oscillating or jerking. We may therefore infer that this kind of movement goes on night and day for a very long period, and it is common to young unexpanded leaves, and to leaves so old as to have lost their sensitiveness to a touch, but which were still capable of absorbing nitrogenous matter. The phenomenon, when well displayed, as in the young leaf just described, is a very interesting one. It often brought before our minds the idea of effort, or of a small animal struggling to escape from some constraint. 16 Eucalyptus racinifera myrtaceae, FAM 94A, young leaf 2 inches in length, together with the petiole produced by a lateral shoot from a cut-down tree, was observed in the usual manner. The blade had not as yet assumed its vertical position on June 7th, only a few observations were made, and the tracing merely showed that the leaf had moved 3 times upwards and 3 downwards on the following day. It was observed more frequently, and 2 tracings were made C-A and B, Fig 108, as a single one would have been too complicated. The apex changed its course 13 times in the course of 16H, chiefly up and down, but with some lateral movement. The actual amount of movement in any one direction was small. Fig 108 Eucalyptus racinifera circumnutation of a leaf traced A from 6 A Roman 1000 to 1 P Roman 1000 June 8th, B from 1 P Roman 1000th to 8 A Roman 1000th apex of leaf, 14-12 inches from the horizontal glass, so figures considerably magnify. 17 Dahlia garden var composite FAM 122A, fine young leaf, 5-34 inches in length, produced by a young plant 2 feet high growing vigorously in a large pot, was directed at an angle of about 45 beneath the horizon on June 18th. The leaf descended from 10 A Roman 1000 till 11 A Roman 1000 C, Fig 109. It then ascended greatly till 6 P Roman 1000, this ascent being probably due to the light coming only from above it, zigzagged between 6 P Roman 1000 and 10 P Roman 1000, and ascended a little during the night. It should be remarked that the vertical distances in the lower part of the diagram are much exaggerated, as the leaf was at first deflected beneath the horizon, and after it had sunk downwards the filament pointed in a very oblique line towards the glass. Next day, the leaf descended from 8 A Roman 1000 till 7 P Roman 1000, then zigzagged, and ascended greatly during the night. On the morning of the 20th, the leaf was probably beginning to descend, though the short line in the diagram is horizontal. The actual distances travelled by the apex of the leaf were considerable, but could not be calculated with safety from the course pursued on the second day, when the plant had accommodated itself to the light. From above there cannot be much doubt that the leaves undergo a daily periodic movement, sinking during the day and rising at night. Fig 109 Dahlia circumnutation of leaf, traced from 10 A Roman 1000 June 18th to 8 A Roman 1000th, but with a break of 1H 40 Roman 1000 on the morning of the 19th, as owing to the glass filament pointing too much to one side, the pot had to be slightly moved. Therefore, the relative position of the 2 tracings is somewhat arbitrary. The figure here given is reduced to 1/5 of the original scale apex of leaf 9 inches from the glass in the line of its inclination, and 434 in a horizontal line. 18 Mutisia clematis composite, the leaves terminate in tendrils and circumnudate like those of other tendril bearers, but this plant is here mentioned on account of an erroneous statement, 11 which has been published, namely, that the leaves sink at night and rise during the day. The leaves which behaved in this manner had been kept for some days in a northern room and had not been sufficiently illuminated. A plant therefore was left undisturbed in the hothouse, and 3 leaves had their angles measured at noon, and at 10 P Roman 1000 all 3 were inclined a little beneath the horizon at noon, but one stood at night 2, the second 21, and the third 10 higher than in the middle of the day, so that instead of sinking they rise a little at night. 19 Cyclamen persicum primulaceae FAM 135, a young leaf, 1 of an inch in length, petiole included, produced by an old rootstock, was observed during 3 days in the usual manner. Fig. 110 on the first day, The leaf fell more than afterwards, apparently from adjusting itself to the light from above. On all 3 days it fell from the early morning to about 7 p. Roman 1000, and from that hour rose during the night, the course being slightly zigzag. The movement therefore is strictly periodic. It should be noted that the leaf would have sunk each evening a little lower down than it did had not the glass filament rested between 5 and 6 p. Roman 1000 on the rim of the pot. The amount of movement was considerable, for if we assume that the whole leaf to the base of the petiole became bent, the tracing would be magnified rather less than 5 times, and this would give to the apex a rise and fall of half an inch, with some lateral movement. This amount, however, would not attract attention without the aid of a tracing or measurement of some kind. 20 Alamander scotii Aparsony fam. 140. 4. The young leaves of this shrub are elongated with the blade bowed so much downwards as almost to form a semicircle. The chord that is a line drawn from the apex of the blade to the base of the petiole of a young leaf for 34 inches in length stood at 2 p. Roman 1000 on deck 5th, at an angle of 13 beneath the horizon, but by 9 p. Roman 1000 the blade had straightened itself so much, which implies the raising of the apex, that the chord now stood at 37 above the horizon, and had therefore risen 50 on the next day. Similar angular measurements of the same leaf were made, and at noon the chord stood 36 beneath the horizon, and 9 p. Roman 10,002 above it, so had risen 39:12. The chief cause of the rising movement lies in the straightening of the blade, but the short petiole rises between 4 and 5 on the third night. The chord stood at 35 above the horizon, and if the leaf occupied the same position at noon as on the previous day, it had risen 71. With older leaves no such chain of curvature could be detected. The plant was then brought into the house and kept in a northeast room, but at night there was no change in the curvature of the young leaves, so that previous exposure to a strong light is apparently requisite for the periodical change of curvature in the blade, and for the slight rising of the petiole. Fig. 110 Cyclamen persicum circumnutation of leaf traced from 6 A Roman 1000 June 2nd to 6 A Roman 1000th apex of leaf, 7 inches from the vertical glass. 21 Wigandia hydrolacea fam. 149 Professor Pfeffer informs us that the leaves of this plant rise in the evening, but as we do not know whether or not the rising is great, this species ought perhaps to be classed amongst sleeping plants. Fig. 111 Petunia violacea downward movement and circumnutation of a very young leaf traced from 10 A Roman 1000 June 2nd to 9 A Roman 1000 June 6th. N-bat 6 A Roman 1000. On the 5th it was necessary to move the part a little, and a new tracing was begun at the point where 2 dots are not joined in the diagram apex of leaf 7 inches from the vertical glass temp, generally 1712 Roman 10,022, Petunia violacea salini fam. 157. A very young leaf, only 34 inch in length, highly inclined upwards, was observed for 4 days. During the whole of this time it bent outwards and downwards, so as to become more and more nearly horizontal. The strongly marked zigzag line in the figure on p. 248 Fig. 111 shows that this was effected by modified circumnutation, and during the latter part of the time there was much ordinary circumnutation on a small scale. The movement in the diagram is magnified between 10 and 11 times. It exhibits a clear trace of periodicity, as the leaf rose a little each evening, but this upward tendency appeared to be almost conquered by the leaf striving to become more and more horizontal. As it grew older, the angles which 2 older leaves formed together were measured in the evening, and about noon on 3 successive days, and each night the angle decreased a little, though irregularly. Fig. 112 Acanthus Marley's circumnutation of young leaf traced from 9 A Roman 1000 June 14th to 8 A Roman 1000th apex of leaf, 11 inches from the vertical glass, so movement considerably magnified. Figure here, reduced to 1/2 of original scale temp, 151,612, Roman 10,023, Acanthus Marley's Acanthaceae fam. 168, the younger of 2 leaves, 14 inches in length petiole included, produced by a seedling plant, was observed during 47h early on each of the 3 mornings. The apex of the leaf fell, and it continued to fall till 3 p. Roman 1000 on the 2 afternoons. When observed after 3 p. Roman 1000, it rose considerably, and continued to rise on the second night until the early morning, but on the first night it fell instead of rising, and we have little doubt that this was owing to the leaf being very young, and becoming through epinastic growth more and more horizontal, for it may be seen in the diagram Fig. 112 that the leaf stood on a higher level on the first, than on the second day the leaves of an allied species. A Spinosus certainly rose every night, and the rise between noon and 10 p. Roman 1000, when measured on one occasion, was 10. This rise was chiefly or exclusively due to the straightening of the blade, and not to the movement of the petiole. We may therefore conclude that the leaves of acanthus circumnudate periodically, falling in the morning and rising in the afternoon and night. 24. Cannabis sativa cannabini, fam. 195. We have here the rare case of leaves moving downwards in the evening, but not to a sufficient degree to be called sleep 12 in the early morning, or in the latter part of the night. They move upwards. For instance, all the young leaves near the summits of several stems stood almost horizontally at 8 a Roman 1000 May 29th, and at 10 p Roman 1000 were considerably declined on a subsequent day too. Leaves stood at 2 p Roman 1000 at 21 and 12 beneath the horizon, and at 10 p Roman 1000 at 38 beneath it. Two other leaves on a younger plant were horizontal at 2 p Roman 1000, and at 10 p Roman 1000 had sunk to 36 beneath the horizon. With respect to this downward movement of the leaves, Krauss believes that it is due to their epinastic growth. He adds that the leaves are relaxed during the day and tense at night, both in sunny and rainy weather. 25. Pinus pinaster conifer, fam. 223. The leaves on the summits of the terminal shoots stand at first in a bundle almost upright, but they soon diverge and ultimately become almost horizontal. The movements of a young leaf, nearly 1 inch in length, on the summit of a seedling plant, only 3 inches high, were traced from the early morning of June 2nd to the evening of the 7th. During these 5 days the leaf diverged, and its apex descended at first in an almost straight line, but during the 2 latter days it zigzagged so much that it was evidently circumnudating the same little plant. When grown to a height of 5 inches was again observed during 4 days. A filament was fixed transversely to the apex of a leaf 1 inch in length, and, which had already diverged considerably from its originally upright position, it continued to diverge, see a Fig 113, and to descend from 11 a Roman 1000 July 31st to 6 a Roman 1000 Aug. 1st. On August 1st, it circumnudated about the same small space and again descended at night. Next morning, the part was moved nearly 1 inch to the right, and a new tracing was begun b from this time, viz. 7 a Roman 1000 August 2nd to 8 a Roman 1000 on the 4th. The leaf manifestly circumnudated. It does not appear from the diagram that the leaves move periodically, for the descending course during the first 2 nights was clearly due to epinastic growth, and at the close of our observations, the leaf was not nearly so horizontal as it would ultimately become. Fig 113. Pinus pinaster circumnutation of young leaf traced from 11 a Roman 1000 July 31st to 8 a Roman 1000 Aug. 4th, at 7 a Roman 1000 Aug. 2nd. The part was moved an inch to one side, so that the tracing consists of 2 figures. Apex of leaf 14-12 inches from the vertical glass, so movements much magnified. Pinus austriaca 2, leaves 3 inches in length, but not quite fully grown, produced by a lateral shoot on a young tree 3 feet in height, were observed during 29h, July 31st in the same manner as the leaves of the previous species. Both these leaves certainly circumnudated, making within the above period 2 or 2.5 small irregular ellipses. 26. Cycas pectinata cycade, fam. 224. A young leaf, 11-12 inches in length, of which the leaflets had only recently become uncurled, was observed during 47h 30 Roman 1000. The main petiole was secured to a stick at the base of the 2 terminal leaflets, to one of the latter 3.34 inches in length. A filament was fixed. The leaflet was much bowed downward, but as the terminal part was upturned, the filament projected almost horizontally. The leaflet moved, see Fig 114, largely and periodically, for it fell until about 7 p Roman 1000, and rose during the night, falling again next morning after 6 a Roman 1000. The descending lines are in a marked manner zigzag, and so probably would have been the ascending lines if they had been traced throughout the night. Fig 114. Cycas pectinata circumnutation of one of the terminal leaflets traced from 8 a Roman 1000 June 22nd to 8 a Roman 1000 June 24th, apex of leaflet 7.34 inches from the vertical glass, so tracing not greatly magnified, and here reduced to 1/3 of original scale. Temp. 1921. Roman 100. Circumnutation of leaves monocotyledons. 27. Canna warsuixii canaceae, fam. 2. The movements of a young leaf 8 inches in length and 312 in breadth, produced by a vigorous young plant, were observed during 45h 50 Roman 1000 as shown in Fig 115. The part was slided about an inch to the right on the morning of the 11th, as a single figure would have been too complicated, but the two figures are continuous in time. The movement is periodical as the leaf descended from the early morning until about 5 p. Roman 1000, and ascended during the rest of the evening and part of the night on the evening of the 11th. It circumnuted on a small scale for some time about the same spot. Fig 115, can a Warsuixii circumnutation of leaf, traced A from 11 A Roman 1000 June 10th to 6 A Roman 1000th, and B from 6 A Roman 1000th to 8 A Roman 1000th apex of leaf 9 inches from the vertical glass. 28 Iris pseudoacorus iridi fam 10, the movements of a young leaf rising 13 inches above the water in which the plant grew were traced as shown in the figure Fig 116, during 27 H 30 Roman 1000. It manifestly circumnuted, though only to a small extent, on the second morning, between 6 A Roman 1000 and 2 P Roman 1000, at which latter hour the figure here given ends. The apex changed its course 5 times during the next 8 H 40 Roman 1000. It zigzagged much and descended as far as the lowest dot in the figure, making in its course 2 very small ellipses. But if these lines had been added to the diagram, it would have been too complex. Fig 116, Iris pseudoacorus circumnutation of leaf traced from 10 A Roman 1000 May 28th to 2 P Roman 1000th tracing, continued to 11 P Roman 1000, but not here. Carpid apex of leaf 12 inches beneath the horizontal glass, so figure considerably magnified. Temp 1516 Roman 10,029, Crinum capens amaryllide, fam 11. The leaves of this plant are remarkable for their great length and narrowness. One was measured and found to be 53 inches long, and only one broad at the base. Whilst quite young they stand up almost vertically to the height of about a foot. Afterwards, their tips begin to bend over and subsequently hang vertically down, and thus continue to grow. A rather young leaf was selected, of which the dependent tapering point was as yet only 512 inches in length, the upright basal part being 20 inches high, though this part would ultimately become shorter by being more bent over. A large bell glass was placed over the plant with a black dot on one side, and by bringing the dependent apex of the leaf into a line with this dot, the accompanying figure, Fig 117, was traced on the other side of the bell during 212 days. During the first day, 22nd, the tip travelled laterally far to the left, perhaps in consequence of the plant having been disturbed, and the last dot made at 10 P Roman 1000 on this day is alone here given. As we see in the figure, there can be no doubt that the apex of this leaf circumnuted. Fig 117, Crinum capens circumnutation of dependent tip of young leaf, traced on a bell glass from 10 P Roman 1000 May 22nd to 10 A Roman 1000th, figure not greatly magnified. A glass filament with little triangles of paper was at the same time fixed obliquely across the tip of a still younger leaf, which stood vertically up, and was as yet straight. Its movements were traced from 3 P Roman 1000 May 22nd to 10 A Roman 1000th. The leaf was growing rapidly, so that the apex ascended greatly during this period. As it zigzagged much, it was clearly circumnudating, and it apparently tended to form one ellipse each day. The lines traced during the night were much more vertical than those traced during the day, and this indicates that the tracing would have exhibited a nocturnal rise and a diurnal fall if the leaf had not grown so quickly. The movement of this same leaf, after an interval of 6 days, May 31st, by which time the tip had curved outwards into a horizontal position, and had thus made the first step towards becoming dependent, was traced orthogonically by the aid of a cube of wood in the manner before explained, and it was thus ascertained that the actual distance travelled by the apex, and due to circumnutation, was 318 inches in the course of 2012 H. During the next 24 H, it travelled 212 inches. The circumnudating movement, therefore, of this young leaf was strongly marked. 30 Pancratium littoral amaryllide, the movements much magnified of a leaf 9 inches in length, and inclined at about 45 above the horizon, were traced during 2 days. On the first day, it changed its course completely upwards and downwards, and laterally 9 times in 12 H, and the figure traced apparently represented 5 ellipses. On the second day, it was observed seldomer, and was therefore not seen to change its course so often, viz. Only 6 times, but in the same complex manner as before. The movements were small in extent, but there could be no doubt about the circumnutation of the leaf. 31 Ematophyllum velclivia sp amaryllide, a long glass filament was fixed to a leaf, and the angle formed by it with the horizon was measured occasionally during 3 successive days. It fell each morning until between 3 and 4 p. Roman 1000, and rose at night. The smallest angle at any time above the horizon was 48, and the largest 50, so that it rose only 2 at night, but as this was observed each day, and as similar observations were nightly made on another leaf on a distinct plant, there can be no doubt that the leaves move periodically, though to a very small extent. The position of the apex when it stood highest was 1/8 of an inch above its lowest point. 32 Pistis stratiotes aredi fam. 30 Hofmeister remarks that the leaves of this floating water plant are more highly inclined at night than by day. 13. We therefore fastened a fine glass filament to the midrib of a moderately young leaf, and on Sept. 19th measured the angle which it formed with the horizon 14 times between 9 A Roman 1000 and 11 P Roman 1000. The temperature of the hothouse varied during the 2 days of observation between 1812 and 2312 Roman 100. At 9 A Roman 1000, the filament stood at 32 above the horizon at 3 P Roman 1000 at 10, and at 11 P Roman 1000 at 55, these two latter angles being the highest and the lowest observed during the day show difference of 45. The rising did not become strongly marked until between 5 and 6 P Roman 1000. On the next day, the leaf stood at only 10 above the horizon at 8 A Roman 1000, and it remained at about 15 till past 3 P Roman 1000. At 5 P Roman 1000, it was 23, and at 9 P Roman 1000, so that the rise was more sudden this evening than on the previous one, and the difference in the angle amounted to 48. The movement is obviously periodical, and as the leaf stood on the first night at 55, and on the second night at 58 above the horizon, it appeared very steeply inclined. This case, as we shall see in a future chapter, ought perhaps to have been included under the head of sleeping plants. 33 Pontederia sp. From the highlands of St. Catharina, Brazil, Pontederiaceae fam. 46 A filament was fixed across the apex of a moderately young leaf 712 inches in height, and its movements were traced during 4212 HC Fig. 118 on the first evening when the tracing was begun, and during the night the leaf descended considerably. On the next morning, it ascended in a strongly marked zigzag line, and descended again in the evening and during the night. The movement therefore seems to be periodic, but some doubt is thrown on this conclusion, because another leaf 8 inches in height, appearing older and standing more highly inclined, behaved differently during the first 12 H. It circumnudated over a small space, but during the night and the whole following day it ascended in the same general direction, the ascent being affected by repeated up and down well-pronounced oscillations. Fig. 118 Pontederia sp. Circumnutation of leaf traced from 4 P Roman 1000 July 2nd to 10 A Roman 1000th apex of leaf 1612 inches from the vertical glass, so tracing greatly magnified temp about 17 Roman 100, and therefore rather too low. Cryptogams 34 Nephrodium malphilices fam. 1A filament was fixed near the apex of a young frond of this fern 17 inches in height, which was not as yet fully uncurled, and its movements were traced during 24 H. We see in Fig. 119 that it plainly circumnudated. The movement was not greatly magnified, as the frond was placed near to the vertical glass, and would probably have been greater and more rapid had the day been warmer, for the plant was brought out of a warm greenhouse and observed under a skylight where the temperature was between 15 and 16 Roman 100. We have seen in Chap Roman 1 that a frond of this fern, as yet only slightly lobed, and with a rachis only 23 inch in height, plainly circumnudated. 14. Fig. 119 Nephrodium mal circumnutation of rachis, traced from 9 A Roman 1000 May 28th to 9 A Roman 1000th. Figure here, given 2/3 of original scale. In the chapter on the sleep of plants, the conspicuous circumnutation of Marsilia quadrifoliata Marsiliaceae fam. 4 will be described. It has also been shown in Chap Roman 1 that a very young Selaginella lycopodiace fam. 6 only 4 inch in height, plainly circumnudated. We may therefore conclude that older plants whilst growing would do the same. 35 Lunularia vulgaris hepatici fam. 11 Muscles. The earth in an old flower pot was coated with this plant bearing gemmy, a highly inclined frond, which projected 3 inch above the soil, and was 4 inch in breadth, was selected for observation. A glass hair of extreme tenuity 75 inch in length with its end whitened, was cemented with shellac to the frond at right angles to its breadth. and a white stick with a minute black spot was driven into the soil close behind the end of the hair. The white end could be accurately brought into a line with the black spot, and dots could thus be successively made on the vertical glass plate. In front, any movement of the frond would of course be exhibited and increased by the long glass hair, and the black spot was placed so close behind the end of the hair, relatively to the distance of the glass plate, in front that the movement of the end was magnified about 40 times. Nevertheless, we are convinced that our tracing gives a fairly faithful representation of the movements of the frond in the intervals between each observation. The plant was covered by a small belglass. The frond, as already stated, was highly inclined, and the pot stood in front of a northeast window. During the 5 first days, the frond moved downwards, or became less inclined, and the long line which was traced was strongly zigzag, with loops occasionally formed or nearly formed, and this indicated circumnutation. Whether the sinking was due to epinastic growth or a pheliotropism, we do not know, as the sinking was slight on the 5th day. A new tracing was begun on the 6th day, Oct. 25th, and was continued for 47h. It is here given Fig. 120. Another tracing was made on the next day, 27th, and the frond was found to be still circumnudating, for during 14h 30 Roman 1000, it changed its course completely. Besides minor changes 10 times, it was casually observed for 2 more days, and was seen to be continually moving. Fig. 120. Lunularia vulgaris circumnutation of a frond traced from 9a Roman 1000 Oct. 25th to 8a Roman 1000th. The lowest members of the vegetable series, the thalagens, apparently circumnudate. If an oscillaria be watched under the microscope, it may be seen to describe circles about every 40 seconds after it has bent to one side. The tip first begins to bend back to the opposite side, and then the whole filament curves over in the same direction. Hofmeister 15 has given a minute account of the curious, but less regular though constant movements of Spirogyra during 212h. The filament moved 4 times to the left and 3 times to the right, and he refers to a movement at right angles to the above. The tip moved at the rate of about 0 Roman 2000 in 5 minutes. He compares the movement with the nutation of the higher plants. 16. We shall hereafter see that heliotropic movements result from modified circumnutation, and as unicellular molds bend to the light, we may infer that they also circumnudate. Concluding remarks on the circumnutation of leaves. The circumnutating movements of young leaves in 33 genera, belonging to 25 families, widely distributed amongst ordinary and gymnospermous dicotyledons, and amongst monocotyledons together with several cryptogams, have now been described. It would therefore not be rash to assume that the growing leaves of all plants circumnudate, as we have seen reason to conclude. Is the case with cotyledons. The seat of movement generally lies in the petiole, but sometimes both in the petiole and blade, or in the blade alone. The extent of the movement differed much. Different plants, but the distance passed over was never great except with pistia, which ought perhaps to have been included amongst sleeping plants. The angular movement of the leaves was only occasionally measured. It commonly varied from only 2 and probably even less in some instances to about 10, but it amounted to 23 in the common bean. The movement is chiefly in a vertical plane, but as the ascending and descending lines never coincided, there was always some lateral movement, and thus irregular ellipses were formed. The movement therefore deserves to be called one of circumnutation, for all circumnudating organs tend to describe ellipsis. That is, growth on one side is succeeded by growth on nearly, but not quite the opposite side. The ellipses, or the zigzag lines representing drawn-out ellipses, are generally very narrow, yet with the camellia their minor axes were half as long, and with the eucalyptus more than half as long as their major axes. In the case of cissus, parts of the figure more nearly represented circles than ellipses. The amount of lateral movement is therefore sometimes considerable. Moreover, the longer axes of the successively formed ellipses, as with the bean, cissus and secale, and in several instances the zigzag lines representing ellipses, were extended in very different directions during the same day, or on the next day. The course followed was curvilinear or straight, or slightly or strongly zigzag, and little loops or triangles were often formed. A single large irregular ellipse may be described on one day, and 2 smaller ones by the same plant on the next day. With Drosera too, and with lupinous eucalyptus and pancratium, several were formed each day. The oscillatory and jerking movements of the leaves of Dionea, which resemble those of the hypocotyl of the cabbage, are highly remarkable as seen under the microscope. They continue night and day for some months, and are displayed by young unexpanded leaves, and by old ones which have lost their sensibility to a touch. but which after absorbing animal matter close their lobes. We shall hereafter meet with the same kind of movement in the joints of certain gramine, and it is probably common to many plants, while circumnudating it is therefore a strange fact that no such movement could be detected in the tentacles of Drosera rotundifolia, though a member of the same family with Dionea. Yet the tentacle which was observed was so sensitive that it began to curl inwards in 23 seconds after being touched by a bit of raw meat. One of the most interesting facts with respect to the circumnutation of leaves is the periodicity of their movements, for they often, or even generally, rise a little in the evening and early part of the night, and sink again on the following morning. Exactly the same phenomenon was observed in the case of cotyledons. The leaves in 16 genera, out of the 33, which were observed behaved in this manner, as did probably 2 others, nor must it be supposed that in the remaining 15 genera there was no periodicity in their movements, for 6 of them were observed during too short a period for any judgment to be formed on this head, and 3 were so young that their epinastic growth, which serves to bring them down into a horizontal position, overpowered every other kind of movement in only one genus, Cannabis. Did the leaves sink in the evening, and Krauss attributes this movement to the prepotency of their epinastic growth, that the periodicity is determined by the daily alternations of light and darkness. There can hardly be a doubt, as will hereafter be shown. Insectivorous plants are very little affected as far as their movements are concerned by light, and hence probably it is that their leaves, at least in the cases of Sarracenia drosera and Dionea, do not move periodically. The upward movement in the evening is at first slow, and with different plants begins at very different hours, with Glossium as early as 11 A Roman 1000, commonly between 3 and 5 P Roman 1000, but sometimes as late as 7 P Roman 1000. It should be observed that none of the leaves described in this chapter, except as we believe those of Lupinus speciosus, possess a pulvinus for the periodical movements of leaves thus provided have generally been amplified into so-called sleep movements, with which we are not here concerned. The fact of leaves and cotyledons frequently, or even generally rising a little in the evening and sinking in the morning, is of interest, as giving the foundation from which the specialized sleep movements of many leaves and cotyledons not provided with a pulvinus have been developed. The above periodicity should be kept in mind by anyone considering the problem of the horizontal position of leaves and cotyledons during the day whilst illuminated from above. Chapter Roman 5 Modified circumnutation, climbing plants' epinastic and hyponastic movements. Circumnutation modified through innate causes, or through the action of external conditions. Innate causes climbing plants, similarity of their movements with those of ordinary plants, increased amplitude, occasional points of difference, epinastic growth of young leaves, hyponastic growth of the hypocotyls and epicotyls of seedlings, hook tips of climbing and other plants, due to modified circumnutation. Ampelopsis, Tricuspidata smithia, fundii, straightening of the tip, due to hyponasty. Epinastic growth and circumnutation of the flower peduncles of Trifolium repens and Oxalis carnosa. The radicals, hypocotyls and epicotyls of seedling plants, even before they emerge from the ground and afterwards, the cotyledons are all continually circumnudating. So it is with the stems, stolons, flower peduncles, and leaves of older plants. We may therefore infer with a considerable degree of safety that all the growing parts of all plants circumnudate, although this movement in its ordinary or unmodified state appears in some cases to be of service to plants either directly or indirectly. For instance, the circumnutation of the radical in penetrating the ground, or that of the arched hypocotyl and epicotyl in breaking through the surface. Yet circumnutation is so general, or rather so universal a phenomenon, that we cannot suppose it to have been gained for any special purpose. We must believe that it follows in some unknown way from the manner in which vegetable tissues grow. We shall now consider the many cases in which circumnutation has been modified for various special purposes, that is, a movement already in progress is temporarily increased in some one direction, and temporarily diminished or quite arrested in other directions. These cases may be divided in 2 subclasses, in one of which the modification depends on innate or constitutional causes, and is independent of external conditions, excepting in so far that the proper ones for growth must be present. In the second subclass, the modification depends to a large extent on external agencies, such as the daily alternations of light and darkness, or light alone temperature, or the attraction of gravity. The first small subclass will be considered in the present chapter, and the second subclass in the remainder of this volume. The circumnutation of climbing plants. The simplest case of modified circumnutation is that offered by climbing plants, with the exception of those which climb by the aid of motionless hooks or of rootlets, for the modification consists chiefly in the greatly increased amplitude of the movement. This would follow either from greatly increased growth over a small length, or more probably from moderately increased growth spread over a considerable length of the moving organ, preceded by turgescence and acting successively on all sides. The circumnutation of climbers is more regular than that of ordinary plants, but in almost every other respect there is a close similarity between their movements, namely in their tendency to describe ellipses directed successively to all points of the compasson, their courses being often interrupted by zigzag lines, triangles, loops, or small ellipses in the rate of movement, and in different species, revolving once or several times within the same length of time in the same internode. The movements cease first in the lower part, and then slowly upwards in both sets of cases. The movement may be modified in a closely analogous manner by geotropism and by heliotropism, though few climbing plants are heliotropic. Other points of similarity might be pointed out. That the movements of climbing plants consist of ordinary circumnutation modified by being increased in amplitude is well exhibited. Whilst the plants are very young, for at this early age they move like other seedlings, but as they grow older their movements gradually increase without undergoing any other change. That this power is innate, and is not excited by any external agencies beyond those necessary for growth and vigor, is obvious. No one doubts that this power has been gained for the sake of enabling climbing plants to ascend to a height, and thus to reach the light. This is effected by two very different methods. First, by twining spirally round a support, but to do so their stems must be long and flexible, and secondly, in the case of leaf climbers and tendril bearers, by bringing these organs into contact with a support which is then seized by the aid of their sensitiveness. It may be here remarked that these latter movements have no relation, as far as we can judge, with circumnutation. In other cases, the tips of tendrils, after having been brought into contact with a support, become developed into little discs which adhere firmly to it. We have said that the circumnutation of climbing plants differs from that of ordinary plants, chiefly by its greater amplitude, but most leaves circumnudate in an almost vertical plane, and therefore describe very narrow ellipses, whereas the many kinds of tendrils, which consist of metamorphosed leaves, make much broader ellipses, or nearly circular figures, and thus they have a far better chance of catching hold of a support on any side. The movements of climbing plants have also been modified in some few other special ways. Thus the circumnudating stems of Solnanum dulcamera can twine round a support only when this is as thin and flexible as a string or thread. The twining stems of several British plants cannot twine round a support when it is more than a few inches in thickness, whilst in tropical forests some can embrace thick trunks. And this great difference in power depends on some unknown difference in their manner of circumnutation. The most remarkable special modification of this movement which we have observed is in the tendrils of Echinocystes lobata. These are usually inclined at about 45 above the horizon, but they stiffen and straighten themselves so as to stand upright in a part of their circular course, namely when they approach, and have to pass over the summit or the shoot from which they arise. If they had not possessed and exercised this curious power, they would infallibly have struck against the summit of the shoot and been arrested in their course. As soon as one of these tendrils with its 3 branches begins to stiffen itself and rise up vertically, the revolving motion becomes more rapid, and as soon as it has passed over the point of difficulty, its motion, coinciding with that from its own weight, causes it to fall into its previously inclined position so quickly that the apex can be seen travelling like the hand of a gigantic clock. A large number of ordinary leaves and leaflets and a few flower peduncles are provided with pulvini, but this is not the case with a single tendril at present known. The cause of this difference probably lies in the fact that the chief service of a pulvinus is to prolong the movement of the part thus provided after growth has ceased, and as tendrils or other climbing organs are of use only whilst the plant is increasing in height or growing, a pulvinus, which served to prolong their movements, would be useless. It was shown in the last chapter that the stolons or runners of certain plants circumnudate largely, and that this movement apparently aids them in finding a passage between the crowded stems of adjoining plants. If it could be proved that their movements had been modified and increased for this special purpose, they ought to have been included in the present chapter. But as the amplitude of their revolutions is not so conspicuously different from that of ordinary plants, as in the case of climbers we have no evidence on this head, we encounter the same doubt in the case of some plants, which bury their pods in the ground. This burying process is certainly favoured by the circumnutation of the flower peduncle, but we do not know whether it has been increased for this special purpose. Epinasty. The term epinasty is used by de Vries too to express greater longitudinal growth along the upper than along the lower side of a part, which is thus caused to bend downwards, and hyponasty is used for the reversed process by which the part is made to bend upwards. These actions come into play so frequently that the use of the above two terms is highly convenient. The movements thus induced result from a modified form of circumnutation, for as we shall immediately see, an organ under the influence of epinasty does not generally move in a straight line downwards or under that of hyponasty upwards, but oscillates up and down with some lateral movement. It moves, however, in a preponderant manner in one direction. This shows that there is some growth on all sides of the part, but more on the upper side in the case of epinasty, and more on the lower side in that of hyponasty, than on the other sides at the same time. There may be in addition, as de Vries insists, increased growth on one side due to geotropism, and on another side due to heliotropism, and thus the effects of epinasty or of hyponasty may be either increased or lessened. He who likes may speak of ordinary circumnutation as being combined with epinasty-hyponasty, the effects of gravitation, light, etc., but it seems to us from reasons hereafter to be given to be more correct to say that circumnutation is modified by these several agencies. We will therefore speak of circumnutation, which is always in progress as modified by epinasty-hyponasty, geotropism, or other agencies, whether internal or external. One of the commonest and simplest cases of epinasty is that offered by leaves which at an early age are crowded together round the buds and diverge as they grow older. Sachs first remarked that this was due to increased growth along the upper side of the petiole and blade, and de Vries has now shown in more detail that the movement is thus caused, aided slightly by the weight of the leaf, and resisted, as he believes, by apogeotropism, at least after the leaf has somewhat diverged. In our observations on the circumnutation of leaves, some were selected which were rather too young so that they continued to diverge or sink downwards, whilst their movements were being traced. This may be seen in the diagrams Figs 98 and 112 pp 232 and 249, representing the circumnutation of the young leaves of Acanthus mallees and Pelargonium zonale. Similar cases were observed with Drosera. The movements of a young leaf only 34-inch in length of Petunia violacea were traced during 4 days, and offers a better instance Fig 111 p 248, as it diverged during the whole of this time in a curiously zigzag line, with some of the angles sharply acute, and during the latter days plainly circumnutated some young leaves of about the same age on a plant of this Petunia which had been laid horizontally, and on another plant which was left upright, both being kept in complete darkness, diverged in the same manner for 48h, and apparently were not affected by apogeotropism, though their stems were in a state of high tension, for when freed from the sticks to which they had been tied they instantly curled upwards. The leaves, whilst very young on the leading shoots of the carnation Dianthus caryophyllus, are highly inclined or vertical, and if the plant is growing vigorously, they diverge so quickly that they become almost horizontal in a day, but they move downwards in a rather oblique line and continue for some time afterwards to move in the same direction in connection, we presume, with their spiral arrangement on the stem. The course pursued by a young leaf, whilst thus obliquely descending, was traced, and the line was distinctly, yet not strongly zigzag. The larger angles formed by the successive lines, amounting only to 135, 154, and 163, the subsequent lateral movement shown in Fig 96 p 230, one was strongly zigzag, with occasional circumnutations. The divergence and sinking of the young leaves of this plant seem to be very little affected by geotropism, or heliotropism, for a plant, the leaves of which were growing rather slowly as ascertained by measurement, was laid horizontally, and the opposite young leaves diverged from one another symmetrically in the usual manner, without any upturning in the direction of gravitation or towards the light. The needle-like leaves of Pinus pinaster form a bundle, whilst young afterwards they slowly diverge, so that those on the upright shoots become horizontal. The movements of one such young leaf was traced during 412 days, and the tracing here given, 121, shows that it descended at first in a nearly straight line, but afterwards zigzagged, making 1 or 2 little loops. The diverging and descending movements of a rather older leaf were also traced. See former Fig 113 p 251. It descended during the first day and night in a somewhat zigzag line. It then circumnutated round a small space and again descended by this time, The leaf had nearly assumed its final position, and now plainly circumnutated, as in the case of the carnation the leaves whilst very young do not seem to be much affected by geotropism or heliotropism, for those on a young plant laid horizontally, and those on another plant left upright both kept in the dark, continued to diverge in the usual manner, without bending to either side. Fig 121 Pinus pinaster epinastic downward movement of a young leaf produced by a young plant, in a part traced on a vertical glass under a skylight, from 6 Roman 1000 June 2nd to 10 P Roman 1000th. With coba scandens the young leaves as they successively diverge from the leading shoot, which is bent to one side, rise up so as to project vertically, and they retain this position for some time, whilst the tendril is revolving the diverging and ascending movements of the petiole of one such a leaf were traced on a vertical glass under a skylight, and the course pursued was in most parts nearly straight, but there were two well-marked zigzags, one of them forming an angle of 112, and this indicates circumnutation. The still closed lobes of a young leaf of Dionea projected at right angles to the petiole, and were in the act of slowly rising. A glass filament was attached to the underside of the midrib, and its movements were traced on a vertical glass. It circumnutated once in the evening, and on the next day rose as already described, see Fig 106p 240, by a number of acutely zigzag lines closely approaching in character to ellipses. This movement, no doubt, was due to epinasty aided by apogeotropism for the closed lobes of a very young leaf on a plant, which had been placed horizontally moved into nearly the same line with the petiole, as if the plant had stood upright. But at the same time, the lobes curved laterally upwards, and thus occupied an unnatural position obliquely to the plane of the foliaceous petiole. As the hypocartels and epicartels of some plants protrude from the seed coats in an arched form, it is doubtful whether the arching of these parts, which is invariably present when they break through the ground, ought always to be attributed to epinasty. But when they are at first straight, and afterwards become arched, as often happens, the arching is certainly due to epinasty. As long as the arch is surrounded by compact earth it must retain its form, but as soon as it rises above the surface, or even before this period, if artificially freed from the surrounding pressure, it begins to straighten itself, and this no doubt is mainly due to hyponasty. The movement of the upper and lower half of the arch and of the crown was occasionally traced, and the course was more or less zigzag, showing modified circumnutation. With not a few plants, especially climbers, the summit of the shoot is hooked, so that the apex points vertically downwards. In 7 genera of twining plants, 3 the hooking, or as it has been called by Sachs, the nutation of the tip, is mainly due to an exaggerated form of circumnutation. That is, the growth is so great along one side that it bends the shoot completely over to the opposite side, thus forming a hook. The longitudinal line or zone of growth then travels a little laterally round the shoot, and the hook points in a slightly different direction, and so onwards, until the hook is completely reversed. Ultimately, it comes back to the point whence it started. This was ascertained by painting narrow lines with Indian ink along the convex surface of several hooks, and the line was found slowly to become at first lateral, then to appear along the concave surface, and ultimately back again on the convex surface. In the case of Lonicera brachypoda, the hooked terminal part of the revolving shoot straightens itself periodically, but is never reversed. That is, the periodically increased growth of the concave side of the hook is sufficient only to straighten it, and not to bend it over to the opposite side. The hooking of the tip is of service to twining plants by aiding them to catch hold of a support, and afterwards by enabling this part to embrace the support much more closely than it could otherwise have done at first, thus preventing it, as we often observed, from being blown away by a strong wind. Whether the advantage thus gained by twining plants accounts for their summits being so frequently hooked, we do not know, as this structure is not very rare with plants which do not climb, and with some climbers, for instance Vitis ampelopsis cissus etc., to whom it does not afford any assistance in climbing. With respect to those cases in which the tip remains always bent or hooked towards the same side, as in the genera just named, the most obvious explanation is that the bending is due to continued growth in excess along the convex side. Wiesner, however, maintains that in all cases the hooking of the tip is the result of its plasticity and weight, a conclusion which, from what we have already seen with several climbing plants, is certainly erroneous. Nevertheless, we fully admit that the weight of the part as well as geotropism etc. sometimes come into play. Ampelopsis tricuspidata, this plant climbs by the aid of adhesive tendrils, and the hooked tips of the shoots do not appear to be of any service to it, The hooking depends chiefly, as far as we could ascertain, on the tip being affected by epinasty and geotropism, the lower and older parts continually straightening themselves through hyponasty and apogeotropism. We believe that the weight of the apex is an unimportant element, because on horizontal or inclined shoots, the hook is often extended horizontally or even faces upwards. Moreover, shoots frequently form loops instead of hooks, and in this case the extreme part, instead of hanging vertically down, as would follow if weight was the efficient cause, extends horizontally or even points upwards. A shoot, which terminated in a rather open, was fastened in a highly inclined downward position so that the concave side faced upwards, and the result was that the apex at first curved upwards. This apparently was due to epinasty, and not to apogeotropism, for the apex soon after passing the perpendicular curved so rapidly downwards that we could not doubt that the movement was at least aided by geotropism. In the course of a few hours, the hook was thus converted into a loop, with the apex of the shoot pointing straight downwards. The longer axis of the loop was at first horizontal but afterwards became vertical during this same time. The basal part of the hook, and subsequently of the loop, curved itself slowly upwards, and this must have been wholly due to apogeotropism in opposition to hyponasty. The loop was then fastened upside down so that its basal half would be simultaneously acted on by hyponasty if present, and by apogeotropism, and now it curved itself so greatly upwards in the course of only 4h that there could hardly be a doubt that both forces were acting together at the same time. The loop became open and was thus reconverted into a hook, and this apparently was affected by the geotropic movement of the apex. In opposition to epinasty in the case of Ampelopsis heteracea, weight plays, as far as we could judge, a more important part in the hooking of the tip. Fig 122, Ampelopsis tricuspidata, hyponastic movement of hooked tip of leading shoot, traced from 8A Roman 1000 July 13th to 8A Roman 1000th apex, of shoot 512 inches, from the vertical glass plant, illuminated through a skylight temp, 171,219 Roman 100 diagram, reduced to 1/3 of original scale. Fig 123, Smithia fundii, hyponastic movement of the curved summit of a stem, while straightening itself, traced from 9A Roman 1000 July 10th to 3P Roman 1000th apex, 912 inches from the vertical glass diagram, reduced to 1/5 of original scale plant, illuminated through skylight temp, 171,219 Roman 100. In order to ascertain whether the shoots of a tricuspidata, in straightening themselves under the combined action of hyponasty and apogeotropism, moved in a simple, straight course, or whether they circumnudated glass filaments were fixed to the crowns of 4 hook tips, standing in their natural position, and the movements of the filaments were traced on a vertical glass, all 4 tracings resembled each other in a general manner, but we will give only one. See Fig 122 p. 273. The filament rose at first, which shows that the hook was straightening itself. It then zigzagged, moving a little to the left between 9A Roman 1000 and 9P Roman 1000 from this latter hour on the 13th to 10A Roman 1000 on the following morning, 14th. The hook continued to straighten itself, and then zigzagged a short distance to the right, but from 1P Roman 1000 to 10P Roman 1000 on the 14th the movement was reversed, and the shoot became more hooked during the night. After 10P Roman 1000 to 8A Roman 1000 on the 15th, the hook again opened, or straightened itself. By this time, the glass filament had become so highly inclined that its movements could no longer be traced with accuracy, and by 1P Roman 1000 on this same day, the crown of the former arch or hook had become perfectly straight and vertical. There can therefore be no doubt that the straightening of the hooked shoot of this plant is effected by the circumnutation of the arch portion, that is, by growth alternating between the upper and lower surface, but preponderant on the lower surface, with some little lateral movement. We were enabled to trace the movement of another straightening shoot for a longer period owing to its slower growth, and to its having been placed further from the vertical glass, namely from the early morning on July 13th to late in the evening of the 16th. During the whole daytime of the 14th, the hook straightened itself very little, but zigzagged and plainly circumnudated about nearly the same spot. By the 16th it had become nearly straight, and the tracing was no longer accurate, yet it was manifest that there was still a considerable amount of movement both up and down, and laterally, for the crown, whilst continuing to straighten itself, occasionally became for a short time more curved, causing the filament to descend twice during the day. Smithia fundii, the stiff terminal shoots of this leguminous water plant from Africa project, so as to make a rectangle with the stem below. But this occurs only when the plants are growing vigorously, for when kept in a cool place, the summits of the stems become straight, as they likewise did at the close of the growing season. The direction of the rectangularly bent part is independent of the chief source of light, but from observing the effects of placing plants in the dark, in which case several shoots became in 2 or 3 days upright or nearly upright, and when brought back into the light again, became rectangularly curved. We believe that the bending is in part due to apheliotropism, apparently somewhat opposed by apogeotropism on the other hand, from observing the effects of tying a shoot downwards, so that the rectangle faced upwards, we are led to believe that the curvature is partly due to epinasty, as the rectangularly bent portion of an upright stem grows older, the lower part straightens itself, and this is effected through hyponasty. He who has read Sachs' recent essay on the vertical and inclined positions of the parts of plants 5 will see how difficult a subject this is, and will feel no surprise at our expressing ourselves doubtfully in this and other such cases. A plant 20 inches in height was secured to a stick close beneath the curved summit, which formed rather less than a rectangle with the stem below the shoot pointed away from the observer, and a glass filament pointing towards the vertical glass on which the tracing was made was fixed to the convex surface of the curved portion. Therefore the descending lines in the figure represent the straightening of the curved portion. As it grew older, the tracing, Fig 123p 274, was begun at 9A Roman 1000 on July 10th. The filament at first moved but little in a zigzag line, but at 2P Roman 1000 it began rising and continued to do so till 9P Roman 1000, and this proves that the terminal portion was being more bent downwards. After 9P Roman 1000 on the 10th, an opposite movement commenced, and the curved portion began to straighten itself, and this continued till 11A Roman 1000 on the 12th, but was interrupted by some small oscillations and zigzags showing movement in different directions. After 11A Roman 1000 on the 12th, this part of the stem still considerably curved circumnudated in a conspicuous manner, until nearly 3P Roman 1000 on the 13th, but during all this time, a downward movement of the filament prevailed caused by the continued straightening of the stem. By the afternoon of the 13th, the summit, which had originally been deflected more than a right angle from perpendicular, had grown so nearly straight that the tracing could no longer be continued on the vertical glass. There can therefore be no doubt that the straightening of the abruptly curved portion of the growing stem of this plant, which appears to be wholly due to hyponasty, is the result of modified circumnutation. We will only add that a filament was fixed in a different manner across the curved summit of another plant, and the same general kind of movement was observed. Trifolium repends in many but not in all the species of Trifolium as the separate little flowers, whither the subpeduncles bend downwards, so as to depend parallel to the upper part of the main peduncle. In Tr subterraneum, the main peduncle curves downwards for the sake of burying its capsules, and in this species, the subpeduncles of the separate flowers bend upwards so as to occupy the same position relatively to the upper part of the main peduncle, as in Tr repens. This fact alone would render it probable that the movements of the subpeduncles in Tr repens were independent of geotropism. Nevertheless, to make sure, some flower heads were tied to little sticks upside down, and others in a horizontal position, their subpeduncles however all quickly curved upwards through the action of heliotropism. We therefore protected some flower heads similarly secured to sticks from the light, and although some of them rotted, many of their subpeduncles turned very slowly from their reversed or from their horizontal positions, so as to stand in the normal manner parallel to the upper part of the main peduncle. These facts show that the movement is independent of geotropism or apheliotropism. It must therefore be attributed to epinasty, which however is checked at least as long as the flowers are young by heliotropism. Most of the above flowers were never fertilized owing to the exclusion of bees. They consequently withered very slowly, and the movements of the subpeduncles were in like manner much retarded. Fig 124 Trifolium repends circumnudating and epinastic movements of the subpeduncle of a single flower, traced on a vertical glass under a skylight in A from 11A Roman 1000 Aug. 27th to 7A Roman 1000th in B, from 7A Roman 1000 Aug. 30th to a little after 6P Roman 1000 Sept. 8th. To ascertain the nature of the movement of the subpeduncle whilst bending downwards, a filament was fixed across the summit of the calyx of a not fully expanded and almost upright flower, nearly in the centre of the head. The main peduncle was secured to a stick close beneath the head, in order to see the marks on the glass filament. A few flowers had to be cut away on the lower side of the head. The flower under observation at first diverged a little from its upright position, so as to occupy the open space caused by the removal of the adjoining flowers. This required 2 days, after which time a new tracing was begun. Fig. 124 in A, we see the complex circumnudating course pursued from 11A Roman 1000 Aug. 26th to 7A Roman 1000 on the 30th. The part was then moved a very little to the right, and the tracing B was continued without interruption from 7A Roman 1000 Aug. 30th to after 6P Roman 1000, sept 8th. It should be observed that on most of these days only a single dot was made. Each morning at the same hour, whenever the flower was observed carefully, as on Aug. 30th, and sept 5th and 6th, it was found to be circumnudating over a small space. At last on sept 7th, it began to bend downwards, and continued to do so until after 6P Roman 1000 on the 8th, and indeed until the morning of the 9th, when its movements could no longer be traced on the vertical glass. It was carefully observed during the whole of the 8th, and by 10P Roman 1000, it had descended to a point lower down by 2/3 of the length of the figure as here given, but from want of space, the tracing has been copied in B only to a little. After 6P Roman 1000 on the morning of the 9th, the flower was withered, and the subpeduncle now stood at an angle of 57 beneath the horizon. If the flower had been fertilized, it would have withered much sooner, and have moved much more quickly. We thus see that the subpeduncle oscillated up and down, or circumnudated during its whole downward epinastic course. The subpeduncles of the fertilized and withered flowers of Oxalis carnosa likewise bend downwards through epinasty, as will be shown in a future chapter, and their downward course is strongly zigzag, indicating circumnutation. The number of instances in which various organs move through epinasty or hyponasty, often in combination with other forces for the most diversified purposes, seems to be inexhaustibly great, and from the several cases which have been here given we may safely infer that such movements are due to modified circumnutation. Chapter Roman 6 Modified circumnutation sleep, or nyctotropic movements, their use. Sleep of cotyledons. Preliminary sketch of the sleep or nyctotropic movements of leaves. Presence of pulvini. The lessening of radiation, the final cause of nyctotropic movements. Manner of trying experiments on leaves of Oxalis arachis, Cassia melillatus lotus and Marsilia, and on the cotyledons of mimosa. Concluding remarks on radiation from leaves. Small differences. The conditions make a great difference in the result. Description of the nyctotropic position and movements of the cotyledons of various plants. List of species. Concluding remarks. Independence of the nyctotropic movements of the leaves and cotyledons of the same species. Reasons for believing that the movements have been acquired for a special purpose. The so-called sleep of leaves is so conspicuous a phenomenon that it was observed as early as the time of Pliny I, and since Linus published his famous essay Somnus Plantarum, it has been the subject of several memoirs. Many flowers close at night, and these are likewise said to sleep, but we are not here concerned with their movements, for although affected by the same mechanism as in the case of young leaves, namely unequal growth on the opposite sides, as first proved by Pfeffer, yet they differ essentially in being excited chiefly by changes of temperature, instead of light, and in being affected, as far as we can judge, for a different purpose. Hardly anyone supposes that there is any real analogy between the sleep of animals and that of plants too, whether of leaves or flowers. It seems therefore advisable to give a distinct name to the so-called sleep movements of plants. These have also generally been confounded under the term periodic with the slight daily rise and fall of leaves, as described in the 4th chapter, and this makes it all the more desirable to give some distinct name to sleep movements. Nyctotropism and nyctotropic Roman 1e nightening may be applied both to leaves and flowers and will be occasionally used by us, but it would be best to confine the term to leaves. The leaves of some few plants move either upwards or downwards when the sun shines intensely on them, and this movement has sometimes been called diurnal sleep, but we believe it to be of an essentially different nature from the nocturnal movement, and it will be briefly considered in a future chapter. The sleep or nyctotropism of leaves is a large subject, and we think that the most convenient plan will be first to give a brief account of the position which leaves assume at night, and of the advantages apparently thus gained afterwards. The more remarkable cases will be described in detail with respect to cotyledons in the present chapter, and to leaves in the next chapter. Finally, it will be shown that these movements result from circumnutation, much modified and regulated by the alternations of day and night or light and darkness, but that they are also to a certain extent inherited. Leaves when they go to sleep move either upwards or downwards, or in the case of the leaflets of compound leaves, forwards, that is towards the apex of the leaf, or backwards, that is towards its base, or again they may rotate on their own axes, without moving either upwards or downwards, but in almost every case the plane of the blade is so placed as to stand nearly or quite vertically at night. Therefore the apex or the base or either lateral edge may be directed towards the zenith. Moreover, the upper surface of each leaf, and more especially of each leaflet, is often brought into close contact with that of the opposite one, and this is sometimes affected by singularly complicated movements. This fact suggests that the upper surface requires more protection than the lower one. For instance, the terminal leaflet in trifolium, after turning up at night, so as to stand vertically, often continues to bend over until the upper surface is directed downwards, whilst the lower surface is fully exposed to the sky, and an arched roof is thus formed over the two lateral leaflets, which have their upper surfaces pressed closely together. Here we have the unusual case of one of the leaflets not standing vertically, or almost vertically at night. Considering that leaves, in assuming their nyctotropic positions, often move through an angle of 90, that the movement is rapid in the evening, that in some cases, as we shall see in the next chapter, it is extraordinarily complicated, that with certain seedlings old enough to bear true leaves the cotyledons move vertically upwards at night, whilst at the same time the leaflets move vertically downwards, and that in the same genus the leaves or cotyledons of some species move upwards, whilst those of other species move downwards. From these, and other such facts, it is hardly possible to doubt that plants must derive some great advantage from such remarkable powers of movement. The nyctotropic movements of leaves and cotyledons are effected in two ways. Firstly, by means of pulvini, which become, as Pfeffer has shown, alternately more turgescent on opposite sides, and secondly by increased growth along one side of the petiole or midrib, and then on the opposite side, as was first proved by Battle in 4, but as it has been shown by De Vries 5, that in these latter cases increased growth is preceded by the increased turgescence of the cells. The difference between the above two means of movement is much diminished, and consists chiefly in the turgescence of the cells of a fully developed pulvinus, not being followed by growth. When the movements of leaves or cotyledons furnished with a pulvinus and destitute of one are compared, they are seen to be closely similar, and are apparently effected for the same purpose. Therefore, with our object in view, it does not appear advisable to separate the above two sets of cases into two distinct classes. There is, however, one important distinction between them, namely, that movements affected by growth on the alternate sides are confined to young growing leaves, whilst those affected by means of a pulvinus last for a long time. We have already seen well-marked instances of this latter fact with cotyledons, and so it is with leaves, as has been observed by Pfeffer and by ourselves. The long endurance of the nyctotropic movements, when affected by the aid of pulvini, indicates, in addition to the evidence already advanced, the functional importance of such movements to the plant. There is another difference between the two sets of cases, namely that there is never or very rarely any torsion of the leaves, excepting when a pulvinus is present. 6. But this statement applies only to periodic and nyctotropic movements, as may be inferred from other cases given by Frank 7. The fact that the leaves of many plants place themselves at night in widely different positions from what they hold during the day, but with the one point in common that their upper surfaces avoid facing the zenith, often with the additional fact that they come into close contact with opposite leaves or leaflets, clearly indicates, as it seems to us, that the object gained is the protection of the upper surfaces from being chilled at night by radiation. There is nothing improbable in the upper surface needing protection more than the lower, as the two differ function and structure. All gardeners know that plants suffer from radiation. It is this, and not cold winds, which the peasants of southern Europe fear for their olives. 8. Seedlings are often protected from radiation by a very thin covering of straw and fruit trees on walls, by a few fir branches, or even by a fishing net suspended over them. There is a variety of the gooseberry 9, the flowers of which, from being produced before the leaves, are not protected by them from radiation, and consequently often fail to yield fruit. An excellent observer 10 has remarked that one variety of the cherry has the petals of its flowers much curled backwards, and after a severe frost all the stigmas were killed, whilst at the same time in another variety with incurved petals, the stigmas were not in the least injured. This view that the sleep of leaves saves them from being chilled at night by radiation would no doubt have occurred to Linnaeus, had the principle of radiation been then discovered, for he suggests in many parts of his Somnus Plantarum that the position of the leaves at night protects the young stems and buds, and often the young inflorescence, against cold winds, we are far from doubting that an additional advantage may be thus gained, and we have observed with several plants, for instance Desmodium gyrans, that whilst the blade of the leaf sinks vertically down at night, the petiole rises so that the blade has to move through a greater angle in order to assume its vertical position than would otherwise have been necessary, but with the result that all the leaves on the same plant are crowded together, as if for mutual protection. We doubted at first whether radiation would affect in any important manner objects so thin, as are many cotyledons and leaves, and more especially affect differently their upper and lower surfaces, for although the temperature of their upper surfaces would undoubtedly fall when freely exposed to a clear sky, yet we thought that they would so quickly acquire by conduction the temperature of the surrounding air that it could hardly make any sensible difference to them whether they stood horizontally and radiated into the open sky or vertically, and radiated chiefly in a lateral direction towards neighbouring plants and other objects. We endeavoured therefore to ascertain something on this head, by preventing the leaves of several plants from going to sleep and by exposing to a clear sky when the temperature was beneath the freezing point these, as well as the other leaves on the same plants, which had already assumed their nocturnal vertical position. Our experiments show that leaves thus compelled to remain horizontal at night suffered much more injury from frost than those which were allowed to assume their normal vertical position. It may however be said that conclusions drawn from such observations are not applicable to sleeping plants, the inhabitants of countries where frosts do not occur, but in every country and at all seasons leaves must be exposed to nocturnal chills through radiation which might be in some degree injurious to them, and which they would escape by assuming a vertical position. In our experiments, leaves were prevented from assuming their nyctotropic position generally by being fastened with the finest entomological pins, which did not sensibly injure them, to thin sheets of cork supported on sticks, but in some instances they were fastened down by narrow strips of card, and in others by their petioles being passed through slits in the cork. The leaves were at first fastened close to the cork, for as this is a bad conductor, and as the leaves were not exposed for long periods, we thought that the cork which had been kept in the house would very slightly warm them, so that if they were injured by the frost in a greater degree than the free vertical leaves, the evidence would be so much the stronger that the horizontal position was injurious. But we found that when there was any slight difference in the result, which could be detected only occasionally, the leaves which had been fastened closely down suffered rather more than those fastened with very long and thin pins, so as to stand from 12 to 34 inch above the cork. This difference in the result, which is in itself curious, as showing what a very slight difference in the conditions influences the amount of injury inflicted, may be attributed, as we believe, to the surrounding warmer air not circulating freely beneath the closely pinned leaves, and thus slightly warming them. This conclusion is supported by some analogous facts hereafter to be given. We will now describe in detail the experiments which were tried. These were troublesome from our not being able to predict how much cold the leaves of the several species could endure. Many plants had every leaf killed, both those which were secured in a horizontal position, and those which were allowed to sleep, that is, to rise up or sink down vertically. Others, again, had not a single leaf in the least injured, and these had to be re-exposed either for a longer time or to a lower temperature. Oxalis acetosella, a very large part thickly covered with between 300 and 400 leaves, had been kept all winter in the greenhouse. 7 leaves were pinned horizontally open, and were exposed on March 16th for 2h to a clear sky, the temperature on the surrounding grass being 4 Roman 10,024 to 25 F. Next morning, all 7 leaves were found quite killed, so were many of the free ones which had previously gone to sleep, and about 100 of them, either dead or browned and injured, were picked off. Some leaves showed that they had been slightly injured by not expanding during the whole of the next day, though they afterwards recovered, as all the leaves which were pinned open were killed, and only about a third or fourth of the others were either killed or injured. We had some little evidence that those which were prevented from assuming their vertically dependent position suffered most. The following night, 17th, was clear, and almost equally cold, 3 to 4 Roman 100 on the grass, and the part was again exposed, but this time for only 30 Roman 1008 leaves had been pinned out, and in the morning 2 of them were dead, whilst not a single other leaf on the many plants was even injured. On the 23rd, the part was exposed for 1h 30 Roman 1000, the temperature on the grass being only 2 Roman 100, and not one leaf was injured. The pinned open leaves, however, all stood from 12 to 34 of an inch above the cork. On the 24th, the part was again placed on the ground, and exposed to a clear sky for between 35 Roman 1000 and 40 Roman 1000. By a mistake, the thermometer was left on an adjoining sundial 3 feet high, instead of being placed on the grass. It recorded 25 to 26 F3 to 3 Roman 100, but when looked at after 1H had fallen to 22 F5 Roman 100, so that the part was perhaps exposed to rather lower temperature than on the two first occasions. 8 leaves had been pinned out, some close to the cork, and some above it, and on the following morning 5 of them, Roman 1E 63%, were found killed. By counting a portion of the leaves, we estimated that about 250 had been allowed to go to sleep, and of these about 20 were killed. Roman 1E only 8%, and about 30 injured. Considering these cases, there can be no doubt that the leaves of this oxalis, when allowed to assume their normal vertically dependent position at night, suffer much less from frost than those 23 in number which had their upper surfaces exposed to the zenith. Oxalis carnosa, a plant of this Chilean species, was exposed for 30 Roman 1000 to a clear sky, the thermometer on the grass standing at 2 Roman 100, with some of its leaves pinned open, and not one leaf on the whole bushy plant was in the least injured. On the 16th of March, another plant was similarly exposed for 3 Roman 1000, when the temperature on the grass was only a little lower, viz. 3 to 4 Roman 106 of the leaves had been pinned open, and next morning 5 of them were found much browned. The plant was a large one, and none of the free leaves which were asleep and depended vertically were browned, excepting 4 very young ones, but 3 other leaves, though not browned, were in a rather flaccid condition, and retained their nocturnal position during the whole of the following day. In this case, it was obvious that the leaves which were exposed horizontally to the zenith suffered most. This same part was afterwards exposed for 35-40 Roman 1000 on a slightly colder night, and every leaf, both the pinned open and the free ones, was killed. It may be added that 2 parts of O. corniculata var. Atropurpurea were exposed for 2H and 3H to a clear sky with the temp on grass 2 Roman 100, and none of the leaves, whether free or pinned open, were at all injured. Arachis hypogea, some plants in a part, were exposed at night for 30 Roman 1000 to a clear sky, the temperature on the surrounding grass being 2 Roman 100, and on 2 nights afterwards they were again exposed to the same temperature, but this time during 1H 30 Roman 1000. On neither occasion was a single leaf, whether pinned open or free, injured, and this surprised us much, considering its native tropical African home. 2 plants were next exposed, March 16th, for 30 Roman 1000 to a clear sky, the temperature of the surrounding grass being now lower, viz. between 3 and 4 Roman 100, and all 4 pinned open leaves were killed and blackened. These 2 plants bore 22 other and free leaves, excluding some very young bud-like ones, and only 2 of these were killed, and 3 somewhat injured, that is 23%, were either killed or injured, whereas all 4 pinned open leaves were utterly killed. On another night, 2 parts with several plants were exposed for between 35 Roman 1000 and 40 Roman 1000 to a clear sky, and perhaps to a rather lower temperature, for a thermometer on a dial 3 feet high close by stood at 3 to 3 Roman 100. In 1 part 3 leaves were pinned open, and all were badly injured. Of the 44 free leaves, 26 were injured, that is 59%. In the other part 3 leaves were pinned open, and all were killed. 4 other leaves were prevented from sleeping by narrow strips of stiff paper gummed across them, and all were killed. Of 24 free leaves, 10 were killed, 2 much injured and 12 unhurt, that is 50% of the free leaves were either killed or much injured. Taking the 2 parts together, we may say that rather more than half of the free leaves which were asleep were either killed or injured, whilst all the 10 horizontally extended leaves which had been prevented from going to sleep were either killed or much injured. Cassia floribundae bush was exposed at night for 40 Roman 1000 to a clear sky, the temperature on the surrounding grass being 2 Roman 100, and not a leaf was injured. 11. It was again exposed on another night for 1H, when the temperature of the grass was 4 Roman 100, and now all the leaves on a large bush, whether pinned flat open or free, were killed, blackened, and shriveled, with the exception of those on one small branch low down, which was very slightly protected by the leaves on the branches above another tall bush, with 4 of its large compound leaves pinned out horizontally, was afterwards exposed. Temp of surrounding grass exactly the same, viz. 4 Roman 100, but only for 30 Roman 1000. On the following morning, every single leaflet on these 4 leaves was dead, with both their upper and lower surfaces completely blackened. Of the many free leaves on the bush, only 7 were blackened, and of these only a single one, which was a younger and more tender leaf than any of the pinned ones, had both surfaces of the leaflets blackened. The contrast in this latter respect was well shown by a free leaf, which stood between two pinnadopen ones. For these latter had the lower surfaces of their leaflets as black as ink, whilst the intermediate free leaf, though badly injured, still retained a plain tinge of green on the lower surface of the leaflets. This bush exhibited in a striking manner the evil effects of the leaves not being allowed to assume at night their normal dependent position, for had they all been prevented from doing so, assuredly every single leaf on the book would have been utterly killed by this exposure of only 30 Roman 1000. The leaves, whilst sinking downwards in the evening, twist round, so that the upper surface is turned inwards, and is thus better protected than the outwardly turned lower surface. Nevertheless, it was always the upper surface which was more blackened than the lower, whenever any difference could be perceived between them. But whether this was due to the cells near the upper surface being more tender, or merely to their containing more chlorophyll, we do not know. Melilotus officinalis, a large pot with many plants which had been kept during the winter in the greenhouse, was exposed during 5h at night to a slight frost and clear sky. 4 leaves had been pinned out, and these died after a few days, but so did many of the free leaves. Therefore nothing certain could be inferred from this trial, though it indicated that the horizontally extended leaves suffered most. Another large pot with many plants was next exposed for 1h. The temperature on the surrounding grass being lower, viz. 3 to 4 Roman 110 leaves had been pinned out, and the result was striking, for on the following morning all these were found much injured or killed, and none of the many free leaves on the several plants were at all injured, with the doubtful exception of 2 or 3 very young ones. Melilotus italica, 6 leaves were pinned out horizontally, 3 with their upper and 3 with their lower surfaces turned to the zenith. The plants were exposed for 5h to a clear sky, the temperature on ground being about 1 Roman 100. Next morning, the 6 pinnadopen leaves seemed more injured even than the younger and more tender free ones on the same branches. The exposure, however, had been too long, for after an interval of some days, many of the free leaves seemed in almost as bad a condition as the pinned out ones. It was not possible to decide whether the leaves with their upper or those with their lower surfaces turned to the zenith had suffered most. Melilotus suivolans, some plants with 8 leaves pinned out, were exposed to a clear sky during 2h. The temperature on the surrounding grass being 2 Roman 100. Next morning, 6 out of these 8 leaves were in a flaccid condition. There were about 150 free leaves on the plant, and none of these were injured, except 2 or 3 very young ones. But after 2 days, the plants having been brought back into the greenhouse, the 6 pinned out leaves all recovered. Melilotus taurica, several plants were exposed for 5h during 2 nights to a clear sky and slight frost, accompanied by some wind, and 5 leaves, which had been pinned out, suffered more than those both above and below on the same branches, which had gone to sleep. Another part, which had likewise been kept in the greenhouse, was exposed for 35-40 Roman 1000 to a clear sky, the temperature of the surrounding grass being between 3 and 4 Roman 109 leaves had been pinned out, and all of these were killed on the same plants. There were 210 free leaves which had been allowed to go to sleep, and of these about 80 were killed Roman 1, only 38%. Melilotus petitpirina, the plants were exposed to a clear sky for 35-40 Roman 1000 temperature on surrounding grass. 3 to 4 Roman 106 leaves had been pinned out so as to stand about 12 inch above the cork, and 4 had been pinned close to it. These 10 leaves were all killed, but the closely pinned ones suffered most, as 4 of the 6 which stood above the cork still retained small patches of a green color, a considerable number, but not nearly all of the free leaves were killed or much injured, whereas all the pinned out ones were killed. Melilotus macrohyza, the plants were exposed in the same manner, as in the last case 6 leaves had been pinned out horizontally, and 5 of them were killed, that is 83%. We estimated that there were 200 free leaves on the plants, and of these about 50 were killed, and 20 badly injured, so that about 35% of the free leaves were killed or injured. Lotus aristata, 6 plants were exposed for nearly 5h to a clear sky temperature on surrounding grass. 1 Roman 104 leaves had been pinned out horizontally, and 2 of these suffered more than those above or below on the same branches, which had been allowed to go to sleep. It is rather a remarkable fact that some plants of Lotus jacobous, an inhabitant of so hot a country as the Cape Verde Islands, were exposed one night to a clear sky with the temperature of the surrounding grass 2 Roman 100, and on a second night for 30 Roman 1000 with the temperature of the grass between 3 and 4 Roman 100, and not a single leaf, either the pinned out or free ones, was in the least injured. Marsilia quadrifoliata, a large plant of this species, only cryptogamic plant known to sleep with some leaves pinned open, was exposed for 1H35 Roman 1000 to a clear sky, the temperature on the surrounding ground being 2 Roman 100, and not a single leaf was injured. After an interval of some days, the plant was again exposed for 1H to a clear sky with the temperature on the surrounding ground lower, viz. 4 Roman 106 leaves had been pinned out horizontally, and all of them were utterly killed. The plant had emitted long trailing stems, and these had been wrapped round with a blanket so as to protect them from the frozen ground and from radiation, but a very large number of leaves were left freely exposed which had gone to sleep, and of these only 12 were killed. After another interval, the plant with 9 leaves pinned out was again exposed for 1H, the temperature on the ground being again 4 Roman 106 of the leaves were killed, and one which did not at first appear injured afterwards became streaked with brown. The trailing branches which rested on the frozen ground had 1/2 or 3/4 of their leaves killed, but of the many other leaves on the plant, which alone could be fairly compared with the pinned out ones, none appeared at first sight to have been killed, but on careful search 12 were found in this state. After another interval, the plant with 9 leaves pinned out was exposed for 35-40 Roman 1000 to a clear sky, and to nearly the same or perhaps a rather lower temperature, for the thermometer, by an accident, had been left on a sundial close by, and 8 of these leaves were killed. Of the free leaves, those on the trailing branches not being considered, a good many were killed, but their number compared with the uninjured ones was small. Finally, taking the 3 trials together, 24 leaves extended horizontally were exposed to the zenith and to unobstructed radiation, and of these 20 were killed and 1 injured, whilst a relatively very small proportion of the leaves which had been allowed to go to sleep with their leaflets vertically dependent were killed or injured. The cotyledons of several plants were prepared for trial, but the weather was mild, and we succeeded only in a single instance in having seedlings of the proper age on nights which were clear and cold. The cotyledons of 6 seedlings of Mimosa pudica were fastened open on cork and were thus exposed for 1H45 Roman 1000 to a clear sky with the temperature on the surrounding ground at 29°F. Of these 3 were killed. 2 other seedlings, after their cotyledons had risen up and had closed together, were bent over and fastened so that they stood horizontally with the lower surface of one cotyledon fully exposed to the zenith, and both were killed. Therefore, of the 8 seedlings thus tried, 5 or more than half were killed. 7 other seedlings with their cotyledons in their normal nocturnal position, viz. vertical and closed, were exposed at the same time, and of these only 2 were killed. 12 hence, it appears, as far as these few trials tell anything, that the vertical position at night of the cotyledons of Mimosa pudica protects them to a certain degree from the evil effects of radiation and cold. Concluding remarks on the radiation from leaves at night: we exposed on 2 occasions during the summer to a clear sky several pinned open leaflets of Trifolium pratense, which naturally rise at night, and of Oxalis purpurea, which naturally sink at night, the plants growing out of doors, and looked at them early on several successive mornings, after they had assumed their diurnal positions. The difference in the amount of dew on the pinned open leaflets and on those which had gone to sleep was generally conspicuous, the latter being sometimes absolutely dry, whilst the leaflets which had been horizontal were coated with large beads of dew. This shows how much cooler the leaflets fully exposed to the zenith must have become than those which stood almost vertically either upwards or downwards during the night. From the several cases above given, there can be no doubt that the position of the leaves at night affects their temperature through radiation to such a degree that when exposed to a clear sky during a frost, it is a question of life and death. We may therefore admit as highly probable, seeing that their nocturnal position is so well adapted to lessen radiation, that the object gained by their often complicated sleep movements is to lessen the degree to which they are chilled at night. It should be kept in mind that it is especially the upper surface which is thus protected, as it is never directed towards the zenith, and is often brought into close contact with the upper surface of an opposite leaf or leaflet. We failed to obtain sufficient evidence whether the better protection of the upper surface has been gained from its being more easily injured than the lower surface, or from its injury being a greater evil to the plant. That there is some difference in constitution between the 2 surfaces is shown by the following cases. Cassia floribunda was exposed to a clear sky on a sharp frosty night, and several leaflets which had assumed their nocturnal dependent position with their lower surfaces turned outwards so as to be exposed obliquely to the zenith, nevertheless had these lower surfaces less blackened than the upper surfaces which were turned inwards, and were in close contact with those of the opposite leaflets again apart of plants of Trifolium resupinatum, which had been kept in a warm room for 3 days, was turned out of doors, Sept 21st on a clear and almost frosty night. Next morning, 10 of the terminal leaflets were examined as opaque objects under the microscope. These leaflets in going to sleep either turn vertically upwards, or more commonly bend a little over the lateral leaflets so that their lower surfaces are more exposed to the zenith than their upper surfaces. Nevertheless, 6 of these 10 leaflets were distinctly yellower on the upper than on the lower, and more exposed surface in the remaining 4. The result was not so plain, but certainly whatever difference, there was leaned to the side of the upper surface having suffered most. It has been stated that some of the leaflets experimented on were fastened close to the cork, and others at a height of from 12 to 34 of an inch above it, and that whenever after exposure to a frost any difference could be detected in their states, the closely pinned ones had suffered most. We attributed this difference to the air not cooled by radiation having been prevented from circulating freely beneath the closely pinned leaflets. That there was really a difference in the temperature of leaves treated in these 2 different methods was plainly shown on one occasion, for after the exposure of a pot with plants of Mellilotus dentata, for 2h to a clear sky, the temperature on the surrounding grass being 2 Roman 100, it was manifest that more dew had congealed into hoarfrost on the closely pinned leaflets than on those which stood horizontally a little above the cork. Again, the tips of some few leaflets, which had been pinned close to the cork, projected a little beyond the edge, so that the air could circulate freely round them. This occurred with 6 leaflets of Oxalis acetosella, and their tips certainly suffered, rather less than the rest of the same leaflets, for on the following morning they were still slightly green. The same result followed even still more clearly in 2 cases, with leaflets of Mellilotus officinales, which projected a little beyond the cork, and in 2 other cases, some leaflets which were pinned close to the cork were injured, whilst other free leaflets on the same leaves, which had not space to rotate and assume their proper vertical position, were not at all injured. Another analogous fact deserves notice. We observed on several occasions that a greater number of free leaves were injured on the branches which had been kept motionless, by some of their leaves having been pinned to the corks, than on the other branches. This was conspicuously the case with those of Mellilotus petitpirina, but the injured leaves in this instance were not actually counted with Arachis. Hypogaea, a young plant with 7 stems, bore 22 free leaves, and of these 5 were injured by the frost, all of which were on 2 stems bearing 4 leaves pinned to the cork supports. With Oxalis carnosa, 7 free leaves were injured, and every one of them belonged to a cluster of leaves, some of which had been pinned to the cork. We could account for these cases only by supposing that the branches which were quite free had been slightly waved about by the wind, and that their leaves had thus been a little warmed by the surrounding warmer air. If we hold our hands motionless before a hot fire, and then wave them about, we immediately feel relief, and this is evidently an analogous though reversed case. These several facts in relation to leaves pinned close to or a little above the cork supports, though their tips projecting beyond it, and to the leaves on branches kept motionless, seem to us curious, as showing how a difference apparently trifling may determine the greater or less injury of the leaves. We may even infer as probable that the less or greater destruction during a frost of the leaves on a plant which does not sleep may often depend on the greater or less degree of flexibility of their petioles, and of the branches which bear them. Nyctotropic or sleep movements of cotyledons. We now come to the descriptive part of our work, and will begin with cotyledons, passing on to leaves in the next chapter. We have met with only 2 brief notices of cotyledons sleeping. Hofmeister 13, after stating that the cotyledons of all the observed seedlings of the Caryophyllae alcinae and silene bend upwards at night, but to what angle he does not state, remarks that those of Stellaria media rise up so as to touch one another. They may therefore safely be said to sleep. Secondly, according to Ramy 14, the cotyledons of Mimosa pudica and of Clyanthus damperi rise up almost vertically at night and approach each other closely. It has been shown in a previous chapter that the cotyledons of a large number of plants bend a little upwards at night, and we here have to meet the difficult question, at what inclination may they be said to sleep? According to the view, which we maintain, no movement deserves to be called nyctotropic, unless it has been acquired for the sake of lessening radiation, but this could be discovered only by a long series of experiments, showing that the leaves of each species suffered from this cause if prevented from sleeping. We must therefore take an arbitrary limit If a cotyledon or leaf is inclined at 60 above or beneath the horizon, it exposes to the zenith about 1/2 of its area. Consequently, the intensity of its radiation will be lessened by about half compared with what it would have been if the cotyledon or leaf had remained horizontal. This degree of diminution, certainly, would make a great difference to a plant having a tender constitution. We will therefore speak of a cotyledon and hereafter of a leaf as sleeping only when it rises at night, to an angle of about 60, or to a still higher angle above the horizon, or sinks beneath it to the same amount not, but that a lesser diminution of radiation may be advantageous to a plant, as in the case of Datura stramonium, the cotyledons of which rose from 31 at noon to 55 at night above the horizon. The Swedish turnip may profit by the area of its leaves being reduced at night by about 30% as estimated by Mr. A. S. Wilson, though in this case, the angle through which the leaves rose was not observed. On the other hand, when the angular rise of cotyledons or of leaves is small, such as less than 30, the diminution of radiation is so slight that it probably is of no significance to the plant. In relation to radiation, for instance, the cotyledons of Geranium ibericum rose at night to 27 above the horizon, and this would lessen radiation by only 11%. Those of Linum berenderi rose to 33, and this would lessen radiation by 16%. There are, however, some other sources of doubt with respect to the sleep of cotyledons. In certain cases, the cotyledons whilst young diverge during the day to only a very moderate extent, so that a small rise at night, which we know occurs with the cotyledons of many plants, would necessarily cause them to assume a vertical or nearly vertical position at night, and in this case it would be rash to infer that the movement was effected for any special purpose. On this account, we hesitated long whether we should introduce several cucurbitaceous plants into the following list, but from reasons presently to be given we thought that they had better be at least temporarily included. This same source of doubt applies in some few other cases, for at the commencement of our observations we did not always attend sufficiently to whether the cotyledons stood nearly horizontally in the middle of the day with several seedlings. The cotyledons assume a highly inclined position at night during so short a period of their life that a doubt naturally arises whether this can be of any service to the plant. Nevertheless, in most of the cases given in the following list, the cotyledons may be as certainly said to sleep as may the leaves of any plant. In two cases, namely with the cabbage and radish, the cotyledons of which rise almost vertically during the few first nights of their life, it was ascertained by placing young seedlings in the clinostat that the upward movement was not due to apogotropism. The names of the plants, the cotyledons of which stand at night at an angle of at least 60 with the horizon, are arranged in the appended list on the same system as previously followed the numbers of the families, and with the leguminosae, the numbers of the tribes have been added to show how widely the plants in question are distributed throughout the dicotyledonous series. A few remarks will have to be made about many of the plants in the list. In doing so, it will be convenient not to follow strictly any systematic order, but to treat of the oxalid and the leguminosae at the close, for in these two families, the cotyledons are generally provided with a pulvinus, and their movements endure for a much longer time than those of the other plants in the list. List of seedling plants, the cotyledons of which rise or sink at night to an angle of at least 60 above or beneath the horizon. Brassica auracea cruciferi, fam. 14 napus, as we are informed by Prof. Raffinus sativus cruciferi, Githago segetum cariophili, fam. 26 stellaria media, according to Hofmeister as quoted cariophili, Anoda wrightii malvaceae, fam. 36 Gossypium varnenkin cotton malvaceae oxalis rosea, oxalid fam. 41 Floribunda articulata valdiviana sensitiva, Geranium rotundifolium, Geraniaceae fam. 47 Trifolium subterraneum leguminosae, fam. 75 Tribe 3, Strictum leucanthemum lotus ornithopopoids leguminosae Tribe 4, Peregrinus jacobus clianthus damperi leguminosae Tribe 5, according to Roman 1000 Rami smithia sensitiva leguminosae, Tribe 6 Hematoxylon campicianum leguminosae Tribe 13, according to Mr. R. Roman 1 Lynch cassia mimosoids leguminosae Tribe 14 Glauca, Florida corymbosa pubescens tora negulcta, 3 other Brazilian unnamed species, Bohinia sp leguminosae Tribe 15 Neptunia auracea leguminosae Tribe 20 Mimosa pudica leguminosae Tribe 21 Albida cucurbita ovifera cucurbitaceae, fam. 106 Aurantialegnaria vulgaris cucurbitaceae cucumis dudame cucurbitaceae apium petroslinum umbelliferi, Fam 113 Gravelans lactuca scariola composite Fam 122 Helianthus annus composite Ipoma caerulea convolvulaceae, Fam 151 Purpurea barnanox coccinea solanum lycopersicum salani, Fam 157 Mimulus sp scrofularini, Fam 159, from information given us by Prof. Pfeffer Mirabilis halapa nictigini, Fam 177 Mirabilis longiflora beta vulgaris polygoni, Fam 179 Amaranthus caudatus amaranthacea, Fam 180 Cannabis sativa cannabini, Fam 195 Brassica auracea cruciferi. It was shown in the first chapter that the cotyledons of the common cabbage rise in the evening and stand vertically up at night with their petioles in contact. But as the two cotyledons are of unequal height, they frequently interfere a little with each other's movements, the shorter one often not standing quite vertically. They awake early in the morning, thus at 6 A Roman 1000 on Nav 27th, whilst it was still dark the cotyledons which had been vertical and in contact on the previous evening were reflexed, and thus presented a very different appearance. It should be borne in mind that seedlings in germinating at the proper season would not be subjected to darkness at this hour in the morning. The above amount of movement of the cotyledons is only temporary, lasting with plants kept in a warm greenhouse from 4 to 6 days. How long it would last with seedlings growing out of doors, we do not know. Raphanus sativus, in the middle of the day, the blades of the cotyledons of 10 seedlings stood at right angles to their hypocotyls with their petioles, a little divergent at night. The blades stood vertically with their bases in contact, and with their petioles parallel next morning at 6 A Roman 1000. Whilst it was still dark, the blades were horizontal. On the following night they were much raised but hardly stood sufficiently vertical to be said to be asleep, and so it was in a still less degree on the third night. Therefore the cotyledons of this plant kept in the greenhouse go to sleep for even a shorter time than those of the cabbage. Similar observations were made, but only during a single day and night on 13 other seedlings likewise raised in the greenhouse, with the same result. The petioles of the cotyledons of 11 young seedlings of Sinapis nigra were slightly divergent at noon, and the blades stood at right angles to the hypocotyls at night. The petioles were in close contact, and the blades considerably raised with their bases in contact, but only a few stood sufficiently upright to be called asleep on the following morning. The petioles diverged before it was light. The hypocotyl is slightly sensitive, so that if rubbed with a needle it bends towards the rubbed side. In the case of Lepidium sativum, the petioles of the cotyledons of young seedlings diverge during the day and converge, so as to touch each other during the night, by which means the bases of the tripartite blades are brought into contact, but the blades are so little raised that they cannot be said to sleep. The cotyledons of several other cruciferous plants were observed, but they did not rise sufficiently during the night to be said to sleep. Githago segetum coriophyllae. On the first day, after the cotyledons had burst through the seed coats, they stood at noon at an angle of 75 above the horizon. At night, they moved upwards each through an angle of 15, so as to stand quite vertical, and in contact with one another. On the second day, they stood at noon at 59 above the horizon, and again at night were completely closed, each having risen 31 on the fourth day. The cotyledons did not quite close at night. The first and succeeding pairs of young true leaves behaved in exactly the same manner. We think that the movement in this case may be called nyctotropic, though the angle passed through was small. The cotyledons are very sensitive to light, and will not expand if exposed to an extremely dim one. Anoda rhytii malvaceae, the cotyledons whilst moderately young, and only from 2 to 3 inch in diameter, sink in the evening from their midday horizontal position to about 35 beneath the horizon. But when the same seedlings were older, and had produced small true leaves, the almost orbicular cotyledons, now 55 inch in diameter, moved vertically downwards at night. This fact made us suspect that their sinking might be due merely to their weight, but they were not in the least flaccid, and when lifted up sprang back through elasticity into their former dependent position. A pot with some old seedlings was turned upside down in the afternoon before the nocturnal fall had commenced, and at night they assumed, in opposition to their own weight and to any geotropic action, an upwardly directed vertical position. When pots were thus reversed after the evening fall had already commenced, the sinking movement appeared to be somewhat disturbed, but all their movements were occasionally variable, without any apparent cause. This latter fact, as well as that of the young cotyledons not sinking nearly so much as the older ones, deserves notice. Although the movement of the cotyledons endured for a long time, no pulvinus was exteriorly visible, but their growth continued for a long time, The cotyledons appear to be only slightly heliotropic, though the hypercotyl is strongly so. Gossypium arboreum var Nankin cot Malvaceae, the cotyledons behave in nearly the same manner as those of the anoda on June 15. The cotyledons of two seedlings were 65 inch in length, measured along the midrib and stood horizontally at noon at 10 p Roman 1000. They occupied the same position and had not fallen at all on June 23. The cotyledons of one of these seedlings were 1 inch in length, and by 10 p Roman 1000, they had fallen from a horizontal position to 62. Beneath the horizon, the cotyledons of the other seedling were 1 inch in length, and a minute true leaf had been formed. They had fallen at 10 p Roman 1000 to 70. Beneath the horizon on June 25, the true leaf of this latter seedling was 9 inch in length, and the cotyledons occupied nearly the same position at night. By July 9, the cotyledons appeared very old and showed signs of withering, but they stood at noon almost horizontally, and at 10 p Roman 1000 hung down vertically. Gossypium herbaceum, it is remarkable that the cotyledons of this species behave differently from those of the last. They were observed during 6 weeks from their first development, until they had grown to a very large size, still appearing fresh and green, viz. 212 inches in breadth at this age. A true leaf had been formed which with its petiole was 2 inches long during the whole of these 6 weeks. The cotyledons did not sink at night yet, when old their weight was considerable, and they were borne by much elongated petiole. Seedlings raised from some seed, sent us from Naples, behaved in the same manner as did those of a kind cultivated in Alabama, and of the Seasland cotton. To what species these three latter forms belong we do not know. We could not make out in the case of the Naples cotton that the position of the cotyledons at night was influenced by the soil being more or less dry, care being taken that they were not rendered flaccid by being too dry. The weight of the large cotyledons of the Alabama and Seasland kinds caused them to hang somewhat downwards when the parts in which they grew were left for a time upside down. It should however be observed that these three kinds were raised in the middle of the winter, which sometimes greatly interferes with the proper nyctotropic movements of leaves and cotyledons. Cucurbidaceae, the cotyledons of Cucurbita aurantia and ovifera, and of Lagnaria vulgaris, stand from the first to the third day of their life at about 60 above the horizon, and at night rise up so as to become vertical and in close contact with one another. With Cucumis dudame, they stood at noon at 45 above the horizon and closed at night. The tips of the cotyledons of all these species are however reflexed, so that this part is fully exposed to the zenith at night, and this fact is opposed to the belief that the movement is of the same nature as that of sleeping plants. After the first 2 or 3 days, the cotyledons diverge more during the day and cease to close at night. Those of Trichosanthes anguina are somewhat thick and fleshy, and did not rise at night, and they could perhaps hardly be expected to do so. On the other hand, those of Acanthosisios horrida, 15, present nothing in their appearance opposed to their moving at night in the same manner as the preceding species, yet they did not rise up in any plain manner. This fact leads to the belief that the nocturnal movements of the above-named species has been acquired for some special purpose, which may be to protect the young plumule from radiation by the close contact of the whole basal portion of the two cotyledons. Geranium rotundifolium geraniaceae, a single seedling came up accidentally in a pot, and its cotyledons were observed to bend perpendicularly downwards during several successive nights. Having been horizontal at noon, it grew into a fine plant, but died before flowering. It was sent to Kew and pronounced to be certainly a geranium, and in all probability the above-named species. This case is remarkable because the cotyledons of G. cinereum, Endressii ibericum richardsoni and subcalescens were observed during some weeks in the winter, and they did not sink, whilst those of G. ibericum rose 27 at night. Apium petroslinum umbelliferae, a seedling, had its cotyledons nav 22nd almost fully expanded during the day. By 8 p Roman 1000, they had risen considerably, and at 10 p Roman 1000 were almost closed, their tips being only 80/100 of an inch apart. On the following morning, 23rd, the tips were 58,100 of an inch apart, or more than 7 times as much. On the next night, the cotyledons occupied nearly the same position as before. On the morning of the 24th, they stood horizontally, and at night were 60 above the horizon, and so it was on the night of the 25th, but 4 days afterwards, on the 29th, when the seedlings were a week old, the cotyledons had ceased to rise at night to any plain degree. Apium graveolens, the cotyledons at noon were horizontal, and at 10 p Roman 1000 stood at an angle of 61 above the horizon. Lactuca scariola composite the cotyledons whilst young stood subhorizontally during the day, and at night rose so as to be almost vertical, and some were quite vertical and closed. But this movement ceased when they had grown old and large after an interval of 11 days. Helianthus annus composite this case is rather doubtful. The cotyledons rise at night, and on one occasion they stood at 73 above the horizon, so that they might then be said to have been asleep. Ipoma caerulea vel farbitis nil convolvulaceae, the cotyledons behave in nearly the same manner as those of the Anoda and Nankin cotton, and like them grow to a large size, whilst young and small, so that their blades were from 5 to 6 of an inch in length, measured along the middle to the base of the central notch. They remained horizontal both during the middle of the day, and at night as they increased in size, they began to sink more and more in the evening and early night, and when they had grown to a length measured in the above manner of from 1 to 1 inch, they sank between 55 and 70 beneath the horizon. They acted, however, in this manner only when they had been well illuminated during the day. Nevertheless, the cotyledons have little or no power of bending towards a lateral light. Although the hypocotyle is strongly heliotropic, they are not provided with a pulvinus, but continue to grow for a long time. Ipoma purpurea vel farbitis hispida, the cotyledons behave in all respects like those of Roman 1 caerulea, a seedling with cotyledons 75 inch in length, measured as before, and 1 inch in breadth, having a small true leaf, developed, was placed at 5 p Roman 1000 on a clinostat in a darkened box, so that neither weight nor geotropism could act on them. At 10 p Roman 1001, cotyledons stood at 77, and the other at 82 beneath the horizon. Before being placed in the clinostat, they stood at 15 and 29 beneath the horizon. The nocturnal position depends chiefly on the curvature of the petiole close to the blade, but the whole petiole becomes slightly curved downwards. It deserves notice that seedlings of this and the last named species were raised at the end of February, and another lot in the middle of March, and the cotyledons in neither case exhibited any nyctotropic movement. Ipoma bonanox, the cotyledons after a few days grow to an enormous size, those on a young seedling being 314 inches in breadth. They were extended horizontally at noon, and at 10 p Roman 1000 stood at 63 beneath the horizon 5 days. Afterwards they were 412 inches in breadth, and at night one stood at 64 and the other 48 beneath the horizon. Though the blades are thin yet from their great size, and from the petioles being long, we imagined that their depression at night might be determined by their weight, but when the part was laid horizontally, they became curved towards the hypocotyle, which movement could not have been in the least aided by their weight. At the same time, they were somewhat twisted upwards through apogeotropism. Nevertheless, the weight of the cotyledons is so far influential that when on another night the part was turned upside down, they were unable to rise, and thus to assume their proper nocturnal position. Ipoma coccinea, the cotyledons whilst young do not sink at night, but when grown a little older, but still only 4 inch in length measured as before and 82 in breadth, they became greatly depressed. In one case they were horizontal at noon, and at 10 p Roman 1000 one of them stood at 64, and the other at 47 beneath the horizon. The blades are thin, and the petioles, which become much curved down at night, are short, so that here weight can hardly have produced any effect with all the above species of Ipoma, when the two cotyledons on the same seedling were unequally depressed at night. This seemed to depend on the position which they had held during the day with reference to the light. Solanum lycopassicum salini, the cotyledons rise so much at night as to come nearly in contact. Those of S. palinacanthum were horizontal at noon, and by 10 p Roman 1000 had risen only 27-30 minutes, but on the following morning before it was light, they stood at 59 above the horizon, and in the afternoon of the same day were again horizontal. The behavior of the cotyledons of this latter species seems therefore to be anomalous. Mirabilis halapa and longiflora nyctogyni, the cotyledons which are of unequal size stand horizontally during the middle of the day, and at night rise up vertically and come into close contact with one another. But this movement with Roman 1000 longiflora lasted for only the 3 first nights. Beta vulgaris polygoni, a large number of seedlings were observed on 3 occasions during the day. The cotyledons sometimes stood subhorizontally, but more commonly at an angle of about 50 above the horizon, and for the first 2 or 3 nights they rose up vertically, so as to be completely closed. During the succeeding 1 or 2 nights, they rose only a little and afterwards hardly at all. Amaranthus caudatus amaranthacea. At noon the cotyledons of many seedlings, which had just germinated, stood at about 45 above the horizon, and at 10 p Roman 1000 some were nearly, and the others quite closed on the following morning. They were again well expanded or open. Cannabis sativa cannabini, we are very doubtful whether this plant ought to be here, included the cotyledons of a large number of seedlings, after being well illuminated during the day, were curved downwards at night, so that the tips of some pointed directly to the ground, but the basal part 999 not appear to be at all depressed on the following morning. They were again flat and horizontal. The cotyledons of many other seedlings were at the same time not in any way affected. Therefore, this case seems very different from that of ordinary sleep, and probably comes under the head of epinasty, as is the case with the leaves of this plant. According to Krauss, the cotyledons are heliotropic, and so is the hypocotyl in a still stronger degree. Oxalis, we now come to cotyledons provided with a pulvinus, all of which are remarkable from the continuance of the nocturnal movements during several days or even weeks, and apparently after growth has ceased. The cotyledons of O. rosea floribunda and articulata sink vertically down at night and clasp the upper part of the hypocotyl. Those of O. valdiviana and sensitiva, on the contrary, rise vertically up so that their upper surfaces come into close contact, and after the young leaves are developed, these are clasped by the cotyledons, as in the daytime they stand horizontally, or are even a little deflected beneath the horizon. They move in the evening through an angle of at least 90. Their complicated circumnutating movements during the day have been described in the first chapter. The experiment was a superfluous one, but pots with seedlings of O. rosea and floribunda were turned upside down as soon as the cotyledons began to show any signs of sleep, and this made no difference in their movements. Leguminosae, it may be seen in our list that the cotyledons of several species in 9 genera, widely distributed throughout the family, sleep at night, and this probably is the case with many others. The cotyledons of all these species are provided with a pulvinus, and the movement in all is continued during many days or weeks. In Cassia, the cotyledons of the 10 species in the list rise up vertically at night and come into close contact with one another. We observed that those of Roman 100 Florida opened in the morning, rather later than those of Roman 100 glauca and pubescens. The movement is exactly the same in Roman 100 mimosoids as in the other species, though its subsequently developed leaves sleep in a different manner. The cotyledons of an 11th species, namely Roman 100 nodosa, are thick and fleshy, and do not rise up at night. The circumnutation of the cotyledons during the day of Roman 100 tora has been described in the first chapter, although the cotyledons of Smithia sensitiva rose from a horizontal position in the middle of the day to a vertical one at night. Those of S. fundii, which are thick and fleshy, did not sleep when Mimosa pudica and albida have been kept at a sufficiently high temperature during the day. The cotyledons come into close contact at night. Otherwise, they merely rise up almost vertically. The circumnutation of those of Roman 1000 pudica has been described. The cotyledons of a Bohinia from St. Catharina in Brazil stood during the day at an angle of about 50 above the horizon, and at night rose to 77, but it is probable that they would have closed completely if the seedlings had been kept in a warmer place. Lotus, in 3 species of lotus, the cotyledons were observed to sleep. Those of Roman 50 Jacobous present the singular case of not rising at night in any conspicuous manner for the first 5 or 6 days of their life, and the pulvinus is not well developed at this period. Afterwards the sleeping movement is well displayed, though to a variable degree, and is long continued. We shall hereafter meet with a nearly parallel case with the leaves of Cedar rhombifolia. The cotyledons of Roman 50 Gebula are only slightly raised at night, and differ much in this respect from the 3 species in our list. Trifolium, the germination of 21 species was observed in most of them. The cotyledons rise hardly at all or only slightly at night, but those of T. glomeratum striatum and incarnactum rose from 45 to 55 above the horizon. With T. subterraneum leucanthemum and strictum, they stood up vertically, and with T. strictum the rising movement is accompanied, as we shall see, by another movement which makes us believe that the rising is truly nyctotropic. We did not carefully examine the cotyledons of all the species for a pulvinus, but this organ was distinctly present in those of T. subterraneum and strictum, whilst there was no trace of a pulvinus in some species, for instance in T. resupinatum, the cotyledons of which do not rise at night. Trifolium subterraneum, the blades of the cotyledons on the first day after germination, Nav 21st, were not fully expanded, being inclined at about 35 above the horizon. At night, they rose to about 75 2 days afterwards. The blades at noon were horizontal, with the petioles highly inclined upwards. and it is remarkable that the nocturnal movement is almost wholly confined to the blades being affected by the pulvinus at their bases, whilst the petioles retain day and night nearly the same inclination on this night Nav 23rd. And for some few succeeding nights, the blades rose from a horizontal into a vertical position, and then became bowed inwards, at about an average angle of 10, so that they had passed through an angle of 100, their tips now almost touched one another, their bases being slightly divergent. The two blades thus formed a highly inclined roof over the axis of the seedling. This movement is the same as that of the terminal leaflet of the tripartite leaves of many species of trifolium. After an interval of 8 days, Nav 29th, the blades were horizontal during the day and vertical at night, and now they were no longer bowed inwards. They continued to move in the same manner for the following 2 months, by which time they had increased greatly in size, their petioles being no less than 1/8 of an inch in length, and 2 true leaves had by this time been developed. Trifolium strictum. On the first day after germination, the cotyledons, which are provided with a pulvinus, stood at noon horizontally, and at night rose to only about 45 above the horizon. 4 days afterwards, the seedlings were again observed at night, and now the blades stood vertically, and were in contact excepting the tips, which were much deflexed, so that they faced the zenith. At this age the petioles are curved upwards, and at night when the bases of the blades are in contact, the 2 petioles together form a vertical ring surrounding the plumule. The cotyledons continued to act in nearly the same manner for 8 or 10 days from the period of germination, but the petioles had by this time become straight and had increased much in length. After from 12 to 14 days, the first simple true leaf was formed, and during the ensuing fortnight, a remarkable movement was repeatedly observed. At Roman 1 Fig 125, we have a sketch made in the middle of the day of a seedling about a fortnight old. The 2 cotyledons, of which RC is the right and LC the left one, stand directly opposite one another, and the first true leaf F projects at right angles to them at night. See Roman 2 and Roman 3. The right cotyledon RC is greatly raised, but is not otherwise changed in position. The left cotyledon LC is likewise raised, but it is also twisted so that its blade, instead of exactly facing the opposite one, now stands at nearly right angles to it. This nocturnal twisting movement is effected not by means of the pulvinus, but by the twisting of the whole length of the petiole, as could be seen by the curved line of its upper concave surface. At the same time, the true leaf F rises up so as to stand vertically, or it even passes the vertical, and is inclined a little inwards. It also twists a little, by which means the upper surface of its blade fronts and almost comes into contact with the upper surface of the twisted left cotyledon. This seems to be the object gained by these singular movements. Altogether, 20 seedlings were examined on successive nights, and in 19 of them, it was the left cotyledon alone which became twisted with the true leaf, always so twisted that its upper surface approached closely and fronted that of the left cotyledon. In only one instance was the right cotyledon twisted with the true leaf twisted towards it, but this seedling was in an abnormal condition, as the left cotyledon did not rise up properly at night. This whole case is remarkable, as with the cotyledons of no other plant have we seen any nocturnal movement, except vertically, upwards or downwards. It is the more remarkable because we shall meet with an analogous case in the leaves of the allied genus Melilotus, in which the terminal leaflet rotates at night, so as to present one edge to the zenith, and at the same time bends to one side, so that its upper surface comes into contact with that of one of the 2 now vertical lateral leaflets. Fig 125. Trifolium strictum diurnal and nocturnal positions of the 2 cotyledons, and of the first leaf Roman 1 seedling, viewed obliquely from above during the day. RC right cotyledon, LC left cotyledon, F first true leaf Roman 2, A rather younger seedling viewed at night. RC right cotyledon raised, but its position not otherwise changed. LC left cotyledon raised, and laterally twisted. F first leaf raised and twisted so as to face the left twisted cotyledon. Roman 3 same seedling viewed at night from the opposite side. The back of the first leaf F is here shown, instead of the front, as in Roman 2. Concluding remarks on the nyctotropic movements of cotyledons. The sleep of cotyledons, though this is a subject which has been little attended to, seems to be a more common phenomenon than that of leaves. We observed the position of the cotyledons during the day and night in 153 genera, widely distributed throughout the dicotyledonous series, but otherwise selected almost by hazard, and 1 or more species in 26 of these genera placed their cotyledons at night so as to stand vertically or almost vertically, having generally moved through an angle of at least 60. if we lay on one side the Leguminosae, the cotyledons of which are particularly liable to sleep, 140 genera remain, and out of these, the cotyledons of at least one species in 19 genera slept. Now, if we were to select by hazard 140 genera, excluding the Leguminosae, and observed their leaves at night, assuredly not nearly so many as 19 would be found to include sleeping species. We here refer exclusively to the plants observed by ourselves. In our entire list of seedlings, there are 30 genera belonging to 16 families, the cotyledons of which in some of the species rise or sink in the evening or early night, so as to stand at least 60 above or beneath the horizon. In a large majority of the genera, namely 24, the movement is a rising one, so that the same direction prevails in these nyctotropic movements as in the lesser periodic ones described in the second chapter. The cotyledons move downwards during the early part of the night in only 6 of the genera, and in one of them, cannabis, the curving down of the tip is probably due to epinasty, as Krauss believes to be the case with the leaves. The downward movement to the amount of 90 is very decided in Oxalis valdiviana and sensitiva, and in Geranium rotundifolium it is a remarkable fact that with Anoda wrightii, one species of Gossypium, and at least 3 species of Ipoma, the cotyledons whilst young and light sink at night very little or not at all, although this movement becomes well pronounced as soon as they have grown large and heavy, although the downward movement cannot be attributed to the weight of the cotyledons in the several cases which were investigated, namely in those of the Anoda Ipoma purpurea and Barnanox, nor in that of Roman 1 coccinea. Yet bearing in mind that cotyledons are continually circumnudating, a slight cause might at first have determined whether the great nocturnal movement should be upwards or downwards. We may therefore suspect that in some aboriginal member of the groups in question, the weight of the cotyledons first determined the downward direction. The fact of the cotyledons of these species not sinking down much whilst they are young and tender seems opposed to the belief that the greater movement when they are grown older has been acquired for the sake of protecting them from radiation at night. But then we should remember that there are many plants the leaves of which sleep, whilst the cotyledons do not, and if in some cases the leaves are protected from cold at night, whilst the cotyledons are not protected, so in other cases, it may be of more importance to the species that the nearly full-grown cotyledons should be better protected than the young ones. In all the species of Oxalis observed by us, the cotyledons are provided with pulvini, but this organ has become more or less rudimentary in O. corniculata, and the amount of upward movement of its cotyledons at night is very variable, but is never enough to be called sleep. We omitted to ascertain whether the cotyledons of Geranium rotundifolium possess pulvini in the Leguminosae. All the cotyledons which sleep as far as we have seen are provided with pulvini, but with Lotus jacobus, these are not fully developed during the first few days of the life of the seedling, and the cotyledons do not then rise much at night. With Trifolium strictum, the blades of the cotyledons rise at night by the aid of their pulvini, whilst the petiole of one cotyledon twists half round at the same time independently of its pulvinus. As a general rule, cotyledons which are provided with pulvini continue to rise or sink at night during a much longer period than those destitute of this organ in this latter case. The movement, no doubt, depends on alternately greater growth on the upper and lower side of the petiole, or of the blade, or of both, preceded probably by the increased turgescence of the growing cells. Such movements generally last for a very short period, for instance with Brassica and Githago for 4 or 5 nights, with Beta for 2 or 3, and with Raphanus for only a single night. There are however some strong exceptions to this rule, as the cotyledons of Gossypium, Anoda and Ipoma do not possess pulvini, yet continue to move and to grow for a long time. We thought at first that when the movement lasted for only 2 or 3 nights it could hardly be of any service to the plant, and hardly deserve to be called sleep, but as many quickly growing leaves sleep for only a few nights, and as cotyledons are rapidly developed and soon complete their growth, this doubt now seems to us not well founded, more especially as these movements are in many instances so strongly pronounced. We may here mention another point of similarity between sleeping leaves and cotyledons, namely that some of the latter, for instance those of Cassia and Githago, are easily affected by the absence of light, and they then either close, or if closed do not open, whereas others, as with the cotyledons of Oxalis, are very little affected by light. In the next chapter, it will be shown that the nyctotropic movements both of cotyledons and leaves consist of a modified form of circumnutation. As in the Leguminosae and Oxalid, the leaves and the cotyledons of the same species generally sleep. The idea at first naturally occurred to us that the sleep of the cotyledons was merely an early development of a habit proper to a more advanced stage of life, but no such explanation can be admitted, although there seems to be some connection, as might have been expected, between the two sets of cases, for the leaves of many plants sleep, whilst their cotyledons do not do so, which fact Desmodium gyrans offers a good instance, as likewise do 3 species of Nicotiana, observed by us also Cedar rhombifolia abutilon darwini, and Chenopodium album. On the other hand, the cotyledons of some plants sleep, and not the leaves, as with the species of Beta brassica geranium apium solanum and mirabilis named in our list. Still more striking is the fact that in the same genus the leaves of several, or of all the species, may sleep, but the cotyledons of only some of them, as occurs with Trifolium lotus gossypium, and partially with Oxalis again, when both the cotyledons and the leaves of the same plant sleep. Their movements may be of a widely dissimilar nature. Thus with Cassia, the cotyledons rise vertically up at night, whilst their leaves sink down and twist round so as to turn their lower surfaces outwards, with seedlings of Oxalis valdiviana having 2 or 3 well-developed leaves. It was a curious spectacle to behold at night, each leaflet folded inwards, and hanging perpendicularly downwards, whilst at the same time, and on the same plant, the cotyledons stood vertically upwards. These several facts, showing the independence of the nocturnal movements of the leaves and cotyledons on the same plant, and on plants belonging to the same genus, lead to the belief that the cotyledons have acquired their power of movement for some special purpose. Other facts lead to the same conclusion, such as the presence of pulvini, by the aid of which the nocturnal movement is continued during some weeks in Oxalis. The cotyledons of some species move vertically upwards, and of others vertically downwards at night, but this great difference within the same natural genus is not so surprising as it may at first appear, seeing that the cotyledons of all the species are continually oscillating up and down during the day, so that small cause might determine whether they should rise or sink at night. Again, the peculiar nocturnal movement of the left-hand cotyledon of Trifolium strictum, in combination with that of the first true leaf. Lastly, the wide distribution in the dicotyledonous series of plants, with cotyledons which sleep. Reflecting on these several facts, our conclusion seems justified that the nyctotropic movements of cotyledons, by which the blade is made to stand either vertically or almost vertically upwards or downwards at night, has been acquired, at least in most cases, for some special purpose, nor can we doubt that this purpose is the protection of the upper surface of the blade, and perhaps of the central bud or plumule from radiation at night. Chapter Romans 7 Modified circumnutation, nyctotropic or sleep movements of leaves. Conditions necessary for these movements. List of genera and families, which include sleeping plants. Description of the movements in the several genera. Oxalis leaflets, folded at night. Avroa rapid movements of the leaflets. Porleria, leaflets close, when plant kept very dry. Tropiolum leaves, do not sleep unless well illuminated during day. Lupinus various modes of sleeping. Melalotus singular movements of terminal leaflet. Trifolium desmodium rudimentary, lateral leaflets, movements of not developed on young plants. State of their pulvini. Cassia, complex movements of the leaflets. Bauhinia leaves, folded at night. Mimosa pudica, compounded movements of leaves. Effect of darkness. Mimosa albida, reduced leaflets of Schrankia. Downward movement of the Pinny marsilia, the only cryptogam known to sleep. Concluding remarks and summary. Nyctotropism consists of modified circumnutation, regulated by the alternations of light and darkness shape of first true leaves. We now come to the nyctotropic or sleep movements of leaves. It should be remembered that we confine this term to leaves which place their blades at night either in a vertical position or not more than 30 from the vertical, that is at least 60 above or beneath the horizon. In some few cases, this is affected by the rotation of the blade, the petiole not being either raised or lowered to any considerable extent. The limit of 30 from the vertical is obviously arbitrary one and has been selected for reasons previously assigned, namely, that when the blade approaches the perpendicular, as nearly as this, only half as much of the surface is exposed at night to the zenith, and to free radiation as when the blade is horizontal. Nevertheless, in a few instances leaves, which seem to be prevented by their structure from moving to so great an extent as 60 above or beneath the horizon, have been included amongst sleeping plants. It should be premised that the nyctotropic movements of leaves are easily affected by the conditions to which the plants have been subjected. If the ground is kept too dry, the movements are much delayed or fail. According to Dasson 1, even if the air is very dry, the leaves of impatiens and malva are rendered motionless. Karl Kraus has also lately insisted too on the great influence which the quantity of water absorbed has on the periodic movements of leaves, and he believes that this cause chiefly determines the variable amount of sinking of the leaves of Polygonum convolvulus at night, and if so their movements are not in our sense strictly nyctotropic plants in order to sleep, must have been exposed to a proper temperature erythrina, Christogalli out of doors, and nailed against a wall seemed in fairly good health, but the leaflets did not sleep, whilst those on another plant kept in a warm greenhouse were all vertically dependent at night in a kitchen garden. The leaflets of Phasalis vulgaris did not sleep during the early part of the summer. Ch. Royer says 3, referring I suppose to the native plants in France, that they do not sleep when the temperature is below 5 Roman 100 or 41 F, in the case of several sleeping plants, viz. Species of Tropiolum lupinus Ipoma abutilon siege specia, and probably other genera. It is indispensable that the leaves should be well illuminated during the day, in order that they may assume at night a vertical position, and it was probably owing to this cause that seedlings of Chenopodium album and Siege specia orientalis, raised by us during the middle of the winter, though kept at a proper temperature, did not sleep. Lastly, violent agitation by a strong wind during a few minutes of the leaves of Maranta arundinacea, which previously had not been disturbed in the hothouse, prevented their sleeping during the 2 next nights. We will now give our observations on sleeping plants made in the manner described in the introduction. The stem of the plant was always secured, when not stated to the contrary, close to the base of the leaf, the movements of which were being observed so as to prevent the stem from circumnudating. As the tracings were made on a vertical glass in front of the plant, it was obviously impossible to trace its course. As soon as the leaf became in the evening greatly inclined either upwards or downwards, it must therefore be understood that the broken lines in the diagrams, which represent the evening and nocturnal courses, ought always to be prolonged to a much greater distance either upwards or downwards than appears in them. The conclusions which may be deduced from our observations will be given near the end of this chapter. In the following list, all the genera which include sleeping plants are given as far as known to us. The same arrangement is followed as in former cases, and the number of the family is appended. This list possesses some interest as it shows that the habit of sleeping is common to some few plants throughout the whole vascular series. The greater number of the genera in the list have been observed by ourselves with more or less care, but several are given on the authority of others whose names are appended in the list, and about these we have nothing more to say. No doubt the list is very imperfect, and several genera might have been added from the Somnus plantarum by Linus, but we could not judge in some of his cases whether the blades occupied at night a nearly vertical position. He refers to some plants as sleeping, for instance Lathyrus odoratus and Vicia faber, in which we could observe no movement deserving to be called sleep, and as no one can doubt the accuracy of Linus, we are left in doubt. List of genera including species the leaves of which sleep. Class Roman 1 Dicotyledons. Subclass Roman 1 Angiosperms. Genus Family Githago Caryophyllae 26 Stellaria Battle Portulaca, Ch. Royer Portulaceae 27, Cedar malvaceae 36 Abutilon malva Linus and Pfeffer hibiscus Linus, Anoda Gossypium aenea Linus sterculaceae 37 Triumpheta Linus tiliaceae 38 Linum battling Linni 39 Oxalis oxalid 41 Avaroa porliria zygophyll 45 Geacum impatiens Linus Pfeffer battling balsamini 48 Tropioli 49 Crotolaria Thyselton dire leguminosae 75 Tribe Roman 2 Lupinus cytisus trigonella Tr Roman 3 Medicago melilotus trifolium securigera Tr Roman 4 Lotus Soralia Tr Roman 5 Amorpha cuchata Dahlia indigofera Tephrosia wisteria Robinia spherifissa colutea Astragalus glycyrrhiza coronilla Tr Roman 6 Hedysarum genus family Onobriches leguminosae 75 Tr Roman 6 Smithia arachis Desmodium urania vicia Tr Roman 7 Centrosma Tr Roman 8 Amphicarpa glycine erythrina Apios phasalis sophora Tr Roman 10 Caesalpinia Tr Roman 13 Hematoxylin Gladicia duchata poinciana Cassia Tr Roman 14 Bohinia Tr Roman 15 Tamarindus Tr Roman 16 Adenanthera Tr Roman 20 Prosopes Neptunia mimosa Schrankia acacia Tr Roman 22 Albizia Tr Roman 23 Melaleuca Bouch Myrtaceae 94 Genus family Enithera Linus omegrarii 100 Passiflora Passifloracea 105 Siege specia composite 122 Ipoma convolvulacea 151 Nicotiana salini 157 Mirabilis nyctogeni 177 Polygonum Batalin polygoni, 179 Amaranthus amaranthaceae, 180 Chenopodium chenopodii, 181 Pimelia bouch thymti, 188 Euphorbia euphorbiaceae, 202 Philanthus pfeffer. Subclass Roman II Gymnosperms Aes chatin. Class Roman II Monocotyledons. Thalia canaceae 21 Maranta colocasia, Arodi 30 Strephium gramen 55. Class Roman III Acotyledons. Marsilia marsiliaceae 4. Githago segetum caryophily, the first leaves produced by young seedlings rise up and close together at night on a rather older seedling. 2 young leaves stood at noon at 55 above the horizon, and at night at 86, so each had risen 31. The angle, however, was less in some cases. Similar observations were occasionally made on young leaves, for the older ones moved very little produced by nearly full-grown plants. Batalin, says Flora Oct, 1st 1873 p. 437, that the young leaves of Stellaria close up so completely at night that they form together great buds. Cedar malvaceae nyctotropic movements of the leaves in this genus are remarkable in some respects. Batalin informs us, see also, Flora Oct, 1st 1873 p. 437, that those of S. napia fall at night, but to what angle he cannot remember. The leaves of S. rhombifolia and retusa, on the other hand, rise up vertically, and are pressed against the stem. We have therefore here, within the same genus, directly opposite movements. Again, the leaves of S. rhombifolia are furnished with a pulvinus formed of a mass of small cells destitute of chlorophyll, and with their longer axes perpendicular to the axis of the petiole, as measured along this latter line. These cells are only 1/15 of the length of those of the petiole, but instead of being abruptly separated from them, as is usual with the pulvinus in most plants, they graduate into the larger cells of the petiole. On the other hand, S. napia, according to Batalin, does not possess a pulvinus, and he informs us that a gradation may be traced in the several species of the genus between these two states of the petiole. Cedar rhombifolia presents another peculiarity of which we have seen no other instance with leaves that sleep, for those on very young plants, though they rise somewhat in the evening, do not go to sleep, as we observed on several occasions, whilst those on rather older plants sleep in a conspicuous manner. For instance, a leaf 85 of an inch in length on a very young seedling 2 inches high stood at noon 9 above the horizon, and at 10 p. Roman 1000 at 28, so it had risen only 19. Another leaf 1 inch in length on a seedling of the same height stood at the same 2 periods at 7 and 32, and therefore had risen 25. These leaves, which moved so little, had a fairly well-developed pulvinus. After an interval of some weeks when the same seedlings were 212 and 3 inches in height, some of the young leaves stood up at night quite vertically, and others were highly inclined, and so it was with bushes which were fully grown and were flowering. Fig. 126 Cedar rhombifolia circumnutation, and nyctotropic or sleep movements of a leaf, on a young plant 912 inches high filament, fixed to midrib, of nearly full-grown leaf, 238 inches in length movement, traced under a skylight apex of leaf, 558 inches from the vertical glass, so diagram not greatly enlarged. The movement of a leaf was traced from 9A Roman 1000 on May 28 to 8A Roman 1000 on the 30th, the temperature was too low 15-16 Roman 100, and the illumination hardly sufficient. Consequently, the leaves did not become quite so highly inclined at night as they had done previously, and as they did subsequently in the hothouse, but the movements did not appear otherwise disturbed. On the first day the leaf sank till 5 p. Roman 1000, it then rose rapidly and greatly till 10 p. Roman 1000, and only a little higher during the rest of the night. Fig. 126 Early on the next day 29th, it fell in a slightly zigzag line rapidly, until 9A Roman 1000, by which time it had reached nearly the same place as on the previous morning. During the remainder of the day it fell slowly, and zigzagged laterally. The evening rise began after 4 p. Roman 1000 in the same manner as before, and on the second morning it again fell rapidly. The ascending and descending lines do not coincide, as may be seen in the diagram on the 30th. A new tracing was made, not here given on a rather enlarged scale, as the apex of the leaf now stood 9 inches from the vertical glass. In order to observe more carefully the course pursued at the time when the diurnal changes into the nocturnal rise, darts were made every half-hour between 4 p. Roman 1000 and 10 p. Roman 1000. This rendered the lateral zigzagging movement during the evening more conspicuous than in the diagram given, but it was of the same nature as there shown. The impression forced on our minds was that the leaf was expending superfluous movement, so that the great nocturnal rise might not occur at too early an hour. Abutilon darwini malvaceae, the leaves on some very young plants stood almost horizontally during the day, and hung down vertically at night. Very fine plants, kept in a large hole lighted only from the roof, did not sleep at night, for in order to do so the leaves must be well illuminated during the day. The cotyledons do not sleep. Linus says that the leaves of his cedar abutilon sink perpendicularly down at night, though the petioles rise. Prof. Pfeffer informs us that the leaves of a malva allied to Roman 1000 silvestris rise greatly at night, and this genus as well as that of hibiscus are included by Linus in his list of sleeping plants. Anoda rhytii malvaceae, the leaves produced by very young plants when grown to a moderate size sink at night, either almost vertically down, or to an angle of about 45 beneath the horizon, for there is a considerable degree of variability in the amount of sinking at night, which depends in part on the degree to which they have been illuminated during the day, but the leaves whilst quite young do not sink down at night, and this is a very unusual circumstance. The summit of the petiole, where it joins the blade, is developed into a pulvinus, and this is present in very young leaves, which do not sleep, though it is not so well defined as in older leaves. Gossypium var Nenkin cart malvaceae, some young leaves between 1 and 2 inches in length, borne by 2 seedlings 6 and 712 inches in height, stood horizontally, or were raised a little above the horizon at noon on July 8 and 9th, but by 10 P Roman 1000, they had sunk down to between 68 and 90 beneath the horizon. When the same plants had grown to double the above height, their leaves stood at night almost or quite vertically, dependent. The leaves on some large plants of G. maritimum and brazilans, which were kept in a very badly lighted hothouse, only occasionally sank much downwards at night, and hardly enough to be called sleep. Oxalis oxalid, in most of the species in this large genus, the 3 leaflets sink vertically down at night, but as their subpetioles are short, the blades could not assume this position from the want of space, unless they were in some manner rendered narrower, and this is effected by their becoming more or less folded. Fig. 127. The angle formed by the 2 halves of the same leaflet was found to vary in different individuals of several species between 92 and 150. In 3 of the best folded leaflets of O. fragrans, it was 76, 74, and 54. The angle is often different in the 3 leaflets of the same leaf, as the leaflets sink down at night and become folded. Their lower surfaces are brought near together, cb, or even into close contact, and from this circumstance it might be thought that the object of the folding was the protection of their lower surfaces. If this had been the case, it would have formed a strongly marked exception to the rule that, when there is any difference in the degree of protection from radiation of the 2 surfaces of the leaves, it is always the upper surface which is the best protected, but that the folding of the leaflets and consequent mutual approximation of their lower surfaces serves merely to allow them to sink down vertically, may be inferred from the fact that when the leaflets do not radiate from the summit of a common petiole, or again, when there is plenty of room from the subpetioles not being very short, the leaflets sink down without becoming folded. This occurs with the leaflets of O. sensitiva plumeri and Buplerifolia. Fig. 127, Oxalis acetosella, a leaf seen from vertically above. B. Diagram of leaf asleep, also seen from vertically above. There is no use in giving a long list of the many species which sleep in the above described manner. This holds good with species having rather fleshy leaves like those of O. carnosa, or large leaves like those of O. ortigesii, or 4 leaflets like those of O. variabilis. There are however some species which show no signs of sleep, viz. O. pentaphylla, Eniphylla hirta and rubella. We will now describe the nature of the movements in some of the species. Oxalis acetosella, the movement of a leaflet together with that of the main petiole, are shown in the following diagram. Fig. 128, traced between 11 A Roman 1000 on October 4th and 7 A Roman 1000 on the 5th. After 5 P Roman 1000 on the 4th, the leaflet sank rapidly, and at 7 P Roman 1000 depended vertically for some time before it assumed this latter position. Its movements could of course no longer be traced on the vertical glass, and the broken line in the diagram ought to be extended much further down. In this and all other cases, by 6 A Roman 1000 on the following morning, it had risen considerably and continued to rise for the next hour, but judging from other observations, it would soon have begun to fall again between 11 A Roman 1000 and 5 P Roman 1000. The leaflet moved at least 4 times up and 4 times down before the great nocturnal fall commenced. It reached its highest point at noon. Similar observations were made on 2 other leaflets, with nearly the same results. Sachs and Pfeffer have also described briefly for the autonomous movements of the leaves of this plant. Fig 128 Oxalis acetocellar circumnutation and nyctotropic movements of a nearly full-grown leaf, with filament attached to the midrib of one of the leaflets traced on vertical glass during 20H45 m. On another occasion, the petiole of a leaf was secured to a little stick close beneath the leaflets, and a filament tipped with a bead of sealing wax was affixed to the midrib of one of them, and a mark was placed close behind at 7 p Roman 1000. When the leaflets were asleep, the filament depended vertically down, and the movements of the bead were then traced till 10 p Roman 1000 as shown in the following diagram. Fig. 129. We here see that the leaflet moved a little from side to side, as well as a little up and down whilst asleep. Oxalis valdiviana, the leaves resemble those of the last species, and the movements of 2 leaflets, the main petioles of both having been secured, were traced during 2 days, but the tracings are not given as they resembled that of O. acetocella, with the exception that the up and down oscillations were not so frequent during the day and there was more lateral movement, so that broader ellipses were described. The leaves awoke early in the morning, for by 6 A Roman 1000 on June 12th and 13th, they had not only risen to their full height, but had already begun to fall, that is, they were circumnutating. We have seen in the last chapter that the cotyledons, instead of sinking, rise up vertically at night. Fig. 129, Oxalis acetocellar circumnutation of leaflet, when asleep traced on vertical glass during 3H40 Roman 1000. Oxalis ortogesiae, the large leaves of this plant sleep like those of the previous species. The main petioles are long, and that of a young leaf rose 20 between noon and 10 p Roman 1000, whilst the petiole of an older leaf rose only 13 owing to this rising of the petioles, and the vertical sinking of the large leaflets. The leaves become crowded together at night, and the whole plant then exposes a much smaller surface to radiation than during the day. Oxalis plumerae, in this species, the 3 leaflets do not surround the summit of the petiole, but the terminal leaflet projects in the line of the petiole with a lateral leaflet on each side. They all sleep by bending vertically downwards, but do not become at all folded. The petiole is rather long, and one having been secured to a stick, the movement of the terminal leaflet was traced during 45H on a vertical glass. It moved in a very simple manner, sinking rapidly after 5 p Roman 1000, and rising rapidly early next morning. During the middle of the day, it moved slowly, and a little laterally. Consequently, the ascending and descending lines did not coincide, and a single great ellipse was formed each day. There was no other evidence of circumnutation, and this fact is of interest, as we shall hereafter see. Oxalis sensitiva, the leaflets, as in the last species, bend vertically down at night without becoming folded. The much elongated main petiole rises considerably in the evening, but in some very young plants the rise did not commence until late at night. We have seen that the cotyledons, instead of sinking like the leaflets, rise up vertically at night. Oxalis buplerifolia, this species is rendered remarkable by the petioles being foliaceous like the phyllodes of many acacias. The leaflets are small, of a paler green and more tender consistence than the foliaceous petioles. The leaflet which was observed was 55 inch in length, and was borne by a petiole 2 inches long and 3 inch broad. It may be suspected that the leaflets are on the road to abortion or obliteration, as has actually occurred with those of another Brazilian species, O. russiformis. Nevertheless, in the present species, the nyctotropic movements are perfectly performed. The foliaceous petiole was first observed during 48H, and found to be in continued circumnutation as shown in the accompanying figure. Fig. 130. It rose during the day and early part of the night, and fell during the remainder of the night and early morning, but the movement was not sufficient to be called sleep. The ascending and descending lines did not coincide, so that an ellipse was formed each day. There was but little zigzagging. If the filament had been fixed longitudinally, we should probably have seen that there was more lateral movement than appears in the diagram. Fig. 130 Oxalis buplerifolia circumnutation of foliaceous petiole filament, fixed obliquely across end of petiole movements, traced on vertical glass from 9 A Roman 1000 June 26th to 8 A Roman 1000th apex of leaflet 412 inches from the glass. So movement not much magnified. Plant 9 inches high, illuminated from above. Temp 23,122,412 Roman 100 A. Terminal leaflet on another leaf was next observed, the petiole being secured, and its movements are shown in Fig 131. During the day, the leaflets are extended horizontally, and at night depend vertically. And as the petiole rises during the day, the leaflets have to bend down in the evening more than 90, so as to assume at night their vertical position on the first day. The leaflet simply moved up and down on the second day. It plainly circumnutated between 8A Roman 1000 and 4P Roman 1000, after which hour the great evening fall commenced. Fig 131, oxalis buplerifolia circumnutation, and nyctotropic movement of terminal leaflet, with filament affixed along the midrib, traced on a vertical glass, from 9A Roman 1000 on June 26 to 8A Roman 1000 conditions, the same as in the last case. Of Varroa bilimbi oxalid it has long been known firstly, that the leaflets in this genus sleep; secondly, that they move spontaneously during the day, and thirdly, that they are sensitive to touch. But in none of these respects do they differ essentially from the species of oxalis. They differ, however, as Mr. R. Roman 1 Lynch 6 has lately shown, in their spontaneous movements being strongly marked. In the case of a bilimbi, it is a wonderful spectacle to behold on a warm sunny day the leaflets one after the other sinking rapidly downwards, and again ascending slowly. Their movements rival those of Desmodium gyrans. At night the leaflets hang vertically down, and now they are motionless, but this may be due to the opposite ones being pressed together. Fig 132. The main petiole is in constant movement during the day, but no careful observations were made on it. The following diagrams are graphic representations of the variations in the angle which a given leaflet makes with the vertical. The observations were made as follows: the plant growing in a pot was kept in a high temperature, the petiole of the leaf to be observed pointing straight at the observer, being separated from him by a vertical pane of glass. The petiole was secured so that the basal joint or pulvinus of one of the lateral leaflets was at the center of a graduated arc placed close behind the leaflet. A fine glass filament was fixed to the leaf so as to project like a continuation of the midrib. This filament acted as an index, and as the leaf rose and fell rotating about its basal joint, its angular movement could be recorded by reading off at short intervals of time the position of the glass filament on the graduated arc. In order to avoid errors of parallax, all readings were made by looking through a small ring painted on the vertical glass in a line with the joint of the leaflet and the center of the graduated arc. In the following diagrams, the ordinates represent the angles which the leaflet made with the vertical at successive instants. 7. It follows that a fall in the curve represents an actual dropping of the leaf, and that the zero line represents a vertically dependent position. Fig 133 represents the nature of the movements which occur in the evening as soon as the leaflets begin to assume their nocturnal position. At 4P Roman 1000, the leaflet formed an angle of 85 with the vertical, or was only 5 below the horizontal. But in order that the diagram might get into our page, the leaflet is represented falling from 75 instead of 85. Shortly after 6P Roman 1000, it hung vertically down, and had attained its nocturnal position between 6 and 6P Roman 1000. It performed a number of minute oscillations of about 2 each, occupying periods of 4 or 5 Roman 1000. The complete state of rest of the leaflet which ultimately followed is not shown in the diagram. It is manifest that each oscillation consists of a gradual rise followed by a sudden fall. Each time the leaflet fell, it approached nearer to the nocturnal position than it did on the previous fall. The amplitude of the oscillations diminished, while the periods of oscillation became shorter. Fig 132, a Varroa bilimbi leaf asleep drawing reduced. Fig 133, a Varroa bilimbi angular movements of a leaflet during its evening descent, when going to sleep. Temp 7881F. In bright sunshine, the leaflets assume a highly inclined dependent position. A leaflet in diffused light was observed rising for 25 Roman 1000 A blind, was then pulled up so that the plant was brightly illuminated BR in Fig 134, and within a minute it began to fall, and ultimately fell 47 as shown in the diagram. This descent was performed by 6 descending steps, precisely similar to those by which the nocturnal fall is effected. The plant was then again shaded SH, and a long slow rise occurred until another series of falls commenced at BR, when the sun was again admitted. In this experiment, cool air was allowed to enter by the windows being opened at the same time that the blinds were pulled up, so that in spite of the sun shining on the plant, the temperature was not raised. The effect of an increase of temperature in diffused light is shown in Fig 135. The temperature began to rise at 11 A Roman 1000, in consequence of the fire being lighted, but by 12 a marked fall had occurred. It may be seen in the diagram that when the temperature was highest, there were rapid oscillations of small amplitude, the mean position of the leaflet being at the time nearer the vertical. When the temperature began to fall, the oscillations became slower and larger, and the mean position of the leaf again approached the horizontal. The rate of oscillation was sometimes quicker than is represented in the above diagram. Thus, when the temperature was between 31 and 32 Roman 114, oscillations of a few degrees occurred in 19 Roman 1000. On the other hand, an oscillation may be much slower. Thus a leaflet was observed temperature 25 Roman 100 to rise during 40 Roman 1000 before it fell, and completed its oscillation. Fig. 134, a varroa bilimbi angular movements of leaflet, during a change from bright illumination to shade temperature broken line, remaining nearly the same. Fig. 135, a varroa bilimbi angular movement of leaflet, during a change of temperature light, remaining the same. The broken line shows the change of temperature. Fig. 136, Porleria hygrometrica circumnutation, and nyctotropic movements of petiole of leaf traced from 9a Roman 1000 July 7th to about midnight on the 8th apex of leaf 712 inches, from the vertical glass temp 19,122,012, Roman 100 Porleria hygrometrica, zygophyll. The leaves of this plant Chilean form are from 1 to 112 inch in length and bear as many as 16 or 17 small leaflets on each side, which do not stand opposite one another. They are articulated to the petiole, and the petiole to the branch by a pulvinus. We must premise that apparently two forms are confounded under the same name. The leaves on a bush from Chile, which was sent to us from Kew, bore many leaflets, whilst those on plants in the Botanic Garden at Wurzburg bore only 8 or 9 pairs, and the whole character of the bushes appeared somewhat different. We shall also see that they differ in a remarkable physiological peculiarity. On the Chilean plant, the petioles of the younger leaves on upright branches stood horizontally during the day, and at night sank down vertically, so as to depend parallel and close to the branch beneath. The petioles of rather older leaves did not become at night vertically depressed, but only highly inclined. In one instance, we found a branch which had grown perpendicularly downwards, and the petioles on it moved in the same direction relatively to the branch, as just stated, and therefore moved upwards on horizontal branches. The younger petioles likewise move at night in the same direction as before, that is, towards the branch, and are consequently then extended horizontally. But it is remarkable that the older petioles on the same branch, though moving a little in the same direction, also bend downwards. They thus occupy a somewhat different position relatively to the centre of the earth, and to the branch from that of the petioles on the upright branches. With respect to the leaflets, they move at night towards the apex of the petiole until their midribs stand nearly parallel to it, and they then lie neatly imbricated one over the other. Thus half of the upper surface of each leaflet is in close contact with half of the lower surface of the one next in advance, and all the leaflets excepting the basal ones have the whole of their upper surfaces and half of their lower surfaces well protected. Those on the opposite sides of the same petiole do not come into close contact at night, as occurs with the leaflets of so many leguminosae, but are separated by an open furrow, nor could they exactly coincide, as they stand alternately with respect to one another. The circumnutation of the petiole of a leaf 34 of an inch in length on an upright branch was observed during 36h, and is shown in the preceding diagram. Fig. 136. On the first morning, the leaf fell a little, and then rose until 1 p Roman 1000, and this was probably due to its being now illuminated through a skylight from above it, then circumnutated on a very small scale round the same spot, until about 4 p Roman 1000, when the great evening fall commenced during the latter part of the night, or very early on the next morning. The leaf rose again on the second day. It fell during the morning, till 1 p Roman 1000, and this no doubt is its normal habit from 1 to 4 p Roman 1000. It rose in a zigzag line, and soon afterwards the great evening fall commenced. It thus completed a double oscillation during the 24h. The specific name given to this plant by Ruiz and Pavon indicates that in its native arid home it is affected in some manner by the dryness or dampness of the atmosphere. 8. In the Botanic Garden at Wurzburg, there was a plant in a pot out of doors, which was daily watered, and another in the open ground, which was never watered after some hot and dry weather. There was a great difference in the state of the leaflets on these two plants, those on the unwatered plant in the open ground remaining half or even quite closed during the day, but twigs cut from this bush with their ends standing in water or wholly immersed in it, or kept in damp air under a bell glass, opened their leaves, though exposed to a blazing sun, whilst those on the plant in the ground remained, closed the leaves on this same plant, after some heavy rain remained open for 2 days, they then became half closed during 2 days, and after an additional day were quite closed, this plant was now copiously watered, and on the following morning the leaflets were fully expanded. The other plant, growing in a pot, after having been exposed to heavy rain, was placed before a window in the laboratory with its leaflets open, and they remained so during the daytime for 48 h. But after an additional day were half closed, the plant was then watered, and the leaflets on the 2 following days remained open. On the 3rd day they were again half closed, but on being again watered remained open during the 2 next days. From these several facts, we may conclude that the plant soon feels the want of water, and that as soon as this occurs it, partially or quite, closes its leaflets, which in their then imbricated condition expose a small surface to evaporation. It is therefore probable that this sleep-like movement, which occurs only when the ground is dry, is an adaptation against the loss of moisture. A bush about 4 feet in height, a native of Chile, which was thickly covered with leaves, behaved very differently, for during the day it never closed its leaflets. On July 6 the earth in the small pot in which it grew appeared extremely dry, and it was given a very little water after 21 and 22 days on the 27th and 28th, during the whole of which time the plant did not receive a drop of water. The leaves began to droop, but they showed no signs of closing during the day. It appeared almost incredible that any plant except a fleshy one could have kept alive in soil so dry, which resembled the dust on a road. On the 29th, when the bush was shaken, some leaves fell off, and the remaining ones were unable to sleep at night. It was therefore moderately watered as well as syringed late in the evening. On the next morning, 30th, the bush looked as fresh as ever, and at night the leaves went to sleep. It may be added that a small branch while growing on the bush was enclosed by means of a curtain of bladder during 13 days in a large bottle half full of quicklime, so that the air within must have been intensely dry, yet the leaves on this branch did not suffer in the least, and did not close at all during the hottest days. Another trial was made with the same bush on August 2nd and 6th, the soil appearing at this latter date extremely dry, for it was exposed out of doors during the whole day to the wind, but the leaflets showed no signs of closing. The Chilean form therefore differs widely from the one at Wurzburg in not closing its leaflets when suffering from the want of water, and it can live for a surprisingly long time without water. Tropiolum majus cultivated var tropioli. Several plants in pots stood in the greenhouse, and the blades of the leaves, which faced the front lights, were during the day highly inclined, and at night vertical, whilst the leaves on the back of the pots, though of course illuminated through the roof, did not become vertical at night. We thought at first that this difference in their positions was in some manner due to heliotropism, for the leaves are highly heliotropic. The true explanation, however, is that unless they are well illuminated during at least a part of the day, they do not sleep at night, and a little difference in the degree of illumination determines whether or not they shall become vertical at night. We have observed no other so well marked a case as this of the influence of previous illumination on nyctotropic movements. The leaves present also another peculiarity in their habit of rising or awaking in the morning, being more strongly fixed or inherited than that of sinking or sleeping at night. The movements are caused by the bending of an upper part of the petiole between 12 and 1 inch in length, but the part close to the blade, for about 14 of an inch in length, does not bend, and always remains at right angles to the blade. The bending portion does not present any external or internal difference in structure from the rest of the petiole. We will now give the experiments on which the above conclusions are founded. A large pot with several plants was brought on the morning of Sept. 3rd out of the greenhouse, and placed before a northeast window in the same position as before with respect to the light as far as that was possible on the front of the plants. 24 leaves were marked with thread, some of which had their blades horizontal, but the greater number were inclined at about 45 beneath the horizon at night. All these without exception became vertical early on the following morning. 4th, they reassumed their former positions, and at night again became vertical. On the 5th, the shutters were opened at 6A Roman 1000, and by 8A Roman 1000, after the leaves had been illuminated for 2H3 Roman 1000, and had acquired their diurnal position, they were placed in a dark cupboard. They were looked at twice during the day and thrice in the evening, the last time at 10P Roman 1000, and not one had become vertical. At 8A Roman 1000 on the following morning 6th, they still retained the same diurnal position, and were now replaced. Before the northeast window at night all the leaves which had faced the light had their petioles curved, and their blades vertical, whereas none of the leaves on the back of the plants, although they had been moderately illuminated, by the diffused light of the room were vertical, they were now at night placed in the same dark cupboard at 9 Roman 1000 on the next morning 7th. All those which had been asleep had reassumed their diurnal position. The pot was then placed for 3h in the sunshine, so as to stimulate the plants at noon. They were placed before the same northeast window, and at night the leaves slept in the usual manner, and awoke on the following morning at noon. On this day 8th, the plants, after having been left before the northeast window for 5h 45 Roman 1000, and thus illuminated though not brightly, as the sky was cloudy during the whole time, were replaced in the dark cupboard, and at 3p Roman 1000 the position of the leaves was very little if at all altered, so that they are not quickly affected by darkness, but by 10p Roman 1000 all the leaves which had faced the northeast sky during the 5h 45 Roman 1000 of illumination stood vertical, whereas those on the back of the plant retained their diurnal position. On the following morning 9th, the leaves awoke as on the two former occasions in the dark, and they were kept in the dark during the whole day. At night, a very few of them became vertical, and this was the one instance in which we observed any inherited tendency or habit in this plant to sleep at the proper time, that it was real sleep was shown by these same leaves reassuming their diurnal position on the following morning 10th, whilst still kept in the dark. The pot was then 9a Roman 1000th replaced, after having been kept for 36h in darkness before the northeast window, and at night the blades of all the leaves, excepting a few on the back of the plants, became conspicuously vertical. At 6a Roman 100,011th, after the plants had been illuminated on the same side as before during only 25 Roman 1000, the pot was turned round, so that the leaves which had faced the light now faced the interior of the room, and not one of these went to sleep at night, whilst some, but not many of those which had formerly stood facing the back of the room, and which had never before been well illuminated or gone to sleep, now assumed a vertical position at night. On the next day 12th, the plant was turned round into its original position, so that the same leaves faced the light as formerly, and these now went to sleep in the usual manner. We will only add that with some young seedlings kept in the greenhouse, the blades of the first pair of true leaves, the cotyledons being hypogene, stood during the day almost horizontally, and at night almost vertically. A few observations were subsequently made on the circumnutation of 3 leaves, whilst facing a northeast window, but the tracings are not given, as the leaves moved somewhat towards the light. It was however manifest that they rose and fell more than once during the daytime, the ascending and descending lines being in parts extremely zigzag. The nocturnal fall commenced about 7p Roman 1000, and the leaves had risen considerably by 6a Roman 1000 on the following morning. Leguminosae. This family includes many more genera with sleeping species than all the other families put together. The number of the tribes, to which each genus belongs according to Bentham and Hooker's arrangement, has been added. Crotalaria sp. Tribe 2, this plant is monophylous, and we are informed by Mr. T. Thiselton Dyer that the leaves rise up vertically at night and press against the stem. Lupinus Tribe 2, the palmate or digitate leaves of the species in this large genus sleep in 3 different manners. One of the simplest is that all the leaflets become steeply inclined downwards at night, having been during the day extended horizontally. This is shown in the accompanying figures. Fig. 137, of a leaf of Roman 50 pilosus as seen during the day from vertically above, and of another leaf asleep, with the leaflets inclined downwards. As in this position they are crowded together, and as they do not become folded like those in the genus Oxalis, they cannot occupy a vertically dependent position, but they are often inclined at an angle of 50 beneath the horizon in this species, whilst the leaflets are sinking. The petioles rise up in 2 instances, when the angles were measured to the extent of 23. The leaflets of Roman 50 subcarnosus and arboreus, which were horizontal during the day, sank down at night in nearly the same manner, the former to an angle of 38, and the latter of 36 beneath the horizon, but their petioles did not move in any plainly perceptible degree. It is however quite possible, as we shall presently see, that if a large number of plants of the 3 foregoing and of the following species were to be observed at all seasons, some of the leaves would be found to sleep in a different manner. Fig. 137, Lupinus pilosus, a leaf seen from vertically above in daytime, b leaf asleep, seen laterally at night. In the 2 following species, the leaflets, instead of moving downwards, rise at night, with Roman 50 Hartwige, some stood at noon at a mean angle of 36 above the horizon, and at night at 51, thus forming together a hollow cone with moderately steep sides. The petiole of one leaf rose 14, and of a second 11 at night, with Roman 50 luteus, A leaflet rose from 47 at noon to 65 above the horizon at night, and another on a distinct leaf rose from 45 to 69. The petioles, however, sink at night, to a small extent, viz. in 3 instances, by 2/6 and 9/30 seconds. Owing to this movement of the petioles, the outer and longer leaflets have to bend up a little more than the shorter and inner ones in order that all should stand symmetrically at night. We shall presently see that some leaves on the same individual plants of Roman 50 luteus sleep in a very different manner. We now come to a remarkable position of the leaves when asleep, which is common to several species of lupins on the same leaf. The shorter leaflets, which generally face the center of the plant, sink at night, whilst the longer ones on the opposite side rise, the intermediate and lateral ones merely twisting on their own axes. But there is some variability with respect to which leaflets rise or fall, as might have been expected from such diverse and complicated movements. The base of each leaflet is developed, at least in the case of Roman 50 luteus, into a pulvinus. The result is that all the leaflets on the same leaf stand at night more or less highly inclined, or even quite vertically, forming in this latter case a vertical star. This occurs with the leaves of a species purchased under the name of Roman 50 pubescens, and in the accompanying figures we see at a Fig 138 the leaves in their diurnal position, and at B the same plant at night with the 2 upper leaves having their leaflets almost vertical. At C another leaf viewed laterally is shown with the leaflets quite vertical. It is chiefly or exclusively the youngest leaves which form at night vertical stars, but there is much variability in the position of the leaves at night on the same plant, some remaining with their leaflets almost horizontal, others forming more or less highly inclined or vertical stars, and some with all their leaflets sloping downwards. As in our first class of cases, it is also a remarkable fact that although all the plants produced from the same lot of seeds were identical in appearance, yet some individuals at night had the leaflets of all their leaves arranged so as to form more or less highly inclined stars, others had them all sloping downwards and never forming a star, and others again retained them either in a horizontal position or raised them a little. Fig 138 Lupinus pubescens, a leaf viewed laterally during the day. B same leaf at night. C another leaf with the leaflet forming a vertical star at night. Figures reduced. We have as yet referred only to the different positions of the leaflets of Roman 50 pubescens at night, but the petioles likewise differ in their movements. That of a young leaf which formed a highly inclined star at night stood at noon at 42 above the horizon, and during the night at 72, so had risen 30. The petiole of another leaf, the leaflets of which occupied a similar position at night, rose only 6. On the other hand, the petiole of a leaf, with all its leaflets sloping down at night, fell at this time, for the petioles of 2 rather older leaves were subsequently observed, both of which stood during the day at exactly the same angle, viz. 50 above the horizon, and one of these rose 78, and the other fell 34 at night. We meet with cases like that of Roman 50 pubescens with some other species on a single plant of Roman 50 mutabilis. Some leaves which stood horizontally during the day formed highly inclined stars at night, and the petiole of one rose 7. Other leaves, which likewise stood horizontally during the day, had at night all their leaflets sloping downwards at 46 beneath the horizon, but their petioles had hardly moved again. Roman 50 luteus offered a still more remarkable case, for on 2 leaves, the leaflets which stood at noon at about 45 above the horizon rose at night to 65 and 69, so that they formed a hollow cone with steep sides. 4 leaves on the same plant which had their leaflets horizontal at noon formed vertical stars at night, and 3 other leaves equally horizontal at noon had all their leaflets sloping downwards at night, so that the leaves on this one plant assumed at night 3 different positions. Though we cannot account for this fact, we can see that such a stock might readily give birth to species having widely different nyctotropic habits. Little more need be said about the sleep of the species of Lupinus. Several, namely Roman 50 Polyphilus, Nanus menzica, Speciosus, and Albifrons, though observed out of doors and in the greenhouse, did not change the position of their leaves sufficiently at night to be said to sleep. From observations made on 2 sleeping species, it appears that, as with Tropiolum majus, the leaves must be well illuminated during the day in order to sleep at night, for several plants kept all day in a sitting room with northeast windows did not sleep at night, but when the pots were placed on the following day out of doors and were brought in at night, they slept in the usual manner. The trial was repeated on the following day and night with the same result. Some observations were made on the circumnutation of the leaves of Roman 50 luteus and arboreus. It will suffice to say that the leaflets of the latter exhibited a double oscillation in the course of 24h, for they fell from the early morning until 10 A. Roman 1000, then rose and zigzagged greatly, till 4 p. Roman 1000, after which hour the great nocturnal fall commenced by 8 a. Roman 1000 on the following morning. The leaflets had risen to their proper height. We have seen in the 4th chapter that the leaves of Lupinus speciosus, which do not sleep, circumnudate to an extraordinary extent, making many ellipses in the course of the day. Cytisus tribe 2, Trigonella and Medicago tribe 3. Only a few observations were made on these 3 genera. The petioles, on a young plant, about a foot in height of Cytisus fragrans, rose at night on one occasion 23, and on another 33, the 3 leaflets also bend upwards, and at the same time approach each other, so that the base of the central leaflet overlaps the bases of the 2 lateral leaflets. They bend up so much that they press against the stem, and on looking down on one of these young plants, from vertically above, the lower surfaces of the leaflets are visible, and thus their upper surfaces, in accordance with the general rule, are best protected from radiation, whilst the leaves on these young plants were thus behaving. Those on an old bush in full flower did not sleep at night. Fig. 139, Medicago marina, A leaves during the day, B leaves asleep at night. Trigonella cretica resembles a melilatus in its sleep, which will be immediately described, according to Roman 1000 Royer 9. The leaves of Medicago maculata rise up at night, and si renversant un più de manière, a presenter obliquement, ocil leur face inferiora. A drawing is here given. Fig. 139 of the leaves of Roman 1000 marina awake and asleep, and this would almost serve for Cytisus fragrans in the same 2 states. Melilatus tribe 3. The species in this genus sleep in a remarkable manner. The 3 leaflets of each leaf twist through an angle of 90, so that their blades stand vertically at night, with one lateral edge presented to the zenith. Fig. 140. We shall best understand the other and more complicated movements if we imagine ourselves always to hold the leaf with the tip of the terminal leaflet pointed to the north. The leaflets, in becoming vertical at night, could of course twist, so that their upper surfaces should face to either side, but the 2 lateral leaflets always twist, so that this surface tends to face the north, but as they move at the same time towards the terminal leaflet, the upper surface of the one faces about NNW, and that of the other NNE. The terminal leaflet behaves differently, for it twists to either side, the upper surface facing sometimes east and sometimes west, but rather more commonly west than east. The terminal leaflet also moves in another and more remarkable manner, for whilst its blade is twisting and becoming vertical, the whole leaflet bends to one side, and invariably to the side towards which the upper surface is directed, so that if this surface faces the west, the whole leaflet bends to the west, until it comes into contact with the upper and vertical surface of the western lateral leaflet. Thus the upper surface of the terminal and of one of the 2 lateral leaflets is well protected. The fact of the terminal leaflet twisting indifferently to either side and afterwards bending to the same side seemed to us so remarkable that we endeavoured to discover the cause. We imagined that at the commencement of the movement it might be determined by one of the 2 halves of the leaflet being a little heavier than the other. Therefore bits of wood were gummed on one side of several leaflets, but this produced no effect, and they continued to twist in the same direction as they had previously done. In order to discover whether the same leaflet twisted permanently in the same direction, black threads were tied to 20 leaves, the terminal leaflets of which twisted, so that their upper surfaces faced west, and 14 white threads to leaflets which twisted to the east. These were observed occasionally during 14 days, and they all continued, with a single exception, to twist and bend in the same direction, for one leaflet, which had originally faced east, was observed after 9 days to face west. The seat of both the twisting and bending movement is in the pulvinus of the subpetioles. Fig. 140, Melilatus officinalis, a leaf during the daytime, B another leaf asleep. See a leaf asleep as viewed from vertically above, but in this case the terminal leaflet did not happen to be in such close contact with the lateral one as is usual. We believe that the leaflets, especially the 2 lateral ones, in performing the above described complicated movements, generally bend a little downwards, but we are not sure of this, for as far as the main petiole is concerned, its nocturnal movement is largely determined by the position which the leaf happens to occupy during the day. Thus one main petiole was observed to rise at night 59, whilst 3 others rose only 7 and 9. The petioles and subpetioles are continually circumnudating during the whole 24h, as we shall presently see. The leaves of the following 15 species, Roman 1000 officinalis, sui volans, parviflora alba, infesta dentata gracilis sulcata elegans, coerulia petitpirina macrohyza italica secundiflora, and torica sleep, in nearly the same manner as just described. but the bending to one side of the terminal leaflet is apt to fail unless the plants are growing vigorously. With Roman 1000 Petitpirina and Secundiflora, the terminal leaflet was rarely seen to bend to one side in young plants of Roman 1000 Italica. It bent in the usual manner, but with old plants in full flower growing in the same pot, and observed at the same hour, viz. 8p Roman 1000, none of the terminal leaflets on several scores of leaves had bent to one side, though they stood vertically, nor had the two lateral leaflets, though standing vertically, moved towards the terminal one at 10p Roman 1000, and again 1 hour after midnight, the terminal leaflets had become very slightly bent to one side, and the lateral leaflets had moved a very little towards the terminal one, so that the position of the leaflets even at this late hour was far from the ordinary one. Again, with Roman 1000 Taurica, the terminal leaflets were never seen to bend towards either of the two lateral leaflets, though these, whilst becoming vertical, had bent towards the terminal one. The subpetiole of the terminal leaflet in this species is of unusual length, and if the leaflet had bent to one side, its upper surface could have come into contact only with the apex of either lateral leaflet, and this perhaps is the meaning of the loss of the lateral movement. The cotyledons do not sleep at night. The first leaf consists of a single orbicular leaflet which twists at night, so that the blade stands vertically. It is a remarkable fact that with Roman 1000 Taurica, and in a somewhat less degree with Roman 1000 Macrorhiza and Petitpirina, all the many small and young leaves produced during the early spring from shoots on some cut-down plants in the greenhouse slept in a totally different manner from the normal one, for the three leaflets, instead of twisting on their own axes, so as to present their lateral edges to the zenith, turned upwards, and stood vertically with their apices pointing to the zenith. They thus assumed nearly the same position as in the allied genus Trifolium, and on the same principle that embryological characters reveal the lines of descent in the animal kingdom, so the movements of the small leaves in the above three species of Melilotus perhaps indicate that this genus is descended from a form which was closely allied to, and slept like a Trifolium. Moreover, there is one species, Roman 1000 Messinensis, the leaves of which on full-grown plants between 2 and 3 feet in height sleep like the foregoing small leaves, and like those of a Trifolium. We were so much surprised at this latter case, that until the flowers and fruit were examined, we thought that the seeds of some Trifolium had been sown by mistake, instead of those of a Melilotus. It appears therefore probable that Roman 1000 Messinensis has either retained or recovered a primordial habit. The circumnutation of a leaf of Roman 1000 officinales was traced, the stem being left free, and the apex of the terminal leaflet described 3 laterally extended ellipses between 8a Roman 1000 and 4p Roman 1000. After the latter hour, the nocturnal twisting movement commenced. It was afterwards ascertained that the above movement was compounded of the circumnutation of the stem on a small scale of the main petiole, which moved most, and of the subpetiole of the terminal leaflet, the main petiole of a leaf having been secured to a stick close to the base of the subpetiole of the terminal leaflet. The latter described 2 small ellipses between 10a Roman 1000 and 2p Roman 1000 at 7p Roman 1000. After this same leaflet, as well as another, had twisted themselves into their vertical nocturnal position, they began to rise slowly, and continued to do so until 10p Roman 1000, after which hour they were no longer observed. As Roman 1000 Messinensis sleeps in an anomalous manner, unlike that of any other species in the genus, the circumnutation of a terminal leaflet with the stem secured was traced during 2 days. On each morning the leaflet fell until about noon, and then began to rise very slowly, but on the first day the rising movement was interrupted between 1 and 3p Roman 1000 by the formation of a laterally extended ellipse, and on the second day at the same time by 2 smaller ellipses. The rising movement then recommenced, and became rapid late in the evening, when the leaflet was beginning to go to sleep. The awaking or sinking movement had already commenced by 6a Roman 1000 on both mornings. Trifolium tribe 3, the nyctotropic movements of 11 species were observed, and were found to be closely similar if we select a leaf of T. repens having an upright petiole, and with the 3 leaflets expanded horizontally. The 2 lateral leaflets will be seen in the evening to twist and approach each other until their upper surfaces come into contact. At the same time they bend downwards in a plane at right angles to that of their former position, until their midribs form an angle of about 45 with the upper part of the petiole. This peculiar change of position requires a considerable amount of torsion in the pulvinus. The terminal leaflet merely rises up without any twisting and bends over, until it rests on and forms a roof over the edges of the now vertical and united lateral leaflets. Thus the terminal leaflet always passes through an angle of at least 90, generally of 130 or 140, and not rarely, as was often observed with T. subterraneum off 180. In this latter case, the terminal leaflet stands at night horizontally, as in Fig 141, with its lower surface fully exposed to the zenith, besides the difference in the angles at which the terminal leaflets stand at night in the individuals of the same species. The degree to which the lateral leaflets approach each other often likewise differs. Fig 141 trifolium repends a leaf during the day, be leaf asleep at night. We have seen that the cotyledons of some species, and not of others, rise up vertically at night. The first true leaf is generally unifoliate and orbicular. It always rises, and either stands vertically at night or, more commonly, bends a little over so as to expose the lower surface obliquely to the zenith in the same manner as does the terminal leaflet of the mature leaf, but it does not twist itself like the corresponding first simple leaf of Melilotus. With T. panonicum, the first true leaf was generally unifoliate, but sometimes trifoliate or again partially lobed, and in an intermediate condition. Circumnutation Sachs described in 186,310 the spontaneous up and down movements of the leaflets of T. incarnatum when kept in darkness. Pfeffer made many observations on the similar movements in T. pratense 11. He states that the terminal leaflet of this species observed at different times passed through angles of from 30 to 120, in the course of from 112 to 4h. We observed the movements of T. subterraneum resupinatum and repens. Trifolium subterraneum a petiole was secured close to the base of the three leaflets, and the movement of the terminal leaflet was traced during 2612h, as shown in the figure on the next page. Between 6a Roman 1000 and 6p Roman 1000, the apex moved 3 times up and 3 times down, completing 3 ellipses in 11h 15 Roman 1000. The ascending and descending lines stand nearer to one another than is usual with most plants, yet there was some lateral motion. At 6p Roman 1000, the great nocturnal rise commenced, and on the next morning the sinking of the leaflet was continued until 8a Roman 1000, after which hour it circumnutated in the manner just described in the figure. The great nocturnal rise and the morning fall are greatly abbreviated from the want of space, and are merely represented by a short curved line. The leaflet stood horizontally, when at a point a little beneath the middle of the diagram, so that during the daytime it oscillated almost equally above and beneath a horizontal position. At 8a Roman 1000, it stood 48 beneath the horizon, and by 11a Roman 1000, it had risen 50 above the horizon, so that it passed through 98 in 3h. By the aid of the tracing, we ascertained that the distance travelled in the 3h by the apex of this leaflet was 1 inch. If we look at the figure and prolong upwards in our minds the short curved broken line, which represents the nocturnal course, we see that the latter movement is merely an exaggeration or prolongation of one of the diurnal ellipses. The same leaflet had been observed on the previous day, and the course then pursued was almost identically the same as that here described. Fig 142 trifolium subterraneum circumnutation and nyctotropic movement of terminal leaflet 68 inch in length, traced from 6a Roman 1000 July 4th to 9a Roman 1000th apex of leaf, 378 inches from the vertical glass, and movement, as here shown, magnified 514 times, reduced to 1/2 of original scale plant, illuminated from above temp, 1617 Roman 100 trifolium resupinatum, a plant left entirely free, was placed before a northeast window in such a position that a terminal leaflet projected at right angles to the source of the light. The sky being uniformly clouded all day, the movements of this leaflet were traced during 2 days, and on both were closely similar. Those executed on the second day are shown in Fig 143. The obliquity of the several lines is due partly to the manner in which the leaflet was viewed, and partly to its having moved a little towards the light from 7a Roman 1000 to 8a Roman 1000. The leaflet fell, that is, the awakening movement was continued. It then rose, and moved a little laterally towards the light. At 12 it retrograded, and at 2 resumed its original course. Having thus completed a small ellipse during the middle of the day and the evening, it rose rapidly, and by 8a Roman 1000 on the following morning had returned to exactly the same spot as on the previous morning. The line representing the nocturnal course ought to be extended much higher up, and is here abbreviated into a short curved broken line. The terminal leaflet therefore of this species described during the daytime, only a single additional ellipse instead of two additional ones as in the case of T. subterraneum, but we should remember that it was shown in the 4th chapter that the stem circumnudates as no doubt does the main petiole, and the subpetioles, so that the movement represented in Fig. 143 is a compounded one. We tried to observe the movements of a leaf kept during the day in darkness, but it began to go to sleep after 2H15 Roman 1000, and this was well pronounced after 4H30 Roman 1000 Fig. 143 trifolium resupinatum circumnutation, and nyctotropic movements of the terminal leaflet during 24 hours. Trifolium repensae stem was secured close to the base of a moderately old leaf, and the movement of the terminal leaflet was observed during 2 days. This case is interesting solely from the simplicity of the movements in contrast with those of the two preceding species. On the first day, the leaflet fell between 8A Roman 1000 and 3P Roman 1000, and on the second between 7A Roman 1000 and 1P Roman 1000. On both days, the descending course was somewhat zigzag, and this evidently represents the circumnudating movement of the two previous species during the middle of the day after 1P Roman 1000 arced first Fig. 140. The leaflet began to rise, but the movement was slow on both days both before and after this hour, until 4P Roman 1000, the rapid evening and nocturnal rise then commenced. Thus in this species the course during 24H consists of a single great ellipse in T resupinatum of 2 ellipses, one of which includes the nocturnal movement, and is much elongated, and in T subterraneum of 3 ellipses, of which the nocturnal one is likewise of great length. Securigera coronilla, tribe 4. The leaflets which stand opposite one another, and are numerous rise up at night, come into close contact, and bend backwards at a moderate angle towards the base of the petiole. Fig. 144 trifolium repends circumnutation and nyctotropic movements of a nearly full-grown terminal leaflet, traced on a vertical glass, from 7A Roman 1000 sept 30th to 8A Roman 1000 arced, first nocturnal course, represented by curved broken line, much abbreviated. Lotus tribe 4. The nyctotropic movements of 10 species in this genus were observed and found to be the same. The main petiole rises a little at night, and the 3 leaflets rise till they become vertical, and at the same time approach each other. This was conspicuous with Roman 50 Jacobous, in which the leaflets are almost linear in most of the species. The leaflets rise so much as to press against the stem, and not rarely they become inclined a little inwards, with their lower surfaces exposed obliquely to the zenith. This was clearly the case with Roman 50 major, as its petioles are unusually long, and the leaflets are thus enabled to bend further inwards. The young leaves on the summits of the stems, close up at night so much as often to resemble large buds. The stipule-like leaflets, which are often of large size, rise up like the other leaflets and press against the stem. Fig. 145. All the leaflets of Roman 50 Gebellae, and probably of the other species, are provided at their bases with distinct pulvini of a yellowish color, and formed of very small cells. The circumnutation of a terminal leaflet of Roman 50 peregrinus, with the stem secured, was traced during 2 days, but the movement was so simple that it is not worthwhile to give the diagram. The leaflet fell slowly from the early morning till about 1P Roman 1000. It then rose gradually at first, but rapidly late in the evening. It occasionally stood still for about 20 Roman 1000 during the day, and sometimes zigzagged a little. The movement of one of the basal stipule-like leaflets was likewise traced in the same manner, and at the same time, and its course was closely similar to that of the terminal leaflet. Fig. 145. Lotus creticus A stem, with leaves awake during the day. B, with leaves asleep at night. SS stipule-like leaflets. In tribe 5 of Bentham and Hooker, the sleep movements of species in 12 genera have been observed by ourselves and others, but only in Robinia with Enicaire Soralia acalis raises its 3 leaflets at night, whilst Amorpha fruticosa, 12 Dahlia alopecuroids and Indigo fratinctoria depress them. Dutch Art 13 states that Tephrosia caribea is the sole example of folioles couches le long du pétiole, et vers la base, but a similar movement occurs, as we have already seen, and shall again see in other cases. Wisteria sinensis. According to Royer 14, a base less folioles qui par une disposition, bizarre sont inclines dans la même fuel les supérieurs, vers le sommet les inférieurs vers la base du pétiole commune, but the leaflets on a young plant observed by us in the greenhouse merely sank vertically downwards at night. The leaflets are raised in Spherifissa solsola colutea arborea and Astragalus uliginosus, but are depressed according to Linus in Glycyrrhiza. The leaflets of Robinia pseudoacacia likewise sink vertically down at night, but the petioles rise a little, viz. in one case 3, and in another 4. The circumnudating movements of a terminal leaflet on a rather old leaf were traced during 2 days, and were simple. The leaflet fell slowly in a slightly zigzag line from 8a Roman 1000 to 5p Roman 1000, and then more rapidly by 7a Roman 1000 on the following morning. It had risen to its diurnal position. There was only one peculiarity in the movement, namely, that on both days there was a distinct though small oscillation up and down between 8 and 10a Roman 1000, and this would probably have been more strongly pronounced if the leaf had been younger. Coronilla rosea tribe 6. The leaves bear 9 or 10 pairs of opposite leaflets, which during the day stand horizontally with their midribs at right angles to the petiole. At night they rise up so that the opposite leaflets come nearly into contact, and those on the younger leaves into close contact. At the same time they bend back towards the base of the petiole, until their midribs form with it angles of from 40 to 50 in a vertical plane, as here figured Fig 146. The leaflets, however, sometimes bend so much back that their midribs become parallel to and lie on the petiole. They thus occupy a reversed position to what they do in several leguminosae, for instance in Mimosa pudica, but from standing further apart they do not overlap one another nearly so much as in this latter plant. The main petiole is curved slightly downwards during the day but straightens itself at night. In 3 cases, it rose from 3 above the horizon at noon to 9 at 10p Roman 1000, from 11 to 33, and from 5 to 33, the amount of angular movement in this latter case amounting to 28. In several other species of Coronilla, the leaflets showed only feeble movements of a similar kind. Fig 146. Coronilla rosea leaf asleep. Hedysarum coronarium tribe 6. The small lateral leaflets on plants growing out of doors rose up vertically at night, but the large terminal one became only moderately inclined. The petioles apparently did not rise at all. Smithia fundii tribe 6. The leaflets rise up vertically, and the main petiole also rises considerably. Arachis hypogea tribe 6. The shape of a leaf with its 2 pairs of leaflets is shown at a Fig 147, and a leaf asleep traced from a photograph made by the aid of aluminum light is given at B. The 2 terminal leaflets twist round at night until their blades stand vertically and approach each other until they meet at the same time, moving a little upwards and backwards. The 2 lateral leaflets meet each other in this same manner, but move to greater extent forwards, that is, in a contrary direction to the 2 terminal leaflets, which they partially embrace. Thus all 4 leaflets form together a single packet, with their edges directed to the zenith, and with their lower surfaces turned outwards on a plant which was not growing vigorously. The closed leaflets seemed too heavy for the petioles to support them in a vertical position, so that each night the main petiole became twisted, and all the packets were extended horizontally, with the lower surfaces of the leaflets on one side, directed to the zenith in a most anomalous manner. This fact is mentioned solely as a caution, as it surprised us greatly, until we discovered that it was an anomaly. The petioles are inclined upwards during the day, but sink at night, so as to stand at about right angles with the stem. The amount of sinking was measured only on one occasion, and, found to be 39, a petiole was secured to a stick at the base of the 2 terminal leaflets, and the circumnudating movement of one of these leaflets was traced from 6a Roman 1000 to 10p Roman 1000. The plant being illuminated from above, the temperature was 171,712 Roman 100, and therefore rather too low. During the 16h, the leaflet moved thrice up and thrice down, and as the ascending and descending lines did not coincide, 3 ellipses were formed. Fig 147. Arachis hypogea, a leaf during the day seen from vertically above B. Leaf asleep seen, laterally copied from a photograph, figures much reduced. Fig 148. Desmodium gyrans leaf seen from above reduced to 1/2 natural, size. The minute stipules unusually large. Desmodium gyrans tribe 6a. Large and full-grown leaf of this plant, so famous for the spontaneous movements of the 2 little lateral leaflets, is here represented. Fig 148. The large terminal leaflet sleeps by sinking vertically down, whilst the petiole rises up. The cotyledons do not sleep, but the first formed leaf sleeps equally well as the older ones. The appearance presented by a sleeping branch, and one in the daytime, copied from 2 photographs, are shown at A and B. Fig 149, and we see how at night the leaves are crowded together, as if for mutual protection, by the rising of the petioles. The petioles of the younger leaves near the summits of the shoots rise up at night, so as to stand vertical and parallel to the stem, whilst those on the sides were found in 4 cases to have risen respectively 46-12, 36-20 and 19 above the inclined positions which they had occupied during the day. For instance, in the first of these 4 cases, the petiole stood in the day at 23, and at night at 69-12 above the horizon. In the evening, the rising of the petioles is almost completed before the leaflets sink perpendicularly downwards. Circumnutation. The circumnudating movements of 4 young shoots were observed during 5H15 Roman 1000, and in this time each completed an oval figure of small size. The main petiole also circumnudates rapidly, for in the course of 31 Roman 1000 temp 91, it changed its course by as much as a rectangle, 6 times, describing a figure which apparently represented 2 ellipses. The movement of the terminal leaflet, by means of its subpetiole or pulvinus, is quite as rapid or even more so than that of the main petiole, and has much greater amplitude. Pfeffer has seen 15 these leaflets move through an angle of 8 in the course of from 10 to 30 seconds. Fig 149. Desmodium gyrans a stem during the day. B stem, with leaves asleep. Figures reduced. A fine, nearly full-grown leaf on a young plant 8 inches in height, with the stem secured to a stick at the base of the leaf, was observed from 8A Roman 1000 June 22nd to 8A Roman 1000 June 24th. In the diagram given on the next page, Fig 150, the 2 curved broken lines at the base, which represent the nocturnal courses, ought to be prolonged far downwards. On the first day, the leaflet moved thrice down and thrice up, and, to a considerable distance laterally, the course was also remarkably crooked. The darts were generally made every hour. If they had been made every few minutes, all the lines would have been zigzag to an extraordinary degree. With here and there a loop formed, we may infer that this would have been the case, because 5 darts were made in the course of 31 Roman 1000 between 12 and 1 P Roman 1000, and we see in the upper part of the diagram how crooked the course here is. If only the first and last darts had been joined, we should have had a straight line exactly. The same fact may be seen in the lines representing the course between 2 P Roman 1000 and 3 P Roman 1000, when 6 intermediate darts were made, and again at 4 and 4, but the result was widely different after 6 P Roman 1000, that is, after the great nocturnal descent had commenced. For though 9 darts were then made in the course of 32 Roman 1000, when these were joined, see figure, the line thus formed was almost straight. The leaflets therefore begin to descend in the afternoon by zigzag lines, but as soon as the descent becomes rapid, their whole energy is expended in thus moving, and their course becomes rectilinear. After the leaflets are completely asleep, they move very little or not at all. Fig 150. Desmodium gyrans circumnutation and nyctotropic movement of leaf, 334 inches in length. Petiole, included during 48H filament, affixed to midrib of terminal leaflet, its apex 6 inches from the vertical glass diagram, reduced to 1/3 of original. Scale plant illuminated from above temp 1920 Roman 100, had the above plant been subjected to a higher temperature than 6770 F, the movements of the terminal leaflet would probably have been even more rapid and wider in extent than those shown in the diagram. For a plant was kept for some time in the hothouse at from 92-93 F, and in the course of 35 Roman 1000, the apex of a leaflet twice descended, and once ascended, travelling over a space of 1 inch in a vertical direction, and of 82 inch in a horizontal direction. Whilst thus moving, the leaflet also rotated on its own axis, and this was a point to which no attention had been before paid. For the plane of the blade differed by 41 after an interval of only a few minutes. Occasionally, the leaflet stood still for a short time. There was no jerking movement, which is so characteristic of the little lateral leaflets. A sudden and considerable fall of temperature causes the terminal leaflet to sink downwards. Thus a cut-off leaf was immersed in water at 95 F, which was slowly raised to 103 F, and afterwards allowed to sink to 70 F, and the subpetiole of the terminal leaflet then curved downwards. The water was afterwards raised to 120 F, and the subpetiole straightened itself. Similar experiments with leaves in water were twice repeated with nearly the same result. It should be added that water raised to even 122 F does not soon kill a leaf. A plant was placed in darkness at 8A Roman 1000, and at 2P Roman 1000 Roman 1E, after 5H 23 Roman 1000, though the leaflets had sunk considerably, they had by no means acquired their nocturnal vertically dependent position. Pfeffer, on the other hand, says 16, that this occurred with him in from 34H to 2H. Perhaps the difference in our results may be due to the plant, on which we experimented, being a very young and vigorous seedling. The movements of the little lateral leaflets, these, have been so often described that we will endeavor to be as brief as possible in giving a few new facts and conclusions. The leaflets sometimes quickly change their position by as much as nearly 180, and their subpetioles can then be seen to become greatly curved. They rotate on their own axes, so that their upper surfaces are directed to all points of the compass. The figure described by the apex is an irregular oval or ellipse. They sometimes remain stationary for a period in these several respects. There is no difference except in rapidity and extent between their movements and the lesser ones performed by the large terminal leaflet. Whilst making its great oscillations, the movements of the little leaflets are much influenced, as is well known, by temperature. This was clearly shown by immersing leaves with motionless leaflets in cold water, which was slowly raised to 103 F, and the leaflets then moved quickly, describing about a dozen little irregular circles in 40 Roman 1000. By this time, the water had become much cooler, and the movements became slower or almost ceased. It was then raised to 100 F, and the leaflets again began to move quickly. On another occasion, a tuft of fine leaves was immersed in water at 53 F, and the leaflets were of course motionless. The water was raised to 99, and the leaflets soon began to move. It was raised to 105, and the movements became much more rapid, each little circle or oval being completed in from 1 Roman 1000 S to 1 Roman 1000 S. There was, however, no jerking, and this fact may perhaps be attributed to the resistance of the water. Sachs states that the leaflets do not move until the surrounding air is as high as 71-72 F, and this agrees with our experience on full-grown or nearly full-grown plants, but the leaflets of young seedlings exhibit a jerking movement at much lower temperatures. A seedling was kept April 16 in a room for half the day where the temperature was steady at 64 F, and the one leaflet which it bore was continually jerking, but not so rapidly. As in the hothouse, the part was taken in the evening into a bedroom, where the temperature remained at 62 during nearly the whole night at 10 and 11 P Roman 1000, and at 1 A Roman 1000, the leaflet was still jerking rapidly. At 3 A Roman 1000 it was not seen to jerk, but was observed during only a short time. It was, however, now inclined at a much lower angle than that occupied at 1 A Roman 1000, at 6 A Roman 1000 temp 61, F. Its inclination was still less than before, and again less at 6 A Roman 1000. By 7 A Roman 1000, it had risen, and at 8 A Roman 1000 was again seen to jerk. This leaflet therefore was moving during the whole night, and the movement was by jerks up to 1 A Roman 1000, and possibly later, and again at 8 A Roman 1000, though the temperature was only 61 to 62 F. We must therefore conclude that the lateral leaflets produced by young plants differ somewhat in constitution from those on older plants. In the large genus Desmodium, by far the greater number of the species are trifoliate, but some are unifoliate, and even the same plant may bear uni- and trifoliate leaves. In most of the species, the lateral leaflets are only a little smaller than the terminal one. Therefore, the lateral leaflets of Roman 500 gyrans, c. Fig. 148, must be considered as almost rudimentary. They are also rudimentary in function, if this expression may be used, for they certainly do not sleep like the full-sized terminal leaflets. It is, however, possible that the sinking down of the leaflets between 1 A Roman 1000 and 6 A Roman 1000, as above described, may represent sleep. It is well known that the leaflets go on jerking during the early part of the night, but my gardener observed Oct. 13th a plant in the hothouse between 5 and 5 A Roman 1000, the temperature having been kept up to 82 F, and found that all the leaflets were inclined, but he saw no jerking movement until 6 A Roman 1000, by which time the terminal leaflet had risen, and was awake 2 days afterwards. Oct. 15th the same plant was observed by him at 4 A Roman 1000 temp 77 F, and he found that the large terminal leaflets were awake, though not quite horizontal, and the only cause which we could assign for this anomalous wakefulness was that the plant had been kept, for experimental purposes during the previous day, at an unusually high temperature. The little lateral leaflets were also jerking at this hour, but whether there was any connection between this latter fact and the subhorizontal position of the terminal leaflets, we do not know. Anyhow, it is certain that the lateral leaflets do not sleep like the terminal leaflets, and in so far they may be said to be in a functionally rudimentary condition, they are in a similar condition in relation to irritability, for if a plant be shaken or syringed, the terminal leaflets sink down to about 45 beneath the horizon, but we could never detect any effect thus produced on the lateral leaflets. Yet we are not prepared to assert positively that rubbing or pricking the pulvinus produces no effect. As in the case of most rudimentary organs, the leaflets are variable in size. They often depart from their normal position and do not stand opposite one another, and one of the two is frequently absent. This absence appeared in some, but not in all the cases, to be due to the leaflet having become completely confluent with the main petiole, as might be inferred from the presence of a slight ridge along its upper margin, and from the course of the vessels. In one instance there was a vestige of the leaflet in the shape of a minute point at the further end of the ridge. The frequent sudden and complete disappearance of one or both of the rudimentary leaflets is a rather singular fact, but it is a much more surprising one that the leaves which are first developed on seedling plants are not provided with them. Thus on one seedling the seventh leaf above the cotyledons was the first which bore any lateral leaflets, and then only a single one on another. Seedling the 11th leaf first bore a leaflet of the 9 succeeding leaves, 5 bore a single lateral leaflet, and 4 bore none at all. At last a leaf, the 21st above the cotyledons, was provided with 2 rudimentary lateral leaflets. From a widespread analogy in the animal kingdom, it might have been expected that these rudimentary leaflets would have been better developed and more regularly present on very young than on older plants, but bearing in mind, firstly, that long-lost characters sometimes reappear late in life, and secondly, that the species of Desmodium are generally trifoliate, but that some are unifoliate, the suspicion arises that Roman 500 gyrans is descended from a unifoliate species, and that this was descended from a trifoliate one, for in this case, both the absence of the little lateral leaflets on very young seedlings and their subsequent appearance may be attributed to reversion to more or less distant progenitors. 17. No one supposes that the rapid movements of the lateral leaflets of Roman 500 gyrans are of any use to the plant, and why they should behave in this manner is quite unknown. We imagined that their power of movement might stand in some relation with their rudimentary condition, and therefore observed the almost rudimentary leaflets of Mimosa albida vel sensitiva, of which a drawing will hereafter be given, Fig. 159, but they exhibited no extraordinary movements, and at night they went to sleep like the full-sized leaflets. There is, however, this remarkable difference in the two cases. In Desmodium, the pulvinus of the rudimentary leaflets has not been reduced in length, in correspondence with the reduction of the blade, to the same extent as has occurred in the mimosa, and it is on the length and degree of curvature of the pulvinus that the amount of movement of the blade depends. Thus the average length of the pulvinus in the large terminal leaflets of Desmodium is 3 Roman 2000, whilst that of the rudimentary leaflets is 2 Roman 2000, so that they differ only a little in length, but in diameter they differ much, that of the pulvinus of the little leaflets being only 0 Roman 2000 to 0 Roman 2000, whilst that of the terminal leaflets is 1 Roman 2000. If we now turn to the mimosa, we find that the average length of the pulvinus of the almost rudimentary leaflets is only 0 Roman 2000, or rather more than a quarter of the length of the pulvinus of the full-sized leaflets, namely 1 Roman 2000. In this small reduction in length of the pulvinus of the rudimentary leaflets of Desmodium, we apparently have the proximate cause of their great and rapid circumnudating movement, in contrast with that of the almost rudimentary leaflets of the mimosa. The small size and weight of the blade, and the little resistance opposed by the air to its movement, no doubt also come into play, for we have seen that these leaflets, if immersed in water when the resistance would be much greater, were prevented from jerking forwards. Why during the reduction of the lateral leaflets of Desmodium, or during their reappearance, if they owe their origin to reversion, the pulvinus should have been so much less affected than the blade, whilst with the mimosa the pulvinus has been greatly reduced, we do not know. Nevertheless, it deserves notice that the reduction of the leaflets in these two genera has apparently been effected by a different process, and for a different end, for with the mimosa, the reduction of the inner and basal leaflets was necessary from the want of space, but no such necessity exists with Desmodium, and the reduction of its lateral leaflets seems to have been due to the principle of compensation, in consequence of the great size of the terminal leaflet Uraria tribe 6 and Centrosma tribe 8. The leaflets of Uraria lagopus and the leaves of a Centrosma from Brazil both sink vertically down at night. In the latter plant, the petiole at the same time rose. 1612. Amphicarpia monoica tribe 8. The leaflets sink down vertically at night, and the petioles likewise fall considerably. A petiole, which was carefully observed, stood during the day 25 above the horizon, and at night 32 below it. It therefore fell 57. A filament was fixed transversely across the terminal leaflet, of a fine young leaf 14 inches in length, including the petiole, and the movement of the whole leaf was traced on a vertical glass. This was a bad plan in some respects, because the rotation of the leaflet, independently of its rising or falling, raised and depressed the filament, but it was the best plan for our special purpose of observing whether the leaf moved much after it had gone to sleep. The plant had twined closely round a thin stick so that the circumnutation of the stem was prevented. The movement of the leaf was traced during 48H from 9 Roman 1000 July 10th to 9 Roman 1000 July 12th. In the figure given, Fig. 151, we see how complicated its course was on both days. During the second day, it changed its course greatly 13 times. The leaflets began to go to sleep a little after 6 P Roman 1000, and by 7 P Roman 1000 hung vertically down and were completely asleep, but on both nights they continued to move from 7 P Roman 1000 to 10 and 10 P Roman 1000, quite as much as during the day. And this was the point which we wished to ascertain. We see in the figure that the great sinking movement late in the evening does not differ essentially from the circumnutation during the day. Fig. 151, Amphicarpia monoica circumnutation and nyctotropic movement of leaf during 48H, its apex 9 inches from the vertical glass figure, reduced to 1/3 of original scale plant, illuminated from above temp, 17,121,812. Roman 100 glycine hispida, tribe 8. The 3 leaflets sink vertically down at night. Erythrina tribe 8. 5 species were observed, and the leaflets of all sank vertically down at night with E. caphra, and with a second unnamed species, the petioles at the same time rose slightly. The movements of the terminal leaflet of E. christogalli, with the main petiole secured to a stick, were traced from 6 A Roman 1000 June 8th to 8 A Roman 1000 on the 10th. In order to observe the nyctotropic movements of this plant, it is necessary that it should have grown in a warm greenhouse for out of doors in our climate. It does not sleep. We see in the tracing Fig. 152 that the leaflet oscillated twice up and down between early morning and noon. It then fell greatly afterwards, rising till 3 P Roman 1000. At this latter hour, the great nocturnal fall commenced on the second day, of which the tracing is not given. There was exactly the same double oscillation before noon, but only a very small one in the afternoon. On the third morning, the leaflet moved laterally, which was due to its beginning to assume an oblique position, as seems invariably to occur with the leaflets of this species, as they grow old. On both nights after the leaflets were asleep and hung vertically down, they continued to move a little both up and down, and from side to side. Erythrina caphra A filament was fixed transversely across a terminal leaflet, as we wished to observe its movements. When asleep, the plant was placed in the morning of June 10th under a skylight where the light was not bright, and we do not know whether it was owing to this cause or to the plant having been disturbed, but the leaflet hung vertically down all day. Nevertheless, it circumnuted in this position, describing a figure which represented 2 irregular ellipses. On the next day, it circumnuted in a greater degree, describing 4 irregular ellipses, and by 3 P Roman 1000 had risen into a horizontal position. By 7 P Roman 1000, it was asleep and vertically dependent, but continued to circumnutate as long as observed, until 11 P Roman 1000. Fig. 152 Erythrina christogalli circumnutation and nyctotropic movement of terminal leaflet, 334 inches in length, traced during 25H, apex of leaf 312 inches, from the vertical glass figure, reduced to 1/2 of original scale plant, illuminated from above temp, 17,121,812. Roman 100 Erythrina corallodendron. The movements of a terminal leaflet were traced during the second day. It oscillated 4 times up and 4 times down between 8 A Roman 1000 and 4 P Roman 1000, after which hour the great nocturnal fall commenced. On the third day, the movement was equally great in amplitude, but was remarkably simple, for the leaflet rose in an almost perfectly straight line from 6 A Roman 1000 to 3 P Roman 1000, and then sank down in an equally straight line until vertically dependent and asleep. Apios tuberosa tribe 8. The leaflets sink vertically down at night. Phasalis vulgaris tribe 8. The leaflets likewise sink vertically down at night in the greenhouse. The petiole of a young leaf rose 16, and that of an older leaf 10 at night. With plants growing out of doors, the leaflets apparently do not sleep until somewhat late in the season, for on the nights of July 11th and 12th none of them were asleep, whereas on the night of August 15th, the same plants had most of their leaflets vertically dependent and asleep, with Ph. caracalla and Hernandeza at the primary unifoliate leaves, and the leaflets of the secondary trifoliate leaves sink vertically down at night. This holds good with the secondary trifoliate leaves of Ph. Roxburgh, but it is remarkable that the primary unifoliate leaves, which are much elongated, rise at night, from about 20 to about 60 above the horizon, with older seedlings, however, having the secondary leaves. Just developed, the primary leaves stand in the middle of the day horizontally, or are deflected a little beneath the horizon. In one such case, the primary leaves rose from 26 beneath the horizon at noon to 20 above it at 10 p. Roman 1000, whilst at this same hour, the leaflets of the secondary leaves were vertically dependent. Here, then, we have the extraordinary case of the primary and secondary leaves on the same plant moving at the same time in opposite directions. We have now seen that the leaflets in the 6 genera of Phaceolae observed by us, with the exception of the primary leaves of Phaceolus roxburghae, all sleep in the same manner, namely, by sinking vertically down. The movements of the petioles were observed in only 3 of these genera. They rose in Centrosma and Phaceolus, and sunk in Amphicarpa. Sophora chrysophylla tribe 10, the leaflets rise at night, and are at the same time directed towards the apex of the leaf, as in Mimosa pudica. Caesalpinia homotoxylon gladicia, poinciana. The leaflets of 2 species of Caesalpinia tribe 13 rose at night with Hematoxylon campicianum tribe 13. The leaflets move forwards at night, so that their midribs stand parallel to the petiole, and their now vertical lower surfaces are turned outwards. Fig. 153. The petiole sinks a little in gladicia, if we understand correctly Dutcharter's description, and in Poinciana gillisae, both belonging to tribe 13, the leaves behave in the same manner. Fig. 153. Hematoxylon campicianum, a branch during daytime. B branch with leaves, asleep, reduced to 2/3 of natural scale. Cassia tribe 14. The nyctotropic movements of the leaves in many species in this genus are closely alike, and are highly complex. They were first briefly described by Linus, and since by Dutcharter our observations were made chiefly on Roman 100 Floribunda 18 and Corymbosa, but several other species were casually observed. The horizontally extended leaflets sink down vertically at night, but not simply as in so many other genera, for each leaflet rotates on its own axis so that its lower surface faces outwards. The upper surfaces of the opposite leaflets are thus brought into contact with one another beneath the petiole, and are well protected. Fig. 154. The rotation and other movements are effected by means of a well-developed pulvinus at the base of each leaflet, as could be plainly seen when a straight narrow black line had been painted along it during the day. The 2 terminal leaflets in the daytime include rather less than a right angle, but their divergence increases greatly whilst they sink downwards and rotate, so that they stand laterally at night, as may be seen in the figure. Moreover, they move somewhat backwards, so as to point towards the base of the petiole. In one instance, we found that the midrib of a terminal leaflet formed at night an angle of 36, with a line dropped perpendicularly from the end of the petiole. The second pair of leaflets likewise moves a little backwards, but less than the terminal pair, and the third pair moves vertically downwards, or even a little forwards. Thus all the leaflets in those species, which bear only 3 or 4 pairs, tend to form a single packet with their upper surfaces in contact, and their lower surfaces turned outwards. Lastly, the main petiole rises at night, but with leaves of different ages to very different degrees, namely some rose through an angle of only 12, and others as much as 41. Fig. 154. Cassia corymbosa, a plant during day. B same plant at night, both figures copied from photographs. Cassia caliantha, the leaves bear a large number of leaflets which move at night in nearly the same manner as just described, but the petioles apparently do not rise, and one which was carefully observed certainly fell 3. Cassia pubescens, the chief difference in the nyctotropic movements of this species compared with those of the former species consists in the leaflets not rotating nearly so much. Therefore their lower surfaces face but little outwards at night. The petioles, which during the day are inclined only a little above the horizon, rise at night in a remarkable manner, and stand nearly or quite vertically. This, together with the dependent position of the leaflets, makes the whole plant wonderfully compact at night. In the 2 foregoing figures copied from photographs, the same plant is represented awake and asleep. Fig. 155, and we see how different is its appearance. Fig. 155. Cassia pubescens, a upper part of plant during the day. B same plant at night. Figures reduced from photographs. Cassia mimosoids at night, the numerous leaflets on each leaf rotate on their axes, and their tips move towards the apex of the leaf. They thus become imbricated with their lower surfaces directed upwards, and with their midribs almost parallel to the petiole. Consequently, this species differs from all the others seen by us, with the exception of the following one in the leaflets not sinking down at night, a petiole, the movement of which was measured, rose 8 at night. Cassia barclayana, the leaflets of this Australian species, are numerous, very narrow, and almost linear. At night they rise up a little, and also move towards the apex of the leaf, for instance 2 opposite leaflets, which diverged from one another during the day at an angle of 104, diverted at night only 72, so that each had risen 16 above its diurnal position. The petiole of a young leaf rose at night 34, and that of an older leaf 19, owing to the slight movement of the leaflets, and the considerable movement of the petiole. The bush presents a different appearance at night to what it does by day, yet the leaves can hardly be said to sleep. The circumnudating movements of the leaves of Roman 100 floribunda, Caliantha and pubescens were observed, each during 3 or 4 days. They were essentially alike, those of the last-named species being the simplest. The petiole of Roman 100 floribunda was secured to a stick at the base of the 2 terminal leaflets, and a filament was fixed along the midrib of one of them. Its movements were traced from 1 p Roman 1000 on August 13th to 8 a Roman 1000th, but those during the last 2h are alone given in Fig 156, from 8 a Roman 1000 on each day, by which hour the leaf had assumed its diurnal position, to 2 or 3 p Roman 1000, it either zigzagged or circumnudated over nearly the same small space, at between 2 and 3 p Roman 1000. The great evening fall commenced. The lines representing this fall and the early morning rise are oblique, owing to the peculiar manner in which the leaflets sleep, as already described, after the leaflet was asleep at 6 p Roman 1000, and whilst the glass filament hung perpendicularly, down the movement of its apex was traced until 10 p Roman 1000, and during this whole time it swayed from side to side, completing more than one ellipse. Fig 156 Cassia floribunda circumnutation and nyctotropic movement of a terminal leaflet 156 inch in length, traced from 8 a Roman 1000 to same hour on following morning apex of leaflet 512 inches, from the vertical glass main petiole, 334 inches long temp, 161,712, Roman 100 figure, reduced to 1/2 of the original scale. Bauhinia tribe 15, the nyctotropic movements of 4 species were alike, and were highly peculiar. A plant raised from seed sent us from South Brazil, by Fritz Müller, was more especially observed. The leaves are large and deeply notched at their ends. At night the 2 halves rise up and close completely together like the opposite leaflets of many leguminosae. With very young plants, the petioles rise considerably at the same time. One which was inclined at noon 45 above the horizon at night stood at 75. It thus rose 30, another rose 34, whilst the 2 halves of the leaf are closing the midrib at first, sinks vertically downwards, and afterwards bends backwards, so as to pass close along one side of its own upwardly inclined petiole, the midrib being thus directed towards the stem or axis of the plant. The angle which the midrib formed with the horizon was measured in one case at different hours. At noon, it stood horizontally; late in the evening, it depended vertically, then rose to the opposite side, and at 10 p Roman 1000 stood at only 27, beneath the horizon being directed towards the stem. It had thus travelled through 153. Owing to this movimento, the leaves being folded and to the petioles rising, the whole plant is as much more compact at night than during the day. As a fastigiate Lombardy poplar is compared with any other species of poplar, it is remarkable that when our plants had grown a little older, viz. to a height of 2 or 3 feet, the petioles did not rise at night, and the midribs of the folded leaves were no longer bent back along one side of the petiole. We have noticed in some other genera that the petioles of very young plants rise much more at night than do those of older plants. Tamarindus indica tribe 16, the leaflets approach or meet each other at night, and are all directed towards the apex of the leaf. They thus become imbricated with their midribs parallel to the petiole. The movement is closely similar to that of hematoxylon, see Fig. 153, but more striking from the greater number of the leaflets. Adenanthera prosopes and Neptunia tribe 20, with Adenanthera pavonia, the leaflets turn edgeways and sink at night. In prosopes they turn upwards. With Neptunia auracea, the leaflets on the opposite sides of the same pinna come into contact at night, and are directed forwards. The pinnae themselves move downwards, and at the same time backwards or towards the stem of the plant. The main petiole rises. Mimosa pudica tribe 20, this plant has been the subject of innumerable observations, but there are some points in relation to our subject which have not been sufficiently attended to. At night, as is well known, the opposite leaflets come into contact, and point towards the apex of the leaf. They thus become neatly imbricated with their upper surfaces, protected. The four pinnae also approach each other closely, and the whole leaf is thus rendered very compact. The main petiole sinks downwards during the day, till late in the evening, and rises until very early in the morning. The stem is continually circumnudating at a rapid rate, though not to a wide extent. Some very young plants kept in darkness were observed during 2 days, and although subjected to a rather low temperature of 57-59 F, the stem of one described 4 small ellipses in the course of 12 H. We shall immediately see that the main petiole is likewise continually circumnudating, as is each separate pinna, and each separate leaflet. Therefore, if the movement of the apex of any one leaflet were to be traced, the course described would be compounded of the movements of 4 separate parts. A filament had been fixed on the previous evening, longitudinally to the main petiole of a nearly full-grown high-sensitive leaf, 4 inches in length, the stem having been secured to a stick at its base, and a tracing was made on a vertical glass in the hothouse under a high temperature. In the figure given, Fig. 157, the first dart was made at 8 A Roman 1000 August 2nd, and the last at 7 P Roman 1000 on the 3rd. During 12 H on the first day, the petiole moved thrice downwards and twice upwards within the same length of time. On the second day, it moved 5 times downwards and 4 times upwards, as the ascending and descending lines do not coincide. The petiole manifestly circumnudates the great evening fall and nocturnal rise. Being an exaggeration of one of the circumnutations, it should however be observed that the petiole fell much lower down in the evenings than could be seen on the vertical glass, or is represented in the diagram after 7 P Roman 1000 on the 3rd. When the last dart in Fig. 157 was made, the part was carried into a bedroom, and the petiole was found at 12 A Roman 1000 Roman 1 after midnight, standing almost upright and much more highly inclined than it was at 10 P Roman 1000. When observed again at 4 A Roman 1000, it had begun to fall and continued falling till 6 A Roman 1000, after which hour it zigzagged, and again circumnudated. Similar observations were made on another petiole with nearly the same result. Fig. 157, Mimosa pudica circumnutation and nyctotropic movement of main petiole, traced during 34 H 30 Roman 1000 on 2 other occasions. The movement of the main petiole was observed every 2 or 3 minutes, the plants being kept at a rather high temperature, viz. on the first occasion at 77-81 F, and the filament then described 212 ellipses in 69 Roman 1000. On the second occasion, when the temperature was 81-86 F, it made rather more than 3 ellipses in 67 Roman 1000. Therefore, Fig. 157, though now sufficiently complex, would have been incomparably more so if darts had been made on the glass every 2 or 3 minutes, instead of every hour or half-hour, although the main petiole is continually and rapidly describing small ellipses during the day. Yet after the great nocturnal rising movement has commenced, if darts are made every 2 or 3 minutes, as was done for an hour between 9 and 10 P Roman 1000 temp 84 F, and the darts are then joined, an almost absolutely straight line is the result. To show that the movement of the petiole is in all probability due to the varying turgescence of the pulvinus, and not to growth, in accordance with the conclusions of Pfeffer, a very old leaf, with some of its leaflets yellowish and hardly at all sensitive, was selected for observation, and the plant was kept at the highly favourable temp of 80 F. The petiole fell from 8 A Roman 1000 till 10 A Roman 1000. It then rose a little in a somewhat zigzag line, often remaining stationary, till 5 P Roman 1000, when the great evening fall commenced, which was continued till at least 10 P Roman 1000. By 7 A Roman 1000 on the following morning, it had risen to the same level as on the previous morning, and then descended in a zigzag line, but from 10 A Roman 1000 till 4 P Roman 1000, it remained almost motionless, all power of movement being now lost. The petiole, therefore, of this very old leaf, which must have long ceased growing, moved periodically, but instead of circumnudating several times during the day, it moved only twice down and twice up in the course of 24 H, with the ascending and descending lines not coincident. It has already been stated that the pinnae move independently of the main petiole. The petiole of a leaf was fixed to a cork support close to the point, whence the 4 pinnae diverge with a short fine filament cemented longitudinally to one of the 2 terminal pinnae, and a graduated semicircle was placed close beneath it. By looking vertically down, its angular or lateral movements could be measured with accuracy between noon and 4 P Roman 1000. the pinna changed its position to one side by only 7, but not continuously in the same direction, as it moved 4 times to one side, and 3 times to the opposite side in one instance to the extent of 16. This pinna therefore circumnudated later in the evening. The 4 pinnae approach each other, and the one which was observed moved inwards 59 between noon and 6 p. Roman 1010. Observations were made in the course of 2h 20 Roman 1000 at average intervals of 14 Roman 1000 between 4 and 6 p. Roman 1000, and there was now, when the leaf was going to sleep, no swaying from side to side, but a steady inward movement. Here therefore there is in the evening the same conversion of a circumnudating into a steady movement in one direction as in the case of the main petiole. It has also been stated that each separate leaflet circumnudates. A pinna was cemented with shellac on the summit of a little stick, driven firmly into the ground, immediately beneath a pair of leaflets, to the midribs of both of which excessively fine glass filaments were attached. This treatment did not injure the leaflets, for they went to sleep in the usual manner, and long retained their sensitiveness. The movements of one of them were traced during 49h as shown in Fig. 158 on the first day. The leaflets sank down till 11 a Roman 1000, and then rose till late in the evening in a zigzag line, indicating circumnutation. On the second day, when more accustomed to its new state, it oscillated twice up and twice down during the 24h. This plant was subjected to a rather low temperature, viz. 62-64 F. Had it been kept warmer, no doubt, the movements of the leaflet would have been much more rapid and complicated. It may be seen in the diagram that the ascending and descending lines do not coincide, but the large amount of lateral movement in the evening is the result of the leaflets bending towards the apex of the leaf. When going to sleep, another leaflet was casually observed and found to be continually circumnudating during the same length of time. The circumnutation of the leaves is not destroyed by their being subjected to moderately long continued darkness, but the proper periodicity of their movements is lost. Some very young seedlings were kept during 2 days in the dark temp 57-59 F, except when the circumnutation of their stems was occasionally observed, and on the evening of the second day, the leaflets did not fully and properly go to sleep. The pot was then placed for 3 days in a dark cupboard under nearly the same temperature, and at the close of this period, the leaflets showed no signs of sleeping and were only slightly sensitive to a touch. On the following day, the stem was cemented to a stick, and the movements of 2 leaves were traced on a vertical glass during 72h. The plants were still kept in the dark, excepting that at each observation, which lasted 3 or 4 minutes, they were illuminated by 2 candles. On the third day, the leaflets still exhibited a vestige of sensitiveness when forcibly pressed, but in the evening they showed no signs of sleep. Nevertheless, their petioles continued to circumnudate distinctly, although the proper order of their movements in relation to the day and night was wholly lost. Thus 1 leaf descended during the first 2 nights Roman 1e between 10 p. Roman 1000 and 7 a Roman 1000 next morning, instead of ascending, and on the third night it moved chiefly in a lateral direction. The second leaf behaved in an equally abnormal manner, moving laterally during the first night, descending greatly during the second, and ascending to an unusual height during the third night. Fig. 158 Mimosa pudica circumnutation and nyctotropic movement of a leaflet with pinna, secured traced on a vertical glass from 8 a Roman 1000, sept 14th to 9 a Roman 1000th. With plants kept at a high temperature and exposed to the light, the most rapid circumnudating movement of the apex of a leaf, which was observed, amounted to 1500 of an inch in 1 second, and this would have equaled 18 of an inch in a minute, had not the leaf occasionally stood still. The actual distance travelled by the apex, as ascertained by a measure placed close to the leaf, was on one occasion nearly 34 of an inch in a vertical direction in 15 Roman 1000, and on another occasion 58 of an inch in 60 Roman 1000, but there was also some lateral movement. Mimosa albida 19, the leaves of this plant, one of which is here figured Fig. 159, reduced to 23 of the natural size, present some interesting peculiarities. It consists of a long petiole, bearing only 2 pinnae, here represented as rather more divergent than is usual, each with 2 pairs of leaflets, but the inner basal leaflets are greatly reduced in size, owing probably to the want of space for their full development, so that they may be considered as almost rudimentary. They vary somewhat in size, and both occasionally disappear, or only one. Nevertheless, they are not in the least rudimentary in function, for they are sensitive, extremely heliotropic, circumnudate at nearly the same rate as the fully developed leaflets, and assume, when asleep exactly the same position with Roman 1000 pudica, the inner leaflets at the base and between the pinnae are likewise much shortened and obliquely truncated. This fact was well seen in some seedlings of Roman 1000 pudica, in which the third leaf above the cotyledons bore only 2 pinnae each, with only 3 or 4 pairs of leaflets, of which the inner basal one was less than half as long as its fellow, so that the whole leaf resembled pretty closely that of Roman 1000 albida. In this latter species the main petiole terminates in a little point, and on each side of this there is a pair of minute flattened lancet-shaped projections, hairy on their margins, which drop off and disappear soon after the leaf is fully developed. There can hardly be a doubt that these little projections are the last and fugacious representatives of an additional pair of leaflets to each pinna, for the outer one is twice as broad as the inner one, and a little longer, viz. 70/100 of an inch, whilst the inner one is only 51,006,100 long. Now, if the basal pair of leaflets of the existing leaves were to become rudimentary, we should expect that the rudiments would still exhibit some trace of their present great inequality of size. The conclusion that the pinnae of the parent form of Roman 1000 albida possessed at least 3 pairs of leaflets, instead of as at present only 2, is supported by the structure of the first true leaf, for this consists of a simple petiole often bearing 3 pairs of leaflets. This latter fact, as well as the presence of the rudiments, both lead to the conclusion that Roman 1000 albida is descended from a form, the leaves of which bore more than 2 pairs of leaflets. The second leaf above the cotyledons resembles in all respects the leaves on fully developed plants. Fig. 159, Mimosa albida leaf seen from vertically above.